Hi everyone, welcome to PrepFusion. So the wait is over. We are going to start EDC now, and the first chapter is Basic Semiconductor Physics. So for Basic Semiconductor Physics, there will be two marathons. This is Marathon 1 and Marathon 2 will also come. So all the topics, whatever that has been written here, all these topics will be covered. And what I expect from your side, comments. Just as you have watched this video, just you are done watching this video, I would expect that you will be writing down what you felt after watching this 12 hour of marathon. So only thing I am expecting from your side is comments. If you want to share it, you can share. I would expect that I get 5k views before the next marathon. But even if you are not completing it, still the marathon will come. There is no doubt that complete semiconductor physics will come on YouTube. So just it is my expectation, but you should comment down. If you have studied, then you should comment down. Okay, so timestamp and everything would be there. So just sit with the pen and paper. If possible, you can download the notes as well. I will be putting the notes in the Telegram group. So from there you can download the notes. You can get the printout of the notes as well. So just sit with the pen and paper, sit with the cool mindset and watch this 12 hour of marathon. Thank you very much. Let's get started. Hi everyone, welcome to PrepFusion. So we are going to start our new subject now, that is electronic devices and circuits. So communication system and EDC will run parallelly. So as of now we are going to study EDC, right? So in EDC mostly 4 chapters are there: basic semiconductor physics, PN junction and diodes, then BJTs, and then MOSFET and MOSFET. Okay, and miscellaneous, here all the concept will be there from all 4 chapters. So mostly there are 4 chapters. Now this is the most important one, basic semiconductor physics. Okay, basic semiconductor physics, 50% of the questions will be framed from this particular chapter only. And if you don't study basic semiconductor physics, that means you are not going to understand any of these chapters. So if I want to put the star, I will put 4 stars on this one. After that, importance comes from here. I will put 3 star on this one, MOSFET and MOSFET. Okay, and then I would put 2 star on PN junction and diode and 1 star on BJTs. Okay, and in the miscellaneous, all the concept will be there from all the chapters, right? So this would be the flow. So first we are going to study basic semiconductor physics, then PN junction and diode, then BJTs, and then MOSFET and MOSFET. But basic semiconductor physics is very, very important. Now, one important thing, before starting EDC, you need to have patience. Here it will not happen that, sir, within 10 minutes, sir, I will be able to solve the questions. Some numerical problem will be there, sir, I will be able to solve it. No. This subject requires the patience. You need to have the patience. First, we will understand the theory, then we will move to the formula, and then we will move to the questions. Because here, if you don't understand theory, then formula will be of no use. If you want to utilize the formula, that means you need to study the theory in a good manner. So you need to have patience. In the beginning, you may feel like that, sir, what is going on? How we will be able to solve numerical problem out of it? But you will be able to solve numerical problem. You need to have some patience. So this particular lecture, this is going to be our first lecture. This will be completely based on theory. There will be no formula, nothing. Here I will be explaining you the meaning of semiconductor, why we are studying semiconductor, and how we are getting conductivity out of semiconductor. Okay, so that explanation I am going to give you. From the next lecture onwards, questions will start coming. But as of now, in this lecture, only theory will be there. Okay, only theoretical part would be there. So let's get started. So what we are going to study, basic semiconductor physics. So all the devices that you see in front of you, you might be watching this video in laptop or in computer or anywhere you are watching this video. You might be watching it in mobile. You are having your earphones. Whatever the devices you are having, in all the devices there are some tiny devices, and those tiny devices are known as semiconductors. So your world, your whole things are running because of semiconductor. If there is no semiconductor, that means there is no world. Okay, so that's why we need to study basic semiconductor physics. So first we need to study about semiconductors, right? Now there are basically 3 kind of materials: conductor, semiconductors, and insulator. Conductor, semiconductors, and insulator, based on the conductivity. What is the meaning of conductivity? Conductivity means ability of driving the current. Let's just say there is some device and I connect a voltage source around it. Now will this conduct some current? Voltage source has the ability of conducting the current. This wire will have the ability of conducting the current, but will this device conduct the current or not? So based on that, there are 3 kind of materials: conductor, semiconductors, and insulator. So if it is conducting, that means it is having high conductivity. If it is conducting the current, that means if it is letting this current pass, then it is having high conductivity. Okay, so for the conductors, conductivity is high. That means in the conductors you can drive the current. If this material is conductor, then it will let the current flow. So from the battery, current will go out, and in the battery only the current will go in, and in the device as well the current will flow. If it is an insulator, then it will not allow the current. Look, let's just say this is a wire, this is my, this wire I am having, this is the charger I am having, right? So if I connect this charger and from here if I connect my mobile, then mobile will be getting charged because the current is flowing inside it. But here there is coating, like, right? There is plastic coating here. On the wire there is plastic coating. Even if I connect it and if I hold the wire, will I get any current? Will I get any shock? No, I will not get any electric shock. Why is that so? Because this plastic coating is insulator, right? But the wire that is inside it, that is conductor. So for the insulator, insulator means it will not allow the current to flow. It will not conduct the current. If it is not allowing the current to flow, that means it is an insulator. If it is allowing the current to flow, that means it is conductor. So for the conductor, conductivity is high. For the insulator, conductivity is low. What is the example of conductor? That is copper. What is the example of insulator? That is plastic coating on this wire. And if you see, other examples are also there. Wood. Wood is also example of conductor, right? Wood will never allow the current to flow, right? Let's just say you take a piece of wood and then you connect a battery around it, and will you be getting some current? No, you will not get any current. You take a piece of wood and then connect a battery around it, will you get any current? No, you will not get any current because wood will not allow the current to flow. So this is known as conductor and insulator. Now there is something called semiconductors. So in the semiconductors you can control that conductivity. This is the best thing. What I am saying, semiconductors, conductivity of the semiconductors is controllable. That means you can move from here to here. That means you can make the conductivity high as well, and you can make the conductivity zero as well. Basically the semiconductor can work as a conductor as well, and it can work as an insulator as well. Along with that, you can control its conductivity. What does that mean? That means if I want a very high current, that also I can do. If I want low current, that also I can do. If I want zero current, that also I can do. And as an engineer, you want to be controllable. Controllable for your partner? No. Controllable for the devices that you are using. Okay. You want to be controllable. That means you want the control in your hand. If I give a supply, if I give a particular supply, or if I do any activity, based on that activity, I want to control the things that is happening on my chip. Right? If I have a remote, if I press the button to 25, that means the AC should be working at 25 degrees Celsius. If I press the button at 23, that means AC should be working at 23 degrees Celsius temperature. So as an engineer, I want to be controllable, and semiconductor is doing that particular thing. That if you want to make it as an insulator, you can make it as an insulator as well. If you want to make it as a conductor, you can make it as a conductor as well. Examples are silicon, germanium. A lot of examples are there. Silicon, germanium, GaAs, gallium arsenide, okay, indium phosphide, INP. A lot of examples are there. We will study about them. Is that clear? Is this slide clear to you? So every tiny devices that you are seeing, every device that you are seeing, in those devices, some tiny devices are there. Those devices are known as semiconductors. Semiconductors have controllable conductivity. Insulators will have zero conductivity or very low conductivity, while the conductors will have very high conductivity. Examples are there. Okay. So why we are studying semiconductors? Because semiconductors are special. We can control when and how much they conduct, and this controllability will make other devices like diodes, transistors, solar cell, microchips and all. So we will study about all these devices, like what is diode, what is transistor. So everything we will study. In BJTs and MOSFETs we will study about transistors, and in the PN junction we will study about diodes. Okay. So that's why we are going to study semiconductors. Now before studying the semiconductors, we need to start right from the scratch. What do you mean by right from the scratch? So how a particular material is made, how we are made, how everything is made in this universe. So that kind of physics, from that kind of scratch we need to start, that how a particular semiconductor device was made. So in this video, in the first half, we will be just building a particular semiconductor. So how it started? So every single thing, let's just say this is some material. So this material is made of some atoms. So in this material there will be a lot of atoms. So this material is made of all the atoms. Now this atom is made of three particles. In the atom, there will be three particles, and those particles are electron, proton, and neutron. So every material is made of atom, and atom is made of electron, proton, and neutron. So in each material there will be a lot of atoms, and in each atom there will be three kind of particle: electron, proton, and neutron. Okay, and this proton and neutron combined is known as nucleus. Okay, so I will tell you the structure of atom, but before that let's study about electron, proton, and neutron. So what is electron? Electron is a negatively charged particle having a charge of minus 1.6 into 10 to the power minus 19. So it is shown by E. The charge of electron is shown by E. Charge of electron is shown by E, which is given as minus 1.6 into 10 to the power minus 19 coulomb. Okay, mass, very small mass is there, 9.1 into 10 to the power minus 31 kg. Okay, and position, what is the position, that I will tell. So forget about this point, this position I will tell you. What about the proton? Positively charged particle. It is having the same charge. This was a negative charge, this is just a positive charge. So here the charge is 1.6 into 10 to the power minus 19. Okay, and what is the mass? Mass is, this is heavier than the electron, right? 10 to the power minus 31. That means after 0 point, after that there are 31 zeros. That means 10 to the power minus 31 is lesser than 10 to the power minus 27, right? So this is much heavier than the electron. And neutron is having no charge, but the mass of neutron is same as the proton. And about the position I will tell you now. So these are very simple things that you have already studied in the chemistry, right? In chemistry you have already studied these kind of things, just I am making you revise. Okay, so now how your atom will look like. So in an atom there will be something called nucleus. Now in this nucleus, proton and neutron will be there. So proton are positively charged, neutron are neutral, right? Neutron means neutral, there is no charge. So on the neutron there is no charge, in proton there is positive charge. So positive charge plus zero charge, what that would be? Effectively it will be positive charge only, no? So in the nucleus, at the center there will be nucleus. In the nucleus there will be proton and neutron. Nucleus I will be showing by the positive sign. Why I am showing by the positive sign? Because there is proton and neutron. Proton are positively charged. Now around the nucleus, electrons will be there. Electrons will be walking around the nucleus in a fixed closed path. Electrons will be walking around the nucleus in a fixed closed path. So in an atom there will be proton, neutron and electrons. Proton and neutrons combined are called as nucleus. They will be right in the center. Around the nucleus, electrons will be moving around in fixed circular path. Okay, so let me show you the structure. So this is the structure. So this is a model of an atom. Right in between there is a nucleus. In the nucleus there is proton and neutron. Effectively it will have a positive charge. Effectively it will have a positive charge. Around the nucleus there are electrons. These are the electrons. These are the electrons. Electrons are revolving around the nucleus. Electrons are revolving around the nucleus in a fixed circular path. It's like our solar system only. In our solar system, what is there? Sun is there. In the center, sun is there. Now around the sun, your earth is moving, right? Around the sun, your earth is moving. But earth will always move in a fixed circular path. It's not that, sir, this year earth is moving like this, and after that it will lose its radius. It will keep on losing its radius, and eventually it will fall into sun. Will that happen? No. Earth will always keep on revolving in this circular path only. Similar things will happen with the electrons as well. Electrons will keep on moving on this fixed circular path. Okay, so this is what I have written. This atomic model was given by Bohr, but scientist name is not important for us to understand the semiconductor physics. As of now, we are just learning what we have already studied in the chemistry. So what they are saying, electrons move in a fixed circular path around the nucleus. Now each orbit, or you can call it energy level. So this is known as energy level. This is your first energy level. This is your n equals to 1. First energy level. This is your first energy level. So I am calling it n equals to 1. So in this first energy level, you can see there are 2 electrons. This is your second energy level. I am calling it n equals to 2. And this is your third energy level. I am calling it n equals to 3. So what is written? each orbit has a fixed energy. That means if you are working in this particular circle, if your electron is working in this particular circle, that means electron is having a fixed particular energy. At any point on this particular energy level, at any point on this particular energy level, the energy will be fixed. Here, 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 here. Everywhere the energy will be fixed. Okay, it will have the same energy, but two different levels will have different energies. This level will have different energy, this level will have different energy, this level will have different energy. Let's just say this level is having E1 energy, this will have E2 energy, this will have E3 energy. Are you able to understand this point? Okay, but in this E1 energy level, all the electrons will have the same energy. That means if I call this electron as electron 1 and this electron as electron 2, so both electron 1 and electron 2 is having energy of E1 only. If I call this as 3, 4, 5 and 6, so all the electrons 3, 4, 5, 6 is having the energy E2. Let's call it alpha, beta, gamma. So alpha electron, beta electron and gamma electron, all the electrons are having energy E3. So in a particular energy level, all the electrons will have the same energy. And if electrons are working in this fixed circular path, if this electron is working in this fixed circular path, it will not lose its energy. Let's understand by an analogy. Let's just say there is some particular center and I ask you to walk around this circular path. I ask you to walk around this center in this fixed circular path. So what will happen? You will keep on working, 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 but slowly what will happen? You will start losing your energy. So what will happen? Your circular path will reduce. Then again and again you will keep on losing the energy, you will again keep on losing the energy, you will lose energy, the circular path will keep on reducing and then you will fall into this center, right? Just imagine, here this is the center and you are revolving. So you will lose the energy. If you are losing the energy, what does that mean? That means your circular path will reduce and eventually you will fall down. But what if you are working with the constant energy? You are that kind of human being, you are an alien who is not losing the energy. So electrons are like that only. If electron is working in this fixed path, then it will not lose the energy. What does that mean? It will keep on revolving around the nucleus in this fixed particular path only, and it will not lose the energy. This electron will also not lose the energy, they will just keep on revolving around that. It's like our earth only. What earth does? It will keep on revolving around sun in a fixed particular path only. It will not lose the energy and fall into sun. This thing doesn't happen. So similarly with the electrons, it will keep on revolving around the nucleus, it will not lose the energy and fall into the nucleus. It will not happen. Okay. Now let's just say this electron from here wants to go into this level. This electron is there in the n equals to 1 level, it wants to go into n equals to 2 level. N equals to 2 level electron wants to go into n equals to 3 level electron. So what will happen? It needs to get some energy. The electron needs to absorb some energy. If it gets some energy, then it can make the transition. What I am saying is that, let's just say this was your energy level E1 and this is your energy level E2. One electron is there in energy level E1. Now if this electron wants to go to energy level E2, what will happen is that it needs to take some energy. Now whatever the energy gap is there, let's just say this energy E2 is 1 electron volt and this energy E1 is 0.5 electron volt. So the gap between them is 0.5 electron volt only. Let's take it 0.3. So gap between them will be 0.7 electron volt. So if this electron gets the energy of 0.7 electron volt, then what will happen is that it will make a transition from this energy level to this energy level. So how much energy it will require? It will require delta E energy. How much energy it will require? It will require delta E energy, which is equals to E2 minus E1. So as you go further from the nucleus, like this particular orbit, You can call it orbit or you can call it energy level. So this particular energy level will have the least energy. As you go further from the nucleus, the energy will increase. Sir, why that happens? You will see it. Don't worry about that. As of now, on a crude level only, I am telling that this will have the least energy, then it will have more energy, it will have more energy. In that manner, the energy will keep on increasing. And you can directly see that this electron is near to the nucleus, no? Who is having lesser distance? Who is nearer to the nucleus? This electron or this electron? This particular electron is nearer to the nucleus. That means this nucleus is making more force on this electron. Let's just say there is some Q1 charge and then there is some Q2 charge. This is positively charged, this is negatively charged. So what they will do? They will attract each other, right? They will attract each other. If the distance is small, then the attraction will be large, and if the distance is larger, then the attraction will be lower. So here the distance is low, here the distance is less. If the distance is less, that means it is more attracted towards the nucleus. So it is bound. This electron is bound by this nucleus, but this electron is lesser bound by this nucleus, and this electron is even lesser bound by this nucleus. Are you able to understand this point? So if it is bound, that means it cannot move freely. What is the meaning of energy? If I say I am having the energy, that means I am teaching now. I can do the activity, right? If I have the energy, that means I can get out of my house and I can walk around the park, right? I can walk around the path. I can do anything if I have the energy. And when I will have the energy, if I am not bound, what if my parents says that you need to stay in the home only? That means I am bound by them. But since now if my age is 25, 26, then what they will say? You are not bound. So similarly, this electron is not bound. This electron is not bound by this nucleus. That means it is having more energy. More energy means it can go out. It can go out easily. If I am not bound by parents, that means I can go out very easily. So similarly, this electron is not bound by the nucleus. That means it can go out very easily. So this will have least energy, this will have more energy, this will have even more energy. Here more energy, more energy. So if you go further from the nucleus, the energy will keep on increasing. Okay. So if you are in level 1, if you are in energy level 1, if you are in n equals to 1, then your energy is lesser. If you are in level 2, then your energy is more. So if you want to go from E1 to E2, that means you need to absorb some energy. Another analogy I will give you. Have you seen firecracker? Have you seen rocket? Rocket. Firecracker, right? Some firecracker you would have surely seen. So in firecracker, what do? You will fire it up, you will give some light to it, you will give it some energy, you will give it some heat, right? If you give it some heat, what happens? It absorbs this energy and it will go up, right? It will go in the sky, it will go up in the sky. After some time, what will happen? It will fall back. There was a firecracker, there was this firecracker, you gave it some energy, you gave it some heat, you gave it some fire. What happened is that this rocket went up in the sky and then fall back. Similarly here, you need to give some energy to this electron. What will happen is that it will go into the higher level and then again it may fall back. And when it is going up, at that time it will absorb the energy, absorbing the energy. So this have been already written, so I will not tell it. So at that time it will absorbing the energy, and when it falls back, it will release the energy. And how much energy it will release? Whatever the energy it has taken, the same energy it will release. If it has taken delta E energy, then the same energy delta E only it will release. Are you able to understand this point? So if it is jumped to a higher orbit, that means it is absorbing the energy. If it jumps to a lower orbit, that means if it is coming from E2 to E1, that means it will release the energy as light or as heat. It can release the energy as light as well or as heat as well. Is that clear to you? Is the meaning of atom clear to you? In an atom, there will be a nucleus. In nucleus, there will be proton, neutron. So effectively, it will be positively charged. Around the nucleus, electrons will be revolving around in fixed circular path. Each fixed circular path will have a certain fixed energy. In that particular path, if electron is moving, it will have a certain energy. As you go further from the nucleus, as the distance from the nucleus increases, the energy level The energy of these energy levels will increase. If you are farther from the nucleus, that means your energy will be more. If you are near to the nucleus, your energy will be less. Why is that so? Because you are bound to the nucleus. Now, if an electron wants to make a transition from lower energy level to higher energy level, then it needs to absorb some energy. It needs to take some energy by any mean, by light, by heat, by any mean. If it gets some energy, then what will happen is that it will make a transition from lower energy level to higher energy level. And if it is coming from higher energy level to lower energy level, then what will happen is that it will release some energy. So this is about the atom. And now all these atoms combined will make some material. So you are also made from atoms only. Small atoms will combine and will make one material. Is that clear to you? All good? All fine? Now let's understand what is the meaning of energy. So what is energy? Let's just say there was some material. In this material there was some Q charge. Now around this material, what do I do is that I connect a battery of V volt. So if this Q charge gets the acceleration of a voltage V, then its energy will be Q into V. What I am saying, if some Q charge gets the voltage difference of V, there was some charge lying there, I gave it some voltage, then it will attain an energy of Q into V. That means now this charge can move. Energy means if you are having energy, that means you can move. If you are having energy, that means you can move. So this Q charge was there. Around this Q charge there was no potential, but just as I applied potential V, it will start moving. So a charge Q getting a potential difference of V, then it will gain an energy of Q into V. Is that clear to you? Now what is the unit of energy? Unit of energy is joule. What do you mean by joule? Joule is simply, what is the unit of charge? I hope you know these kind of basic things. Unit of charge is 1 coulomb and unit of voltage is 1 volt. So coulomb into volt. Okay, 1 joule means coulomb into volt. Now what do you understand by 1 electron volt? So there are two units of energy. One unit is joule, other unit is electron volt. In our EDC we will use this one. In signal system, in network analysis, we mostly use joule, but in our EDC we will use electron volt. What is the meaning of this electron volt? So similarly, what I explained there, what is the meaning of energy? If this Q charge is getting a voltage V, now in place of this Q charge, if one electron is getting a voltage V, now what is the charge on the electron? 1.6 into 10 to the power minus 19 coulomb. So if 1.6 into 10 to the power minus 19 coulomb gets an energy of, gets an potential difference of V volt, or you can say potential difference of 1 volt, because we are telling the definition of 1 electron volt, right? We are telling the definition of 1 electron volt. Here what was the definition of 1 joule? If 1 coulomb charge gets a voltage difference of 1 volt, 1 coulomb charge gets a voltage difference of 1 volt, then what will be the energy? 1 joule. What will be the definition of 1 electron volt? If a 1 electron charge, what is 1 electron charge? 1.6 into 10 to the power minus 19 coulomb. So 1.6 into 10 to the power minus 19 coulomb charge gets a voltage difference of 1 volt. Then its energy would be 1 electron volt. So this is what have been written. 1 electron volt is the energy gained by an electron when it is accelerated through a potential difference of 1 volt. Is that clear to you? So this is the meaning of 1 electron volt. So from here, what do you understand? Can I write it down in this manner? 1.6 into 10 to the power minus 19. This will be coulomb, this will be volt. What is coulomb into volt? Joule. So 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. You don't need to mug it up. Never ever mug it up, because what will happen is that if you mug it up, you will get the confusion. Sir, 1 joule is equals to 1.6 into 10 to the power minus 19 electron volt, or sir, 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. In longer run, this kind of problem you will face if you just remember it, if you just try to memorize the formula. So here you are not going to memorize the formula. What you will do? You will simply say, okay, 1 electron volt. That means 1 electron is getting a potential difference of V. That means 1.6 into 10 to the power minus 19 coulomb into volt. Coulomb into volt, What is coulomb into volt? 1 coulomb is getting a potential difference of 1 volt. What does that mean? Okay, it is joule. So 1 electron volt will be equal to 1.6 into 10 to the power minus 19 joule. So don't mug it up. Better than that, you understand it. What is the meaning of 1 electron volt? Okay, so let's solve some question. An electron in a semiconductor is given an energy of 3.2 electron volt. Through what potential difference it must be accelerated from rest to acquire this energy? Did you understand this point? An electron in the semiconductor, let's just say this is the semiconductor you are having. In this semiconductor, you are having this electron. This is having an energy of 3.2 electron volt. Electron is having an energy of 3.2 electron volt. What is the formula of energy? Q into V. If your charge Q gets a potential difference of V, then it will have energy E. Energy E is already given. Now what is the charge? Who is getting this much energy? Electron. And what is the charge on electron? E only, into potential difference. Into potential difference. So what will be the potential difference? Potential difference is coming out to be 3.2 volt only. So from here, what do you understand? From next time onwards, if the energy of electron is mentioned, let's just say energy of electron is mentioned as alpha electron volt, and I ask you to calculate the potential difference. Can you tell the potential difference? Yes, sir, the potential difference will be alpha volt. So if anywhere electron volt is mentioned, then directly you can tell voltage. If energy is mentioned, you can directly tell the voltage. Because in this whole chapter, in this whole subject, we will just talk about the electrons, and energy will be mentioned in electron volt. So whenever I say from electron volt, you need to find voltage. How will you find it? Just divide by the charge. Here what you are doing, you are dividing by the charge. E and E get cancelled out. So what is the answer you are getting? 3.2 volt. Right? So did you understand the meaning of electron volt? Did you understand why I spent so much time here? Why I spent so much time on electron volt? Because at a lot of places, energy of the electron will be mentioned. Then you should know that what should have been the potential around it. If energy of the electron is alpha electron volt, that means I should have given alpha potential. I should have given alpha potential difference around this electron. Then only it would have got alpha electron volt energy. Is that clear to you? Okay. Next question also very easy. A proton is accelerated and gain this much of energy. What is the energy? Energy is given as Q into V. Energy given is 4.8 into 10 to the power minus 16 joule this time. So this is the energy of proton. Okay, through what potential difference it must be accelerated. So what is the charge on the proton? Same charge as electron, 1.6 into 10 to the power minus 19 into potential difference. So what will be the answer you will be getting? 3 millivolt, right? Because 3 and then, okay, no, 3 kilovolt. Sorry guys, 3 kilovolt. 3 kilovolt. So that would be the answer. This would be the potential difference. Okay, very simple question. You don't need to convert it to the electron volt, right? Why would you convert it to the electron volt? Directly you can find the answer. Or what some people would have done is that 4.8 into 10 to the power minus 16 joule is there, no? So how will I convert it to electron volt? So I know that 1 electron volt is equals to 1.6 into 10 to the power minus 19 joule. 10 to the power minus 19 joule. That means from here, what would be your 3 electron volt? So 3 electron volt will be equals to 4.6 into 10 to the power minus 19 joule. Right? So answer would have been 3 electron volt. So it is having 3 electron volt energy. So here what could have been given? Yeah, but this is 4.8 into 10 to the power minus 19. Now if I need to do 3000 electron volt. So 3000 electron volts means here I am multiplying with the 10 to the power 3. So here also I will multiply with 10 to the power 3. So what I will be getting? So what does that mean? That means this was given as 3 kilo electron volt. So the energy of the proton was 3 kilo electron volt. So what would have been the potential difference? That would have been 3 kilovolt. So every time you don't need to convert a joule into electron volt, right? If you require converting into electron volt, then you can convert it. And for the conversion as well, I am asking you not to mug up the formula, but to think about it. But all good? All fine? Now let's talk about the energy of an electron in hydrogen atom. So in hydrogen atom, you guys would be knowing that there is only one electron, right? So the energy of that particular electron is given by minus 13.6 divided by n square, and this is given in electron volt. Okay, this is the energy of hydrogen electron that is available in hydrogen atom. Okay, energy of electron in hydrogen atom, this is given by minus 13.6 electron volt divided by n square. N is known as quantum number, but as of now you will say that n is energy level. Okay, n is nothing but a energy level. Now this one electron in the hydrogen atom, this one electron will be lying either in n equals to 1, either it would be lying in n equals to 1, n equals to 1 level, or it could be lying in n equals to 2 level, or it could be lying in n equals to 3 level. The electron could be here, this is your nucleus, right? Electron could be here, or it could be here, or it could be here. It could be anywhere. Ideally it should lie near to the nucleus, but what if I have given it some energy? Let's just say ideally the electron should be lying in the first orbit, it should be lying in the first energy level near to the nucleus. But what if someone has given it some energy and it has reached to level 2? What if someone has given its energy and it has reached to level 3, or it might have reached to level 4 as well, right? So this would be the scenario. Now if it is lying in the energy level 1, so what would be its energy? Its energy would have been minus 13.6 divided by 1. What that would be? Minus 13.6 electron volt. If it is lying in the energy level 2, what would have been its energy? Minus 13.6 divided by 2. So 2 square will become 4. This much energy. And if it is lying in the energy level 3, then what would have been its energy? This would be its energy. This has become minus 3.4 electron volt, and this has become minus 1.52 electron volt. Okay. So what I am doing is that with respect to the energy level, with respect to energy levels, I am plotting the energy. So on this axis, I am plotting the electron energy. Sir, how this formula came, you don't need to worry about it. No one will ask you. Okay. I will use this concept to make you understand something else. That's why we are studying it here. Sir, how this formula came, no one is going to ask you. So electron energy on this axis. Okay. Now this is the nucleus, right? This is the nucleus that we are having. This is the nucleus that we are having. So I am taking the nucleus as a reference. This is my nucleus. This is as a reference I am taking. This is my nucleus. This I am taking as a reference. After that, this is my level 1. After that, this is my level 1. This is your n equals to 1. N equals to 1. This is your n equals to 1. N equals to 1. Right? What was the energy? So let's write down n equals to 1 here. What was the energy? Level 1 was there. What was the energy? Minus 13.6 electron volt. Now n equals to 2. N equals to 2. What is the energy? Minus 3.4 electron volt. And then n equals to 3. N equals to 3. What is the energy? Minus 1.52 electron volt. Which number is larger? This number is larger or this number is larger? A lot of people will directly say, blindly they will say, sir, minus 13.6 electron volt is larger. No, it is not larger. There is a negative sign. No. Minus 2 is larger or minus 4 is larger or minus 2 is larger? Minus 2 is larger. No, because there is a negative sign. So this is larger. So as you go upside, as you go upward, the energy of the electron is increasing. As you go upward, the energy of the electron is increasing. So whenever we walk in the upward direction, the energy of the electron will increase, because we have taken nucleus as the reference. Taking the nucleus as a reference, as we go in the upward direction, energy of the electron will increase. And that is certain for all the atoms, not only for hydrogen atom. Here we are talking about hydrogen atom only. First we will take the reference of hydrogen atom. First we will understand everything about the hydrogen atom, and then we will relate it to the semiconductor. So what do you understand? In hydrogen atom there was one electron. That electron could be lying in n equals to 1, n equals to 2 or n equals to 3 energy level. Okay. If it was lying in the energy level n equals to 1, then its energy would have been minus 13.6 electron volt. If it was there in n equals to 2, its energy would have been minus 3.4 electron volt. If it was in n equals to 3, its energy would have been minus 1.52 electron volt. Sir, how this formula came? You don't need to worry about that. So as you go upward in the, as you walk in the upward direction, then the energy of the electron is increasing. Okay. So this point you need to remember. Somewhere when we study our Venn diagrams, I will relate this point. All good, all fine. So this is the theory that has been written here. An isolated hydrogen atom has one proton in its nucleus and one electron. Isolated means it is not being affected by any other atom. Isolated means only one is present. It is not affected by anyone. Okay. This is the meaning of isolated hydrogen atom. So it is not affected by any other parameter. It is not affected by any other atom or anything else. Isolated. It is completely isolated. So an isolated hydrogen atom has one proton in its nucleus and one electron. In Bohr's model, the electron can be only in fixed certain energy level. This we have already discussed, that electron would be either in this energy level or in this energy level or in this energy level. Okay. Given by, the energy is given by minus 13.6 divided by n square electron volt, where n is the energy level number, and these levels are well defined and separated by the gaps where electrons cannot exist. That means electron will be either in n equals to 1, n equals to 2, n equals to 3. It cannot be lying in between. Are you able to understand this point? Either it can lie here or here. It cannot lie in between. That means electron can lie in a particular energy level only. It cannot lie in between. Sir, why we are studying all this? Where it will be used? It will be used somewhere. So have some patience. Okay. You need to have some patience. It will be used somewhere. Let's understand the meaning or difference between energy level and energy state. So let's understand it by an analogy. Let's just say there is a one building. In this building there are a lot of floor. Floor 1, floor 2, floor 3. 3 floors are there. So these floors are known as energy level. Now on this floor there could be a lot of rooms as well. Let's just say on this floor there are 3 rooms. On this floor there are 2 rooms. On this floor there is 1 room. So this room is known as energy state. That's it. This is the difference between energy level and energy state. A lot of places I have seen that people will use energy level, energy state continuously. Like they would say energy level and energy state both are the same thing. No. When we study Fermi directed distribution, at that time I will tell you there is huge importance of energy level and energy state. So Fermi direct distribution is defined for energy state, not for energy level. So this was your energy level, n equals to 1, n equals to 2 energy level, n equals to 3 energy level. Now on one energy level, here you could see that on n equals to 1, on one energy level there were 2 electrons, n equals to 2. On this one energy level there were 8 electrons, n equals to 3. On this one energy level there were 8 electrons, right? So on a particular energy level there can be more than one electron. N equals to 1, 2 electrons, n equals to 2, 8 electrons, n equals to 3, 8 electrons. So on one particular energy level there can be more than one electrons, but on one energy state there can be only one electron of the same spin. Forget about this word spin. Somewhere I would have written spin. Forget about this word. This is related to chemistry. You don't need to worry about it. And if you have studied in class 12th, this is known as opposite spin, and this would be the same spin. So of the same spin, we will be considering only the same spin. You don't need to worry the word same spin. You can just ignore it. So what I am saying is that on this particular floor, two people can be living. Here also two people can live. Here three people can live. But in one room, only one people will live. In one room, only one person will live. Are you able to understand this point? So on different energy levels, energy level 1, 2, 3. On energy level 1, 2 electrons can be there. Energy level 2, 8 electrons can be there. Energy level 3, 8 electrons can be there. But at one energy state, only one electron would be there. Are you able to understand this point? So this is what I have written. Energy level is like a floor. Imagine a building with several floors. Each floor represents a specific amount of energy that electrons can have. Okay. So n equals to 1 will have a specific amount of energy. Now what is this energy state? It is like a room on the floor. So each floor can have many rooms. Each room is a specific position an electron can occupy at that energy. So on this energy level, this is like a specific position that electron is occupying. So this is known as energy state. So energy level and energy state both are complete different thing. Are you able to understand this point? So example also I have given. Floor 1 is energy level 1. Room 1 on floor 1 is like energy state 1. Room 2 on floor 1 is like energy state 2. So electrons can be on the same floor. That means electron can have the same energy level, but it has to be there in the different energy state. Same energy level but different energy state, and according to Pauli's exclusion principle, you don't even need to remember the name of the scientist. Only thing you need to remember is that in one energy state only one electron can lie. In one energy state only one electron can lie of opposite spin, of the same spin, of the same spin. But spinning and all these things is not important, although this subject should be understood by the quantum mechanics. Okay, but we are not going to understand quantum mechanics here, because quantum mechanics, if you need to understand, that means you should have taken engineering physics, but you are studying electronics engineering. Okay, so quantum mechanics and everything you will study if you do your research into the devices. In future, after clearing the gate examination, if you go for masters or PhD in devices only, then you will understand this subject from the quantum mechanics part. So we will start by the psi function there. Okay, so from that kind of that we will start. Probability distribution function. So from there they will start. But here we are understanding on the top level only. So there you will understand the meaning of opposite spin and same spin. Right? So from this slide, what do you understand? On one particular energy state, only one electron will be there. That's it. This is what you understand from this particular slide. Okay. Now there is something called electronic configuration. Now you might be thinking that, sir, we are studying discrete topics. Like first we understood the meaning of energy, then sir, this energy of hydrogen atom came into action. Then in between we are studying energy level and energy state. Now we are studying electronic configuration. So everything will make sense. You need to have some patience. Okay, everything combined will make sense. Just have some patience. So there is something called electronic configuration, which you might have studied in class 11, 12th chemistry. Even if you did not study, don't worry. So in hydrogen atom there is only one electron. So this is how I will represent it, 1s1. So 1s is like a energy level. 1s is like a energy level. In this energy level there is only one electron. And silicon atom, what is the atomic number of silicon atom? That is 14. So there will be 14 electrons. So 1s2, 2s2, 2p6, 3s2, 3p2. So this s is like an energy level. This energy level can have 2 electrons. This p is like an energy level. This p can have 6 electrons. This s is an energy level. This is like a floor. This is also one floor. On this floor 2 rooms are available. On this floor 6 rooms are available. In this hydrogen atom, in this particular floor 2 rooms are available, no? So out of these 2 rooms only one room is filled. On this particular floor 6 rooms are available. Out of these 6 rooms, here 2 rooms are completely filled, 2 rooms are completely filled, 6 rooms are completely filled. But look at this side. So 2 rooms are completely filled, but here 6 rooms are available. Out of these 6 rooms, only 2 rooms are filled. So always we will care about the outermost cell. What I am saying, always we will care about the outermost cell. So this is the outermost cell here. These 4 electrons are the free electrons. What I mean to say is that, let's just say this was our nucleus. Then this was n equals to 1, n equals to 2, n equals to 3. Okay. So here there were 2 electrons. Then 8 electrons were there. 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then 4 electrons. Now these 4 electrons can make the bond with the other atom. Let's just say these 2 atoms come closer, then this electron and this electron can make the bond. These electrons are near to the nucleus, so they are bound by the nucleus, but they are farther away from the nucleus. That means they are more free. So who will be contributing in making the bond? Why we are caring about making the bond? Because now we have studied about atom, right? We have already studied about atom. This is one atom. Now what we will do? We need to make the material. What is our target? Our target is making the material. So now we need to take atoms closer. One atom is here, one atom is here. 2 atoms are very farther away. They will not make any material. If I want to make the material, I need to take the atoms closer, right? If I need to take the atoms closer, then what will happen? These electrons will be influenced by these electrons. Previously, here what I have written, isolated hydrogen atom. That means this hydrogen atom which is not in the influence of any other hydrogen atom. So this electron is getting only one force, that is through this nucleus. That's it. This electron and this electron is not making any force. This nucleus, this electron not making any force. This nucleus, this electron not making any force. This nucleus not making any force. That means they are isolated. That means they are further away. They are far. There is very huge distance between both of them. So if there is huge distance between both of them, that means they are not going to make any bonding. And if they are not closer to each other, there is no bonding. That means there will not be any material. To make the material, we need to take them closer. So which electron I will be caring about? I will be caring about the outermost electrons. So I will be caring about these 2 electrons, and these outermost electrons are present in the outermost cell, outermost energy level. So this outermost energy level is known as valence shell. Okay, what this is known as? Valence shell. Okay, so these outermost energy level is known as valence shell. Here what is the valence shell? Here only one electron is there, so this is the valence shell. So my major matter of concern will be towards the valence shell. Okay, so I will be caring about these 4 electrons when I consider silicon. When I am considering hydrogen, I will be caring about this 1 electron. Now what I am doing is that I am bringing 2 hydrogen atoms together. Why I am doing so? Because I need to make the material. So previously hydrogen atoms were further away. So now I am making a graph. What graph I am making? I am plotting electron energy versus interatomic distance. What is the meaning here? The meaning is, when they are further away, when these 2 hydrogen atoms are further away, that means distance is very large. That means you are somewhere here. The distance is very large. When the distance is very large, at that time this electron is not getting affected by this electron. This electron is not getting affected by this nucleus. This nucleus is not getting affected by this electron and this nucleus. Basically, this electron is only feeling the force of this nucleus, and this electron is only feeling the force of this nucleus. That's it. So if they are farther away, so what will be the energy of this particular electron? It would be minus 13.6 divided by n square electron volt. And what will be the energy of this electron? Minus 13.6 divided by n square electron volt. So both will have the same energy, and both are on the same floor. What is that floor? That floor is 1s. That floor is 1s. Listen to me very carefully, otherwise you will not be able to understand. So both of the electrons are on the same floor. That floor is known as 1s. Both electrons are here. Now you let me know how many rooms are available on this 1s floor. On this 1s floor, how many rooms are available? So for one hydrogen atom, in 1s floor there are 2 rooms, and for other hydrogen atom on 1s floor there are 2 rooms. So here there are actual 4 rooms available. Like, what did I make here? This is the energy I am plotting. This is the energy I am plotting, and this is the interatomic distance. This is the interatomic distance. Like, this distance could be some r naught distance. This distance is r naught. So at the r naught distance, they are not getting affected by each other. That means both electrons are having the same energy. That could be anything, minus 13.6 divided by n square electron volt, minus 13.6 divided by n square electron volt. Now I am saying that this 1s floor is actually having 4 rooms. Do you understand this point? Why 4 rooms? 1s actually has 2 rooms only. 1s actually has 2 rooms, and P actually has 6 rooms. Okay, P will actually have 6 rooms, S will actually have 2 rooms. But since there are 2 1s floor, this 1s floor, this 1s floor, but we have to make the same level because they are having the same energy. So in 1s floor there are 2 rooms, so there are 2 1s floor, so there will be total 4 rooms. That means in this 1s floor there are 4 energy state. Did you understand this point or not? A very important point. This is one energy level, but in this one energy level there are 4 energy state. Did you understand this point or not? And since the hydrogen atom are far away, their energy of this electron is same. But now what will happen? We are reducing the difference between these 2 atoms. What we are doing? We are reducing the distance between these 2 atoms. Reducing the difference between these 2 atoms, that means on the graph we will be moving in this direction, because interatomic distance is being reduced. Interatomic distance is being reduced. What does that mean? That means you are moving in this direction. So as you move in this direction, what will happen? Now this electron will start getting influenced by these electrons. This nucleus will start putting some force on this electron. This nucleus will start putting some force on these electrons. So now the electron energy will change. So there were total 4 rooms. In one room this electron was lying, in one room this electron was lying. When they were far away, they had no problem. But just as they came closer, just as they started coming closer, then their energy level will split. What will happen? Energy level will start splitting. So here there were 4 energy states. Here there were 4 energy states available. As the distance decreases, so what will happen is that the atoms will say that our energy is changing now. So previously this was our energy, but as the distance changed, as they are coming closer, they are being influenced by the other electrons, and since they are being influenced by the other electrons, their energy will change. So at this particular time their energy was this much. Now the energy will change. Sir, it will reduce or it will get higher, you don't know. The energy will change. That thing you know. The energy will change. So there were total 4 rooms. Now these 4 rooms are splitted. Initially all 4 rooms were on the same level, but since the atoms are coming closer, their energy are getting changed, and now these 4 rooms are split. These 4 rooms are split in this manner. Now I will tell a statement that you need to remember, that electrons are lazy. Electrons are lazy. How many electrons you are having? 4 energy states are there and 2 electrons you are having. So electrons are lazy, so they will always occupy the lower energy state. So these 2 electrons will come here. Electrons are lazy, they will always occupy the lower energy state. So there were total 4 states. All states were there at the same level, but just as the atoms came closer, these electrons were getting influenced by the nucleus of the other atom, along with that the electron of the other atom as well. So previously this electron was getting a force of only this electron, but now this electron is getting a force of this electron, this nucleus and this nucleus. So 3 forces are acting upon it, so their energy will change. So if their energy is, it's like you can understand by an analogy that initially you guys were living on the same floor, okay, This was the floor of your hostel room. You were living on the same floor, but you were far away. You were far away. You were not friends, neither friends nor enemy. But just as you started getting closer, you got to know strange thing about each other, right? Like this guy drinks a lot, this guy smokes a lot, this guy studies a lot. So you guys got to know strange things about each other. So just as you guys started coming closer, you got to know that we have to take rooms on the different floor. Or what you will do, you will take up your complete room and you will move to the different floors. So there were actually 4 rooms. 2 rooms were empty and 2 rooms were filled. So on one level only there were 4 rooms, but what you did, you just took the rooms on the different floors now. You just took the complete room, you made a different floor. You took the complete room, you made a different floor. This room also made a different floor. This room also made a different floor. But you guys are lazy, you will occupy the lower energy states. So there are 4 energy states. Out of these 4 energy states, you will occupy the lower energy state. Are you able to understand this point or not? Okay. Sir, what will be the structure? Like how this energy level structure is like this only. Why it is not like this? So all these structures are understood by the differential equation, by the quantum mechanics. So with respect to psi function, you will solve a second order differential equation, and then you will get all this theory. Like all these theories are understood by quantum mechanics only, but you don't need to study quantum mechanics. If I start teaching quantum mechanics, then you will lose the interest here only. You will feel like that EDC is very difficult. So that part we are not going into, right? So that's why in the easiest possible manner I am trying to explain this particular concept. Okay. Once you get into research, like in the industry, these works are not there. Like if you get a job, then in the job you might not be doing research on devices. You might be working on circuits only. But once you get into some good college or some good university for your research, then the research would be based on devices. Okay, so there you will understand everything right from the scratch from quantum mechanics only, but as of now you will understand in this manner only. So just as the atom started coming closer, the electron of the atom are getting influenced by the nucleus of the particular atom and the nucleus of the other atom and the electron of the other atom. Then their energy is getting changed, so energy levels are splitting. You are getting 4 energy state. Out of these 4 energy state, 2 energy states are filled, 2 filled energy state, and 2 energy states are empty. To empty energy state. So just as you keep on reducing the difference, just as you keep on reducing the distance, okay, just as you keep on reducing this distance, there will be one equilibrium distance. At that particular distance, the bond will be made. Are you able to understand this point? Like when they were further away, there was no bond. Coming closer, 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 at one distance, at one particular distance, there will be a stable bond, and that will be more than enough to make a material. So only 2 atoms will never make the material. This is just we are understanding by the example of 2 atoms. Like there will be a lot of atoms. You will keep on taking the atoms closer and closer. Are you able to understand this point? As of now, we are understanding only with respect to 2 atoms. When we study silicon, we will understand with respect to n atoms. First, we will understand with respect to 2 atoms. Then we will understand with respect to n atoms. So as they keep on coming together, the energy levels will. Then there will be a lot of energy states, right? So a lot of energy level will be splitted into energy states. The lowest energy states will be occupied by the electrons, and the higher energy states will not be occupied by the electrons. They will be empty, and there will be one distance. Let's just say this is the equilibrium distance. What I am saying, let's just say this is the equilibrium distance. So there will be one equilibrium distance where the bond will be made. Let's just say this is the equilibrium distance. So I am calling this distance as A0. So at that particular distance, the bond will be made, and that would be enough to make the material. So did you understand this analogy? We have given the theory as well. When many hydrogen atoms are brought close together to form a solid, the outermost electron of each atom begin to interact with the electrons and the nuclei of the neighboring atom. This interaction slightly shift the allowed energy of each electron because the Pauli exclusion principle states that no two electron in the entire system can have the exact same energy state. So I told you on one energy state only one electron can be present. So it's not that sir, two electrons are there, so they will be lying on the same energy state. No, they cannot lie on the same energy state. In one energy state only one electron would be there. So this is what I have written here. As a result, the single discrete level of an isolated hydrogen atom splits into a large number of closely spaced level. Okay, so this is single level has been splitted into the closely spaced energy levels, and this closely spaced energy level is known as energy band. Okay, so this continuous range of frequency, is known as energy band. Sorry, not frequency. This continuous range of energy is known as energy band. This continuous range of energy is known as energy band. So a lot of energy states are there. So a lot of energy states are there, and the distance between these energy states is very low. This distance between these energy states will be very low. Okay, so this is known as energy band. Combined we call it energy band. Okay. Thus, in a solid made from hydrogen atom, the original discrete atomic level give rise to a structure of continuous energy bands due to atomic interaction, and this is the same fundamental mechanism of band formation in all solids. So now we will understand it with respect to silicon. Why silicon? Because silicon will give you a semiconductor. So the same theory that we have understood for hydrogen, the same theory we will understand for silicon now. Okay, the same theory we will study for silicon. Is that clear to you? So I hope till this point we have spent 1 hour here. So in this 1 hour, like in the examination it might not be useful for you, but to understand the subject, you should be at least understanding that how semiconductors are made, how a particular material is made. That there would be one material. In the material, what will happen? There will be atoms. In the atom, there will be nucleus and there will be electron. Then we understood about the energy of the electron, and then we understood that if we are bringing two atoms together, then what is happening? They are framing a energy band. They are framing energy bands. In the lower most energy states, the electrons are occupied. So there are a lot of energy states. The electrons will be occupying the states of lowest energy. So these are the state of lowest energy, because I told you as we go upward, the energy will increase. So they are occupying the lowest energy states. Is that clear to you? Now similar analogy we are going to understand for silicon. But before that, I will take a break, drink some water, and then I will come back. So you can also drink some water, and then we will start studying the similar theory for silicon atoms. So in the silicon atoms, who will be our matter of concern? They will be our matter of concern because they are the valence shell. So in n equals to 1 there are 2 electrons, in n equals to 2 there are 8 electrons, and then this is the S energy level, this is the P energy level, 2 electrons, 2 electrons. So they will be there to make the bonds. So these two energy level will be making the bonds, right? So they are our matter of concern. So we will understand the theory. What we will do is that first we will bring two silicon atoms together, and then we will see what happens. So here there was only one valence shell, that was 1s, but here there are two valence shells, 3s and 3p. So let's see what happens. Okay then, yeah. So let me take a break and then I will come back. Yeah, welcome back guys. So we need to study about energy band formation in silicon now. So what is energy band? Energy band means these continuous energy states, right? So when you see these energy states are continuous, so these continuous energy states are collectively they are known as energy bands. So same kind of energy band that we have studied in the hydrogen atom, the same kind of energy band will be made in the silicon atoms as well, with respect to the silicon atoms as well. So this is one silicon atom. Now what we are going to do is that we are going to bring two silicon atoms together. So this is one silicon atom, this is another silicon atom. In the outermost shell you are having 4 electrons. In silicon, in the outermost shell you are having 4 electrons. So only outermost shell I am making, okay, and surely there is nucleus. 4 electrons we are having, so only the outermost shell we are making. Interatomic distance, initially they are farther away. So if they are farther away, that means these 4 electrons, everyone will have the same energy level. Not everyone will have the same energy level. Like in 3s there are 2 electrons, right? And in 3p there are 2 electrons. So 3s will have the same energy level and 3p will have the same energy level. right? So 3s will have the same energy level and 3p will have the same energy level, although these will be very nearer. Okay, here the distance will be very low, right? But still we are making it farther. So whatever the electrons are there in the 3s energy level and whatever the electrons that are there in the 3p energy level, so they will have the same energy and they will have the same energy. So in 3s, for one silicon atom in 3s there are 2 electrons. So for 2 silicon atom in 3s there will be 4 electrons. Say yes or no? And for one silicon atom in 3p there are 2 electrons. Then for 2 silicon atoms in 3p there will be 4 electrons. For 2 silicon atom, we are making it for the 2 silicon atom. We are bringing 2 silicon atoms together. We are plotting electron energy with respect to interatomic distance. As of now, the interatomic distance is very high. That means they are very farther away. If they are farther away, that means this electron is also influenced by this nucleus only. This electron, this nucleus, this electron, this nucleus, this electron, this nucleus. Although they are in the slightly different energy level. Like this is known as n equals to 3 only. This is your n equals to 3 level only. This is your n equals to 3 level only. But in n equals to 3 level, there are 2 orbits, s orbit and p orbit. S orbital and p orbital. Okay, so they have slightly different energy level. Slightly different energy levels are there. So it might happen that these two are having different energy and these two are having different energy. Almost nearly the same energy level they will have. Okay, and since they are not influenced by each other, so they will have the same energy. So whatever that are available in 3s, they will have the same energy, and whatever that are available in 3p, they will also have the same energy. So total 4 electrons here, 4 electrons here. So total 4 here and 4 here. 8 electrons are there. Is that clear to you? Now, how many states are there in 3p? So 3p, one level of 3p have 6 rooms. One level of 3p have 6 rooms. Out of these 6 rooms, only 2 are filled. Other level of 3p also have the 6 rooms. Out of these 6 rooms, only 2 are filled. So there, in this particular scenario, 2 atoms are coming closer. That means total 12 energy states are there. Total 12 rooms are there. Out of these energy states, how many states are filled? 4 filled energy states. Do you agree to this point? What about 3s? In 3s, how many rooms are there? 2. For one atom, for the other atom as well. For one atom, for the other atom as well, 2 rooms are there. In this atom, 2 electrons are filled. Here also, 2 electrons are filled. So total 4 energy states are there. And all 4 are filled. So total 12 energy states were there in the 3p floor. On the 3p floor, 6 rooms, 6 rooms. Total 12 rooms were there, only 4 were filled. On 3s floor, 2 rooms, 2 rooms. Total 4 rooms were there, all 4 were completely filled. So total energy states are 12 plus 4, 16. Out of those, 8 states are filled. Now what will happen is that they will start coming together. And as they start coming, they will start coming nearer. So if they are coming nearer, then what will happen is that these electrons will get started influenced by this nucleus and these electrons. So now the energy of these electrons will change. So energy level will start splitting. So what will happen is that this energy level will start splitting in this manner, and this energy level will also start splitting in this manner. At some point of time, they will become one energy level only. Like they will merge these two energy level, you can say, or better I should have said energy states. So these energy states have started splitting now. These energy states have started splitting now. At one point of time, they will become together, but after that they will split again. So this kind of energy level splitting you will get. A rough diagram I have made. Sir, how do you get the complete idea of this diagram? So complete idea of this diagram you will get from the wave function. But on a brief level, you can see what really happened? The energy level started splitting. Energy level or energy states started splitting. So this is going like this only. Basically, like this energy level has started splitting in this manner, right? And this energy level has started splitting in this manner. So what you can see is that first they are merging here, and then it is being separated again. This guy is going here and this guy is going here. Like first they will merge and then they will be separated again. Are you able to understand this point? Like, sir, how this kind of waveform only came? Sir, how this is how in this manner only they are splitting. So everything will be explained when you solve this second order differential equation of wave function, of phi function, of this xi function, of this wave function. When you solve the second order differential equation, then this waveform will come. But on the crude level, on the surface level, you just need to see that as they are coming together, that means they are being influenced by each other's nucleus and electrons, and then their energy level will split, right? So now you let me know how many total states are there. How many total states are there? 12 here and 4 here. So total energy states are 16. 12 energy states of this one, 4 energy states of this one. So total energy states are 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Total energy states are 16. Out of these 16 energy states, 8 energy states are filled. 4 plus 4, 8 energy states are filled. So 1, 2, 3, 4, 5, 6, 7, 8. Why I am starting from the bottom? Because I told you electrons will always occupy the lower energy states. And then again it is splitted. So when again it is splitted, what really happens is that 8 energy states will be downward and 8 energy states will be upward. Out of these energy states, out of these 16 energy states, 8 energy states are filled. And now this particular distance that we are getting, this particular distance is the equilibrium distance. So this I am calling as A naught. Like when you have taken these two atoms at A naught distance, at that time they will frame the bond. Like what I was doing, I was reducing the interatomic distance. Started from here, reducing. Just as the distance has become A naught, at that time you will see that yes, silicon crystal has been made. What do you mean by silicon crystal? That means silicon. Here we are talking about only 2 atoms, but we will talk about n atoms as well. So those silicon atoms will keep on coming closer. So then they will frame this kind of silicon crystal. So a lot of silicon atoms will come together. They will make the bond. This bond is known as covalent bond. So this silicon crystal will be made. So this would be the equilibrium distance. Are you able to understand this point? So this is known as equilibrium distance. So did you understand what is happening here? The only confusion part would be there that sir, first they are merging and then they are splitting. First the energy level, this was here all the electrons were there in the same energy level, all the electrons were there in the same energy level. Then what really happened is that both of the energy level splitted into energy states. Now first the energy states were merged and then they were splitted again. So this analogy we cannot explain. Actually here what really happens is that the bond is very weak. Silicon atoms are coming closer, they will frame a bond. Here as well they will frame a bond, but that bond is very weak. But once you reach here, this bond is stronger. And this is the equilibrium state. So first they will merge and then they will split. There is no reasoning. You cannot, like there is reasoning, but I cannot explain it here. Are you able to understand this point? So total states 12 here, 4 here, total 16 energy states were there. Out of those only 8 rooms were filled. Out of those 16 rooms only 8 rooms were filled and electrons will occupy the lowest energy rooms, or you can say lowest energy states. Okay, so this is what is happening. Now these lowest energy states are known as, now energy states, these are very continuous energy states, no? Like these are 8 energy states. Similarly here you made 4 energy states. They were very continuous. So collectively what I called energy band. So collectively here as well what you will call energy band. So these energy states and these energy states, the energy states which are there at a very minute distance, at a very lesser distance, that means this energy state, then this energy state, this energy state, this energy state, this energy state, they are at a very less distance. So they are known as energy band. Okay, energy band. So now this band will be known as valence band and this band will be known as conduction band. Why this is known as valence band? Because all the valence shell electrons are coming here only. All the valence shell electrons, 2 plus 2 4, 4 electrons of one atom and 4 electrons of other atom. So total 8 electrons. All the 8 electrons are coming in this energy band. So if all the 8 electrons are coming in this energy band, then this energy band is known as valence band. What it is known as? Valence band. And this is known as conduction band. Sir, why the name is conduction? You will understand it. When we study the semiconductor, when we study the working of semiconductor, you will understand why we call it conduction band. Because if the electron reaches here, if the electron reaches in this energy band, then it will conduct the current. That's why it is known as conduction band. Sir, how it will conduct the current, that we will see. But as of now, what you need to see is that all the valence shell electrons are being occupied by this energy band. That's why it is known as valence band. Other electrons, if the electrons reaches here, if the electrons reaches in this energy band, then it will conduct the current. That's why this energy band is known as conduction band. And the gap between conduction band and the valence band, the gap between the lowest energy level of the conduction band and highest energy level of the valence band, this is known as forbidden energy gap, or it is known as band gap. All the theory will be written, don't worry about that. What I am saying, the gap between the lowest energy level of the conduction band and highest energy level of the valence band, that is known as band gap, or it is known as forbidden energy gap. All good? More points are there, we will see one by one. But as of now, in conclusion or in summary, what do you understand? You are having 4 valence shell electrons. 2 electrons were there in the s orbit, 2 electrons were there in the p orbit. Both of them were having nearly the same energy, Now you are bringing 2 silicon atoms together. That means 4 electrons in 3s, 4 electrons in 3p. But 3p can have 12 energy states and 3s can have 4 energy states. All electrons are filled here. Here 4 filled energy states are there, 8 empty energy states are there. Since the electrons are coming together, they are being influenced by the nucleus and electrons of the other atom. Since they are being influenced by the nucleus and electron of the other atom, their energy of a particular electron will change. So the energy level will split into energy states. These energy states are continuous, that's why it is known as energy bands. Electrons will occupy the lowest energy level of the energy band. Further, they are again split into different energy bands. The energy band which is occupied by the valence shell electrons, that is known as valence band, which is completely filled. And other band is known as conduction band, which is completely empty. Is that clear to you? So this is the complete theory of bringing 2 silicon atoms together. If I bring n silicon atoms together, then this will be the scenario. So just let me know one thing. If I bring n silicon atoms together, so this will also have 3s orbit, 3p orbit and 3s orbit would be there. In one silicon atom, 3s orbit has how many rooms? 2 rooms. 3s orbit will have 2 rooms. So in n silicon atoms, 3s will have 2n rooms. So 2n states are there. What is the electronic configuration? 3s2, 3p2. So all the 2 rooms are filled. So here also all the rooms will be filled. So 2n states are there, 2n electrons have been there. All the 2n states are filled with the electrons. What about 3p? In 3p, in one silicon atom, how many rooms are there? In one silicon atoms, 3 rooms are there. That means, 6 rooms are there. That means 6 energy states is there. In 3p, for one silicon atoms, 6 energy states are there. For n silicon atom, how many energy states would be there? For n silicon atom, 6n energy state would be there. 6n energy state would be there. What is the electronic configuration? 3p2. Out of these 6 states, only 2 states are filled. In one silicon atoms, 2 states are filled. So in n silicon atoms, 2n states would be filled. So 2n electrons are there. So total 8n states. total states are 8 and filled states are, how many filled states are there? Filled states are 2n, 2n, 4n. 4n filled states are there. Is that clear to you? Is this theory clear to you? You can simply relate it with the previous diagram. Here n was 2. In this particular diagram n was 2. So 16 total states were there, 8 were filled. 12 states were there, 4 were filled. You can see 12 states were there, 4 were filled. Here n equals to 2, you put 4 states were there, 4 were filled. 4 states were there, 4 were filled. Now if they are coming together, then what will happen? First they will be merging, all the states will be merging. First the states are split. First that states are split, right? States are split and then they again merged. So here they are split and then they merged. Here they merged and then again split, right? So here total 4n states will come into action. When n was equals to 2, here total 8 states came, right? 8 filled state, 4 filled state, 4 filled state. So total 8 filled states are there. So in the similar manner, here total 4n states would be there and all the states will be filled. So 4n states with 4n electrons. So here total 4n states would be there. Total 4n states would be there and every state will be filled with the electron. Every state will be filled with the electron. And here also total 4n states would be there and all the states will be empty. And this is known as lowest point of the conduction band, lowest energy point of the conduction band, and this is the highest energy of the valence band. And the difference between the lowest energy level of the conduction band and highest energy level of the valence band is known as forbidden energy gap. Are you able to understand this point or not? Whatever the example, whatever the time that I have spent for 2 silicon atom, the same time, the same theory is there for n silicon atom as well. Is that clear to you or not? I hope it is clear. I don't think that I need to explain this, how this 4n state came into action, how this 0 electrons came into action. I hope everything is clear. Total states available were 8n states. Out of those, 4n states were filled. When energy level split into energy states, energy level were split into energy states. Then it was merged and then again splitted into the energy states. Now electrons will occupy the lowest energy state. Electrons will occupy the lowest energy states. So these are the lowest energy states. So how it is split? It is split in a manner that 4n states come downward and 4n states goes upward. So 4n states are having higher energy, 4n states are having lower energy. And electrons will occupy the lower energy states. And since these energy states are closely spaced, since these energy states are continuous, that's why it is known as energy bands. And now all the valence shell electrons are coming in this particular energy band. So this energy band is known as valence band. Okay, and if the electron reaches from here to this particular energy band, if the electron reaches from valence band to this particular energy band, then our semiconductor will conduct the current, and that's why this band is known as conduction band. Okay, so this uses of conduction band we will study later on, but as of now what you are able to understand, that energy levels are split into two bands, valence band and the conduction band. So let me make the valence band and the conduction band. So how will I make it? So what you can see is that this is the bottom of the conduction band and this is the top of the conduction band. This is the top of the valence band and this is the bottom of the valence band. And here there are states, 4n states here. So I am making 4 states only, 4n states are there, so I am making 4 states. And here also 4 states I am making. Here also total 4n states. Out of these 4n states, all the states are filled with electron. All the states are filled with electron. But these states are completely empty. This is known as conduction band. What this is known as? Conduction band. And this is known as valence band. The lowest energy level of the conduction band is shown by EC. Okay, lowest energy level of the conduction band is shown by EC. The highest energy level of the valence band is shown by EV. The energy gap between both of them is shown by forbidden energy gap, EC minus EV. Okay, well and good. Sir, how this conduction band, how, and this completely, this phenomena is known as band diagram. So sir, why this band diagram is important? You will slowly understand. Okay, now we are moving towards a semiconductor. So slowly you will understand that sir, why this band diagram is important. But did you understand this band diagram? Like, this is a very typical theory which we are understanding in the simplest words possible. Okay, now we will relate the band diagram and the crystal structure. What do you mean by crystal structure, sir? Like, there would be silicon atoms, no? One silicon atom, two silicon atoms, and three silicon atom, four silicon atoms. Now they are coming closer. So n silicon atoms are coming closer, no? Right? These n silicon atoms are coming closer. So let's just say this was one silicon atom. This silicon atom, in the outermost shell, it was having 4 electrons. This was another silicon atom, again in the outermost shell having 4 electrons. Another silicon atoms, outermost shell having 4 electrons. Again there is silicon atoms, outermost shell having 4 electrons. Again silicon atom, outermost shell having 4 electrons. And they are making the bond. They are making this covalent bond. These 4 electrons, 4 electrons, 4 electrons, they are making the covalent bond. Now these electrons will also make the covalent bond from some other silicon atom. This will also make the covalent bond. This will also make the covalent bond. All these silicon atoms will make the covalent bond with the other silicon atoms. So a lot of silicon atoms will be there, and silicon atoms are there which are making the covalent bond. Okay. Now this diagram, this is the crystal structure of silicon. This will be there in the 3D. So in the, like, this we are looking in 2D. So in the 3D it would be there actually. Okay. So this is diamond structure would be there, which will be there in the 3D. So what kind of structure would be there, that you don't need to care about. Just telling that this structure will be there in the 3D. Now we are able to, now we will relate it to band diagram. What do you mean by band diagram? In band diagram there are two kind of bands, valence band and the conduction band. Valence band and the conduction band. So this was the valence band, this was the conduction band. Both of the bands are having the same number of states, but here all the states are filled and here all the states are empty. So if I interrelate, what is the meaning here? Like here, do you see any free electron? This guy was having 4 electrons, all the 4 electrons are making the bonds with the other electron. This guy is having 4 electrons, all the 4 electrons are making bond with the other electron. 4 electrons, all are making bond with the other electron. So there is no free electron. There is no free electron, that means all the electrons are present in the valence band only. Are you able to understand this point? There is no free electron available. That means all the electrons are present in the valence band. So whenever I say there is no free electrons, there are bound electrons. So all the bound electrons are shown in the valence band. So all the bound electrons are having the lowest energy. Why they are having the lowest energy? Because they are bound, right? If they were free, that means they were having higher energy. So by any means, if they become free, that means they will go from valence band to conduction band. This is the meaning. Like, this is how you can relate the band structure, this band diagram with crystal structure. Like, electrons are there in the valence band. What is the meaning of that? The meaning is that all the electrons are bound. They are making the bond. But what if this electron gets free? This electron gets some energy and it gets free. That means what? How I will show it, that this electron has gone to this place. Are you able to understand this point? So again and again this theory will come up and you will be able to understand it. Don't worry about that. Again and again when we study intrinsic semiconductor, extrinsic semiconductor, again and again I will be making this crystal structure and this band diagram, and again and again I will be interrelating it. So slowly you will understand more, but as of now, this is the scenario that silicon, everywhere silicon would be there. 4 electrons are there, all are making the bond. That means all are bound. No free electrons are there. So if there is no free electrons, that means there is no electron in the conduction band. All are bound, that means all electrons are there in the valence band. So this is the meaning of this diagram actually. Okay. So total you are having 4n electrons. All the 4 electrons went into valence band. That means all the foreign electrons are making the bond. No free electron is there. If there was any free electron, then it would have occupied the conduction band, not the valence band. What do you mean by band? Continuous energy states are known as band. Continuous energy states, since these energy states are having very lesser gap. If it was having larger gap, then it would not be called valence band, but they are having very lesser gap, that's why it is known as bands. Okay, now since all the valence shell electrons are coming in the lowest energy band, that's why it is known as valence band, and it is known as conduction band. So this complete theory I have written. So in the whole EDC, I will make sure that you get the best possible theory in the best possible language. So very easy language, you will be able to understand everything. So let's read it out. A single isolated silicon atom has well-defined electron energy levels 3s and 3p. 3p is written there. 3s level can hold 2 electrons and 3p can hold 6 electrons. Now 3s orbital has 2n states, because if n silicon atoms, if we talk about n silicon atoms, then 3s orbital will have 2n states and 3p orbital will have 6n states. When many silicon atoms are brought closer together to make a crystal, these states will further split into very closely spaced levels due to interaction between neighboring atoms. You understood this part? Like if there is interaction between the neighboring atoms, that means one electron is putting some force on the other electron. One nucleus is putting some force on the other electron, right? Forming two distinct energy band. The lower energy band is known as valence band with the 4n fully filled energy states at 0 Kelvin. Okay, so everything we are talking about at 0 Kelvin. 0 Kelvin temperature. Okay, and the upper band is known as conduction band with 4n empty states at 0 Kelvin. So these states are empty, these states are completely filled. Separated by an energy gap where no electron can exist. So first I will mark these lines. Conduction band, 4n fully filled energy states at 0 Kelvin in the valence band, and in the conduction band 4n empty states. Okay, separated by an energy gap where no electrons can exist, and this energy gap is known as forbidden energy gap. Okay, for silicon this energy gap is 1.1 electron volts at room temperature. Approximately it is 1.1 electron volt at room temperature. This energy gap at room temperature for silicon, this energy gap is approximately 1.1 electron volt. Okay, so all these theory I have again written. This is the conduction band, this is the valence band. Energy band diagram for semiconductors I have made. Conduction band, valence band. Lowest energy level of the conduction band is known as EC. EV is known as highest energy level of the valence band, and forbidden energy gap is now given as EC minus EV. Let's just say this EC was 10 electron volt and this EV was 9 electron volt, then EG would have been 1 electron volt. Okay, now you would see that this diagram I have made, then one energy state, then other energy state, and then what I have done is that these energy states are very near. Here also I have done this one energy state, another energy state, and then the energy states I am making very near. So like sir, how it happens, that knowledge you will not have. For that you would require very higher order mathematics. So you just need to remember one thing, that as you go higher in the conduction band, the effective density of the states increases. That means if I go higher, then here the density of states are increasing. What do you mean by density of states? The number of states are higher here, and here also the number of states are higher. So as I go lower in the valence band, the number of states will become higher. The effective density of the states will increase. So this point you just need to remember, nothing else. No mathematics is required that sir, if I go higher, why the number of states are increasing? No one will ask you that. Just if you see this kind of diagram anywhere, you should know that as we go higher in the conduction band, the effective density of the states will increase. As we go lower in the valence band, the effective density of the states will increase. Okay, and this density of state, this effective density of state, this DOS concept will also come into action when we study Fermi direct distribution. So when we study Fermi direct distribution, this concept will again come into action, and again I will discuss it. But there also I will tell you only one point, that the density of state will increase as you go higher in the conduction band, and density of states will decrease as we go lower in the valence band. But when I am explaining the theory, look, here I was explaining the theory, so here I made the density same. At all the point I made the density same. So it might happen that even in the textbook as well, even in a lot of NPTEL lectures as well, you will see that educators or professor will make the energy levels same only, like the density of states they will make same. So just for the explanation purpose they can make it, okay, just for the explanation purpose they can make the energy levels in this manner, energy states in this manner. So don't think that sir you are drawing it wrong. Just for the sake of understanding they can draw in this manner, just for the sake of understanding they can draw in this manner, but actual diagram will be like this. Actual diagram will be like this. As we go higher the density of states will increase, as we go here as we go lower the density of states will increase. Okay, okay, then now some important points we will discuss and then we will again come back to our theory. Okay, so as of now what we have built up, we have built up this kind of silicon crystal, and in this silicon crystal at 0 Kelvin everything is happening at 0 Kelvin. That means there is no temperature, there is 0 Kelvin temperature. So everything is happening at 0 Kelvin temperature. So at 0 Kelvin temperature this is the scenario that valence band is completely filled and conduction band is completely empty, because all the electrons are bound, they are making the covalent bond, no electrons is free. Okay, but before that, before understanding the silicon crystal again, we need to understand some points, some very basic point which you might already be knowing. So some very basic point we are going to understand. So this is some material, it could be silicon material, it could be anything. So this is some random material. In this material there is a free electron. In this material there is a free electron. What it is? It is a free electron. Now what I did, I took this material, I connected some wire and I gave it some supply. I gave a supply of V0 voltage. What I did, I gave a supply of V0 voltage. Now if I say here there is zero potential, then what will be the potential here? V0, right? If this is 0, then this will be V0. Basic network analysis, I hope you know it. So across this material, let's just say this is the material. So across this material what I have done is that I connected some wire, I gave it some supply of V0 voltage. So here there is V0 voltage and here there is 0 volt. So V0 voltage I can show by positive and 0 volt I can show by negative. So positive and negative. So it's like here there is a positive charge, here there is a negative charge. Let's just say if here there was a minus V0 by 2 potential, then what would be the potential here? Plus V0 by 2. Because let's just say if I am saying that this potential is not 0 volt, this potential is actually minus V0 by 2. So what will be this potential? Minus V0 by 2 plus V0. So what that would be? Plus V0 by 2. So if I am showing this by negative, this I can show by positive, right? Very simple. So here I am showing 0, here I am showing V0. So this is positive charge, this is negative charge. Do you know what is the direction of electric field? Direction of electric field is always from the positive charge to negative charge. Electric field lines will always come out from the positive charge and will go into the negative charge. So direction of electric field will always be from positive to negative. Electric field, this is the direction of electric field. This is the direction of electric field. So on this material, this could be semiconductor material, this could be conductor, it could be anything. Just I am saying that this material is having some free electrons. This material is having some free electrons. That means here there will be this electric field present. This E field is present. How will I show the electric field? By this sign. I will not show the electric field by this. I will show the electric field by this kind of E. This is the electric field. Now if you have known some basics of EMFT, then in electric field E, if there is a charge Q present, then what kind of force it will have? That will be Q into E. In this electric field some charge Q is present, so it will get a force of Q into E. Now if this charge is positive, then the force on this charge will be in the same direction as the electric field. If this charge is positive, then the force on this, if this charge is positive, then the force on this positive charge will be in the same direction as the electric field. But if this charge is negative, then the force will be opposite to the direction of electric field. So this electron is negatively charged. This electron is negatively charged, right? And then there is an electric field in this direction. So where the electron will feel the force? The electron will feel the force in the opposite direction. So electron will move here. Are you able to understand this point? This material was having a free electron. When it was having a free electron, it was not moving. This electron was not moving. What I did, I connected a battery. Because of this V voltage, there was some potential. Because of this V potential, there was some electric field. This electric field was going from positive to negative. That means it was going from left to right. Because of this electric field, this electron was getting some force. Since it is negatively charged, so it got the force in the opposite direction of the electric field. Now, if you know one thing, if electron is moving in this direction, then the current will be opposite to it. If this is the flow of electron, then this will be the current because of the electron. The current will always flow in the opposite direction of the flow of electron. Very, very basic thing in class 11, 12th or in network analysis you would have studied it. If electron is flowing from right to left, then the current will flow from left to right. That means in this material the current will flow in this direction. So what all points I have written? Electrons move opposite to the direction of applied electric field. Electrons will always move. Electrons are negatively charged. That's why they will always move in the opposite direction to the applied electric field. This is the direction of the applied electric field. This is the direction of the applied electric field. So electrons will always move opposite to the direction of applied electric field. For the current to flow, electron must have a net motion. Look, this material was having free electron, but this electron was not moving. This electron was not moving. But what I did, I applied some potential. Because of that, there was electric field. Because of the electric field, there was some force. And if there is some force, that means it will move. So electron started moving. And since the electron is moving, now it will have some current. Now what will be the direction of that current? So the direction of that current would be opposite to the motion of electron. So if electron is moving here, then the direction of current would be this. So direction of current is this. Direction of current is this. So electrons will move here, here, here. Like if I talk electrons, it will move like this. Electrons will move like this. Okay. And the direction of current would be this. This would be the direction of current. This would be the direction of current. So you can see that this is the path of flow of electron. And this is the path of flow of current. So current always flows in the negative direction of the motion of electron. Is this point clear? Sir, why we are studying all these points? You will understand. Okay. You will understand why we are studying all these points. These points are very, very important. But as of now, you just need to see it that yes, we know these points. Now another point is there. We will do the discussion on energy bands. So first I have made a fully filled energy band. That means there are 4 states. All 4 states are filled with the electrons. Empty energy band. There are 4 states. All the states are empty. Partially filled energy band. There are 4 states. Out of these 4 states, 2 states are filled. Okay. Now you look at this point. For the current to flow, electrons must have a net motion. Do you see any electron here? No. If there is no electron, that means there cannot be any current flow. Do you see electrons here? Yes. Can the electrons move? What I am asking, this is a fully filled energy band. Can the electrons move? Where it will move? Can this electron come here? You will say that, sir, this electron can come here. No, it cannot come here. Why is that so? Because Pauli's exclusion principle says that in one energy state, only one electron can be there. So it cannot happen that, sir, this electron will come here. Or it cannot happen that, sir, this electron will go here. So in the fully filled energy band as well, there is no chance for the electron to flow. But what about partially filled energy band? Can this electron move here? Yes, because this room is empty. Let us say in one floor there are 4 rooms. In all the 4 rooms, 4 people are there. In all 4 rooms, 4 people are there. So can the people move? No. Here 4 rooms are there. All 4 rooms are empty. So can the people move? No. Here 4 rooms are there. Out of these 4 rooms, 2 rooms are empty and 2 people are there. 2 people are there in 2 separate rooms. So now those people can move. So this electron can reach here. This electron can go here. So movement of electrons is possible in partially filled energy band. Movement of electron is possible in partially filled energy band. And I told you, for the current to flow, electrons must have a net motion. Here electrons are not having any net motion, here electrons are not having any net motion. Only in this condition electrons can move. That means only in this condition the current can flow. Whether the current will flow or not, that I don't know, but surely in these conditions current cannot flow. So this is what I have written here. All these points will make sense when we study the silicon crystal. So have patience. So what point is written? If an energy band is completely full or completely empty, no current can flow even if an external electric field is applied. Even if I apply the external electric field and all the bands are completely filled, that means electron cannot move, then current will not flow. Current flows only when the band is partially filled, because then electrons have empty nearby states to move into. They are having empty nearby states to move into. Is this point clear? So whatever the points that we are studying, everything will make sense. Now there is something called thermal energy. Sir, this was a discrete point, like out of the box it came. Sir, this was also a discrete point, out of the box it came. Sir, we were studying silicon crystal, everything was making sense here, sir. Suddenly this point, then suddenly sir this point, and suddenly sir this is thermal energy. Sir, why all these things? So all these combined will make sense, you just need to have some patience, okay? So there is something called thermal energy. So previously what did I tell you, that how the electron will get the energy? This was the electron. What I did, I gave it some voltage. So it got energy of E into V, right? E into V naught. The electron is accelerated by V naught voltage. So energy was given as Q into V. Electron is having a charge of E into V naught. So it got the energy of E into V naught, right? There is another thing that can give energy to electrons, and that is known as temperature. So because of the temperature as well, the electrons can get some energy. Are you able to understand this point? So that energy is given by that energy is known as thermal energy. The energy of the electron that you are getting because of the temperature. Because of the voltage, electron will get some energy, but because of the temperature as well, the electron can get some energy. So that energy is known as thermal energy, which is given by kT, where K is the Boltzmann constant. The value of Boltzmann constant is, you don't need to remember it. Only thing you need to remember is that thermal energy is proportional to the temperature. Thermal, here I should write thermal energy. So ETH I will write down. This thing you need to remember, that thermal energy is proportional to the temperature. As the temperature increases, electron will get more and more energy. So what do you think, what will be the energy at 0 Kelvin? Thermal energy at 0 Kelvin. So E thermal at 0 Kelvin will be equals to 0 only, right? At 0 Kelvin, the electron will not get any thermal energy. But what is the room's temperature? Room temperature is 27 degrees Celsius. Usually the room temperature is 27 degrees Celsius. In Kelvin it will be K equals to C plus 273. So that would be 27 plus 273, that would be 300 Kelvin. So your room's temperature is 300 Kelvin. So at the room's temperature, what will be your thermal energy? So that is coming out to be 4.14 into 10 to the power minus 21 joule. Okay. But I will convert it into the electron volt. So for converting it into the electron volt, what I will do, I will divide by 1.6 into 10 to the power minus 19. So that is coming out to be 26 milli electron volt. So at the room's temperature, without even applying any voltage, this is some material I am having. In this material there is some electrons. In this material there is some electrons, and this material is there at the room's temperature only. This material is lying in my room, in my table. So whatever the electrons are there in this material, they will already have 26 millivolt energy, or it is nearly equal to 25.9 milli electron volt. So they will have 25.9 milli electron volt energy. So what it will feel like that? What it will feel that they are having 26 milli electron volt energy. It feels that there is some 26 millivolt potential has been applied. Just a second. Yeah. So it will feel that 26 millivolt potential has been applied to the electron. Are you able to understand this point? Electron is having 26 milli electron volt energy at room's temperature, although you are not applying any voltage. Although you are not applying any voltage, but at the room's temperature, it will feel like that the electron is accelerated by this much potential, and this potential is known as thermal voltage. So thermal voltage Vt at room temperature is given by approximately, it is given by 25.9 millivolt, or sometimes you can take 26 millivolt. This value will be given in the question, so this value will be given, but you should remember it as well. Okay, the thermal voltage Vth you can write down, or Vt you can write down. So the thermal voltage at room's temperature is 26 milli electron volt. What is the meaning of this thermal voltage? Did you understand that? What is the meaning of thermal energy? Without even applying any external voltage source. Here we were applying some external battery. Because of that battery, it was getting a energy of EV naught, right? But that we are not doing here. Just because of the temperature only, it is getting some energy. Just because of the temperature, it is getting some energy. And that energy at room's temperature is coming out to be 25.9 milli electron volt. No value from here you need to remember, only this value you need to remember. 25.9 milli electron volt. Is that clear to you? Okay. And what is thermal voltage? Since the electron is having an energy of 25.9 milli electron volt, it feels like that it is being accelerated by 25.9 millivolt potential difference. That potential difference is known as thermal voltage. Thermal voltage value at room's temperature is given by 25.9 millivolt. Is that okay for you? So now everything will make sense, and now we are going to study our silicon crystal that we have already seen. So at 0 Kelvin, we have already seen our silicon crystal. Silicon atoms were there. They were making bonds with the nearby atoms at 0 Kelvin. This was the scenario at 0 Kelvin. This was the scenario at 0 Kelvin. At 0 Kelvin, what did you see? That all the valence band energy states are completely filled. All the energy states are completely filled, and all these conduction band energy states are empty. At 0 Kelvin, is there any thermal voltage present? Is there any thermal energy present? No, there is no thermal energy. Did I apply any battery? No battery I applied. That means no electron is having any energy. No electron is having any energy. That means electrons are not moving. If electrons are not moving, that means the current is 0. At 0 Kelvin, in the silicon crystal, all these electrons are making bonds. What does that mean? All are lying in the valence band, and conduction band is completely empty. Even if I apply any battery here, if I don't apply any battery, is there any chance of current? First thing is that, let's just say there is any material, whether it is conductor or semiconductor or insulator, if you don't apply any battery, then you will never get a current. Because you need to give some source, no? You need to give some source. If you give some energy, then only you will get the energy. You cannot create the energy. Energy can never be destroyed. It can never be created. From one mean to other mean, it can be transferred. So if I give voltage energy, then I will get some energy in the electrons. So if I give the energy from my side, then only I will get the energy. So if I am not connecting any battery, then there is no chance of the current flow. But even if you connect the battery, even if at 0 Kelvin I connect the battery, so first question I am asking, is there any thermal energy? No energy is there. If no energy is there, that means these electrons cannot make the transition. These electrons cannot make the transition from here to here. Now if they are not making the transition, then this is the scenario. Now if this is the scenario, then let me know what is this. This band is completely filled. And what is this? This band is completely empty, and this is completely filled. If your bands are completely empty and completely filled, is there any chance of current? No. Right? Where I explained this? Here I explained this. For fully filled energy band and for empty energy band, the current cannot flow even if you are applying the electric field, because electrons are not even having the space to move. So this analogy we have understood by the band diagram. Now the same energy you understood by the crystal structure. Is there any free electrons? All electrons are making the bond, and there is no thermal energy. Since there is no thermal energy, that means no free electrons are there. So if all are making the bond, no free electron is there, then can the electrons move? No, only free electrons can move. These electrons are bound, so they cannot move. So you can understand the analogy by the crystal structure as well, along with the Venn diagram as well. So in Venn diagram, if I had applied any electric field, everything we are talking, any potential at 0 Kelvin, we are just talking about 0 Kelvin. At 0 Kelvin, in the Venn diagram, you can see that conduction band is completely empty and valence band is completely filled. There are no free electrons. Electrons have no other part to move. So even if you apply the battery, there will not be any current flow. So at 0 Kelvin, your silicon crystal, your semiconductor, this silicon crystal is named as semiconductor. It is working as a perfect conductor. Sorry, as a perfect insulator. So all the theory, everything is written, but are you able to understand this point? So this silicon crystal at 0 Kelvin is working as a perfect insulator for us. But now what if I see it at the room's temperature? What if I see it at the room's temperature? But before that, let's see the theory that we have already written. So at absolute 0 Kelvin temperature, a silicon crystal behaves like a perfect insulator. The valence band is completely filled with electrons and the conduction band is completely empty. So there are no free electrons. If no external electric field is applied, the electrons remain bound and cannot move freely. Even if an external electric field is applied, no current can flow because the fully filled valence band cannot contribute to the conduction and the conduction band has no electrons. So conduction band is having no electrons, valence band is completely filled, so there cannot be any chance of current flow. Thus at 0 Kelvin, silicon cannot conduct the electricity under any condition. All good. But now what if we talk at the 300 Kelvin? So at 300 Kelvin, what will happen is that electrons will get some thermal energy at 300 Kelvin. And that thermal energy is 0.26 milli electron volt. So what will happen is that at room's temperature, now these, let's understand by the crystal structure. First we are understanding by crystal structure. So what will happen is that at the room's temperature, some of these bonds will break. This bond will break. So what will happen? Whatever the this electron was here, this electron will go into this gap and it will create a vacancy. It will create a vacancy here. Previously, at this particular space, there was an electron. Now what really happened is that this electron has went into this free space. You will not call it free space, I will call it gap. This electron has went into this gap. So this electron has become free electron now. And this vacancy is known as hole. So here, because of their temperature only, this is having some energy of 26 millivolt. Because of that temperature, this bond gets broken. Here we have made a vacancy and this electron has went into the gap. The same scenario with respect to your Venn diagram. So what will happen is that this electron will get enough energy to clear this band gap. This electron will get enough energy to clear this band gap and it will reach into the conduction band. So what will happen is that here there will be one vacancy and the electron would have reached here. Another bond can break. Another bond can break. So what will happen? Here there is an vacancy. This electron has already reached here and this electron can also reach here. So at room's temperature, because of the thermal energy, what is the thermal energy? 26 milli electron volt. Because of the thermal energy, these electrons have broken these bonds, or in the Venn diagram, what you will say, these electrons from the valence band, they have made transition in the conduction band. Now, one very interesting doubt can come. If you are thinking very deeply, what doubt will come? That sir, you said that this was 1.17, this we are talking at 300 Kelvin, okay? And at 300 Kelvin, this is approximately 1.1 electron volt. The energy gap is 1.1 electron volt at 300 Kelvin. And sir, just 1 hour back you said that if the electron wants to make the transition from here to here, if the electron wants to make the transition from one energy level to another energy level, then it needs to cover this much energy, which is E2 minus E1. And for silicon, this energy is roughly 1.1 electron volt. For silicon, this energy is roughly 1.1 electron volt. But your electron is actually getting 26 milli electron volt only. What I am saying, my electron at the room's temperature is getting only 26 milli electron volt energy, but it needs to cross 1.1 electron volt energy. It needs to cross this 1.1 electron volt energy. So how this 26 milli electron volt energy is enough to make the transition from valence band to conduction band? A very, very good point. But the answer cannot be given as of now. The answer will be given when we study Fermi direct distribution. So with respect to complete mathematics, I will give you the answer. As of now, in a crude way, what you can understand is that electron is getting 26 milli electron volt energy, but this energy is continuous. Are you able to understand this point? This energy is continuous. 26, 26, 26, 26, 26 milli electron volt, it will keep on getting the energy. Are you getting this point or not? What is the doubt? Did you understand the doubt? The doubt is that the energy gap is 1.1 electron volt. And sir, you have previously said that if the electron wants to make the transition from here to here, that means it needs to cross the 1.1 electron volt energy. But at the room's temperature, you are getting 26 milli electron volt energy only. So this energy is actually continuous. At the room temperature, all the time it is getting this energy. 26 milli electron volt, 26, 26, 26, 26, 26. So it will keep on adding up and it will make the transition. In a crude way, you can remember in this manner. But the actual mathematics I will give you when we study Fermi direct distribution. So this doubt can come, which is a very, very good doubt, that at room's temperature, the thermal energy of an electron is about 26 millivolt, which is enough to make some electrons move freely and conduct electricity. That means which is enough to make the transition from valence band to conduction band. How it is possible? Because actually it should be 1.1 electron volt. So how it is possible? That we will understand when we study Fermi direct distribution. Fermi direct distribution. Okay, but as of now, you just need to remember that somehow it makes the transition. But all the electrons will not make the transition. Are you able to understand this point? What I am saying is that, sir, here there are 4 bound electrons. Every silicon atom is having 4 bound electrons, no? So if there are n silicon atoms, so total 4n bound electrons are there. So all the electrons will not go from conduction band to valence. Sorry, all the electrons will not go from valence band to conduction band. Only a few electrons will go. Let's just say in this silicon crystal you are having 100 silicon atoms. What you are having? 100 silicon atoms. If 100 silicon atoms are there, that means 400 bound electrons are there, because each electron is having 4 bound electrons. So 4 bound electrons are there. Now if all the bonds are broken, then all 400 electrons will be free. But this doesn't happen. Only 2 to 3 bonds will be broken. So only 2 to 3 electrons you will get. Are you able to understand this point? 100 silicon atoms were there. These 100 silicon atoms are able to give you 2 to 3 electrons. Are you able to understand this point? 2 to 3 electrons means these free electrons. 2 to 3 free electrons. Electrons are there, like total electrons are 400. So 400 electrons are there. Out of these, only 2 to 3 are free. Is that okay for you? Okay. Yeah, so let me erase. So as of now, let me just conclude what we have studied. At 300 Kelvin, there is thermal energy present. Because of this thermal energy, what will happen is that these electrons will make transition from the valence band to conduction band. It will get enough energy to make the transition from valence band to conduction band. Okay, and by the crystal structure also you can see that bonds are broken. So this is a free electron that we have made, and this is the hole we have made. Another bond I can break. This bond I will break. So here I have created a vacancy. This vacancy is known as hole, and this is known as free electrons. So what is hole? Hole is nothing but a vacancy of the electron. Hole is nothing but the vacancy of the bound electron. Now what will happen? Look, because of the thermal energy as well, because of this thermal energy, this electron can move, right? Because it is having some energy. So if it is having energy, that means it can move. But they will move in the random direction. Some will move here, some will move here, some will move here. So their net motion will be 0. Because of the thermal energy, the electrons can move, but their net motion will be 0. So if I want the current, if I want a net motion, then what I have to do? I will have to apply a battery. Because if I apply the battery, then electrons will be bound to move in a certain direction. What that direction would be? Electrons will be moving in the opposite direction to the applied electric field. So when there was no electric field applied, this was the condition. At 300 Kelvin, no electric field applied. At this point, you are having free electrons, but still these free electrons cannot move. These free electrons can move because of the thermal energy, but they are moving in a random direction. To make them move in a certain direction, what you need to do? You need to apply a potential difference. So what I will do now, at the 300 Kelvin, I am having my silicon crystal. Now I am applying the battery. So in silicon crystal at 300 Kelvin, I am applying V0 potential. So what will happen? This will be positive, this will be negative. So this will be your electric field. And since this is the electric field, so electron will move in the opposite direction to the applied electric field. So this electron will move and this electron will also move. So these two electrons are moving, and since they move, you will get some current. So this electron, this particular electron that I have made here, this particular electron is moving in this direction, and because of that you are getting this current. So this electron is moving in this direction, that's why you are getting one current. All good. Now there is another electron which can move. Which electron? Think about it. There is a vacancy of electron, no? Vacancy means this is there, that this vacancy is saying that I am ready to take electron. And this electron, what this electron will say? Okay, if you are ready to make the if you are ready to take the electron and I am having electric field, that means now I will move from here to here, because this bond is not there, no? This vacancy, this particular vacancy is saying that I am ready to take the electron. So what this electron will say? That I will move here. What this electron will say? I will move here. Just as this electron has moved here, what will happen is that the vacancy will be created here. And just as this electron has moved here, then what will happen is that vacancy will be created here. Vacancy will be created here. Then this electron will say that I will move here. Then what will happen? Vacancy will be created here. Basically, electron from here to here it has moved, so vacancy will be created here. Now what this will say? This electron will say that I will move from here to here. Electrons are moving in the opposite direction to the applied electric field. Electric field is here, so electrons will move here. So this electron will move here. So where the vacancy will be created? This vacancy is created. Now this electron will move here. Then where the vacancy will be created? This vacancy will be created. So electrons are moving in this direction, and this vacancy is moving in this direction. Are you able to understand this point? This vacancy is moving in this direction. There are two kinds of electron. One electron is the free electron. This was the free electron, and other electron was the bound electron. Both kind of electrons are moving. Free electrons were directly moving because of the electric field, they were moving in this direction. Now because of the vacancy, what really happened is that these vacancies were saying that I am ready to take the electron. So since there is applied electric field, the electron said that okay, since there is applied electric field, we can move now. And if you are ready to take the electrons, then we will move. So electrons moved. And if they moved, they created a vacancy, and that vacancy is known as hole. So what do you see here? The electrons are actually moving in the opposite direction to the electric field. It means that holes are actually moving in the direction of electric field. Kind of, can you say that holes are moving in the direction of electric field? Holes are not a particle. Particles are electron only. Holes are not a particle. But since the electrons are moving, it feels like that holes are also moving. The vacancy is also moving. But the vacancy is moving in the same direction. Like this was the free electron, right? Then what I will do is that this was the free electron. Now the bound electron which are there in the covalent bond, they also moved in this direction. Because of that, this hole moved in this direction. So if bound electrons are moving in this direction, where will be the current? The direction of current will be this. Here I am writing IP, and here I will write down IN. or let's write down IE, and here I will write down IH. Now, how much current component are there? One current component is coming because of this free electron, and other component is coming because of this bound electron. Now, if I say that in a semiconductor, total current is 5 microampere, 2 microampere current is coming because of the electrons. So now the user will ask which electron, free electron or bound electron, right? If I say in a semiconductor 5 microampere current is flowing, in those 5 microampere, 2 microampere current is because of the electrons. Now which electron, free electron or bound electron? So again and again you will have to say that in this 5 microampere current, 2 microampere current is because of the free electron and 3 microampere current is because of the bound electron. To avoid that confusion, what the scientists did, they named this current, this particular current, they named this current as hole current. Because if bound electrons are moving, that means vacancy is also moving, no? That means holes are also moving. Are you able to understand this point? Hole is not a particle, hole is nothing but a vacancy of electron. But it feels like that this vacancy is moving. So someone can say that this current is coming because of the movement of this vacancy, although it is because of the movement of electron. But just for the sake of understanding, people can say that this current is coming because of the movement of holes. So one current component will be because of the electrons and one current component will be because of the holes. So whenever I say in the whole electronics from now onwards, whenever I say electrons, that means I am talking about free electron only. From now onwards, whenever I say electrons, that means I am talking about free electrons. And whenever I say hole, I am talking about the vacancy that is there in the covalent bond. The vacancy that is there in the covalent bond, that is the hole. And what is the free electron? Free electron that is present in the conduction band. And here also you can see that if I apply an electric field, these conduction band electrons will have enough space to move, and these valence band electrons will also have the space to move, because these are the vacancy here, no? So they can move towards this vacancy. This is also partially filled, this is also partially filled. If both are partially filled, that means both kind of electrons can move. They can move like this and they can also move like this, right? Are you able to understand this point? So in the theory, what will be written? At 300 Kelvin, at room temperature, in the silicon crystal, because of the thermal energy, you will get electron hole pair. Now what is this electron hole pair? Electron means free electrons. And what is hole? Hole is the vacancy of electron. If I apply a battery, if I apply a external electric field, if I apply this external electric field, the electrons will move opposite to the direction of electric field. When I say electrons, that means the free electron. So free electron is moving in the opposite direction to the electric field, and the holes are moving in the same direction as the electric field. This is the direction of electric field, this is the direction of hole movement. So holes are moving like this. So there are two current component. One current component is coming because of the electrons, that means free electron, and one current component is coming because of the holes, that is vacancy of electrons, or you can say because of the movement of bound electrons. Is this point clear? Like a very, very good point. Usually people don't understand this particular point. Usually student gets confused there. But is that clear? So hole is there, the word hole is introduced just to make you understand the things in an easier manner. So if someone says that 5 microampere is the total current, 3 microampere current is because of the electrons, that means because of these electrons, these free electrons, and 2 microampere current is because of the holes, that means because of these vacancies. Is that clear to you? So complete theory is written. At 300 Kelvin, a silicon crystal gains enough thermal energy for some electrons to jump from the valence band into the conduction band. Each electron that moves up leaves an empty state in the valence band, which behaves like a positive charge carrier. Yeah. Why positive charge carrier? Like electrons are negative charge carrier. Hole I will call as positive charge carrier. Why is that so? Because in the presence of electric field, if there is a charge q, it will get some force, right? It will feel some force. And if this charge is moving if this charge is getting the force in the same direction as the electric field, if this charge is moving in the same direction as the electric field. What does that mean? That means this is a positive charge. So if electrons are the positive charge, then holes are like, if electrons are the negative charge, then holes are like the positive charge. Are you able to understand this point? If electrons are like the negative charge, then holes are like the positive charge, because they are moving in the same direction as the electric field. What is the direction of electric field? This is the direction of electric field. So holes are moving in the same direction as the electric field. That means they feel like as a positive charge, but actually they are not a particle. Holes are actually not a particle. They feel like a positively charged particle, right? So this is what is written. What is written? Each electron that moves up leaves behind a empty states in the valence band, which behaves like a positive charge carrier, called as hole. Called a hole. Thus, at room temperature, silicon have equal number of electrons in the conduction band and holes in the valence band, right? Equal number of electrons in the conduction band and equal number of holes in the valence band. You can directly see that whatever the number of electrons are going in the conduction band, the same number of holes are present in the valence band. No, like if electrons are going, then only you will get the holes. No, like if this electron goes here, if you get a free electron, that means you will surely get a hole. If you get a free electron, that means you will surely get a hole, right? So free electrons are present in the conduction band. Free electrons are present in the conduction band and holes are present in the valence band, right? If no external electric field is applied, the both electrons and hole will have a random motion, will move randomly because of the thermal energy. I told you, like because of the thermal, if there is energy, that means there will be velocity, but the velocity will be very random. They will move here and there. The velocity will be very random. If the velocity is random, that means there will be no net current flow. So even if you are having free electrons, even if you have space to move, still the movement is very random. Since the movement is random, that means there will be no current flow, right? When an electric field is applied, electrons drift opposite to the field and holes drift in the direction of the field, creating a small but definite current. The current will flow, but the value of that current would be low. Okay, the magnitude of that particular current will be low, but the current will flow. Okay, this is why at 300 Kelvin, intrinsic silicon acts as a weak conductor rather than a perfect insulator. So at 0 Kelvin, what we were getting? At 0 Kelvin, we were getting cannot conduct electricity, and here we were getting insulator. But at 300 Kelvin, we are getting a conductor, not a perfect conductor, not a very good conductor, a weak conductor. Like at least some current we are getting. Okay. Note, in semiconductor, the charge carriers are electrons and holes. What do you mean by charge carriers? So charge carriers are those particles which will help you in conducting the current. So who is helping you in conducting the current? This free electron and hole. So from now onwards, whenever I say free electron, whenever we refer to the electrons, we mean the free electrons present in the conduction band. So from now onwards, whenever I say free electrons, that means you need to think about the electrons that is present in the conduction band. And from now onwards, whenever I say holes, that means you need to think about the vacancy of electron that is present in the valence band. Okay, so this is the note we have written. Whenever we refer to electrons, we mean the free electrons present in the conduction band, and whenever we refer to holes, we mean the absence of electrons present in the valence band, which behaves like a positive charge carrier. And what do you mean by charge carriers? Charge carriers means those particles which will help you in conducting the current, which will help the current to flow. So who is helping the current to flow? These free electrons and these bound electrons. Bound electrons means holes only. Because if bound electrons moves, vacancy also moves. Vacancy moves, that means holes move. So here the charge carriers are electrons and holes. And here the number of charge carriers, number of electrons and number of holes, both are equal. Okay. Is that clear to you? So that equal point I haven't written here, that will come later on. What I am saying, yeah, here it is written. There is equal number of electrons in the conduction band and holes in the valence band. So charge carriers are holes and electrons, and in this kind of semiconductor, the number of electrons and the number of holes are same. Is that clear? Okay. What is electron? What is holes? Electrons are negatively charged particle moving in the conduction band, move opposite to the direction of electric field when field is applied. And what about the holes? Holes are the absence of electrons present in the valence band, behaves like a positively charged carriers, move in the same direction as the electric field. Now what is this? Energy increases upward in the Venn diagram, and here energy increases downward in the Venn diagram. What is the meaning of that? So I told you, for electrons, the energy will increase in the upward direction. Where I told you that? In the beginning of our slides only. Here. As you move upper, for the electrons, the energy will increase in the upward direction. The energy will increase in the upward direction. But now for the holes, electron energy increases in the upward direction. Electron energy increases. Now just tell me one thing, electron and holes are like opposite charge only, no? Like electron is a negatively charged particle and hole is acting as a positively charged particle. What is the energy? Energy is Q into V. Forget about the V, just focus on Q. If it is negative, if Q is negative, then energy is increasing in the upward direction. So now if Q becomes positive, then what will happen? In the upward direction, energy will increase. Sorry, in the upward direction, energy will decrease. Are you able to understand what I am saying? And the definition of energy is Q into V. Forget about the V as of now, because V is the potential that we will apply, right? Now I am saying that if Q is negative, if we are talking about the electrons, then energy is increasing in the upward direction. So if Q becomes positive, then what will happen? Then energy will decrease in the upward direction, or you can see that energy will increase in the downward direction. If you go in the downward direction, the whole energy will increase. Just you need to understand that electron and holes are like opposite charge carriers. If one is positively charged carrier, then hole is like a negatively charged carrier. So if electron energy is increasing in the upward direction, then whole energy will increase in the downward direction. So this is the line that I have written. So let's just say I make some Venn diagram. This is the electron I am making. This is E2, this is E1. And this is E3, this is E4. And this is the hole I am making. Find the relation between E2 and E1. E2 will be greater than E1. The electron that is present on this energy level, the energy will be higher. But here, E4 will be greater than E3. This hole will be having more energy. But better than writing down, we should write down in this manner. This electron will have more energy. And this hole will have more energy. Because energy of holes increases in the downward direction, energy of electron increases in the upward direction. This point will be used somewhere, okay? In future, somewhere this point will be very, very crucial. So somewhere I will be using this point. As of now, are you able to understand this point? Hole is actually not a particle. This is just an analogy that will help us to understand a lot of diagrams, a lot of Venn diagram we will be understanding by this concept. Okay, so electron energy increases in the upward direction and hole energy increases in the downward direction. Is that point clear to you? Okay, so I need to take a break, then we will understand. Okay, I will explain this particular thing which you already know, and then I will take a break. Yeah, so the semiconductor that we studied just now, that is known as intrinsic semiconductor. So just now the semiconductor that we have studied, that is intrinsic semiconductor. What do you mean by intrinsic semiconductor? That means pure semiconductor with no impurities. That means everywhere silicon would be there, no? Everywhere silicon would be there. You see this, everywhere silicon. There is no other atom. So if everywhere silicon is there, that means it is intrinsic semiconductor. Okay. Everywhere silicon is there, that means it is intrinsic semiconductor. In this intrinsic semiconductor, the number of free electron is always equals to the number of holes. That also I already told, number of free electrons is always equals to the number of holes. Both combined are known as charge carriers. Okay, so we represent number of electrons by n and holes by p. When I say electrons, that means free electron only. So number of free electrons are n, number of holes are p. So for intrinsic semiconductor, n is equals to p is equals to ni. What is this ni? Ni is known as intrinsic carrier concentration. So in the examination, what will be given? In the silicon crystal, in intrinsic semiconductor, in intrinsic silicon semiconductor, the intrinsic carrier concentration is given as 10 to the power 10 centimeter, 10 to the power 10 per centimeter cube. That means in 1 centimeter cube volume, there are 10 to the power 10 electrons and 10 to the power 10 holes. In the examination, what will be given is that your intrinsic carrier concentration is 10 to the power 10 centimeter cube inverse. What does that mean? That means in 1 centimeter cube volume, there are 10 to the power 10 free electrons and 10 to the power 10 holes. And both will be same in case of intrinsic semiconductor, because electron hole pairs are generated in a pair, right? They are the pair. Why they are the pair? Because if one bond is broken, then what really happened? One hole we got. If one bond was broken, one hole we got. So electron and holes, number of electrons will always be equal to the number of holes in case of intrinsic semiconductor. Some other semiconductor we will study, there it may change. But in case of intrinsic semiconductor, n will be equals to p is equals to ni. Is that okay for you? N is the number of electrons, p is the number of holes. Ni is known as intrinsic carrier concentration. And for silicon at room temperature under thermal equilibrium. What is this thermal equilibrium? As of now, you understand thermal equilibrium means constant temperature. At a constant temperature, that means you have at 300 Kelvin, you have reached the steady state. Now no other electrons and holes are being generated. At 300 Kelvin, at a constant temperature, you have got the steady state. That means no other hole and electron hole pair are being generated. Electron hole pair is fixed. That means number of holes are also fixed, number of electrons are also fixed. That is equal to roughly around 10 to the power 10. It is not a fixed value, it can be varying, it can change. So it will be given in the questions. Sometimes it can be given as 1.5 into 10 to the power 10 as well. Okay, 1.5 into 10 to the power 10 as well. So it can vary according to the question. That means that in every cubic centimeter of pure silicon, about 10 to the power 10 electron hole pairs are naturally generated due to thermal energy. So because of the thermal energy, some bonds were broken and we got free electrons and the vacancy of free electrons and vacancy of electrons, that was known as hole. So we got electron hole pairs. Those are roughly around 1.5 into 10 to the power 10 for silicon crystal at room temperature under thermal equilibrium. Thermal equilibrium means the number of electron hole pairs are fixed now. Now it will not increase, it will not decrease. At thermal equilibrium, at steady state, 1.5 into 10 to the power 10 centimeter cube inverse, these number of free electrons and these number of holes you are having. Is this slide clear to you? Okay. So we have got some current now. In the semiconductor at 300 Kelvin, because we are having electron hole pair, we have got some current, right? But the current is actually very less. So although an intrinsic semiconductor can conduct electricity at room temperature, it's a very poor conductor. It's a very poor conductor. Its conductivity is too low to be useful in practical applications. So that's why we will not use intrinsic semiconductor. Now we will use extrinsic semiconductor. So there what we will do, we will dope the silicon crystal by adding small amount of trivalent atoms, which will create p type of semiconductor, and we will dope pentavalent atoms, which will create n type of semiconductor, and the conductivity will be improved. So as of now, we have built a silicon crystal. There we got to know that we are getting some conductivity, at least some conductivity we have got, and the conductivity is coming because of the free electrons and because of the holes. Conductivity is coming because of the free electrons and holes. If anyhow I increase the number of free electrons, if anyhow I increase the number of free electrons, and if I anyhow increase the number of holes, then my conductivity can increase. So for that, what we did, we started doping the pentavalent atoms and trivalent atoms. So what is this doping? How do we do it? Everything I will tell you, but after a break. Okay. So a semiconductor whose conductivity is improved by this way, that is known as extrinsic semiconductor. Extrinsic semiconductor. So as of now, we are going to study about extrinsic semiconductor. Now, what is this pentavalent atom? What is this trivalent atom? That I will tell you after the break only. I need to take a break. I need to drink some water, and then I will come back. We will study about pentavalent atom, trivalent atom, and from there we will make p-type semiconductor and n-type semiconductor. As of now, you should revise everything that we have currently studied. So it's been roughly around 2.5 hours. In this 2.5 hours, we have seen the basics of semiconductor. So let's meet after the break. Yeah, welcome back guys. So we were studying about intrinsic type of semiconductor. In that kind of semiconductor, we were having number of holes equals to number of electrons, and that is known as intrinsic carrier concentration. But we got to know that conductivity was pretty small. What is the expression of conductivity? All these things we will see later on in the lectures. Okay. But as of now, you got to know that conductivity is very small. So now your target would be to increase the conductivity. You need more current. So for that, what we are going to do? We are going to use extrinsic semiconductor. So what are extrinsic semiconductor? So in the intrinsic semiconductor only. So in intrinsic semiconductor, what was the scenario? Silicon was there. So now in intrinsic semiconductor, what we will do? We will dope pentavalent and trivalent atom. So either we will dope pentavalent atom or we will dope a trivalent atom. So what is this pentavalent and trivalent atom? So in your, do you remember your periodic table? So there were some group 3 element and there were some group 5 element. Why they were called group 3 element? Because in their outermost shell there are 3 electrons, and in their outermost shell there are 5 electrons. They are having 3 electrons in their valence shell and they are having 5 electrons in their valence shell. So what all were the group 3 element? Boron, aluminium, gallium, indium and thallium, right? You can remember in your own way. How I remember? Bangan, alu, gajar in thela. Those who understand Hindi, they will understand. Bangan, alu, gajar in thela. You can remember on your own, right? Similarly here, nitrogen, phosphorus, arsenic, antimony and bismuth. These are the elements. New Zealand, Pakistan, Australia, sub BK. So just I am using Hindi language here, but whatever language you want to remember, in any way you want to remember, you can remember. Group 3 element and group 5 element. Okay. So in group 3 element, in the outermost shell you are having 3 electrons, and in group 5 element, in the outermost shell, in the valence shell you are having 5 electrons. 3 electrons here, 5 electrons here. Now what we will do? We will create extrinsic semiconductor from these atoms. So how we will create it? That we are going to see. Okay, so basically we are going to study two kind of semiconductor, p-type semiconductor and n-type semiconductor. What is this p-type? What is this n-type? That we will study. So let's study about n-type semiconductor now. So this was our intrinsic semiconductor, right? Silicon, everywhere silicon is there, and all are making the covalent bond. Now what we will do? In this silicon, we will insert some group 5 element. So I will be using phosphorus here. Okay. So what I am doing? I am inserting some phosphorus atoms. In place of silicon atom, what we will do? We will insert some phosphor atoms. So phosphorus is having 5 electrons in their outermost shell. Phosphorus is having 5 electrons in their outermost shell. So in place of silicon, if phosphorus is coming, silicon is gone. That means this electron is gone, this electron is gone, this electron is gone, this electron is gone. Now the phosphorus will come. Phosphorus will come. Phosphorus is having 5 electrons. So 4 electrons phosphorus will be using to make these bonds. So again 4 electrons are making the covalent bond. And this 1 electron will be nearly free. This electron is not completely free because phosphorus is having its own proton, right? It is having its nucleus. So this nucleus is imposing some force on these 5 electrons. Out of these 5 electrons, 4 electrons have made the bond. So they have made a stronger bond. They have made a covalent bond. Since they have made the covalent bond, that means they are not free. But this electron is also not completely free. This is approximately free. Or you can say this is nearly free. Or you can say this is loosely bound. They are strongly bound because they are making the covalent bond. But this is loosely bound. So the 5th electron is loosely bound. 4 are making the covalent bond. Now you let me know, if I talk about free electrons. So where are the free electrons? Free electrons will be staying in the conduction band, right? Free electrons will be staying in the conduction band. right? And bound electrons, which are the bound electrons I'm talking about? These are the bound electrons, 1 2 3 4. These are also bound electrons, 1 2 3 4. All these are the bound electrons. So bound electrons always stay in the valence band, right? Free electrons stay in the conduction band. Now what about this electron? This electron is nearly free, or it is about to be free. It is not completely free. This electron is loosely bound, so it is about to be free, right? So what should be its energy level? It should be near to EV, or it should be near to EC. In EC, all free electrons are there. In EV, all bound electrons are there. This electron is nearly free, or you can say it is loosely bound. That means it is about to be free. If it gets some energy, if this electron gets some energy, it will be free. So it requires a very small amount of energy. That means this electron should be lying near to the conduction band. So near to the conduction band, I will make another energy level. That energy level will be known as donor energy level. What I am calling it? Donor energy level, because one electron is donated here. This phosphorus is donating one electron, and that electron is having energy near to the conduction band because it is about to be free, it is loosely bound. But only one phosphorus atom will not come into action, a lot of phosphorus atom will come into action. So this silicon will also be replaced by phosphorus, right? So 1 2 3 4, 4 are making the bond, but one will be loosely bound. It is about to be free, so it will be here. So I am making some more electrons here, some more electrons I am making, right? So this is the scenario at 0 Kelvin. So at 0 Kelvin, you let me know. Now you will be saying that sir, you said that on one energy state only one electron would be there, but how you are making a lot of electrons here? Sir, few times back only you said that on one energy level only one electron would be there. Why you are making these many electrons? So this is not an energy state, this is an energy level. On one energy state one electron would be there, but on energy level, on one energy level a lot of electrons could be there, right? Do you remember 3p 3s? So here I said that a lot of electrons are there, but just as this level got splitted into energy band, just as this level got splitted into energy band, at that time I said that on these energy states only one electrons will be there. So on the energy state only one electron can stay, but on energy level a lot of electrons can stay. So this is a donor energy level, okay? Donor energy level. So this is an important line. But these are the energy bands which are made from energy states. So on each energy state only one electron is there. But on donor energy level a lot of electron can stay. So this is the energy level, but these are the states. Difference is clear, right? Okay, everything should be crystal clear here. No doubt should be there. Now at 0 Kelvin, this electron is having any thermal energy? No. Is this electron is having any thermal energy? No. So no electrons are having any thermal energy. So at 0 Kelvin, there are no free electrons. These are completely bound, right? And these are having no energy. So there is no free electron in the conduction band. Conduction band is completely empty. If conduction band is completely empty and valence band is completely filled, is there any chance of current to flow? No. So at 0 Kelvin, even if you apply the battery or even if you don't apply the battery, there is no chance of current to flow. Across this semiconductor, if I apply a battery, still the current will not flow. Why it will not flow? Because there is no free electrons in the conduction band, or there is no hole in the valence band, or you can say that conduction band is completely empty and valence band is completely free. So valence band is completely filled. So there is no free electrons who can move to conduct some current. So even if you apply an electric field, current will not flow. So this is what I have written. Okay. Okay, the theory will come later on, but as of now, let's see at 300 Kelvin. So this is the scenario at 0 Kelvin, right? This is the scenario at 0 Kelvin, the same scenario we have made here. This is the scenario at 0 Kelvin. At 300 Kelvin, what will happen? This electron is just below the conduction band. That means this energy is very low. This gap is very low. And at room temperature, all of these electrons will be getting enough energy to reach into the conduction band. All these electrons will reach into the conduction band. Okay. all of these electrons will reach into the conduction band because they are just near the conduction band. So at room temperature, because of the thermal energy, they will reach into the conduction band. Along with that, some of these bonds will also break. This bond will also break. Let's just say this bond will break. So what it will do? It will create a hole and it will create an electron. This bond will also break. Let's just say this bond also breaks. So what it will do? It will create a hole. It will create an electron. That means this electron can also go to conduction band. So what it will do? The electron will reach here. The electron will reach here, but it will generate a vacancy. What may happen is that another energy level I need to make, another energy state I need to make. So what may happen is that this electron reaches here and it creates a vacancy. So electron hole pairs are also there. Now what do you see? In the conduction band, how many electrons do you see? 1, 2, 3, 4, 5, 6. 6 free electrons are there in the conduction band. How many holes do you see in the valence band? Only 2 holes are there in the valence band. So in the conduction band, 6 electrons are there and only 2 holes are there in the valence band. So electrons are more or holes are more? When I say electrons, that means I am meaning free electron only. So free electrons are more or holes are more? Which is more? Free electrons are more, right? These free electrons are more. And since free electrons are more, so in n-type semiconductor, majority charge carrier is electrons and minority charge carrier is holes. Okay, and that's why it is known as n-type semiconductor. Here what did you get to know is that majority charge carrier are electron and electrons are negatively charged. That's why n-type semiconductor. Okay, so in n-type semiconductor, what we did, previously we were having intrinsic type of semiconductor. Okay, there what we did, we doped some phosphorus atoms. So each phosphorus atom is having 5 electrons in its valence shell. 4 electrons are making bond. 1 electron is loosely bound. It is nearly free. It is not completely free. It is nearly free. That's why it will be lying in the donor energy level just below the conduction band. At 0 Kelvin temperature, none of the electron is getting enough energy to go from donor energy level to conduction band. So conduction band is completely empty and valence band is completely free. Sorry, valence band is completely filled. Even if you apply any electric field, there will not be any current at 0 Kelvin in n-type semiconductor. But at 300 Kelvin, what really happens is that because of the thermal energy, all the donor energy level electrons will reach into the conduction band. And some electrons from the valence band will also reach to the conduction band, creating a small vacancy which is known as hole. So in the valence band, you are having some holes and in the conduction band, you are having a lot of electrons. So majority charge carriers are electrons and minority charge carriers are holes. And now if I apply the battery, look here I have made only 6 states. More states would be there, no? So don't think that this conduction band is completely filled. No, nothing like that. More states are there. So now these electrons have enough space to move. Like this electron can also move now. This electron can also move. Along with that, these electrons can also move, right? Basically, the way I apply the battery, let's just say I apply the electric field in this direction. So where the electrons will move? Electrons will move in this direction. So this electron can move, this electron can move, this electron can move. Now what will happen is that this electron can also move. So this vacancy will move ahead. So this mechanism we have already seen. So basically now there are free electrons available. So if I apply the electric field, electrons will move in the opposite direction to the applied electric field. And if electrons are moving, that means there will be current flow. Along with the electrons, this vacancy is also moving. So that's why there will be current flow because of this vacancy as well. But that current will be very low. Why that current will be very low? Because number of holes are very low. Here number of holes you could see 1 and 2 only, but you can see electrons 1, 2, 3, 4. A lot of free electrons are there. So free electrons would be much more than the number of holes. That's why the majority current would be there because of the free electrons only, not because of the holes. Are you able to understand this point or not? Okay, so I hope you have understood. This complete theory has been written. So in n-type semiconductor is formed when a pure semiconductor like silicon is doped with pentavalent atom. It could be phosphorus, arsenic, antimony, it could be anything. These atoms will have 5 valence electrons. 4 of them will be making the covalent bond with the neighboring atoms, and 5th electron will be left loosely bound. Okay, the word is written that is loosely bound. It is nearly free. This extra electron create a special energy state just below the conduction band known as donor energy level. Okay, so donor energy level. In this donor energy level, a lot of electrons will be lying there. Okay, and because the energy gap between the donor level and the conduction band, this energy gap between the donor level and the conduction band, this energy gap I am talking about, this energy gap is very low. This energy gap is very low gap, very low gap. And since this gap is very low, since what is written, because the energy gap between this donor level and the conduction band is very low, the electron can easily jump into the conduction band using the thermal energy. Okay, at 0 Kelvin it will not jump. At 0 Kelvin it will not jump, but just as it gets the thermal energy, it will jump. Thus, in n-type semiconductors, electrons are the majority charge carriers, while the holes are the minority charge carriers, right? Because number of electrons will be much more than the number of holes. Let me give you an example. Let's just say initially we were having 100 silicon atoms. Although the number will be very much larger, just for the understanding purpose I am doing it. So we were having 100 silicon atoms, like silicon, everywhere silicon was there. At room temperature, what will happen? All the silicon atom will be broken. What I mean to say is that all these electrons will go into the conduction band. No, only few bonds will be broken, right? I told you here only when we were studying intrinsic semiconductor, at that time also I told you that this energy gap is larger. This energy gap is large. So all the electrons will not be able to clear this energy gap. Only a few electrons will be able to clear this energy gap. So if I am having 100 atoms of silicon in the intrinsic semiconductor, I am talking about intrinsic, I am talking about pure semiconductor. In the pure semiconductor, I was having 100 silicon atoms. That means I was having 400 valence shell electrons. But out of these 400 valence shell electrons, only a few, let's just say only 10 electrons went from valence band to conduction band. So if 10 electrons is going from valence band to conduction band, that means 10 electrons you have got and 10 holes you have got at room temperature. This is happening at room temperature. Now what you have done? You have done the doping. You have done the doping. So 100 silicon atoms you were having. Now you have done the doping, that 50 phosphorus atoms you added. What you did? You added 50 phosphorus atoms. Now one phosphorus atom is giving you one loosely bound electron, right? One phosphorus atom is giving you one loosely bound electron. So 50 phosphorus atom will give you 50 loosely bound electrons. 50 loosely bound electrons. Now all the electrons will be lying just below the donor energy level. This is the energy level. So all the electrons are having the same energy, right? All these electrons, all these loosely bound electrons are having the same energy. And this is just below the conduction band. Now just as you go at the room temperature, just as these electrons get the 300 Kelvin temperature, what they will do is that they will make a transition from conduction band to valence band. So what you did? You did the doping of 50 phosphorus atoms. These 50 phosphorus atoms will give you 50 electrons, loosely bound electrons. But at the room temperature, all the 50 electrons will be getting into the conduction band. Are you able to understand this point? So now you can see previously 10 electrons were there. Now 50 more electrons are there. So number of electrons have become very larger, and number of holes, previously it was 10 and now it did not get changed. It will change, but it will reduce only. What I am saying is that these 10 holes will be reducing. Why it will be reducing, we will understand later on. But as of now, you are able to understand that previously there were 10 electrons and now 50 more came into action. Because here all 50 are going in, but here all 400 are not making the electrons. Are you able to understand this point? At the room's temperature, all 400s are not making the electrons. Only out of these 400s, only 10 are making the electrons. But when you added the impurity, each atom is giving you one free electron, and that free electron at room temperature is going into the conduction band. That free electron at room temperature is going into the conduction band. So all 50 are ionized here. So 50 electrons because of the impurity, and 10 electrons were already there. So total electrons will not be addition. Okay, there is some other law. That law we will study, but you can surely see that 50 and 10 number has become very larger, but number of holes are pretty low only. Okay, this is a very deep understanding that what is actually happening. Like people would be saying that, sir, okay, electrons are also going here, no, so holes can also be very large. But actual thing is that these electrons will not be broken. These covalent bond electrons will be very less. These covalent bond electron holes, this pair will be very less, but these electrons will be very much more. Are you able to understand this point? So that's why holes are minority and electrons are majority. in case of n-type semiconductor. Is that clear to you? Now more things. They are known as donor atoms. What they are known as? Donor atom. Donor atom. So I will show it by Nd. Okay. Donor atom Nd. Donor atom Nd. Okay. Now at 300 Kelvin, what will happen is that thermal energy excites the electron. Yeah. So at 0 Kelvin, I forgot to read. At 0 Kelvin, at absolute 0 Kelvin temperature, all electrons, including the donor electrons, remain tightly bound, since there is no thermal energy to excite them into conduction band. Hence, no free electrons are available for the conduction. With or without electric field, the n-type semiconductor will behave like an insulator at 0 Kelvin. But at 300 Kelvin, at room temperature, without electric field, we are not applying the electric field as of now, okay, without electric field. So at 300 Kelvin, at room temperature, without electric field, what will happen is that thermal energy excites the donor electrons from the donor level into the conduction band. This will give a large number of free electrons compared to the intrinsic semiconductor. In addition, some electron from the valence band will also get excited to the conduction band. Some electron from the valence band will also get excited to the conduction band, leaving behind holes in the valence band. However, since no external electric field is applied, these electrons will be moving randomly, hence there is no net current. Because if there is no electric field, that means there cannot be any current. If it is a simple piece of silicon, and you are not applying any electric field, there will not be any current, because electrons can move, right? Here they are having free space, they can move, but they are moving randomly. But if I apply the electric field, they will move in a certain direction, and if they are moving in the certain direction, it will give us some current. Okay, so movement in certain direction is important. But as of now, without electric field, this is the condition. Without electric field, they are moving randomly. Okay, and by default you will be considering at room temperature only. Let us say some question is coming there, they did not mention any temperature. They are saying that there was a intrinsic silicon semiconductor we were having, and then we doped some donor atoms in it. So donor atoms we used 10 to the power 10. Let's just say they will say that we have done the doping of 10 to the power 10 atoms per centimeter cube. So in 1 centimeter cube volume, we have doped 10 to the power 10 atoms. So at which temperature this is happening? At room temperature it is happening. So you will, by default, you will assume that all 10 to the power 10 atoms will give them free electrons. So all these 10 to the power 10 electrons are giving them free electrons. By default, you will be there at the room temperature only. You will not say, sir, there is no temperature, that means these are of no use. They will not conduct the current. Because you will say that, sir, at 0 Kelvin, they are of no use, because they are not reaching at the conduction band. But by default, you will always be at the room temperature only, at 300 Kelvin only. Okay. So by default, you will say that all of them are ionized. All of them have gone from donor level to the conduction band. Okay. Now, how would I represent n-type semiconductor? So this is my semiconductor. This is my semiconductor. Okay. This is my semiconductor I am having. Now, what phosphorus atom is doing? It was having 5 electrons, right? 4 electrons are making bond. 4 electrons are making bond. And it is donating some electron. 4 are making the bond and 1 electron it is donating. So it is the donor atom. And once you become the donor, you become positive, right? If I give my electron to someone else, what I will become? I will become positive, no? Because I am giving something. That means I will be getting the interest, right? If I am giving you 10 rupees today, tomorrow I can get a 1% interest. So I can get 10.1 rupees next day. 1% interest. Just a joke, okay? Basically, you will become positive, no, if you donate something. So phosphorus will become positive. How I am donating it? By the donor atom. So donor atom are having 4 electrons. Sorry, donor atom are having 5 electrons. 4 are making the bond. 4 are making the bond, and 1 is they are donating. 1 electron they are donating. So donor atom will become Nd positive. So on the donor atom, positive charge will come. Along with the positive charge, they are donating an electron as well. So this is how I will show my n-type semiconductor. Donor atom is becoming positively charged. Along with the positive charge, they are having 1 electron as well. Donor atom is becoming positively charged. Along with that, they are having an electron as well. Positively charged electron, positively charged electron. This has become positively charged. Along with that, they are donating one electron as well. No, so this electron I am making positively charged electron, 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 positively charged electron. So this, because of the phosphorus I have made, some electron hole pair will also be generated. No, electron hole. So some electron hole pair will also be generated. So minority hole concentration will also be there. Minority hole concentration will also be there, and because of these holes, some free electrons would have also been made. So usually in many of the diagram you would see that they will not make these. They will only show these electrons. That's it. The electrons which are coming because of the donor atom. But you can also show that there will be minority holes as well. When we will be studying p-n junction, at that time I will make these minority holes as well. Okay, and then because of these holes, some electrons will also be there. So you don't need to make these electrons because a lot of electrons you have already made. Just I have made some small holes as well. What these holes are saying? These holes are saying that minority holes are also there. Electrons and minority holes are also there. So this is how I will be representing my n-type semiconductor. Is that clear to you? In some diagram, if I forget to make this, don't be confused. Okay, if I am forgetting to draw the minority charge carriers, then it is fine. In a lot of diagram you would not see minority charge carriers, but majority charge carriers, this is how I will be making. Now you just let me know, this particular semiconductor, this particular material, is it positively charged, it is negatively charged, or it is neutral? This particular semiconductor material, look at this diagram, this diagram and this diagram, both are same, right? This diagram, this is the semiconductor only, and this is the same semiconductor. So look at the diagram and let me know, is it positively charged, negatively charged, or neutral? When it is donating some electron, what it is becoming? Positively charged. When it is donating some electron, what it is becoming? Positively charged. This positive charge has been neutralized by this negative charge. This positive charge has been neutralized by this negative charge. This negative charge has been neutralized by this hole. This negative charge has been neutralized by this hole. So this semiconductor is electrically neutral. Like when I represent Nd as Nd plus, they will say that okay, n-type semiconductor is positively charged. No, it is not positively charged. It is electrically neutral. Because if it is becoming positively charged, that means it is giving some electron as well. So there is electron also present, there is positive charge also present. So positive, negative, they will cancel out each other. It is electrically neutral. That's why they will not show these holes. They will only show this particular thing, and then they will tell that positive electron, positive electron, positive electron, positive electron, positive electron. So everything is being neutralized. Although I will show holes here as well because they are the minority charge carriers. Is that clear to you or not? So this n-type semiconductor is electrically neutral. So this is what I have written. Even after doping, the semiconductor as a whole remains electrically neutral. This is because every donor atom, when it donates an electron, it becomes a fixed positive ion, balancing the charge of the free electron when it is released. Okay, is that clear to you? Right. Now, across this semiconductor, across this n-type semiconductor, what I am going to do, I am going to apply the electric field. First, what we studied, absolute 0 Kelvin temperature with and without electric field. Then we studied 300 Kelvin temperature without electric field. Now we are going to study 300 Kelvin temperature with electric field. Okay, and even if the temperature is not mentioned, by default you will take 300 Kelvin temperature only. Is that okay for you? So there is this semiconductor, across this I am applying a V0 battery. Okay, so what will happen? Because of this V0 battery, here there will be positive charge, here there will be negative charge. Because of that, there will be an electric field. This electric field will be E. I am calling it E external because it is coming because of the external source. This battery you applied. So externally you are applying the battery, right? So that's why it is known as external field. So I am applying an external electric field. Electrons will move opposite to the electric field. So electrons will move here. If electrons are moving here, that means electrons are moving in this direction. And since they are moving in this direction, so current of electrons will be in this direction. So I am representing current because of the electrons. What about the hole? This is the minority charge carrier. Hole will move in the direction of the electric field. Holes will move in the direction of the electric field. Holes will move in the direction of the electric field. So these are the holes which will be moving in the direction of the electric field. And since they are moving in the direction of the electric field, what will be the direction of the current? Direction of the current will be in the same direction as the hole. So this will be the direction of the current. Right? I told you hole behaves like a positively charged particle and electrons behave like a negatively charged particle. Since they are the negatively charged particle, so they will move in the opposite direction to the electric field. Right? And since they are moving in the opposite direction to the electric field, then the current will be in the direction of the electric field. What about the holes? Holes will move in the same direction of the electric field. And since they are moving in the same direction of the electric field, the current, basically if holes are moving in the same direction of the electric field, what does that mean? That means electrons are moving opposite, right? Because here only I told you this hole is moving here. What does that mean? This electron is actually moving here. So this current is coming because of the movement of electron only, not because of the movement of hole. Just for the understanding purpose, we are saying that holes are moving, but actually electrons are moving. And since these electrons are moving here, holes are moving here, so the direction of current would be in this direction only, right? So from now onwards, I will just say that holes will move in the direction of the electric field and the current will also be in the same direction of the movement of hole. Okay. So in your mind, what you will think, okay, holes are moving, that means electrons are moving. Which electrons are moving? Covalent bond electrons are moving. And since they are moving here, so the direction of electric field, so direction of current would be in the opposite direction, or you can say in the same direction of the hole movement, or in the opposite direction of the covalent electrons movement, right? So total current, I total would be electron current plus hole current, right? But you know one thing, what do you know? That since number of electrons are very much larger than the number of holes, right? Number of electrons are very much larger than the number of holes. So this IN component will be very larger than the IP component. So this I total will approximately be IN. Basically in the current, majority contribution is of electrons only, because number of electrons are much more larger than the number of holes. Is that clear to you? So this theory is written. When an external electric field is applied, free electrons will drift opposite to the field. This is known as drift current. Okay, what this is known as drift current, because electrons are drifting because of the electric field. Electrons are drifting or holes are drifting because of the electric field. Although we will write down the definition, don't worry about that. This is the drift current. There will be some diffusion current as well. So definition and everything we will write down. Don't worry about that. Just I am telling that if electrons are drifting, if electrons are moving because of the electric field, that's why it is known as drift current. So drift word is coming, that means electric field is there. If the drift word is coming, that means electric field is there. There will be another mechanism because of that electrons can move, and that would be diffusion. So that we will study later on. But as of now, electrons are moving because of the electric field. So if electric field is there, that means drift word would come into action. Okay. Yeah. So in N-type semiconductor, electrons are the majority charge carriers. So the current is mainly due to their motion, making the material as a good conductor. Holes are few in numbers, contributes very little to the current. Okay. So what did you understand here is that in the intrinsic semiconductor we were having lesser current, but in the extrinsic semiconductor what we have done is that we have increased the number of charge carriers. The number of charge carriers have been increased. Previously 10 electrons were there and 10 holes were there. I am speaking thus. In English we call it 10. So previously 10 electrons were there and 10 holes were there. What we did? We introduced donor atoms. 50 donor atoms. All 50 donor atoms will give you 50 electrons, right? So total number would be somewhat different. That formula we will see later on in the next lecture only. We will see that formula, but you could see that from 10 to directly 50. Like at least 50 it would be. It would be more than 50 only. At least 50 electrons would surely be there. Are you able to understand this point? So we have increased the number of charge carriers. Previously number of charge carriers were 10 and 10. You can collectively you can call 20 charge carriers were there, but now already 50 electrons are added. Okay. Yeah, so we have increased the conductivity. So now it is working as a good conductor. So previously here we saw that in the intrinsic semiconductor, it was not a good conductor, it was a very poor conductor. It was a very poor conductor. But now what we have done is that we have made a good conductor which is conducting some good current. Is that clear to you? Okay. So in the same manner that we have studied n-type semiconductor, in the same manner we need to study p-type semiconductor. And everything regarding the p-type semiconductor you would be able to tell on your own. So in p-type semiconductor, what do you think? Which kind of atoms I will dope? Doping means just including the atoms. Doping is a separate process. Like if you want to study the process of doping, that's how I am actually doing it. Like on the silicon crystal, how I am actually introducing phosphorus here. So that process is studied in IC technology that has been removed from the syllabus. So we are not going to study it. As of now, you will just study that doping means some atom is coming and replacing one particular atom. That's it. This is what you will understand. But doping is a separate process that you don't need to study. So now, what do you think? What kind of atom I will be doping here? I will be doping group 3 atoms: boron, aluminium, gallium, indium, helium. So I will dope boron, or you can dope aluminum as well. So let's dope boron here. Okay. So in the outermost orbit or in the valence shell, how many electrons boron is having? Only 3 electrons. So let's just say in this place of silicon, boron is coming. So these 4 electrons are gone. Who is coming? Boron is coming. So boron is saying that I am having only 3 electrons. So all these 3 electrons will make the covalent bond. What will happen here? Here vacancy will be there. Are you able to understand this point? Here vacancy will be there, no? Right? Another boron atom will come. Let's just say it is coming here. So what boron atom will say? Boron atom will say that, sir, I can make 3 bonds because I am having 3 electrons. But one vacancy I will have. Now this vacancy is ready to take electrons. This vacancy is not coming because of the temperature. This vacancy is coming at 0 Kelvin only. This is not electron hole pair. Like this electron is gone and then electron hole pair we are getting. No. This vacancy is coming because of the boron atom. So this vacancy is ready to take this electron. Are you able to understand this point? So what do you think where this holes will be there? Like what will be the energy level of these holes? Here are our bound electrons, right? Here are our bound electrons. This electron I am representing here. This electron I am representing here. This electron I am representing here. So these are our bound electrons. This hole is ready to take these bound electrons. That means this hole should be near to these electrons only, you know. Like if you give just room temperature, what will happen is that this will move. As of now they are bound because they are not getting any temperature. Just as they get the temperature, they will say that okay, near to me only I am having some vacancy, I can move. Or this electron will say that I will move. So at the room's temperature, they will move. That means they are ready to take the electron. This hole is ready to take the electron. That means it will be near to the valence band. Say yes or no. So just above the valence band, you will be having acceptor energy level, because here what you are having holes. What you are having holes. So this is your acceptor energy level. Let me make more here. Similarly, in the conduction band as well, there will be a lot of states, but I am making only few. So this will be your acceptor energy level, which is made just near to the valence band. Why near to the valence band? Because this vacancy is saying that yes, I am ready to take the electron. But at 0 Kelvin will it happen? No, because at 0 Kelvin they cannot move. So this hole will also remain as it is. This vacancy will remain as it is. These electrons will remain as it is, and this will remain empty only. So what do you think? At 0 Kelvin, will there be any current? No, because conduction band is completely empty and valence band is completely free. Sorry, valence band is completely filled. Why? I don't know why I again and again say free. I want to say filled. Okay. So conduction band is completely empty and valence band is completely filled. And since they are completely empty and completely filled, there is no chance of the current even if you apply an external electric field. So at 0 Kelvin, even if I apply an external electric field, it will not conduct any current. But at room's temperature, they will get enough thermal energy to go from here to here, right? So this is what we are going to see at 300 Kelvin. What will happen is that these are the holes. These are not clear. I will make it clear. So these are the holes you are having, and these are the valence band electrons. These are the valence band electrons. Okay. Yeah. So they will get enough energy to recombine here. So this electron will go here. So what will happen? You can say that what you can say this electron, or from here you can say that this electron will go here. So what will happen? Another vacancy is made here and this electron has reached here. Previously this electron reached here, now this electron reached here, right? Now what will happen is that this electron has reached here, now this electron will reach here. So it will create a vacancy and this will reach here again. So in that manner, and some electron hole pair will also be generated, because at that temperature some electrons will get enough energy to reach here as well. So some electron hole pair will also be generated. So here another hole is generated and another electron is generated. What I mean to say is that some these covalent bond will also break. No, this bond will also break, electron hole, right? This bond will also break, hole and electron, right? So let's just break one more bond. Right. Now what do you see? There are a lot of vacancy in the valence band. There are a lot of holes in the valence band. And in the conduction band, there are very fewer free electrons. So these are the free electrons. What do you see here? Free electrons are 1 and 2. But how many vacancies are there? 1, 2, 3, 4. Here I did not replace the vacancy. What I mean to say is that someone would be saying that, sir, from here electrons are going into the from here electrons are going, that's why they are making this hole, right? So what you would show here, that this electron would go here and it will create a hole. So number of hole will remain same only. What I mean to say is that, sir, in diagram why you did not show that electron will go from here to here? Electron will go from this place to the hole. So what will happen is that here vacancy will be made and here this will be filled. So basically vacancy will be there. Vacancy will only be 1. Are you able to understand this point? So that's why I did not show it in this manner. That because of the boron atom there was one vacancy, that vacancy is remaining there only. Just for your understanding purpose, what is happening is that from the valence, these valence shell electrons are getting enough energy to fill the vacancy. These valence shell electrons are getting enough energy to fill this vacancy. Like these electrons will get the energy, it will fill this vacancy. These electrons will also get the energy, it will fill this vacancy, and then they will end up making holes. So all the vacancies that was there in the acceptor energy level, all the vacancies will be filled. So there were how many vacancies? 6 vacancies were there, and because of these 6 vacancies, 6 holes were made, and 2 holes are made because of these covalent bond being broken, right? So 2 holes are made because covalent bonds were broken. So 2 holes and 2 electrons were made because covalent bonds were broken, and rest of the holes are becoming because of the boron atom. So every boron atom will give you 1 hole. Every boron atom will give you 1 hole, and this hole will be taking any kind of electron. If you apply any electric field, with respect to the electric field, electrons will move. Covalent bond electrons can also move. This hole is ready to take the electrons, and since the electrons are moving, that means you will get some current for sure, right? So you can see that in valence band there are a lot of holes. Since there are a lot of holes in the valence band, that means yes, there are vacancy. If vacancies are available, what does that mean? Electrons can move. In the conduction band as well, there are some electrons, but they are very few electrons. So majority of the current will be coming because of the valence band holes only. not because of the electrons. So here who will be the majority charge carriers? Holes will be the majority charge carriers. And who will be the minority charge carriers? Electrons will be the minority charge carriers. Is that clear to you? And since holes are the majority charge carriers and holes are positively charged, that's why it is known as p-type semiconductor. Is that clear to you or not? Well and good. Did you understand this point? So at 0 Kelvin, with or without electric field, it will always work as insulator. At 300 Kelvin, yes, we are having free electrons, we are having holes as well. But since there is no electric field, they will be moving randomly, and since they are moving randomly, the total current would be 0. But just as I apply the electric field, what will happen is that this electron will come here. That means holes will be moving in the direction of the electric field and electrons will be moving in the opposite direction to the applied electric field. And because of this net motion, there will be some current, and that current would be good enough to call it a good conductor, right? So all these theories have been written. A p-type semiconductor is formed when a pure semiconductor like silicon is doped with trivalent atom such as boron, aluminum, gallium. These atoms have 3 valence electron which form covalent bond with the neighboring silicon atoms. However, one bond remains incomplete, creating a hole which acts as a positive charge carrier. Hole will act as a positive charge carrier only. This creates a special energy state just above the valence band because these holes are ready to take the electrons, called the acceptor energy level. This energy gap between the acceptor level and the valence band is very small, so electrons from the valence band can easily jump into the acceptor level, leaving behind some holes in the valence band. Thus, in the p-type semiconductors, holes are the majority charge carriers and electrons are the minority charge carriers. Okay, and from where these electrons are coming? These electrons are coming because of the thermal excitation from the valence band to the conduction band. From the valence band to the conduction band, or you can understand by the crystal structure as well. By both of the analogies I am explaining you, by the crystal structure along with that band diagram as well, right? At 0 Kelvin temperature, there is no thermal energy present, so holes does not get like holes will be existing there, but they are not filled with the valence shell electrons, right? Valence band electrons. Basically, conduction band is completely empty at 0 Kelvin and valence band is completely filled. That's why there will be no current. This is what has been written here. No thermal energy is available. Holes do not exist because electrons cannot jump to the acceptor level. Holes do not exist where it doesn't exist. Holes do not exist in the valence band. Okay, they are saying that holes do not exist in valence band. In valence band or in the crystal structure as well. No, like here holes are not existing. They are ready to take the electrons, but this electron is not moving. No, this hole is ready to take the electron. This hole is ready to take the electron, but this electron will not move because there is no thermal energy, right? So when they are saying that no holes exist, when they are saying that no hole exists, that means they are talking about valence band and conduction band, not about this acceptor energy level. In acceptor energy level, there are holes, but they will not contribute in the current, right? Current contribution will be done because of this band or because of this band. Are you able to understand this point? The valence band is completely filled, so no conduction occurs. With or without electric field, the material will behave like an insulator. But at 300 Kelvin, what will happen is that thermal energy will excite electrons from the valence band to the acceptor level, creating holes in the valence band. Some electrons will also get thermally excited from the conduction band, from valence band to the conduction band. So some minority electrons will also be there and majority holes will also be there. Without an electric field, these motions will be very random, right? If you are not applying the electric field, then holes and electrons will be moving in the random direction. Since they are moving in the random direction, the net motion will be 0, and since the net motion is 0, the net current will also be 0, right? But just as I will apply the electric field, the current will flow. But before that, we will see the representation of a p-type semiconductor. So what do you think, what kind of representation would be there? Boron was having 3 electrons. What it will do? What boron is doing? It is taking 1 electron. So if it is taking some electron, that means it will be negative. If I am taking 10 rupees from you, tomorrow if I return the money, I will have to return you 10.1 rupee because of the interest. That means I am going into the loss. I have lost 0.1 rupee. So that means I am negative. So I will be negative. So if I am taking something, if the boron is taking some money, that means it will be negative. Here they were called as donor atom, right? Here I wrote donor atom. So here they are known as acceptor atom. Boron is a acceptor atom, Na. So in place of boron, what I am writing? Na I am writing. So Na is having 3 valence shell electrons and 1 vacancy it is having, which is ready to take the electron, That's why they will be negatively charged. So they are negatively charged, but they are giving you a hole as well. They are negatively charged, but they are giving you a hole as well. Negatively charged, giving you a hole. Negatively charged, giving you a hole. Not electron, hole. Negatively charged, giving you a hole. Negatively charged, giving you a hole. They are negatively charged, giving you a hole. Negatively charged, giving you a hole. Negatively charged, giving you a hole. Along with that, there will be some conduction band free electrons as well. So minority free electrons also I can make. Even if it is not made, then also you should not be getting confused. Minority charge carriers, they will not make sometime. Okay, but in PN junction, I will surely make the minority charge carriers as well. Right? So what do you think? It is electrically neutral or not? Yes, it is electrically neutral, because boron is negatively charged, acceptor atom is negatively charged, but it is giving you a hole as well, and hole is positively charged. So here negative positive, negative positive, negative positive, everything will cancel out, and electrically it is neutral. So it is neither positively charged, it is nor negatively charged, it is electrically neutral. Everything is electrically neutral. Every material you see, this is electrically neutral. If there was charge on it, then it will not be at the equilibrium. Like, it would be continuously changing. Basically, there is no charge on anything. No, there is no charge on this mobile. There is no charge anywhere. Right? So every material is electrically neutral. So this is also a material only. No, this is a p-type semiconductor. This is also electrically neutral only. And from here as well, you can see that they are taking the electron. Since they are taking the electron, they are giving you a hole as well. So hole is a positive charge particle, and since they are taking the electron, that means they will be negatively charged. They will become a negatively charged ion. So what is this? This is a ion. This is like a ion. Na minus. This has become an ion, right? Negative ion, and this is the particle. I hope you understand the meaning between ion and particle. Ion does not conduct the current, but particle will conduct the current. This ion is not helpful in conducting the current. This boron is not conducting the current. This hole is conducting the current. Electrons are conducting the current. Here, electrons are conducting the current. This positive charge is not conducting the current. So this is also an ion. Are you able to understand this point? Okay. And at room temperature, here I said that all the vacancies are filled. So by default, we will consider that all the vacancies will be filled. But it might happen that in some questions it will be given that only 60% of the vacancies are filled, 70% of the vacancies are filled. What may happen is that, let's just say I am saying that I am doping 50 acceptor atom. What I am doing? I am doping 50 acceptor atoms. So 50 acceptor atoms should give me 50 holes. But they will say that ionization is only 70%. Ionization is 70%. What does that mean? That means only 70% of the holes are filled with the electrons. That means only 70% of the holes will be made. So you were expecting 50 holes, but 70% of 50, 35 holes only you will get. But if nothing is mentioned, you will assume 100% ionization. But if it is mentioned that 70% ionization is done, that means only 70% of the 50 holes you will be getting. That means 35 holes you will be getting in the valence cell, in the valence band. Okay. Similar thing can happen with this donor energy level as well. They will say that 50% of the donor atoms are ionized. 50% of the donor atoms are ionized. What does that mean? That only 50% of these electrons have reached to the conduction band. Rest 50% did not reach the conduction band because temperature was not enough. Anything can happen. Rest 50% were lying here only. They did not reach the conduction band. And if they are not reaching the conduction band, that means they are not contributing in the current. Current will be contributed only by this guy and this guy. Nothing in between. This guy is not contributing in the current. Which guy? This guy is not contributing in the current. If your electron is there in the conduction band, and if your holes are there in the valence band, then only they only will contribute in the current. Nothing else will contribute in the current. Electrons in the conduction band, holes in the valence band. That's it. So whenever I say conduction band, your mind should be going towards electrons. Electrons means free electron. Whenever I say valence band, your mind should be going towards holes, right? Holes means vacancy of electrons. Is that okay for you, right? So now what we are going to do, we are going to apply an electric field. So even after dropping, the semiconductor remains electrically neutral because each trivalent atom that accepts an electron becomes a fixed negative ion, balancing the positive charge of the hole, right? Negative ion balancing the positive charge of the hole. So this is electrically neutral. If I apply external electric field, what will happen? Here I should make a minority electron as well. So if I am applying the external electric field, or you can say if I am applying a battery V naught. So from here positive, this will be the positive side, this will be the negative side. So there will be an electric field that will be developed from positive to negative. So this will be your external electric field, right? Holes will be moving in the same direction of the electric field. Holes will be moving in the same direction of the electric field. So current will be this. And electrons will be moving in the opposite direction to the electric field. Electrons will be moving in the opposite direction to the electric field. And since electrons are moving in this direction, so current will be there in this direction. So your total current would be IP plus IN. But you know that number of holes are very much greater than number of electrons. That's why IP component will be very greater than IN component. So from here, the total current would nearly be equals to the whole current only. Is that clear to you? Okay. So this line only will be written here. When an external electric field is applied, holes drift in the same direction as the applied field and electrons drift opposite to the applied electric field. Since holes are the majority charge carriers, the current is mainly due to their motion only. Electrons are few in number and contribute very little to the current. The semiconductor now conducts electricity efficiently compared to the intrinsic material. Okay. So now here also this has become a very good conductor, right? Now conducts electricity efficiently. So who is having better conductivity? Intrinsic semiconductor or p-type semiconductor? So p-type semiconductor is having better conductivity. And if I compare between p-type and n-type, who is having better conductivity? So n-type is having better conductivity. Why so? That we will study in the next lecture. Okay. Look, intrinsic, extrinsic. Who is better in terms of conductivity? Extrinsic is better. That's why we are making extrinsic. No, first we study intrinsic. In intrinsic, we go to know that it is not enough. That's why we are studying extrinsic. So in extrinsic, we studied two types, n-type and p-type. In n-type, majority charge carriers are free electrons, and in p-type, majority charge carriers are holes. In n-type and p-type, who is having better conductivity? N-type is having better conductivity. Why so? That we will study in the next lecture. Okay. But yeah, as of now, we have just seen the working, no formula, nothing. Only the pure concept we have seen, that how we are getting better conductivity. Formula and everything will come in the next lecture. A lot of questions will also come in the next lecture, and everything you will be able to solve. But in EDC, this is the beauty of EDC, that first you need to focus on theory, that we will see, then we will see problems and formula, and we will build up our problem solving skills. So in EDC, whenever you read any question, not in EDC only, in any subject I will tell you, whenever you read any question, it is not only important to solve the problem. Surely solving the problem is important. But when you read the question, each term, what each term is representing, what is the meaning of each term, you should know that. If you don't know the meaning of each term, still you are able to solve the problem, that means you are not actually learning. So I always say that whenever you are solving the PYQ, you read the question completely, line by line, and the meaning of each line, each word should be clear. And if it is clear, then you are saying that yes, I am going on the right path. As I say in EDC, like statement will be very large, but what student will do? They will do that, okay sir, this value is given, this value is given, this value is given, this formula I will apply, solve the question. This is the wrong way of solving the problems of EDC. 8 out of 10 questions you will get correctly. If you solve the problem in this manner, your efficiency will be 80%, and if you do the minor mistake, then your efficiency will go down to 50%. So your efficiency will be 50%. Now if you need to increase your efficiency from 50 to 80%, then you need to study the theory as well. Without studying all these theory, I could have directly started from the formula, and I would pick the PYQs, you would be able to solve it as well. But there is an importance of theory if you want to solve 100% of the questions. 20% minor mistake would be there, we cannot help it. Even if I know the 100% of the paper, I will get 80 marks only. That I know. About myself, I am telling. I don't know about you. If I know 100% of the paper, I will get 80 marks only. Okay, so that I am telling about myself. So similarly, it would happen with a lot of students. But if you want to maintain that 80% of the efficiency, concepts are also important. Okay. Now we will see some definitions, some important points. Basically, now we will build up our formula. So from here to the next lecture, the same thing will happen. From here to the next lecture, the same thing will happen, that we will build up some formula and these kind of things. Like in this lecture, again and again I was using electric field. So what is this electric field intensity? How it is related to this voltage? So that we are going to see. Then we will see some types, like some basic thing we are going to see. As of now, what we have built up, sir, we started with semiconductor. Why semiconductors are important? How a particular material is made from atoms. In atoms there is nucleus, electrons. Then we saw the energy splitting, and then we go to know that how energy bands are made. Now energy bands are made, then we go to know that we are having conduction band and valence band and the conduction band. Then we studied about intrinsic type of semiconductor. There everything was covered with silicon only. Everywhere silicon was there, covalent bonds were there. Since those covalent bonds were there, they were not breaking up at 0 Kelvin temperature. So we are not having any free electrons. So conduction band is completely empty and valence band is completely filled. So there is no current even if you apply the electric field. Then at room temperature, what happens is that because of the thermal energy, some electrons from the valence band are going to the conduction band. So we are getting some vacancy there. Along with that, we are having some free electrons as well. So these vacancies are also moving and these free electrons are also moving. Because of that, we are getting some current. But that current was not enough because we were studying intrinsic semiconductor. Everywhere there was silicon only, and number of charge carriers were also low. Like we were having electrons, we were having holes. Those numbers were very low. Then we studied extrinsic semiconductor, N-type semiconductor, P-type semiconductor. In N-type, we were doping pentavalent atoms. What all are those pentavalent atoms? Phosphorus, New Zealand, Pakistan, Australia, sub BK. So you can read the name: nitrogen, phosphorus, arsenic, antimony, and bismuth. So these 5 atoms, I was doping phosphorus atom there. Phosphorus is having 5 valence shell electrons, 4 are making the bond, 1 is loosely bound. At 0 Kelvin, this particular electron is not going into the conduction band, but just as the room temperature we get, this electron is having very lesser gap between the conduction band and this donor energy level, and that gap is covered because of the thermal energy, and this electron will get excited into the conduction band, and because of the thermal energy only, some electrons from the valence band will also go to the conduction band. So there will be some holes in the valence band and there will be a lot of electrons in the conduction band. Why a lot of electrons? Because of the donor energy level. So since there are majority electrons and minority holes, both of the electrons and holes will give the current in the same direction. So total current will be added, but majority charge carriers are electrons. That's why the majority current will be because of the electrons only. Then we studied about P-type semiconductor. In P-type semiconductor, we were doping trivalent atoms. There 3 electrons were there in the outermost shell. So 3 electrons were making the bond, 1 vacancy was there. At the room temperature, no electrons could move, nothing could move, so there was no current flow. But at 300 Kelvin temperature, some electrons from the nearby atoms could fill the vacancy and create another hole. Create the same hole only. Basically, previously also you were having the hole. Now just the hole has been shifted. So now the hole can move. Along with that, because of the temperature as well, some electrons are going from the valence band to the conduction band. They are also creating some vacancy. Okay, so holes you are already having, but in the valence band, because of the boron atom, you are having a lot of holes. In the conduction band, there are minority electrons, right? So majority are the holes, minority are the electrons. Because of that, you are getting the current. Holes are drifting in the same direction of the electric field and electrons are drifting in the opposite direction to the electric field. Both are giving the current in the same direction, but majority charge carriers are holes in the P-type semiconductor. Since they are the majority charge carriers, so the current is mainly due to the holes only. So yeah, in the intrinsic semiconductor, we were having lesser current, but in the N-type and P-type semiconductor, we are having more current. And this is what we wanted. We wanted to increase the current, we wanted to increase the conductivity. Because insulator we have already made, perfect insulator we have already made, we want to go from insulator to the conductor. So that we have done. But in between, we used something called electric field intensity. So that we are going to study. Then we are going to see some classification of semiconductor. So hardly 10 to 15 minutes it will take you. Then we will study like what kind of band gap is there in insulator, what kind of band gap is there in semiconductor. In semiconductor we have already studied the band gap, conduction band, valence band, there is a certain gap. So like basic theory, very basic theory it is. In class 11 12 also you would have studied it. So these kind of basic theory we will see. Then we will see that how band gap is related to the temperature, that also we will see. And then we will see that what is the meaning of doping. Like doping we have done that, but how much doping we should have done. Okay, so these things we will see. Hardly it will take 10 to 15 minutes. So I will take a break and then I will come back. I will explain these points. In the next lecture we will move, we will study about some formulas and then we will solve some questions as well. Okay then, yeah. So let me take a break and then I will come back. Yeah, hi everyone. So let's understand the meaning of these terms. So first we are going to understand about electric field intensity. Okay, so what do you mean by electric field intensity? So electric field intensity is given by negative gradient of electric potential. So we will understand that, but ignore this formula. Let's try understanding the meaning of electric field intensity. So let's just say there is this material. This material could be anything, semiconductor, conductor, insulator, it could be anything. So there is this material. Across this material, what I am doing is that I am connecting a battery of V0 volt. I am assuming that here there is zero potential. If this is zero potential, that means this will also be zero potential. If this is zero, then this potential will be V0. So this potential will become V0. The 0, 0, 0, 0 will come here and then it will make a jump to V0. So this potential will be V0, right? So this V0 potential has gone across the material. So if I call this, if I am saying that this material is having a length of L, this material is having a length of L. So if this is x equals to 0, then this will be x equals to L. Now at x equals to 0, what is the potential? V0. So I am drawing Vx versus x. What is Vx? Vx is the potential across this element, or you can say across this material. Vx is the potential across the material or element, whatever you want to call it. So at x equals to 0, what is the potential? V0. At x equals to L, what is the potential? 0. So the potential is going from V0 to 0, right? This is the graph of Vx versus x. Now if you differentiate this graph, what you will be getting? If you differentiate this graph, dVx by x, if I am calculating, what does that mean? Differentiation means simply I am calculating the slope of this graph. The slope will be minus V0 by L. This minus V0 by L multiply with negative sign. Is known as electric field. So basically your potential is decreasing in this direction, right? You started with V0 and it is decreasing to 0. Your potential is decreasing in this direction from V0 to 0. So your direction of electric field is always in the decreasing direction of the potential. Your direction of electric field. This is the direction of your electric field, right? So your direction of electric field is always in the decreasing direction of the potential. Here potential is high, here potential is low. From high to low your potential is going. So this is the direction of your electric field. That's why there is a negative sign. Are you able to understand this point? So here what will be your electric field? Your electric field would be this V0 potential is there across the length L. V0 potential is there across the length L. So your electric field is coming out to be minus of minus V0 by L. So your electric field is V0 by L. So you don't need to care of this sign much. You will just remember E is equals to dV by dx. The sign will be taken care. How it will be taken care? You will see that how the potential is decreasing. So in the direction the potential is decreasing, that will be the direction of electric field. So you don't need to think of the sign. What you will see, across this element V0 potential has been applied and the length of this element is L. So what will be the electric field? V0 by L. What is the unit of the V0? That will be volt. And usually we will see the length will be in centimeter, millimeter or micrometer. The length will not be in meter. Okay. So electric field unit is actually unit of electric field. Unit of electric field. In SI it is volt per meter. Volt per meter. But we will usually use volt per centimeter. Why so? Because usually our length of the semiconductor will be in the centimeter or millimeter or micrometer. Are you getting this point? Okay, so volt per centimeter I can write down, volt per micrometer I can write down, volt per millimeter I can write down. Volt per meter will not be used in EDC, but SI unit is volt per meter only. Is that clear to you? All good, all fine. From here, can you write down the expression of, here I should have written Vx, right? Because your potential is the function of x. Here at x equals to 0, your potential is V0, but at x equals to L, your potential is 0, right? So from here, can you write down the expression of Vx? Expression of Vx would be integration minus E dot dx, and here I will put the limit of x. Now this E can also be a function of x, although here it is coming constant, but it can be a function of x. Let's just say your Vx was 3 minus 2x square. This was your Vx. Then what would have been your electric field? That would be minus dVx by dx. So if you differentiate it, what you will be getting? Minus 4x, and then another minus sign is there, so you will be getting 4x. So your electric field can be a function of x as well, right? And we will see some questions where electric field will become a function of x. So it can be a function of x. So better how I should have written it. So let's remove this formula. I will write down the formula of Vx here. So Vx could be given integration minus Ex dot dx. Okay, and here I will put the limit of x. Let's just say they are asking the potential from x equals to 0 to x equals to L. So I will put x equals to 0 to x equals to L. If they are asking from x equals to 2 to x equals to 5, so x equals to 2 to x equals to 5. So this is how I can find my Vx as well. Is that clear? Very simple thing. In basics of network analysis also you would have studied it, or anywhere in EMFT as well you would have studied it. Only thing you need to remember is this. Electric field is given by minus dVx by dx. There you go. This thing you need to remember. That's it. This thing you need to remember. And from here, this thing you need to remember. Okay, so this is the meaning of electric field, and this theory I have written. The electric field intensity E at a point is defined as the rate at which electric potential Vx changes with distance. So rate of change of electric potential with respect to the distance. Rate of change of the electric potential with respect to the distance. That is your electric field. And the negative sign is indicating that electric field points in the direction of a decreasing potential. So in the direction where potential decreases, in that particular direction you get the electric field. Okay, so this is the meaning of electric field intensity. Now we will do the classifications of a semiconductor. Okay, so there are two kinds of semiconductor: elemental and compound semiconductor. Then we will see direct band gap semiconductor, indirect band gap semiconductor. So classification can be done on many things. So based on the composition, we are doing the classification here. That classification is elemental semiconductor, compound semiconductor. In ESC there can be some questions. In gate examination, questions will not be asked from this particular topic. So basically elemental semiconductor means only one element would be there, like silicon, germanium. Okay, but in compound semiconductor, two or more elements would be there: gallium arsenide, indium phosphide. So here gallium is there, arsenic is there, indium is there, phosphorus is there. So it is made of two or more elements. It is made of single element. The crystal structure is diamond. Here the crystal structure is zinc plant. When you study material science in that particular subject, which is not there in the gate syllabus, in the material science you will understand this particular crystal structure. But as of now you will just remember that silicon germanium will have a diamond type of structure, and compound semiconductor like gallium arsenide, indium phosphide will have a zinc plant semiconductor. Okay, sorry, zinc plant structure. This you will remember. This point we will discuss band gap. Here it is written, usually it is indirect. Always it will be indirect semiconductor, it is not sure. And it can be direct or indirect, anything. So as of now, you don't know what is indirect band gap semiconductor, you don't know what is direct band gap semiconductor. In the third lecture, we are going to study it. But as of now, you can just ignore this line. Just ignore this, okay? This band gap line, you can just ignore it. When we study direct band gap and indirect band gap semiconductor, at that time we will study it. Application, it will be used in making diodes, transistor and some integrated circuits. So diode we will study, transistor we will study, and it will be used in making LEDs, solar cell and laser diode. So we will study LED as well, we will study solar cell as well. So these devices also we are going to study it. Okay, so using these elemental semiconductor only, you will make diodes and transistor. and using this compound semiconductor only you will make LEDs and solar cell. So these applications also we are going to study. So just a very simple point, like in a very low level of interview they can ask you what do you mean by elemental semiconductor or compound semiconductor. So if these words are written somewhere, you should know what is the meaning. That's it. No one will ask you anything regarding this. And these indirect bandgap semiconductor, direct bandgap semiconductor, they are important. So we are going to study in detail. We will draw the EK diagram and we will study the meaning of direct bandgap semiconductor and indirect bandgap semiconductor. Also we will study diode as well, transistor as well. All these things we are going to study. But we are not going to study the structure, diamond structure or zinc plant structure, that we are not going to study. Next we are doing the classification of the materials. So you know there are three kind of materials: metal, semiconductor and insulator. Now let's go in the beginning. Here we saw this energy splitting diagram, right? So we were explaining this diagram with respect to silicon, right? But if it was a metal, if your structure was a metal, then this would have been your equilibrium point. Although, like, I forgot to tell the name, this A naught is known as lattice constant. Okay, the name of this A naught is lattice constant. So if it was not a semiconductor, if it was a metal or if it was a conductor, then this would have been the steady state point. This would have been the equilibrium point. I should not say steady state, this would have been the equilibrium point. So here your bond would have been made. So can you see, is there any gap in the conduction band and valence band? Actually there are no conduction band, there is no valence band, there is only one band. There is only one band. Only one band is there. And there were how many electrons were there? 8 electrons were there which were available. So in the valence cell 8 electrons were available. Now these 8 electrons are having free space. Yes, they can move from here to here. In our case, in semiconductor, all these were filled, all these were empty. If this electron wants to go here, it needs to cross this energy Eg. But in this particular case, it doesn't need to cross any energy. If this electron is here, it can go here. If this electron is here, it can go here without even any energy. So they are free to move. Basically, when we studied about partially filled, this condition we studied, right? This condition we studied. So there is only one band, there is no conduction band, there is no valence band, only one band is there. In this band, some states are filled and some states are empty. Some states are filled, some states are filled, some states are empty. So if this was your equilibrium point, then you would have made a metal, or you can say then you would have made a conductor. So in conductor, there is no band gap, or you can say that conduction band and valence band overlap. Actually, there is no conduction band valence band, but for the theory we can say that in conductor, conduction band and valence band will be overlapping. That means there is no gap in them. That means the value of forbidden energy gap, the value of this band gap is 0 electron volt. Is that clear to you? That's why they conduct the current. So this is the thing that we have written. Yeah, so band gap 0 electron volt, copper, aluminum are the example. Conductivity is very high. Okay, for the for the semiconductor, the band gap is from 0.1 to 4 electron volt, and for the insulator, the band gap will be even higher. So if you go to the insulators, if you go back to the again same diagram, so in this diagram you can see that if I move ahead, so here the energy band gap has increased, right? So if you keep on moving here, that means if you keep on reducing the length, sorry, if you keep on reducing the distance, if you keep on reducing the interatomic distance, and let's just say your equilibrium was attained here, your equilibrium was attained here, that means that would have made a insulator, because here the band gap is very high. Let's just say some conduction band is here, valence band is here. Now valence band electrons needs to cross this much of energy to reach to the conduction band. Valence band electrons needs to cross this much of energy to reach to the conduction band, and getting this much energy at room's temperature will be very difficult. At a very high temperature only you can get this much of energy. Although at room's temperature you get only 26 millivolt energy. How this much energy is enough to make the transition, that I will explain later on in some other lecture that I told you when we study Fermi direct distribution. But using that analogy as well, you will not be able to cross this much of energy because this energy is very high. So in the insulators, the band gap is very high. The forbidden energy gap is very high. That's why the electrons cannot make the transition from valence band to conduction band, and the total current is actually 0, right? The conductivity is pretty low. So this is what have been written there. Okay, so all 3 points you have understood. Insulators, band gap is 4 electron volt, greater than 4 electron volts. You can see the example of diamond. In diamond it is 5.5 electron volt, or in the glass as well it is even higher. So conductivity is very low, almost no conduction. So this is the classification of material based on their band gap. So only thing you need to remember is that band gap in the conductors is 0 electron volt. Valence band and conduction band are overlapping. In case of semiconductor, it is somewhere between 0.1 to 4 electron volts. For silicon, it is 1.1 electron volts. For germanium, it is 0.66 electron volt. And for insulator, it is greater than 4 electron volt. Okay. So this is what you need to remember. Now, band gap versus temperature. So as the temperature increases, the band gap decreases. Okay. So let's just say I am writing down the forbidden energy gap at some temperature T is given by Eg naught minus beta naught into T. Now why that happens? So what they are saying that at higher temperatures the atom will vibrate more. So let's go back to our this diagram again. Okay. So what we have made a silicon crystal. So silicon atoms are there. So at room temperature they are stable, but at higher temperature what will happen? They will start vibrating. At higher temperature they will also start vibrating. So if they are vibrating, then their interatomic distance will increase. And if the interatomic distance is increasing, that means you are moving towards this side. It's not that sir it will increase too much that you will reach here, that band gap will be completely gone. No, it will not happen, but a bit of distance will increase. Their interatomic distance will increase, and if the interatomic distance is increasing, that means in the graph you are moving here, and if you are moving towards this side, you can see that energy band gap is reducing. It will surely be semiconductor only. It's not happen that semiconductor will become conductor. No, it will not happen. Semiconductor will not become a metal. It will not become a conductor. It will be semiconductor only, but by a very small amount it will move, because the distance between the interatomic distance is increasing, because atoms are vibrating. If they are vibrating, that means they are being apart. So distance will increase by a small amount. That means the energy band gap will decrease by a small amount. So just only thing you need to remember is that with increase in temperature, the energy band gap will be reducing in the semiconductors. That's it. The relation, if you don't want to remember, then you can ignore as well. This beta naught is a constant, T is the temperature, okay, and this beta naught depends on the material, whatever the material that you are having. Also it depends on the temperature as well. Actually this formula is actually very complex. It is somewhat alpha T square beta plus 300 Kelvin. As far as I remember, this is the formula, but I don't remember the formula exactly. Okay, this is beta plus T as far as I remember. Yeah, this is the formula. Basically this formula is very complex. The only conclusion is if the temperature increases, then this value will increase. Eg naught, what is Eg naught? Eg naught is the temperature, Eg naught is the band gap at 0 Kelvin. Okay, so let's just try calculating the value. Let's just say at 0 Kelvin band gap is 1.18 electron volt. Now beta naught value is anything. Now I am asking what will be the band gap at 300 Kelvin. So I will put 300 here, and beta naught value will be some constant value. Okay, that will depend on the material. So what will happen? From 1.18 something will be reducing. So your answer will be 1.1 electron volt. So as the temperature increases, the band gap becomes lesser. Okay, so this is the thing you can keep in mind. That's it, nothing else. You don't need to put pressure. Don't put any kind of pressure on your brain. Just remember that at higher temperature the band gap will reduce. Okay, because interatomic distance is increasing, and in that particular diagram you are moving towards increasing interatomic distance. If distance is increasing, that means band gap is reducing. This formula, if you want to remember, you can remember Eg naught minus beta T. Beta is a material constant, T is the temperature in Kelvin, and Eg naught is the temperature at 0 Kelvin. Okay, sorry, not temperature, what I am saying, band gap at 0 Kelvin. Now, in intrinsic semiconductor, what we were doing? We were doing the doping, and from there we got the extrinsic semiconductor, right? How did you get the extrinsic semiconductor? In the intrinsic semiconductor, you did the doping. Now, how much doping did you do? How much doping did you do? Based on that, there are two kinds of semiconductor: degenerate semiconductor and non-degenerate semiconductor. In your curriculum, in your syllabus, you will always study non-degenerate semiconductor only. So in the examination, if it is not given, by default you will say that my n-type semiconductor or my p-type semiconductor is non-degenerate semiconductor. So how much doping you did? Based on that, there are two kinds of semiconductor: degenerate and non-degenerate. So if you are doing very high doping, what does that mean? Let's just say in the intrinsic semiconductor, I was having 10 to the power 18 silicon atoms. 10 to the power 18 silicon atoms. 100 is 10 to the power 2. Then 1000 is 10 to the power 3. I was having 10 to the power 18 silicon atoms. Now, for 10 to the power 3 silicon atoms, I am putting one phosphorus. That means how much phosphorus I will have to put? 10 to the power 15. So in 10 to the power 18, why 10 to the power 15? Because ratio is 1 ratio 10 to the power 3. So for every 10 to the power 3 atoms, I need to put one phosphorus atom. If I say ratio is 1 ratio 2, and I am saying that I am having 10 rupees, that means this guy needs to have 5 rupees. How I can get this 5 value? 10 by 2. So similarly, 10 to the power 18 atoms are there, right? 10 to the power 18 atoms are there, and the ratio is 1 ratio 10 to the power 3. That means for every 10 to the power 3 atom, one phosphorus atom should be there. For every 10 to the power 3 silicon atom, one phosphorus atom should be there. That means 10 to the power 15 phosphorus atom should be there. So this is a very high doping, no? If this is the ratio 1 ratio 10 to the power 3, that means it is very high doping. And if this is the ratio 1 ratio 10 to the power 7, that means it is low doping. And since there is very high doping, that means the number of electrons will be more. And if the number of electrons are more, that means the current will also be very large. So almost metallic behavior you will get. Almost it will behave like a metal. But here you will get the semiconductor behavior. Because the doping is not very high. The doping is 1 ratio 10 to the power 7. That means this is the semiconductor. This is the semiconductor, and or I should write silicon only. I can write this is the silicon, this is the silicon, and this is the doping. Doping could be acceptor atoms, or it could be donor atom, it could be anything. So this is the silicon atom and this is the doping. So if the ratio is 1 ratio 10 to the power 3, that means it is high level of doping, or you can call it degenerate semiconductor. And if the ratio is 1 ratio 10 to the power 7, that means for every 10 to the power 7 silicon atoms, you are doping one phosphorus atom. So total atoms were 10 to the power 18, that means you are doping 10 to the power 11 phosphorus atoms. So if you are doping 10 to the power 11 phosphorus atom, then you are good. But if you are doping 10 to the power 15 phosphorus atom, that means you are going towards degenerate semiconductor, which we are not going to study in our curriculum. In our curriculum, non-degenerate semiconductor only we study. Okay, so understood? And if doping is very high, it will give a metallic behavior. Otherwise, for moderate level of doping, it will give semiconductor behavior. Yeah, so that's it about this lecture. In this lecture, first we studied about the semiconductor. In this lecture, we haven't seen any formula. Only one formula we have seen, which is about the electric field. What all terms we have seen? We have seen drift current, right? We have seen that because of that electric field, the electron are getting some velocity. Now electrons will not move freely. There will be atoms, so there will be some hindrance. There will be some collision, so there will be some collision time. The mass of electron can also change. The mass of holes can also change. So there will be some effective mass. There will be drift velocity. There will be drift current. There will be mobility. What is mobility? Movement plus ability is mobility. That means ability to move. So all these things will be there, and we are going to understand about all these things. We are going to understand the formula of all these things in the next lecture. Okay, so I hope you enjoyed the first lecture. Here I wanted to build up the concept of semiconductor physics. That you are getting into the semiconductor physics now. You are able to understand that what we are going to study in this chapter. Formula and everything will surely come in the next lecture, and we will solve questions as well. Okay then. Okay, then yeah, let's meet in the next lecture. Happy learning. Thank you very much. Hi everyone, welcome to PrepFusion. So now we are going to see some basic terminologies. So whenever you see a particular question based on semiconductor physics, so these terms will be again and again used, like average collision time, effective mass, mobility, drift velocity, drift current density. So these terms will be again and again introduced there. So we will see the basic meaning of these terms, and we will see the formula of these terms. Okay. So first one is average collision time. So what is the average collision time? So let's just say this was your semiconductor. This was your semiconductor. This is the semiconductor that you are having. In this semiconductor, silicon crystal. I'm talking about silicon crystal. So silicon atoms are there, and these silicon atoms will be making the bond. So I'm not showing the bond. I'm just telling that these are the silicon atoms. Now it might happen that there would be some impurity. Let's just say I'm talking about donor impurity. Now one electron is a free electron. Now if the current is flowing, that means this free electron needs to move. If the current is flowing, that means this free electron needs to move. But just as it started moving, the movement is not that smooth, right? Because there are atoms, and because of the temperature, if atom gets some temperature, that means they will be vibrating. I told you, if atom is getting some temperature, then it will be vibrating. If atom is getting some temperature, then it will be vibrating. So these atoms are vibrating. These atoms are vibrating. And this electron needs to work. This electron needs to move. Let's just say electric field is applied in this direction. So now this electron needs to move. But what will happen is that just as it will start moving, so since these atoms are vibrating, so it will collide these atoms. Or what may happen is that, like after a collision, it has reached here. Now what is this? This is your phosphorus atom, which is positively charged. Although the complete system is neutral, but phosphorus is positively charged because it has given some electron. That's why it is positively charged. So now let's just say it is working like this. Now what this phosphorus will do? This phosphorus will change the motion of this electron, because this is positively charged, and positive and negative, what they will do? They will repel each other. So it will change the trajectory. Like it cannot go here. It will change the trajectory. So basically, whenever an electron is working, it will collide with the atoms. It will collide with the atoms. It cannot move freely. So let's just say first collision happened at 2 seconds. The second collision happened at 4 seconds. The third collision happened at 7 seconds. So what was the average time here between two successive collision? Here the time between two successive collision is 2 seconds. Here the time between two successive collision is 3 seconds. So what is the average of 2 seconds plus 3 seconds? That is 2.5 seconds. So this average time is known as average collision time. So average time between two successive collision is known as average collision time, because when the silicon crystal is moving, when the electron is moving into the silicon crystal, it doesn't move freely. It will collide with the atoms, and since it is colliding with the atoms, and between the two successive collision there is a certain time. So when you take the average of all these certain times, then what do you get? You get the average collision time. So this is what have been written in complete theory. This is already written, a very simple term. With the term only you are able to understand the meaning. So what it is? It's the average time an electron or charge carrier travels freely before it collides with something, like it could be atom, or it could be impurity, or it could be other electron as well, because there would be a lot of electrons, no, there would be a lot of charge carriers. So it could be other electron. Impurity, I have already told. What do you mean by impurity? Donor atom or acceptor atom, right? So impurity also I have already told, and atom, because atom will be vibrating at their place because of the temperature. Okay, so analogy he has given. This is a very simple analogy, you can read on your own. So this is the average time an electron travels freely. Like average time electron travels freely, that means I told you that first collision happened at 2 seconds and second collision happened at 4 seconds. So between 2 seconds to 4 seconds it was moving freely, right? And third collision happened at 7 seconds. So between 4 seconds and 7 seconds it was moving freely. So it was moving freely for 3 seconds and 2 seconds. So 3 plus 2 divided by 2, so average time was 2.5 seconds. So it was moving freely for 2.5 seconds. So your average collision time is 2.5 seconds. Or you can define it as the average time between two successive collision. That is known as average collision time. Okay, very simple thing, very simple thing. And this line also you will be able to relate. If collision time is more, what does that mean? First collision happened at 2 seconds. Second collision happened at 10 seconds. That means it is able to move freely in a better manner. Electrons are moving in a better manner. If electrons are moving in a better manner, electrons are moving more freely, what does that mean? Conductivity will be high. Because I told you, for the conductivity, electron has to move. And if they are moving more freely, what does that mean? Conductivity will be high, right? So high collision time means higher conductivity. Okay, so very simple thing, very easily you are able to relate. No one will ask you the definition, but in the examination, if it is mentioned that average collision time, that means you should be able to understand what is the meaning of average collision time. You will see, okay, collision, electrons will be colliding. So between two successive collision, what is the average time? That is known as average collision time. And if the time is larger, that means between two successive collision, electron is moving more freely. If electron is moving more freely, that means conductivity will be high. Very simple thing. Let's go to the next term, that is effective mass. This is important. Here we are going to study effective mass on a very surface level only. Okay, in a very crude way, I will tell you the meaning of effective mass, but again it will come back when we study direct band gap semiconductor and indirect band gap semiconductor. So at that time it will again come back. As of now, you will just understand in a very easy manner and you would be already knowing the meaning of it. Let's just say I am having a mass of 75 kg and I am moving with the velocity of v. I am having a mass of m moving with the velocity of v. Then what will be my momentum? M into v, right? Or what would be my kinetic energy? That would be half mv square. So this formula, who gave this formula? Newton gave this formula. So these formulas I am able to apply because this mass is decent enough. 75 kg, very good mass. Here also 75 kg, very good mass. 60 kg, 1 kg, 2 kg, very good mass. Like this is classical mechanics. This is mechanics only, no? So this is classical mechanics. Here mass is decent enough. But when it comes to electrons, what is the mass of electron? 9.1 into 10 to the power minus 31 kg. And now if my electron is moving with the velocity of v, let's just say my electron is moving with the velocity of v. So what will be its momentum? Mass of electron into v? No. So classical mechanics doesn't work on these particles, these small particles. So that's why we have to introduce the concept of effective mass. So me star I will put. Now what is this effective mass? So let's just say an electron is moving freely and other electron is moving in a silicon crystal. One electron is moving freely, other electron is moving in this silicon crystal with respect to the applied electric field. Along with that, there could be some impurity as well. This impurity, if it is a donor impurity, then it will repel the electron. If it is a acceptor impurity, then it will attract the electron. So here the movement and here the movement, both movement will be different because here it is moving freely and in this silicon crystal there will be some hindrance as well, no? Like these atoms will be vibrating or there are impurities, the hindrance that I already explained, right? So this movement will be different and this movement will be different. Now I am saying that this electron is moving with the velocity of v and this electron is also moving with the velocity of v. So I will say momentum of this one will be mv and momentum of this one will also be mv. No, here the concept of effective mass will come into action. So when the electron is moving into a crystal, its effective mass is different than its actual mass. So this is the definition that has been written. Okay, so effective mass is the apparent mass of an electron or hole inside a crystal. So if you want to use the formula of classical mechanics, then in place of mass you need to put effective mass. Are you able to understand this point or not? Okay, if I want to use this formula of kinetic electric, if I want to use this formula of kinetic energy half mv square, then here in place of m I will put m star, in place of momentum I will put m star into v. Are you able to understand this point? So effective mass is the apparent mass of an electron inside a crystal. It is different from the actual mass because regularly arranged atom in the crystal changes the way electron and hole moves. They don't behave like a free particle in the empty space, so we assign a new effective mass that explains how easily they can accelerate under a force. Okay, so electron moving in a free space, electron moving inside a crystal, both are the different things. If both are moving with the velocity of v, still the momentum will be different. All good, all good, all fine. That's why we introduce the concept of effective mass. So effective mass of electron I will be showing by mass of electron, since it is effective, so me star, or sometimes I can show it by mass of electron is negatively charged particle, so mn. So sometimes I can use me, sometimes I can use mn. Okay, And what about mass of hole? Or sometimes I can use, since holes are positively charged particle, mp star. So mn mp star or me ms star, whatever I want to use, I can use. Okay. So you understood the meaning of effective mass. Like no one is going to ask you, these terms will be used again and again. That's why I'm telling you that you should be knowing the meaning of these terms. Again, effective mass will come into action, like all these formula we are going to use, momentum formula we are going to use, and then we are going to study the EK diagram. Okay. So there direct band gap semiconductor, indirect band gap semiconductor we are going to study. So again, this concept will come into action. Don't worry about that. Okay. What is mobility? Mobility, movement plus ability. Ability to move. So mobility tells how faster an electron or hole can move. Look, all these scenario I explained with respect to electron. So effective mass I explained with respect to electron, but same goes for holes as well. Here I talked about collision time of electron, but same goes for hole as well. No, hole is also a particle. Movement of hole means movement of electron only, but covalent bond electron. Movement of electron means movement of free electron. Movement of hole means movement of covalent bond electron. So when I am explaining everything with respect to electron, the same thing will go with respect to holes as well. Okay. So here I am explaining mobility. Mobility means movement plus ability. So ability to move. So mobility tells the ability of the movement of electrons or holes. Okay. So this is the definition I have been written. Mobility tells us how fast a charge carrier, it could be electron or a hole, can move when we apply an electric field. So whenever we apply an electric field, how fast that particular charge carrier will move. Now what is the relation between mobility, collision time and effective mass? So mobility is given by mobility of electron I am putting. Mobility of electron will be given by E, collision time of electron divided by effective mass of electron. And mobility of hole will be given by, what do you mean by E? In place of E, let's put Q. Q is the charge of electron. Here, Q is the charge of hole. For both of the cases, Q will be 1.6 into 10 to the power minus 19. Because what is the charge on the electron? 1.6 into 10 to the power minus 19 Coulomb. Mobility cannot be negative. So here you don't say that sir charge is negative, so I will put negative. No, nothing like that. So just remember Q2 by M. Q2 by M. Q2 by M. If you are writing for the hole, then Q2P by MP star. From now onwards, whenever you use mass, in place of using mass, you will use effective mass. Is that clear to you? And it makes sense as well, no? Because if tau is high, what does that mean? Collision time is high. Collision time is high means between two successive collision there is more time. If between two successive collision there is more time, what does that mean? Electron is moving more freely. That means movement of ability for the electron is high. What I am saying, if collision time is high, that means ability to move is high. What does that mean? Mobility is high. So tau is proportional to mu. What about effective mass? Let us say I am having a weight of 75 kg and some other guy is having a weight of 50 kg. So who will run faster? This 50 kg guy or 75 kg guy? 50 kg guy, right? Because it is having lesser mass. So if mass is lower, that means ability to move is faster. So lower mass, that means mobility more. So you can see that inverse relation is there. So you will remember the formula Q2 by M. Sir, how this formula came, forget about it. Just remember the formula Q2 by M. Okay. And I have just written that what all are what things. So Q is the charge of the carrier, tau is the collision time, and M is the effective mass of the carrier. What is the unit? Unit is centimeter square volt into second. Sir, do I need to mug it up? No. I will tell you another formula for the mobility. From that particular formula, you will be able to write down this unit. So as of now, for now you can remember it, but later on you will be able to write it down in a very easy manner. Unit is centimeter square upon volt into second. Okay. Later on I will tell you a formula. From that particular formula, you will be able to write down this unit very easily. So till this point, first we started with average collision time. Very simple thing. If average collision time is more, that means mobility is more. Effective mass. You already know what is the meaning of effective mass. That electron moving in a free space, that is different than the electron moving inside a crystal. So that is the effective mass. And if I want to use the classical mechanics formula, then I need to use effective mass. Mobility movement plus ability to move. So how fast your electrons can or holes can move when you apply a external electric field. Formula is Q2 by M. Okay. Now let's not go to the next slide. Here only I will discuss. The thing is, mobility of electron will be higher than the mobility of holes. What I am saying, mobility of the electron will be higher than the mobility of holes. Why is that so? Let's understand. So let's make our silicon crystal again. Okay, this bond is there, this bond is there, this bond is there, and this bond is there. Okay, these bonds are there. At 300 Kelvin, what will happen? One of the electron will go into the free space and it will create a vacancy of hole. Now if I apply the electric field, so tell me which electron will move more freely. This electron will move more freely, or this electron will move more freely. This electron is still in the covalent bond, and this electron has other competition as well. This is also in the competition, this is also in the competition, other competition are also there, no? Like if this electron needs to move, then it will have to jump. If this electron needs to move, it will have to jump from here to here. But this is a free electron, it can move very freely. Basically, one thing is between, this is the valence band and this is the conduction band. One electron from here has gone here and it has created a vacancy of hole. Now this hole is there and these electrons are there. Now let me know which electron will move more freely. This electron, it is alone, it is free, it can move very fastly. But this electron, for this electron in the competition, these electrons are also there, no? Are you able to understand this point? That means if this electron goes here, then this hole will become here. Basically, what I am saying is that this electron moves here. That means moment of hole will be there. For the hole to move, this covalent bond electron needs to move. If the covalent bond electron is moving, that means hole is moving. So for the hole to move, this covalent bond electron needs to move. And now you are saying that this covalent bond electron will be having tougher path than this free electron. That means this free electron is moving more freely. That means this free electron can move very fastly. And whenever I say free electron, that means electron only. And whenever I say covalent bond electron, that means I mean hole. So whose mobility will be higher? So mu n will be greater than mu p. So mobility of electrons will be higher than the mobility of holes. So whenever I say electrons, I mean free electron. Whenever I say hole, I mean vacancy of electron which was there in the covalent bond. So whenever I am saying that holes are moving, that means covalent bond electrons are moving. So covalent bond electrons will move with the hindrance, but free electrons will move more freely, right? So this is the theory that I have written. You will remember always that mobility of electrons will be higher than the mobility of holes. Say yes or no. So this is the theory that has been written. Holes are the missing electrons. A hole is not a practical particle. It is just the absence of electron in the valence band. To move a hole, neighboring electrons have to jump into the empty spot, right? But electrons are free movers, right? Electrons are free movers. Electron in the conduction band can move directly when pushed by an electric field. They don't need any other electrons to move out. Okay. So basically, here for the holes there is a lot of competition. For one hole there is a lot of competition of electrons. But for a free electron there is no competition. They can move freely. So mobility of electrons will be higher than the mobility of holes. Understood? Very simple thing. Let's go to our next point. What is this drift velocity? So drift velocity also we have already seen. This was our semiconductor. In semiconductor there was a free electron, there was a hole. So what we did? We applied a voltage. Because of the voltage there was an induced electric field. Now because of this electric field, this electron was moving and this hole was also moving. So this would be moving with the velocity. This will also move with the velocity. But they will move, but in between there will be collisions, right? Because this is the silicon crystal. So if this electron is moving, or if this hole is moving, then there will be silicon atoms, and because of that there will be collision. So velocity will not be constant. So let's just say sometimes velocity was 2 meters per second, then velocity became 3 meters per second, then velocity became 1.2 meters per second because of the collisions. So when you take the average, that average could be constant. So that is known as drift velocity. So it is the average of the velocity of your charge carriers when they move with respect to the applied external electric field. So this is the definition that has been written. So when you apply an external electric field to a conductor or semiconductor, electron starts moving in a specific direction. Same goes for hole as well. But electrons are constantly bouncing randomly because of the collision with the atoms. Their average speed in the direction of electric field is known as drift velocity. So it is the average speed, because you tell that sir electrons cannot move with the constant speed, that I know. But drift velocity, whenever I say drift velocity, although there is no word of electric field here, sorry, there is no word of average here. Whenever you write down drift velocity, in this word drift velocity, can you see anything called average? No. Average drift velocity we do not call it. We call it drift velocity only. But you should know that drift velocity is the average velocity of the electron or holes. Okay? Because velocity cannot be constant, but average velocity can be a constant number. Right? So what do you think? Drift velocity will be proportional to what? Applied field, right? So drift velocity will be proportional to the electric field. Electric field. So whenever the drift word would come into action, whenever the drift word come into action, drift means electric field. So till this point, if I ask you why the electron moves, when the electron moves, when you apply an electric field, and when you apply an electric field, drift velocity comes into action. And if electrons are moving, then current comes into action. So that current will be known as drift current. So whenever I say drift, in your mind electric field should come into action. Okay, drift means electric field. This should come into action. So your drift velocity Vd, drift velocity is proportional to applied electric field. When you remove this proportionality constant, so when you remove this proportionality sign, there would come into action a proportionality constant, that is mu, and that mu is known as mobility. Sir, mobility constant? We will see, don't worry. Okay, not in this lecture, but in the next lecture. But as of now, what you will say, Vd is equals to mu e. As of now, what you will say, sir, Vd is equals to mu e. So from here, mu will be Vd by e. Mu will be Vd by e. What is the unit of velocity? What is the unit of velocity? Meter per second. But here I told you distance will be centimeter, length will be centimeter, centimeter per second. And what is the electric field? Volt per centimeter, right? So centimeter per second into volt per centimeter. Centimeter goes upward. So this will be the unit of mobility. So Vd is equals to mu e. Till this point, only two formula is there. Mu is equals to Q2 by m. Vd is equals to mu e. But only formula is not important. The concept is also important. What is the meaning of drift velocity? Whenever I say drift, that means electric field. What is the meaning of mobility? Why the mobility of electrons is higher than the mobility of holes? What is the meaning of effective mass? Effective mass will again come into action. Average collision time also you know. So everything you know. All the formula is also clear. Vd is equals to mu e. Everything is crystal clear. Now you solve this question on your own. You should be able to solve. Electrons have an effective mass of m star equals to 0.2 m naught. Average collision time of 0.1 picosecond. Holes have an effective mass of 0.5 m naught. Average collision time of 0.15 picosecond. Applied electric field is 2 volt per centimeter. M naught is given, Q is given. Find the mobility. Mobility of electron and mobility of hole. So mobility of electron, what that will be? E2 by Mn star. 1.6 into 10 to the power minus 19. 2. Average collision time for electron is 0.1 into 10 to the power minus 12. By Mn star. Effective mass is 0.2. M naught, what is the value of M naught? 9.1 into 10 to the power minus 31. Yeah, one more thing you can see, what you can see, that here you have seen that mobility of electrons is greater than mobility of hole, right? So if collision time is same, then effective mass of electron will be lesser than the effective mass of hole, right? If electrons are moving faster, that means their effective mass should be lower. But it is general case. This is also general case, not always true. It may happen that in some material, you will not study those materials, but in some properties, in some material, at a particular condition, holes can also move faster than the electrons. Effective mass of holes can also be lesser than the effective mass of electrons. So here what I will write down, generally effective mass of holes will be greater, right, than the effective mass of electrons. Why is that so? Because here also I have written generally, not always true, generally. In your case it will always be true, okay? But in the examination, in some questions, let's just say mu p is given greater than mu n. So at that time you will not say, sir, this question is wrong. No. Till this date, in all the questions, mu n has been greater than mu p. But in the examination, if mu p greater than mu n is coming, then just apply the formula and solve it. Yeah, we were solving this question. So whenever you solve a question of EDC, always take care of the unit. Here you have put the unit of Coulomb, right? Coulomb. Picosecond it was, but you have converted into second. So Coulomb and then second, and downward you have put kg. So all the SI units are there. So your answer will come in the 1 second. Picosecond, yeah. So your answer should come in which unit? Here unit I have written centimeter square upon second into volt. Sorry, centimeter square upon second into volt. So answer will come in centimeter square upon second into volt. No, answer will be in meter square upon second into volt. Are you able to understand this point? Here I have put second, here I have put Coulomb, and here I have put kg. So all the SI units are there, no? So if all the SI units are there, then the final answer will be coming in meter square upon volt into second, no? Are you able to understand this point? Okay. In the options, if the answer is mentioned in centimeter, then you will convert it into the centimeter. So let's solve it first and then check the answer, and then I will tell you how you can convert. So always take care of the unit, that I am telling. Whenever you solve the questions of EDC, always take care of the unit. So let me pause the video and solve it, or I can solve it directly as well, because 10 to the power minus 19, 10 to the power minus 12, what that would be? 10 to the power minus 31. So this and this will get cancelled. This would become 1 by 2. 1 by 2, 0.8. So 0.8 divided by 9.1. Answer would be 0.8 divided by 9.1. Right? 0.8 divided by 9.1. So 0.08791. Why I have written so many digits? Because it may happen that in answer is given in centimeter square. But as of now, since everything is SI, your answer is coming meter square volt into second. But answer could be given in centimeter square. So here if you need centimeter square, what does that mean? What is the meaning of centimeter square? That means 10 to the power minus 4. This centi is 10 to the power minus 2. If I am doing square, that means 10 to the power minus 4. So if I need to put centi here, that means I am multiplying with 10 to the power minus 4. That means I have to divide by 10 to the power minus 4 as well. Are you able to understand this point? Just the conversion I am telling you. Let me add another page. Nothing but the conversion I am telling you. 1 second, guys. Yeah, so this was the answer. Now I am converting, right? So meter square to centimeter square I am going. That means here I have multiplied with 10 to the power minus 4. Because centi is 10 to the power minus 2. Since there is square, so 10 to the power minus 4. I hope this much is clear to you. So if I am putting centi here, that means I have already multiplied with 10 to the power minus 4. So I will have to divide with the 10 to the power minus 4 as well. And now this 10 to the power minus 4 will go upward. So what will happen? It will become multiply with 10 to the power 4. So what will happen? 1, 2, 3, 4. So 879.12. What will be the answer? 879.12 centimeter square volt into second. Is that clear to you or not? You might be a third semester guy or fourth semester guy, that's why I'm taking time. But if you are someone who has been in third year, then at least this much should be clear to you, right? How to convert into different units. Okay, so this is the mobility of electron that we are getting. Similarly, you can calculate the mobility of holes as well. So 1.6 into 10 to the power minus 19. What is the collision time? 0.15 picosecond divided by 0.5 m naught. So 5 into 9.1 into 10 to the power minus 31. So again here as well. So 1.6 into 0.15, 1.6 into 0.15 divided by 0.5 divided by 9.1. So 0.0527 05274 meter square volt second. And if I need to convert into centimeter, that means 10 to the power 4 I will have to multiply. So 527.47 centimeter square volt into second. So this is your mu p I am getting. What they are expecting next? Drift velocity of electron and holes. So third, drift velocity of electron. That would be mu p into E. What is, sorry, drift velocity of electron. So let's write down VDN, drift velocity of electron, VDN. So mu n into E. So what is the answer you are getting? 879.12. 879.12. So this is in the centimeter square upon volt into second, and E value is also given in the centimeter, 2 volt per centimeter, right, into 2. So what do you think, what will be the answer? What is the unit of drift velocity? Centimeter, meter per second, but everything is there in the centimeter. Everything is fine, volt is fine, second is fine, volt is fine, here centimeter, centimeter. So answer will be meter per second, but no, centimeter per second, because I am using centimeter here. So 879.12 into 2. 879.12 into 2. So 1758.24 centimeter per second. That would be mu p into E. 527.47, and what is applied electric field? That is 2. So 520 1054.94 centimeter per second. There you go. These are the answers. Okay, let's solve. Okay, we will solve more questions, but as of now, let's talk about the conductivity. So you already know the meaning of conductivity. Conductivity is the ability of the current to flow, ability of a material that it can allow the flow of current. So conductivity tells us how easily a material allows electric current to flow. But for the conductivity, there is a formula. So that formula you need to remember. So that formula of conductivity is, here I am writing down N. N doesn't mean electrons here. Okay, N is the charge carrier per unit volume, Q mu, N Q mu. Just tell me one thing, if charge carriers are more, that means conductivity will be more. If mobility is more, mobility means ability to move. So if electrons are moving fastly, not only electrons, any charge carrier, it could be electron, it could be hole. So when I am writing down N here, that means I am meaning it could be any charge carrier. Okay, so N is the N is the charge carrier, Q is the total charge, and mu is the mobility. So if mobility is more and number of charge carriers are more, what does that mean? Conductivity will be more. So always there is a proportional relation, right? So sigma is proportional to n, sigma is proportional to mu, and sigma is proportional, like charge on the charge carrier. Every charge carrier will have some charge. So n q mu. Just remember this formula. You have to remember the formula. First formula, mu was Ito by m, Qto by m, you can say Ito by m. Second, Vd is equals to mu e. Third is sigma equals to n q mu. Derivation and all we are not seeing, but we have to memorize the formula because questions are asked on these particular formula. Very, very straightforward, very simple questions will be asked. Very simple question. So n q mu, just remember n q mu. Like in class 12th as well, you might have studied this formula. What is n, what is q, what is mu? So n is the number of charge carrier per unit volume and mu is the mobility of a particle. Right? Now what is resistivity? This resistivity word have you heard? Resistivity is just the reciprocal of conductivity. Resistivity is just the reciprocal of conductivity. So that would be 1 upon n q mu, where n is the charge carrier. It could be electron or hole. It could be electron or hole. If I am saying or, that means I will use the plus sign. And mobility, it could be electron or hole, anything, right? So n q mu you need to remember. And resistivity is resistivity is just the reciprocal of the conductivity. Now there is something called resistance. You might have heard this word, resistance. What is the formula of resistance? R is equals to rho L by A. Let's just say there is a material. Let's just say there is this material. Okay, I am making it in 3D. And now across this material, what you are doing, you are connecting a battery like this. Okay, you have connected a battery like this. So now the current will flow. The current will flow. The current will be passing through this particular area. No? So from whichever the area, let's just say this was the material. This was the material. And if I have applied battery, let's just say current is passing from this particular area. Or better example would be this book. This is the material. And I have applied battery here. So current is passing through this particular area. So this is known as cross section area. Okay. So cross section area is this. So this is your A. And what is the L? L is the length. So the length at which the current is passing. So current will be passing the complete length L. Cross section area will be this. This will be your cross section area. And rho is the resistivity. So resistance of this particular material will be given by rho L by A. Rho into L by A. Rho into L by A. This rho is a material constant. Like this rho will depend on the material. In the material, the number of charge carriers will be there. The mobility of charge carriers will also be there. So all these things is depending on the material. Like how many charge carriers are there in this material. So rho is the material constant. It will depend on the material. What is rho? Rho is just the inverse of conductivity. What is the formula of conductivity? N q mu. What is the formula of mu? Ito by m. Other formula, Vd is equals to mu e. That's it. 3 formulas till now we have remembered. Right? So you understood the meaning of cross section area as well. Next we need to study about drift current density. So what do you mean by current density? So current density is simply given by I by E. Current per unit cross section area. So let's just say this is a semiconductor material or any material which can conduct the current. If I have connected a battery of V naught having a length of L, what will happen? The current will flow. The current will be passing through this particular cross section, and this cross section I am calling as E. So this current I is passing this particular cross section with the length L. So current density which is given by J. So this is your current density. Current density. So current density which is given by J, that is I by A. So current per unit area. Current density J is the current per unit cross section area. And this theory is written that whenever an electric field is applied across a material, charge carriers, electron or holes, will start moving in a preferred direction. This the current caused by this directional motion of carriers is called as drift current. Drift current is coming because of the electric field. So this is the important part here. Again I will use different color of pen. The drift current is coming because of the electric field that you have applied. Now let's just say this semiconductor material or this any kind of material was having some electron and it was having the hole as well. What is the direction of applied electric field? Direction of applied electric field is this. Why is this? Because this V potential will reach here, this negative potential will reach here. Direction of electric field will always be from positive to negative. Electrons will move in the opposite direction to the electric field. That's why the current will be this, and holes will be moving in the direction to the electric field. That's why the current will be this. So this is the current because of the electrons, this is the current because of the holes. So what will be the total current? In plus Ip. So always current will be added up. It will never happen that until some other electric field comes, it will never happen that these current will be in opposite direction. In some cases, two currents can be in the opposite direction, but because of the electrons and because of the holes, the current will always be in the same direction, because you know that holes are nothing but the movement of electron only. So if electrons are moving from right to left, that's why the holes are moving from left to right. So this will be the total current In plus Ip. Okay, so just a simple thing that we have already studied, that only I explained here. So current density is J equals to I by A. Now you have studied Ohm's law, right? In Ohm's law, what was the formula? J equals to sigma E. Do you remember it? J equals to sigma E. So from here, two kind of formula you will remember. J is equals to sigma E, and I will be, J is I by A, so sigma will be, sorry, J is I by A, so I will be sigma E into E. So this is your drift current. This is your drift current. And from now onwards, I will write down J drift, I drift, J drift, I drift. Okay. Dr means drift. Dr means drift. So this thing only I am repeating. Drift current density and drift current for semiconductors. So same thing I am repeating. Again the same thing I will write down. There is electron, there are holes. Electric field is there in this direction. There was no need of this slide actually. Electric field is there in this direction. Electrons will move here. Electrons will move here. Holes will move here. So your drift current density will be given by J drift because of the electrons. I should write J drift because of the electrons plus J drift because of the holes. Okay. Now just tell me one thing. What will be this J drift? Sigma into E, right? So here I am writing sigma n because I will write down the conductivity because of the electrons, and then I will write down sigma P, and E electric field I will show by this sign. Electric field here also I have shown by this sign, because by this capital E we will be showing energy. That's why I will show the electric field by this sign. Sigma Ne plus sigma Pe. What do you mean by sigma n, sigma p? Sigma n is the conductivity of the electrons. So that would be n q mu n. What will be sigma p? That would be p q mu p into E. What is this n? What is this p? So let's write down. What is the n? Number of electrons per unit volume. Number of electrons per unit volume. What is the formula of sigma? Sigma formula is n q mu, right? What was n here? N was the charge carriers, number of charge carriers per unit volume. Now there are two kind of charge carrier. One is electron, one is hole, and because of both of them, the current is actually being added. Because of both of them, the current is being actually added. And I know the formula of J here. I know the formula of current density, that is sigma E. But here I am considering only the electrons. Here I am considering only the holes. So I am writing down the conductivity of the electrons. That means now my charge carriers will only be electron. Right? Q is the charge on the electrons and Q is the charge on the hole. So that will be same only, right? Charge on the electron is also 1.6 into 10 to the power minus 19, and charge on holes are also 1.6 into 10 to the power minus 19. Now don't say that, sir, I will put negative here. Current are being added, no, current are being added, so don't put negative here, right? So number of electrons number of electrons per centimeter cube, and what are P? Number of holes per centimeter cube. And what is mu n? Electron mobility. And what is mu p? Hole mobility. Right? Q is the charge, or Q is simply the charge which is 1.6 into 10 to the power minus 19 coulomb. E is the applied electric field. E is the, let's just say this was your V naught, okay, and the length was L. Length of this semiconductor was L, and applied potential was V naught. So E is the external electric field, which will be equals to what? dV by dx minus dV by dx, that would be V naught by L, right? So N was number of electrons per centimeter cube, P is number of holes per centimeter cube, mu n is the mobility, electron mobility, mu p is the hole mobility, and both of the both of the currents are added. Both of the currents are there in the same direction, that's why they will be added. So NQ mu, this formula is very important here. So here no new formula you are learning, only one formula is there, J equals to sigma E. Sigma is NQ mu. There are two kind of charge carriers, one charge carrier is electron, one charge carrier is hole. So because of them I can write down the current. So this is my complete drift current. Sorry, drift current density. What is this? Drift current density. This is your drift current density. Now if I want drift current, then what will be the formula? If I want drift current, so the formula will be J drift into the area, J drift multiply with the cross section area, there you go. This will be your drift current, and this is your drift current density. So what will be this? This will be your drift current. Don't worry, these formula will come again and again. So don't feel like that, sir, how you will be able to remember. You will be able to remember, don't worry about that. Very simple thing, where we started with, the first formula came here, Q2 by M. Very rarely it will be used, very rarely. Okay. Then VD is equals to mu E, it will be used. It will be used in a good amount, right? And then conductivity formula came. Conductivity was NQ mu, where N is the charge carrier, number of charge carriers per unit volume. Okay. Or here volume would be in centimeter only, so centimeter cube I have written. Mu is the mobility, Q is the charge. Resistivity is just the reciprocal of the conductivity. Resistance is R equals to rho L by A. Then current density is simply J is equals to sigma E, that is equals to I by A. So I will be equals to sigma E into A. What is sigma? NQ mu. So here N is the charge carrier, which could be electron, which could be hole as well, right? And because of both of the charge carriers, the current is being added. That's why I added the current because of the electrons, the current because of the holes. So these are the formula. Let's write down the current for different kind of semiconductor, for intrinsic semiconductor, for N-type semiconductor, and for P-type semiconductor. Okay. So let's write down the current expression, but I need to drink some water because of the cough that I am having. So I need to take a break and then I will come back. You try writing it down, because for intrinsic semiconductor, what do you know? Number of electrons per unit volume will be equals to number of holes per unit volume will be equals to intrinsic carrier concentration, right? So you write down the formula, which formula you get. Yeah, welcome back. So let's write down the drift current density and drift current for intrinsic semiconductor. Okay, so in intrinsic semiconductor, what was the scenario? This was your intrinsic semiconductor. Here electrons are also there, holes were also there. If you apply an electric field, both will be moving in the opposite direction, and the current will be, for both of them, the current will be in the same direction, and so total current will be added, right? And in the intrinsic semiconductor, number of electrons were equal to the number of holes, and that was known as intrinsic carrier concentration. So number of electrons were equal to the number of holes, that would be equal to intrinsic carrier concentration, right? So what will be the drift current density? So drift current because of the electrons, drift current because of the holes. Drift current density because of the electrons, drift current density because of the holes. So drift current density is sigma into E. What is sigma? N Q mu. So N Q mu N into E. This is because of the electron, and P Q mu P into E. This is because of the holes. And since N equals to P equals to Ni, so what you can do? Niq mu N into E plus Niq mu P into E. So what you can see here? What can come common? Ni into Q into E, that can come common. So Ni into Q mu N plus mu P into E. Basically only difference is mu N and mu P. So this is your drift current density, and if I need to find the current, I will multiply with the area. So this is the drift current density for intrinsic semiconductor. Along with that, you know one thing, that your drift current density would be equal to the sigma, that means conductivity into electric field. So applied electric field is E, so this will represent the conductivity of intrinsic semiconductor, right? So this particular term, J equals to sigma E, right? J is equals to sigma E. So this particular term will represent the conductivity of intrinsic semiconductor. So your sigma I, conductivity of intrinsic semiconductor, would be given as, how will you remember? Sigma is equals to N Q mu. So Ni, here charge carriers are N and P. Charge carriers are electrons and holes. So Ni Q mu N plus mu P. Since both of the currents are in the same direction, so both will be added. So this will be the conductivity of intrinsic semiconductor. Okay. What about N-type semiconductor? So normal formula for everyone. This is the normal formula. In N-type semiconductor, what would be there? Majority charge carriers will be electrons. For N-type semiconductor, majority charge carriers will be electrons. But holes will also be there, no? So both particles are there. Holes are in the minority. Holes are in the minority, but surely they are there. Although they are in the minority, but surely they are there, right? NQ mu N into E, PQ mu P into E. And since number of electrons are much larger than the number of holes, so J drift will also be approximately equals to NQ mu N into E. Although this is the full formula, this is the approximated formula. Okay. For P-type semiconductor, full formula will be the same only, NQ mu N into E. Let's make the P-type semiconductor. This would be your P-type semiconductor, where everywhere holes will be there, but minority electron will also be there. Plus PQ mu P into E, right? But you know that P is much greater than N, so your J drift would be PQ. Like very simple thing. Just now formula has come into action, so don't feel like that, sir, this is difficult. Nothing is difficult. J equals to sigma is equals to NQ mu. If you just remember that, your job is done. Let's see the formula that has been asked in GATE 2025 examination. So very simple question have been asked in GATE 2025 examination. What they are saying, intrinsic carrier concentration they have given, that means Ni value they have given, that is 2.5 into 10 to the power 16 meter cube inverse. Electron and hole mobility they have mentioned 0.15 meter square volt into second. Hole mobility they have mentioned 0.05 meter square volt into second. Intrinsic resistivity they have asked. What they have asked? Resistivity. I forgot to tell the unit of conductivity. What is the unit? It is Siemens per meter. Okay. This is the unit. And here what will be the unit? RA by L. So what is the unit of R? Ohm. What is the unit of meter square upon meter? So ohm into meter, right? Ohm into meter. So unit will be ohm into meter. This will be the unit. So what is this Siemens? This is simply, what will be the unit here? 1 upon ohm into meter, because conductivity is just the reciprocal of resistivity. So 1 upon ohm into meter. Meter you are already writing downwards. So 1 upon ohm is Maho. Maho, or you can call it Siemens. Okay. So Siemens and Maho both are the same thing. So Siemens per meter you can call it, or ohm into meter is the unit of resistivity. Very simple thing. Let's go to our question. This was our question. What you need to find? You need to find the resistivity. What is the resistivity? Resistivity is simply the reciprocal of the conductivity. So when you think of conductivity, you will think that okay, both of the currents will be added. And what is the formula of the conductivity? Nq mu. Nq mu. What is the charge carrier here? For in both of the cases, n equals to p equals to ni. So I will remember that n equals to p equals to ni. So nq mu, ni will come common. Q will also come common. Nq mu, mu will not come common. So that will be mu n plus mu p. There you go. This is the formula, and I will be able to write down the final answer. Now, when I will be solving the problem, I will see the options. In the options, is there any importance of 10 to the power 16 or point or anything? What I mean to say is that, let's just say I solved this particular question and my answer came 12.5. Will I be able to tick on option B? Surely. Like without even taking care of 0.05, I just solved it. Like here I need to take care because 0.15 and 0.05 I need to add. So it would be 0.2. So 0.2 multiply with Q, that would be 1.6 into 10 to the power minus 19, multiply with 2.5, and then I need to take the reciprocal. If I don't care about this point sign, like in place of 2.5 I am writing 25, in place of 1.6 I am writing 16. If I don't care about that and I get my answer 125, still very confidently I can click on option B. But what if in the options 1.25, 12.5, 125 was mentioned? So at that time I need to take care of the calculation. In the examination, if I need to solve the question faster, I would know that here my point would not matter because all the options are different. So I can solve it faster, but here I will solve in a correct manner only. So what is the correct manner? Correct manner is 1 upon Ni value is 2.6 into 10 to the power 16. Sorry, 2.5 into 10 to the power 16. Q value is 1.6 into 10 to the power minus 19, and mu n plus mu p will be 0.2. When you solve it, 1.25 will come out. This will be the answer. Okay, I can see. Let's check 1 by 8. Look, 2.5 into 2, that would be 5. 16 into 5 would be 80. 1 by 8, 10 by 8, what that would be? 1.25. Answer would come out to be 1.25. Here you can see 10 to the power minus 3, and this would be 10 to the power minus 4. 10 to the power 16 and 10 to the power minus 19, that would be 10 to the power minus 3. 10 to the power minus 3, 10 to the power minus 4, 10 to the power minus 5, and 10 to the power minus 6. So if it goes upward, so 10 to the power 6 divided by 25 into 16 into 2. So 25 into 16 into 2. So 25 into 6, 25 into 2 will be 50, 50 into 16. So that would be 10 to the power 6 divided by 800. So it will not be 10 to the power 6, some error we are doing. Yeah, answer is required in kilo ohm into meter. Answer is required in kilo ohm into meter. Okay, so for kilo I need to keep aside 10 to the power 3, and 10 to the power 3 divided by 800. So what will be the answer? 1000 divided by 800. So answer would be 1.25, and this 10 to the power 3 will be kilo ohm into meter, because everything is in the SI unit. Here everything we are putting in SI unit. So what will be my answer? My answer will come out in ohm into meter, right? Here everything I am putting in SI unit. So answer will come out into ohm into meter, not kilo ohm, but you need the answer in kilo ohm. So that's why 10 to the power 3 will also come. So that 10 to the power 3 will go into kilo. So kilo ohm into meter. So answer will be 1.25. Next, another question I have framed, that applied electric field is 2 volt per centimeter. Cross section area is 1 centimeter square. You need to find the drift current. Drift current you need to find. So what will be the drift current? That would be into area. And what will be this? Sigma into E into A. What is the value of sigma? Sigma is 1 by rho. Here I should write down in this manner. So J drift, what is current density? Sigma into E, and we are talking about intrinsic semiconductor, so sigma I into A into E into A. What is sigma I? Sigma I is simply 1 by rho I. What is E? 2 volt per centimeter. But let's put everything in SI unit. Okay, what we are doing, let's put everything in SI unit. So 2 volt per centimeter could be written as 200 volt per meter, because centi is 10 to the power minus 2. If it goes upward, it becomes 10 to the power plus 2. So 200 volt per meter, and this could be written as 10 to the power minus 4 meter square, because centi is 10 to the power minus 2. So 200 into area 10 to the power minus 4 divided by rho I value, because sigma is equals to 1 by rho I. So E into A 1 by rho I. What is the value of rho I? Rho I value we are getting 1.25 into 10 to the power 3. So what is the answer you will be getting? 200 divided by 1.25. 200 divided by 1.25 into 10 to the power minus 7. So 20 divided by 1.25. I should have been able to do it without the calculator, but as of now I just want to depend on calculator only. So 20 divided by 1.25, 16. 20 divided by 1.25 is 16, right? And so 16 micro ampere, that is the current you are getting. So these are the answer. Okay, very simple thing. This was 10 to the power minus 4. I gave 1 10 to the power minus 1 to this one, so this became 20. 20 divided by 1.25, 10 to the power minus 3, and this also goes upward, so 10 to the power minus 6. So 16 microampere. Very simple equation, very straightforward. Let's solve this one. Electric field of 0.01 volt per meter is applied along a length of copper wire. This time they have given copper wire having a circular cross section of diameter 1 millimeter. So there is a copper wire. This is a copper wire. So semiconductor they did not give this time. This time they gave the wire, and this is having a circular cross section. Circular cross section. So can you find out the cross section area? Yes. The diameter is 1 millimeter. So what will be the radius? 1 by 2 millimeter. And do we need the area? Let's see that. Conductivity is given. I need to find the current. Yes. So J is equals to sigma E. I will be equals to sigma E into A. I have the value of conductivity 5.8 into 10 to the power 7. This is in SI, Siemens per meter, although there is no use of the unit. Electric field 0.01, right? And now the area. What will be the area? What will be this cross section area? That would be pi r square. So pi into r is 1 by 2, 10 to the power minus 6, because r value is 1 by 2 into 10 to the power minus 3, right? So 10 to the power minus 3 divided by 2 meter. So it would be r square. It is r square. So your radius is 1 by 2 into 10 to the power minus 3. So it would be 1 by 4 into 10 to the power minus 6 meter square. So pi by 4 into 10 to the power minus 6. So what is the answer you are getting? This is actually 10 to the power minus 2 only. So let's write down in it as 10 to the power minus 2. So 10 to the power minus 2, 10 to the power minus 8, this would become 10 to the power minus 1. So 5.8 into pi, 5.8 into pi divided by 4. So 4.5 you are getting, 4.55 we are getting, roughly around 4.6 we are getting, but 10 to the power 7, 10 to the power minus 1. And everything is in SI, so answer will be in amperes. From here you can see that answer will be 0.46 ampere. So very comfortably, very easily, these kind of questions are just free marks, right? So very easily you would be able to solve. Let's go to the next concept. So next we are going to understand mass action law. Very important concept, very important. So listen to me very carefully. Just keep your full concentration here. So now let's just say I am having an intrinsic semiconductor. In this intrinsic semiconductor, I know that number of electrons will be equals to number of holes, and that will be equals to Ni, right? So here I am telling that number of electrons is equals to number of holes, and that is equals to Ni, and I am saying that these are 10. So 10 electrons are there, 10 holes are there, and Ni value will also be 10. Now what I did the doping of a donor atom. I did the doping of a donor atom. So when I did the doping of donor atom, what will happen? Donor atom will give me electrons, right? Donor atom will give me electrons. So this value will go high. Let's just say because of the doping of donor atom, the number of electrons became 50. What I am saying, previously the number of electrons and the number of holes were same, 10, 10. What is the multiplication of both of them? 10 into 10, that is 100. This is the previous scene when it was intrinsic. Now what I am doing, I am making it extrinsic. So what I did the doping. I did the doping in a manner that at the equilibrium I am getting 50 electrons. I am getting 50 electrons. So number of holes will make sure that I will be that number such that this multiplication remains constant. What I mean to say is that whatever the previous number of electrons into number of holes were there, that will always remain constant at the equilibrium. At the equilibrium, somehow if I did some doping, whatever the process that I did, because of that process, if number of electrons have become 50, the number of holes will be 2 only. Like, sir, how it will happen? Already 10 holes were there. So what happened to those 10 holes? So what really happened was, let's just say there was electrons. Because of the thermal temperature, what you created? Holes you created. Oh, sorry. What I am doing? Yeah, because of the thermal temperature, these electrons are created here and these holes are created here, right? And then you did doping. Because of the doping, what really happened? Because of the doping, there was a donor energy level, and because of the temperature, you got electrons here, right? This was the process. And let's just say another hole I will make here because of the temperature. So these holes you are making because of the temperature. In the intrinsic carrier, in the intrinsic semiconductor, 3 holes were there and 3 electrons were there. And when you did the doping, these more electrons came into action. When you did the doping. Now you know that since electrons have been more, so number of holes should be less because multiplication should be constant. Previously it was 3. This was 3. Number of electrons were 3. Number of holes were 3. So 3 into 3. So multiplication should be 9 only. Now you are saying that for the 9 it would be tough to explain. Let's take 4. So previously number of electrons were 4. Number of holes were 4. Now what really happened? Number of electrons got increased. So number of electrons got increased. 8. So number of holes will be 2 only. So what really happened is that from here the electron will fall back. If the electron is falling back, what will happen? This electron and hole will recombine. What will happen is that from here electron will fall back. First what really happened? This was the generation. This is known as generation and this is known as recombination. So this generation and recombination process will go on, and it will go on till the point that this multiplication and this multiplication becomes similar. So at the thermal equilibrium, this multiplication and this multiplication will be similar. Is that okay for you or not? How the multiplication will become similar? Because whatever the generation was there, one electron went here. Because of that, electron and hole pair were generated. One electron and one hole pair were generated. But what may happen is that to make sure that this multiplication remains constant, one electron can recombine with the hole. The electron can fall back and it can recombine with the hole. So this vacancy will be gone and here free electron will also be gone. Are you able to understand this point? So number of holes has been reduced to 2 now. Previously number of holes were 3, but now it has reduced to 2. So always at thermal equilibrium. What is the thermal equilibrium? As of now you will understand thermal equilibrium is the constant temperature state. At a particular temperature, now the number of electrons and number of holes have been constant. This is known as thermal equilibrium. We will understand thermal equilibrium in detail, but as of now what you will understand that at a particular constant temperature, number of electrons and number of holes have been constant. So that is known as thermal equilibrium. So at the thermal equilibrium, the number of electrons multiplied with the number of holes will always be constant. So this is the theory that has been written and we will use it in the problems. You will be able to understand, don't worry. and this law is valid for any kind of semiconductor. Okay, so this is the complete theory that has been written. In a semiconductor at thermal equilibrium, the product of number of electrons and the product of hole concentration to the product of electron concentration will be constant. Okay, so when it was intrinsic, n was equals to p is equals to ni. So if I multiply n with p, what I will get? N is equals to ni, p is equals to ni. So what I will get? N into p is equals to ni square. So this is known as mass action law. So always electron concentration multiply with the hole concentration will be a constant number, that is known as ni square. Let's understand by a practical example. Let's just say in my silicon, my ni value was like what is this? Ni value when it was intrinsic, when everywhere silicon was there, at that time number of electron and hole pairs were 10 to the power 10. So number of electrons were 10 and number of holes were 10. So what was their multiplication? N into p is equals to ni square, that was 10 to the power 20. Now what I did the doping. I did the doping of donor atom, and because of that doping, now my number of electrons became 10 to the power 50. So what will be my number of holes? The number of holes will be 10 to the power 5, because 10 to the power 15 multiplied with 10 to the power 5 will be 10 to the power 20. So always we will make sure that number of electrons multiplied with the number of holes will be equal to ni square. Is that okay for you? Okay, so we will see a lot of questions, it will be clear to you, don't worry. So this law is particularly useful. Yeah, so this line is also very important. When I will be using this law, so I will be using this law to find out the minority charge carrier concentration. Let's just say in my semiconductor, electrons are the majority charge carrier. In my semiconductor, I am having n-type semiconductor. Let's just say I am having n-type semiconductor. So electrons are the majority charge carrier concentration. So for finding number of electrons, I will use some different formula that we will study. Don't worry about that. But for finding number of holes, I will always use this mass action law. Basically, by somehow I will find out the number of electrons. In my n-type semiconductor, first I will find out number of electrons. Okay, and then I will use this n into p is equals to ni square. Number of electrons I am already having, this value I will already know, I can find out the minority charge carriers. So this law is particularly useful to find out the minority carrier concentration if majority carrier concentration is already known. Okay, and is the electron concentration per centimeter cube, per centimeter cube, and this is also per centimeter cube. And this law is valid for both intrinsic and extrinsic semiconductor. Now there is another equation that is known as charge neutrality equation. So charge will always be neutral. Let's just say I am having some semiconductor. Okay, in this semiconductor I am doping donor atom as well and I am doping acceptor atom as well. Charge neutrality equation. Okay, so if I am doping donor atom, what this donor atom will give you? Positive charge and a electron. And what this acceptor atom will give you? Negative charge and a hole. So here what all are the positive charge? The positive charge are Nd plus and number of holes. And what all are the negative charge? Negative charge are Na minus plus number of electrons. Number of electrons I will represent n, and every of them is having the same charge q, which is 1.6 into 10 to the power minus 19. Let us say this is the ion I am having. What is the charge of this ion? 1.6 into 10 to the power minus 19 only, no? This ion 1.6 into 10 to the power minus 19. This is negatively charged, this is positively charged. 1.6 into 10 to the power minus 19. So in a semiconductor where I am doping donor atom as well and acceptor atom as well, so total charge will be equal, total positive charge will be equal to the total negative charge. Why is that so? Because all the materials are electrically neutral. This thing we have already seen, all the materials are always electrically neutral. So when I am doping Nd atoms, what is really happening with Nd? They are having 5 electrons. So since they are releasing this electron, they are becoming positively charged. And when I am doping Na, what they are having? They are having a hole. So what they will do? They will take a electron, and since they are taking the electron, they will be negatively charged. So this is the negative charge, and electrons are also negatively charged. So electrons are also negatively charged. So this Q and Q will get cancelled out. So Nd plus P is equals to Na minus plus N. So usually I will ignore this plus sign. Usually I will ignore this negative sign as well. So total positive charge is equals to total negative charge. That's it. So this is known as charge neutrality equation. So two things are there in the semiconductor. First one is at thermal equilibrium, number of electrons multiplied with the number of holes will always be constant. That is equals to Ni square. And in a semiconductor, the semiconductor will be electrically neutral. So total positive charge will be equals to total negative charge. Positive charge will be coming because of the hole and donor atom, because of the hole and the donor atom, and negative charge will be coming because of the electrons and acceptor atom. Okay, well and good. So this is something that has been written. A semiconductor is electrically neutral, so total positive charge is always equals to the negative charge. This includes electron holes and ionized dopant. Okay, ionized dopants. P plus Nd P plus Nd plus is equals to N plus Na minus. So N is the electron concentration, P is the hole concentration, Nd plus is the ionized donor concentration, and Na minus is the ionized acceptor concentration. All good. Now let's see where we are going to use it. So what we are going to do, now we are going to find the number of electrons, or basically we are going to find electron and hole concentration per unit volume in our semiconductors. In intrinsic semiconductor, you already know that number of electrons is equals to number of holes is equals to intrinsic carrier concentration, is equals to intrinsic carrier concentration. But what about N-type semiconductor? So in N-type semiconductor, who are the majority charge carriers? Electrons. And who are the minority charge carriers? Holes. Right? And in N-type semiconductor, you do the doping of donor atom, right? It would be non-zero, but acceptor atom would be 0. So there are two kind of law. First law is mass action law. The mass action law will say that at equilibrium, the number of electrons I am representing by N. What is this? Concentration of electron. And this is concentration of hole. At any point at a thermal equilibrium, the concentration of electron multiplied with the concentration of hole will be equals to Ni square. What is this Ni square? When it was intrinsic semiconductor, from intrinsic only you are making it N-type, no? So when it was intrinsic semiconductor, at that time, what was the number of electrons, what was the number of holes? That was equals to N equals to P equals to Ni. So number of electrons when it was intrinsic, that was Ni. Number of holes when it was intrinsic, that was Ni. But now you have done the doping. So now things will change. Number of electrons and number of holes will change. So those changed number of electrons are N, those changed number of holes are P. Another thing also we know, what is that? Charge neutrality equation. What is the charge neutrality equation? Positive charge is equals to negative charge. Now in this N-type semiconductor, you know that what is the scenario? This is the scenario, right? But holes are also there, right? So here there are donor atoms. Donor atoms are positively charged. Along with that, holes are also positively charged. That would be equal to negative charge. Negative charge is only because of the electron. There is no acceptor atom. This is the equation 1 I am having. This is the equation 2 I am having. Now from here, what I will find out? First I will find out the value of N. What I will find out? I will find out the value of N. Okay, so what I would do? This N remains as it is. In place of P, I will put N minus Nd. This is the equation 3. So I will use equation 1 and 3. Using equation 1 and 3. Equation 1 and 3. What I am getting? N into P is equals to Ni square. So what I am finding? I am finding the value of N. So P is replaced with N minus Nd. n minus nd, and that would be equals to ni square, right? So what you are getting, n square n into nd minus ni square is equals to 0. So this is the quadratic equation, minus b plus minus under root b square minus 4ac divided by 2a. So better I can write it down in this manner, nd by 2 plus minus under root, look, I have written under root 4 by 2. What will be the value? Under root 4 is 2, 2 by 2 will be 1. So can I write down in this manner, under root 4 by 4? Basically this 2 goes in the under root. If this 2 is going in the under root, how it will go? If 2 is going in the under root, so how it will go? As under root 4, no? So this has to be squared, right? So this 2 is going in the under root. So nd by 2 square, and here it would become ni square. Because 2 is going in the under root, so it would go as 4. So basically it is actually going as 4. When 2 is going in the under root, it is going as a 4. So nd square plus 4 ni square divided by 4. So it can be written as nd square by 4 plus ni square. So nd square by 4 can be written as nd by 2 whole square plus ni square. So this is the formula that I have written. nd by 2 whole square plus ni square. Now what do you think? Can I take the negative sign? If I take the negative sign, then what will happen? nd by 2 minus nd by 2 whole square plus ni square. This will be a positive value. This will also be a positive value. And these two values will be added. So this particular value will be surely greater than nd by 2. Only I am talking about this particular value. This particular value will always be greater than nd by 2, because nd by 2 square plus ni square. Let's just say nd by 2 was 4. So 4 square plus something you are adding. Let's just say it was 1 only. So what you are getting? 16 plus 1 under root 17. And here what you are getting? nd by 2 was 4 only. So 4 minus under root 17. What is the answer you are getting? Under root 16 is 4. So under root 17 will be somewhat greater than 4. So what will be the answer? Negative value, no? Which is not possible. Concentration cannot be negative. So that's why you cannot take a negative sign. So which sign you will take? Positive sign. Basically, if you take the negative sign, then concentration will be negative. So that's why I will take positive sign. So what is the answer you are getting? Plus ni square. This is the number of electrons that you are getting. Now someone would be saying that, sir, I will try to find out the number of holes also in the same manner. What I would do is that I will generate another equation. What I would do is that I will use equation 1 and 2. What I would do, sir, I would do using equation 1 and 2. So now in place of n I am going to put nd plus p. So in place of n, what I am going to put nd plus p into p is equals to ni square. Someone will be saying that, sir, I will be doing this process. Okay. So p square plus nd into p is equals to ni square, or minus ni square is equals to 0. So what will be the value of p? Minus b plus minus under root b square minus 4ac. So this will become plus upon 2a. Even if you take the positive sign or if you take the negative sign, always this value will be negative. If I take the positive sign, if I take the negative sign, then surely it will be negative, right? Minus 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 will be minus only. Even if I take the positive sign, minus nd plus under root nd square plus 4ni square. So this value will always be larger than this value. That means this will always be negative. This whole value is always negative. and it is not possible, right? If it is always negative, it is not possible, because how the concentration can be negative? I am saying that number of holes are minus 10 to the power 3. So number of holes cannot be negative, no? It has to be a finite number. Number of holes could be 1, 2, 3, 10 to the power 3, 10 to the power 17. It could be a finite, it has to be a non-negative number, right? So not possible. What does that mean? That means you cannot find the number of holes by using this method. That's why I said that this equation, mass action law, is used to find out the minority carrier concentration, So in n-type semiconductor, who is the majority carrier concentration? This is the majority carrier concentration. So if I have find out the majority carrier concentration, how will I find out my minority carrier concentration? So this was your majority carrier concentration. So what will be your minority carrier concentration? So you know that here what I will do, I will draw a line. So you understood why we cannot use these equations to find out the minority carrier concentration. Okay, so what I will do, n into p is equals to ni square. So number of holes will be ni square by n. So n value I will be already knowing. So number of holes will be ni square by n. So this will be your minority. Just I will write down minority carrier concentration. Okay. So for n-type semiconductor. So in conclusion, what I can see, for n-type semiconductor, majority is electron concentration and minority is hole concentration. So electron concentration is coming out to be Nd by 2 plus under root Nd by 2 whole square plus Ni square. Okay. Now in most of the cases what will happen, let's just say my Ni was 10 to the power 10. Like previously my number of electrons and number of holes were 10 to the power 10 when it was intrinsic. Now I will do the doping much higher than this one. I will dope 10 to the power 16. My donor atom, that means I am putting 10 to the power 16 phosphorus atoms. And I am saying that all the phosphorus atom will give you one electron and all are ionized. That means this was your donor energy level and this was your conduction band. So all of these 10 to the power 16 atoms are reaching into the conduction band. This is what I am assuming. So what will happen? This Nd value is very larger than Ni, right? Are you able to understand this point? So in most of the cases what will happen is that Nd, if like this is the generalized formula that should be there in your mind, but in the 99.95% cases what will happen is that usually Nd is much greater than Ni. So what you can do, you can ignore this part. 100 plus 1, what that would be? Roughly 100 only, no? Or 1000. 1000 plus 1, that would be roughly 1000 only. So what I can do, I can ignore this. So with respect to Nd, I can put Ni approximately 0, right? With respect to Nd, I can put Ni approximately equals to 0. So what will happen? Nd by 2 whole square and then under root. So whole square and under root will get cancelled out. Ni I am putting 0, so this is gone, and whole square and under root will get cancelled out. So what you will be getting? You will be getting Nd by 2 plus Nd by 2. What that would be? Nd only. So your number of electrons will roughly be equals to, electron concentration will roughly be equals to the number of donor atoms. Number of donor atoms which are ionized. What I am saying, let's just say I have put 100 phosphorus atoms. So 100 phosphorus atoms will give me 100 electrons, because 4 are making the bond and 1 is nearly free. Now out of these 100 electrons, how many will reach to the conduction band? So here we are assuming that 100% are reaching. Let's just say only 90% are reaching. So what will be the value of ND there? 90, not 100, right? So this concept I have already explained. Also I will pick some question as well. There complete ionization will not take place. So N is roughly equals to ND. And what is the minority carrier concentration? That was Ni square by N, right? So roughly what that would be equals to? Roughly that would be equals to Ni square by Nd. There you go. So this is for the N-type semiconductor. So this formula you should keep in mind. Other formula should be there in your mind, that is N into P is equals to Ni square. N into P is equals to Ni square. So from there P will come out to be Ni square by N. And what is Ni, what is N, what is P, everything should be there in your mind. Similar kind of analysis, the ditto same analysis you are going to do for P-type semiconductor. So all the equations, everything I have written, right? So what you are going to replace here, N into P is equals to Ni square. Who is the majority charge carrier? Who is the majority? P. Who is the minority? N. So for finding minority, what you are going to do? From here only I am telling N will be equals to Ni square by P. But for the majority, you are going to solve these equations. So what you will do? N into P is equals to Ni square. Now here, let's write down these equations again. For P-type semiconductor, negative charge and hole, negative charge and hole, negative charge and hole. Along with that, there will be electrons as well. Wait a second, guys. Yeah, so what I was saying. So this was your P-type semiconductor. So in the P-type semiconductor, what was the scenario? Acceptor atom was there, holes were there, acceptor atom, holes, acceptor atom, holes. So acceptor atoms are negatively charged particle. Plus, who else is negatively charged particle? Electrons. And who is the positively charged particle? That are holes. What you will find out? You will find out the value of P. So for finding out the value of P, what you will do? P is equals to, what you will replace? You will replace the value of N. So N will be equals to P minus Na. So solving equation 1 and 2, what you will get? Here only I am writing now. N will be replaced P minus Na into P is equals to Ni square. So, so similarly, this kind of equation you are getting. In place of N, you are just putting P. So P minus Na is equals to Ni square. The same kind of equation I am getting. So what will be the answer of P? So from here, answer of P will come out to be Na by 2 plus under root Na by 2 whole square plus Ni square. Okay. And what will be the number of electrons? That would be Ni square by P. So these are the two formula, but along with that, two other formula will also come into action. What that would be? That would be usually number of acceptor atom will be much greater than Ni, right? So what will happen is that P will be approximately equals to Na only. So whatever the donor atom is there, sorry, whatever the acceptor atom is there. So what will acceptor atom do? It will give you a hole. So all the holes are taking electrons from the valence band, and if from the valence band electrons are going, that means it is creating some vacancy here. So all the electrons are going here. So what is the meaning is that every acceptor atom is giving you a hole. Okay. So P will be roughly equals to Na and N is roughly equals to Ni square by Na. So always for finding the minority charge carrier concentration, you will use the mass action law, not any equation. So you are remembering the formula only for the majority charge carrier concentration. That is for electrons it is Nd by 2 plus under root Nd by 2 whole square plus Ni square. For P-type semiconductor, for holes it is Na by 2 plus under root Na by 2 whole square plus Ni square. So these are the formula. Now we will write down the summary. So semiconductor, for intrinsic types of semiconductor, number of electrons is equals to number of holes is equals to Ni. For n type semiconductor, number of electrons are coming out to be Nd by 2 plus under root Nd by 2 whole square plus Ni square, and number of holes were coming out to be Ni square by n. And if Ni is much lesser than, or better I should write down, Nd is much greater than Ni, then n is approximately equals to Nd, and P is approximately equals to Ni square by Nd. Okay. What about the P type? In P type, Na by 2 plus under root Na by 2 whole square plus Ni square. Ni square by P. If Na is very much greater than Ni, then P will be approximately equals to Na, n will be approximately equals to Ni square by Na. There you go. Okay, well and good. So this is the summary of everything that we have studied. So don't feel like that, sir, there are a lot of formulas. There are not a lot of formula. Okay, let's solve the questions. So two questions are there, both you should be able to solve. Both of the questions you should be able to solve. At 300 Kelvin, n-type silicon semiconductor is doped with the donor concentration of Nd 10 to the power 16. Intrinsic carrier concentration is 1.5 into 10 to the power 10. Electric field is applied. Electron and hole mobilities are given. Equilibrium electron and hole concentration you need to find. So first thing I will see n-type semiconductor. What is the answer of first one? Answer of first one, n-type semiconductor. So for n-type semiconductor, I remember the formula n equals to Nd by 2. Although I will not apply this formula blindly in the examination. In the examination, what I will do is that, as of now we are learning it for the first time, that's why I am writing it. In the examination, what I will see is that Nd, which is 10 to the power 16, and Ni, which is 1.5 into 10 to the power 10. So this Nd is much greater than Ni, right? So n will be approximately equals to Nd only. So your electron concentration is coming out to be 10 to the power 16. And what about the hole concentration? So hole concentration will be Ni square by Nd. Again approximately, right? So what is Ni square? So intrinsic carrier concentration was 1.5 into 10 to the power 10. So what is the what is the square of 1.5? 2.25, right? So 2.25 into 10 to the power 20. You can do the square, right? 1.5 square would be 2.25, 10 to the power 10 square would be 10 to the power 20, divided by value of Nd, that is 10 to the power 16. Again here also there is a mistake, per centimeter cube. So number of holes would be coming out to be 2.25 into 10 to the power 4 per centimeter cube. So this is the answer of second one. Number of electron and number of holes we have told, right? Now what they are asking, total drift current density. Drift current density. So that will be because of the electrons, n q mu n into E. plus that will be because of holes as well. Now just think about it. Let's write down the formula. Okay, what is the value of n? Value of n is 10 to the power 16. And what is the value of p? 2.25 into 10 to the power 4. Q will be same for both of them. E will be same for both of them. What is mu and mu p? They are nearly double of each other. Like this is 650, this is 1350, nearly double of each other. But here what is the difference? 10 to the power 4, 10 to the power 16. Very large difference. 10 to the power 4, 10 to the power 16. Are you able to understand this point? Right? 10 to the power 4. That means 10,000. 10 to the power 16 is billions ahead. One guy is having 10,000 rupees, one guy is having billions of rupees. So, way more difference is there, no? Right? Even 10 to the power 2 and 1, you are getting 1 marks, and one guy is getting 10 to the power 2 marks. Out of 100, one guy is getting 10 to the power 2 marks, one guy is getting 1 mark. So, this is way larger, right? So, this is 10 to the power 2 ahead, but this is 10 to the power 4, 10 to the power 16, 10 to the power 12 ahead. So, very large. Here the difference is only double. So, forget about this difference. Let's just understand that both are equal only. But this p is very smaller than n. So, you can see that n is very greater than p. So, approximately your j will be nearly equals to n q mu n into E only. So, here mu p is of no use, and this also is of no use, although in the first question they are asking the concentration, but actually this is coming out to be of no use, right? So, in the previous lecture, whatever the theory that we have studied, now based on that theory we are solving all the numericals, nothing else, and some formula we have seen, nothing else, right? So, here because of this condition the formula has reduced. So, our hard work will be reduced now. Answer would be 10 to the power 16 into 1.6 into 10 to the power minus 19. Now you would see n is in the centimeter cube inverse, right? Q is in the coulomb. Mu n is only issue is centimeter. So I am just writing 1350. 1350. So here it is centimeter. It is in the centimeter square. And electric field is there in, where is the electric field? Volt per centimeter. Electric field is also there in volt per centimeter. Now you remember the unit of charge density. What is the unit? Charge density is I by A. So ampere by, what is the area? Meter square. But here everything we are dealing in centimeter. So what will be the unit? Ampere per centimeter square. Did you understand this point or not? Right? Rest all the things are fine. Volt, second, volt, centimeter cube, centimeter square. So our answer will also be ampere per centimeter square. Is that okay for you? Right? So what we can see, 13.5 10 to the power 2, 10 to the power 3, 10 to the power 13.5 into 1.6. 13.5 into 1.6. 21.6 ampere per centimeter square. 13.6 because 10 to the power 16, and here from here what I am doing, 10 to the power 2 I can take. So 10 to the power 18 it will become. I need to cancel 10 to the power minus 19. So 13.5 I can make here. So 13.5 into 1.6, that is coming out to be 21.6. 21.6. 21.6 ampere per centimeter square. This is the approximate answer. Now let's solve the question 2. This was your answer 1. Let's solve question 2. So now answer 2. At 300 Kelvin, n-type silicon semiconductor is having donor concentration of this much, intrinsic carrier concentration of this one. Find out the equilibrium, majority and minority carrier concentration. See the ND value and see the NI value. ND is much larger than NI? Absolutely not, right? So first thing is that I always need to see the type of semiconductor, N type semiconductor it is. Nd value is given as, so here very low doping they have done, 3 into 10 to the power 10 centimeter cube inverse, right? 3 into 10 to the power 10 centimeter cube inverse, and Ni is 1.5 into 10 to the power 10. Ni is 1.5 into 10 to the power 10 centimeter cube inverse. So now here a lot of people will do n equals to n nearly is equals to nd, but now you are not going to do that because nd and ni are comparable. So value of n would be nd by 2 plus under root nd by 2 whole square plus ni square. So nd 3 into 10 to the power 10 divided by 2 plus under root 3 into 10 to the power 10. So it would also be 1.5 into 10 to the power 10 whole square. So yes or no? Did you understand what I did here? 3 into 10 to the power 10 divided by 2. So 1.5 into 10 to the power 10. This is what you will be getting here. No? 3 by 2. What that would be? 1.5. 1.5 into 10 to the power 10. And what is the value of Ni square? That will also be same. Basically Ni is equals to Nd by 2. Ni here is equals to Nd by 2. Right? So from here you could directly see that I could have taken Nd by 2 under root 2. So Nd by 2 into 1 plus under root 2. That would be the answer. But yeah, let's solve in this manner. 1.5 into 10 to the power 10 whole square, right? So from here what I will be getting, this will be 1.5 into 10 to the power 10, and from here I can take 1.5 into 10 to the power 10 into under root 2, right? Because 1.5 into 10 to the power 10 whole square will come common, 1 plus 1 will be 2. Basically this is 1.5 into 10 to the power 10 whole square into 2. So whole square and under root will get cancelled out each other, under root 2 will remain there as it is, right? So what will be the answer you will be getting? Under root 2 plus 1, under root 2 plus 1 plus 1 into 1.5, 1.5. So 3.62, 3.62 into 10 to the power 10 centimeter cube inverse. This is the answer that you are getting. Okay, fine. Let's check the calculation again. Yeah, 3.62 into 10 to the power 10, right? So this is your electron concentration that I am writing down on the next page. 3.62 into 10 to the power 10 centimeter cube inverse. And what will be your whole concentration then? Because holes are the minority, right? So Ni square divided by n. What is the value of Ni square? Ni square is 2.25 into 10 to the power 20. Now what is the number of electrons? Number of electrons are 3.62 into 10 to the power 10. So if number of electrons you already know, and when it was intrinsic at that time what was the concentration, that also you already know. So you can surely find out the number of holes as well. So what will be the answer you will be getting? 2.25 divided by 3.62. 25 divided by 3.62. 0.62. 0.62, or you can write down 6.21. 6.21 into 10 to the power 9 centimeter cube inverse. This is the concentration of holes. Ten to the power 10 multiply, yeah. This is the concentration of electrons and this is the concentration of hole at the equilibrium. So you can see that concentration of electron is not much greater than the concentration of holes. And if you multiply both of them, if you multiply 3.62 with 6.21, you will get 2.25 roughly round. Sorry, 3.62, 3.62 multiply with 6.21 Yeah, so 22.5 we are getting. Because here 10 to the power 9 is there, no? So 2.25 into 10 to the power 20, roughly around that value only you are getting, right? Very easy thing. You should have solved it. You should have solved both of the questions on your own. You don't need to see the solution. Let's go to the next concept. Next concept is compensated. Okay, before that there is a question. After that there is compensated n-type semiconductor. So let's solve this question. Try doing it on your own. At 300 Kelvin, p-type silicon sample is having acceptor atom of 2 into 10 to the power 10. Okay, so previously it was intrinsic. Having 1.5 into 10 to the power 10, and then you did the doping of Na. That was 2 into 10 to the power 10. Now what is the line written? Only 60% of the acceptors are ionized. Only 60% of the acceptors are ionized. What does that mean? That means you wanted to get 2 into 10 to the power 10 holes. Every acceptor atom could have given you 10 to the power 2 into 10 to the power 10 holes. But actually you did not get that much of. Actually you did not get that much of holes. Why is that so? Because only 60% have been ionized. What does that mean? That your actual Na minus is 60% of Na. What does that actually mean? This was your acceptor, this was your valence band, and this was your acceptor energy level. So this was the conduction band, this was valence band, and this was the acceptor energy level. So let's just say there was 10 holes. Let's just say I did the doping of 10 acceptor atom only. Here it is given 2 into 10 to the power 10, but I am saying that I did the doping of 10 acceptor atoms. So 10 acceptor atoms will give me 10 holes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 holes. And here there are a lot of electrons. Bound electrons are there. A lot of bound electrons are there. Now what really happened was only 60% of them was ionized. That means from here only 1, 2, 3, 4, 5 and 6 electron games, and all these were ionized. So here only 6 holes you get. 1, 2, 3, 4, 5, 6. So in valence band you are actually getting only 6 holes. So here also the same thing is happening. 2 into 10 to the power 10 acceptor atoms you doped, but only 60% of the acceptor atoms are useful for you. This is what you can understand. So 60% of this, what that would be? 0.6 multiply with 2 into 10 to the power 10. I hope you know how to calculate the 60%. 60% of 100. I got 60% of marks. What does that mean? 60% of 100. So 0.6 into 100. That means I got 60 marks. So just I am multiplying with 0.6. So these are the actual number of holes. Like actual number of holes, this is not the number of holes now. This is not the equilibrium number of holes. Because of the boron atom, these many holes could have come. What is the equilibrium number of holes? That we will see. For that we need to apply the formula. And this is your p-type semiconductor. That's why my majority charge carrier concentration will be holes. So Na minus I have got, that is 1.2 into 10 to the power 10 centimeter cube inverse. Now number of holes will be, in place of Na, now I will be putting Na minus by 2 under root. So previously I was using 100% ionization. Here nothing about the ionization was mentioned. So 100% ionization in both of the cases. But here they have mentioned that 60% ionization is there. And this is comparable to Ni, right? This value. And what is the value of Ni? Ni value is 1.5 into 10 to the power 10 centimeter cube inverse. So these two values are comparable, right? So you solve this question, you write down the value of P, okay, because both of the values are comparable now. Actually you need to calculate total current density. So you know that if I apply the formula of total current density, what that would be? In the total current density, number of electrons will also come into action, number of holes will also come into action. So NQ mu N plus electric field, sorry, multiply with electric field, and PQ mu P multiply with electric field. Then you saw that number of holes that you will get, and number of electrons that you are going to get, they will be nearly equal, because Na is nearly equals to Ni. So you cannot ignore anything. Both of the parts will come into action. This part will also come into action and this part will also come into action. So that's why you are doing all the calculation. Do this calculation. I will take some break because of the cough that I am having. So I need to take some break and then I will come back and we will solve this particular question. Yeah, welcome back. So when I put the values, the answer I am getting is 2.21 into 10 to the power 10 centimeter cube inverse. Okay, so this is the number of holes. So again I am writing number of holes are 2.21 into 10 to the power 10 whole cube inverse. So what will be the number of electrons? That would be Ni square by P. So that value I can put. What is the value of Ni square? 2.25 into 10 to the power 20 divided by value of P is 2.21 into 10 to the power 10. So this answer I am getting is 1.01 into 10 to the power 10 centimeter cube inverse. But our target was to find out the drift current, that was NQ mu n into E plus PQ mu P into E. Here what I can take common? I can take Q into E, I can take common, right? Q into E. So number of electron concentration will be multiplied with mobility. Number of hole concentration will be multiplied with mobility. 1.6 into 10 to the power minus 19. Value of electric field is 10. Electron concentration is 2.21 into, electron concentration is 1.01. Sorry. Electron concentration is 1.01 into 10 to the power 10 and mu n value is 1350 plus here this is 2.21 into 10 to the power 10 and mu p value is 650. So there you go, this is what we need to solve. So everything is going into centimeter, like volt per centimeter, centimeter cube. So answer will be ampere per centimeter square, right? That would be the answer. Now from here I can take out 10 to the power 10 outside, right? So this will be 10 to the power 11. So 1.6 into 10 to the power minus 7. So this is 10 to the power minus 18 already, and 10 to the power 10 is coming outside. So 10 to the power minus 8, right? 10 to the power 10 is coming outside. So 10 to the power minus 8. Here what I am getting, 1.01 into 1350. 1.01 into 1350 plus 2.21 into 650. So 2800 I am getting. 2800. This is what I am getting. Okay. Then 2800 into 1.6. I am getting 4480. 4480 into 10 to the power minus 8 ampere per centimeter square. And if I want to write it down in a better manner, what that would be? 44.8, because 10 to the power 2 I want to give this to this one. So 10 to the power 2 into 10 to the power minus 8, what that would be? 10 to the power minus 6. So that would be micro ampere per centimeter square. So that would be the conduction, that would be your drift current density, 44.8 microampere per centimeter square. Okay, so that would be this would be the answer. Very simple thing. Just here the new thing was that 60% of Na. Then from there you find out the value of Na. From there you find out the value of hole concentration. From there you got the value of electron concentration. Then you applied the formula and you solved it. Now there is something called compensated N type of semiconductor. So this is an N type of semiconductor, but here donor atom and acceptor atom both will be doped. What I mean to say is that previously you were having intrinsic, right? Previously it was intrinsic, but here you will be doing the doping of Na as well, you will be doing the doping of Nd as well. But since this is N type, that means Nd will be larger than Na. Are you able to understand this point? So here what will be your mass action law? Mass action law will be N into P is equals to Ni square. Because previously it was having Ni when it was intrinsic. Now the electron concentration is N, hole concentration is P, right? So N into P is equals to Ni square. This is your mass action law. What will be your charge neutrality equation? Did you understand this point? Compensated N-type semiconductor, since it is N-type, Nd will be greater than Na, but both of the donor atom and acceptor atom both will be doped. Okay, what will be your neutrality equation? Negative charge is Na, right? Negative charge is Na and electrons, and positive charge is Nd and holes, right? Who is the majority here? Who is the majority? Majority is N, and who is the minority? Minority carrier concentration is P. So whom I will replace? I will replace P here, right? So value of P will come out to be Na minus Nd plus N, right? Or what you can write down? Okay, it is fine. Previously, what was the scenario? When we solved this particular question, when we solved this particular equation. So here the scenario was N minus Nd, right? So what I will write down? Can I write it down in this manner? N minus Nd minus Na. This is the value of P. This is equation 1. This is equation 2. So previously what did you solve? N into P is equals to Ni square and P is equals to N minus Nd. This is what you solved. Previously this is what you solved. And you know the answer. What was the answer? N is equals to Nd by 2. Now in place of Nd, what you have replaced? Nd minus Na. In place of Nd, what you have replaced? Nd minus Na. Because this is N minus Nd minus Na. So in place of Nd, what you are getting? Nd minus Na. So what do you think? What will be the answer? You can solve it on your own. So the electron concentration will come out to be Nd minus Na by 2 plus under root Nd minus Na by 2 whole square plus Ni square. There you go. So what you will see first? First, in these kind of questions, you will see that which is greater, Nd is greater or Na is greater. From that, you will decide that who is the majority, who is the minority. From there, you can write down this formula very directly. Because you know that Nd is greater than Na. So here you will write down something positive, no? So Nd minus Nd divided by 2 plus under root Nd minus Nd whole square plus Ni square. Right? So in place of Nd, you are just putting Nd minus Na. And what will be your whole concentration? So for that, Ni square by N. And if your Nd minus Na is much greater than Ni, okay, that means doping is very high. Both of the dopings are very high, or Nd is very high. Whatever it is, Nd minus Na is very greater than Ni. Then what will be the answer? N will be approximately equals to Na minus Nd, right? Because you can see that Nd minus Na, not Na minus Nd, because Nd is higher, no? It would be approximately equals to Nd minus Na. And what about the holes? That would be Ni square by Nd minus Na. There you go. Similarly, there will be compensated p-type semiconductor as well. I don't think it is tough to remember. Very easy. Compensated n-type, compensated p-type. That means both donor and acceptor atoms are there. Since it is n-type, donor atom is more. So directly I can write down the formula. Nd minus Na divided by 2 plus under root Nd minus Na divided by 2 whole square plus Ni square. There you go. What about this one? compensated p type. So what do you think, what will be equilibrium hole concentration? That would be Na minus Nd divided by 2 plus under root Na minus Nd divided by 2 whole square plus Ni square. And what will be your electron concentration? That would be Ni square by P. And if your Na minus Nd is much greater than Ni, then your P will be Na minus Nd, and your approximately your P will be approximately Na minus Nd, your N will be approximately Ni square upon Na minus Nd. There you go. Okay, so not tough to remember, everything is easy, not tough to remember at all, because you know that Na is already greater than Nd because it is compensated p type. So this is the question. Like this question will just clear everything that we have studied till now. We have been studying semiconductor physics for roughly around 6 hours now, 4 hours in the previous video, 2 hours in this video. So in this 6 hours, whatever that you have studied, most of the part would be covered in this particular question. So what you need to find, calculate the electron and hole concentration and the current density. Okay, so I would require what it is given, compensated p type, it is already given, or without, even if it was not given, then you could see that this is the value of Na, this is the value of Nd. That means both of the dopings are there. Na is there 10 to the power 14 per centimeter cube, and Nd is there 2 into 10 to the power 13 per centimeter cube. So you can directly see that Na is greater than Nd. If Na is greater than Nd, that means it is p type, compensated p type, right? And what is the value of Nd minus Na? Sorry, Na minus Nd, because it is p type, so I will calculate Na minus Nd. So this is your Na is actually 10 into 10 to the power 13, right? So 10 into 10 to the power 13 is subtracted from 10 into 10 to the power 13. 2 into 10 to the power 13 is subtracted. So what will be the answer? 10 minus 2 will be 8. I hope you are able to do this calculation. This is not tough. Na minus Nd. Na minus Nd. 10 into 10 to the power 13 minus 2 into 10 to the power 13. So 8 into 10 to the power 13 centimeter cube inverse. And what is the value of Ni? Ni is 5 into 10 to the power 13 centimeter cube inverse. So again the values are comparable, right? What all things are given? Intrinsic carrier concentration, all these things are given. Electric field is given. So first let's find out the electron and hole concentration. So for finding out electron and hole concentration, this is something I require and this is something I require. My job is done. So I can find out the hole concentration by my formula Na minus Nd by 2 plus under root Na minus Nd by 2 whole square plus Ni square. What is the value of Na minus Nd? Na minus Nd is 8. 8 divided by 2 will be 4. So 4 into 10 to the power 13 plus under root. Now what will be 4 square? That would be 16. 10 to the power 13 will be 10 to the power 26 plus Ni square. 25 into 5 square will be 25, or this will be 10 to the power 26. So here 10 to the power 13 will come outside and 4 will be there. So 4 plus 25 plus 16, what that would be? 41 into 10 to the power 13. Did you understand this point? 10 to the power 26 will be coming common. So 10 to the power 13, 25 plus 16, that would be 41. So under root 41 plus 4. So 10.4, 10.40 you are getting. So 10.4 into 10 to the power 13 centimeter cube inverse. So the number of holes are coming out to be 1.04 into 10 to the power 14. Roughly I can call it in this manner, right? Yeah. And answer also matching. Yeah, 1.04 into 10 to the power 14. And number of electrons will come out to be Ni square by P. So 25 into 10 to the power 26 divided by 1.04 into 10 to the power 14. Reciprocal into 25. So 2.4 into 10 to the power 13, right? 2. So basically here I am getting 24. 25 divided by 1.04 is 24 I am getting, and 24 into 10 to the power 12 I will get. So if I need to make 10 to the power 13, so what I will do? 2.40 into 10 to the power 13 centimeter cube inverse. This is my number of electrons. Now what I need to find? I need to find the current densities. What I need to find? I need to find current density. I know that number of electrons and number of holes both will be drifting in the same direction, so both of the currents will be added. So N Q mu N into E plus P Q mu P into E. This value I am having, P value I am having, Q value I already know, E value also I am having, right? E value is given. The only concern is mu N and mu P. They haven't given the value, but they have given mu P divided by mu N is 1 by 2. Mu P divided by mu N is 1 by 2. This is what they have given. So I can write down 2 mu P is equals to mu N. So mu N is just that double of mu P, right? This is what they have given. Now I need to apply this formula. But before that, there is one more thing given. Intrinsic resistivity they have given. So somehow I will use this particular thing. So resistivity, intrinsic resistivity they have given, that is 50 ohm into centimeter. Okay, centimeter. 50 ohm into centimeter. So everything is going into centimeter only, right? And that would be equals to, this is intrinsic. So here what I will write down? Intrinsic conductivity, that is Niq into mu N plus mu P. Did you understand this point or not? Right? This is the intrinsic resistivity. So intrinsic resistivity would be equals to 1 by intrinsic conductivity. What is intrinsic conductivity? Nq mu N plus Nq mu P. Sorry, Nq mu N plus Pq mu P. N equals to P equals to Ni. So Ni into Q bracket mu N plus mu P. Right? One thing I know that mu N is equals to 2 mu P. So here what I will get? 1 by Ni Q into 3 mu P. So value of mu P will be 1 by 3 into Ni. What is the value of Ni? I again forgot the value of Ni. Ni was given as 5 into 10 to the power 13. So let's write down in a better manner. 5 into 10 to the power 13. So 1 by 3 is already there. 5 into 10 to the power 13 into charge 1.6 into 10 to the power minus 19 into 50. So answer will be coming in centimeter square. Centimeter square upon volt into second, because everything is going into centimeter. So how will I solve it? 1.6 15 into 1.6 into 50. This I have done, this I have done, this I have done, this I have done. And what this will give you? 10 to the power minus 6. So if it goes upward, it will give you 10 to the power 6. 10 to the power 6 divided by 1200. If I take the reciprocal, I am getting 8.33 into 10 to the power minus 4. So answer would be 8.33 into 10 to the power minus 2. Something doesn't seem like 10 to the power minus 2, this much low conductivity, this much low mobility, 8.33 into 10 to the power minus 2. Oh, sorry, 10 to the power plus 2, sorry, 10 to the power plus 2, because this is 10 to the power 13 and 10 to the power minus 19. Because I know that generally what value we are seeing, 1350 and 500, this is the general value of mu p and this is the general value of mu n. Basically, I know that in centimeter square into volt into second. So here I was messing up the calculation, I was getting this thing. So just I thought that this much low value of mobility cannot be there. So then I know that, yeah, 8.33 into 10 to the power minus 4 you are getting, and here you are getting 10 to the power plus 6. So this will be 10 to the power 2. Okay, yeah, centimeter square volt into second. So from here mu n value you would know just that double of it, and that would be 16 point. I should not have used the calculator for this, double of it, I should have done it, right? But yeah, now it's been roughly around 4 to 5 hours since I am recording, so I'm training as of now. So after this question I will stop, I will come back tomorrow. But videos I will add up together, but after this question I will have to stop because I'm not at my 100% now, right? So yeah, mu and mu p value we are having, so now we can apply the formula. One thing I can see that q into E I can take common. So n into mu n plus p into mu p. So 1.6 into 10 to the power minus 19. What is the value of E? Value of E is 3. What is the value of n? N is 2.4 into 10 to the power 13 into what is the value of mu n? That is 16.66 into 10 to the power 2 plus what is the value of P? Value of P is 1.04 into 10 to the power 14 and 8.33 into 10 to the power 2. So here 10 to the power 15 I am getting, 10 to the power 16 I am getting. So let's make it 10 to the power 16 only. So if I take out 10 to the power 16, so 4.8 into 10 to the power 16 I am taking out, 10 to the power minus 3 I will get. And inside 0.24 into 16.66, 0.24 into 16.66 plus. I hope you are understanding how I am doing the calculation. Here 10 to the power 13, 10 to the power 2, 10 to the power 15 it would be, and here 10 to the power 16. So here also I thought of making 10 to the power 16. So for that what I need to do, 2.4 can be replaced with 0.24. So 10 to the power 16 I am taking outward. So 10 to the power minus 19 into 10 to the power 16, that would be 10 to the power minus 3. 1.6 into 3, that I know, 48, 4.8. And inside I am doing the calculation, 2.4 into 0.24 into 16.66. So that value I am getting, and then 1.04 into 8.33. So 12.66 you are getting, 12.66 here, and that will be multiplied with 4.8. So 16.77. Yeah, 16.77. So we are getting 60.77. 10 to the power 3 can be 10 to the power minus 3 can be replaced with milliampere divided by, everything is going in centimeter, right? So centimeter square. So that would be the answer. Again, not very tough question, but calculation is there. So you need to have some patience and solve the question in this manner. Calculations are there, but again, easy question only, right? So acceptor atom was also there, donor atom was also there. Then you subtracted both of them. You got to know that it is comparable to Ni. So you have to apply the exact formula. From there, you find out the value of concentration of electron and holes. Then you go to know that I need the mobility value as well, but only relation is given. Then you search for some other value. So this other value was given, which was 50. From here you could get to know that yes, now I can apply another formula and I can get my answer, right? So from there you got the value of mobility, and that mobility value you use there, and you got the conduction current, sorry, you got the drift current density. Okay, that is the answer. So for this video, this part is completed, but another part is there. In this part, what we discussed? We discussed some terms, some formula, and then we solved some question. So within 10 to 15 minutes, you will be able to revise it. So just go back, collision time, effective mass, then mobility, E tau by m. That formula came into action, E tau by m star. Then drift velocity, Vd is equals to mu e. Then conductivity, n q mu, where n is the charge carrier concentration, q is charge only, and mu is the mobility. And then charge density, J is equals to sigma e. Sigma value you already know, and E value you will be given, right? From there you can find out the current as well, because current is simply equals to J into A. For intrinsic carrier concentration, n is equals to P is equals to Ni, so you can put there and you will get your answer. For n type semiconductor, n is much greater than Nd. Sorry, for n type semiconductor, n is much greater than P, and for p type semiconductor, P is much greater than n. Then we studied about mass action law, n equals to n into P is equals to Ni square. So always at the thermal equilibrium, number of electron concentration multiplied with the whole concentration will be equals to a constant, that is equals to Ni square. Okay, then charge neutrality equation, who is the positive charge? Positive charge is Nd plus P, that would be equals to Na plus N. From these two equations, we got to know that we can find out the concentration of electron and holes in semiconductors. For intrinsic semiconductor, n equals to P equals to Ni. For n type semiconductor, n is equals to, because for the majority charge carrier concentration, we remember the formula. For minority, we will apply again the mass action law only. So for majority, the answer is coming out to be, for n type semiconductor, for majority, the answer came out to be Nd by 2 plus under root Nd by 2 whole square plus Ni square. That is the concentration of electrons. Then concentration of hole is Ni square by n. For the p type semiconductor, concentration of holes is Na by 2 plus under root Na by 2 whole square plus Ni square. And concentration of electron from the mass action law you can find out. Then we studied about compensated n type semiconductor and compensated p type semiconductor. In compensated semiconductors, both of the dopings would be there, but for n type semiconductor, Na is greater than Nd. For p type semiconductor, sorry, for n type semiconductor, Nd is greater than Na. For p type semiconductor, Na is greater than Nd. For both of them, you can write down the formula of electron concentration and hole concentration just by the formula that you have already remembered. In place of Nd, you will place Nd minus Na, and in place of Na, you will place Na minus Nd. For both of them, you will remember the formula for majority charge carrier concentration. For minority, you will just apply the mass action law. There you go. This is how you can devise this particular lecture. In this lecture only, we will study about some graphs. Okay. So we have studied about mobility, but how this mobility will change with respect to the temperature. We have studied about conductivity, how this conductivity will change with respect to the temperature. We have studied about drift velocity, right? So how drift velocity is related to electric field. So these kind of a lot of graph would be there. For all the parameters that we have studied, we will see the graphs and we will see how those graphs will go. Okay, so that we will study in this video only, but in the second half. Okay then, yeah, thank you very much. Happy learning. Hi everyone, welcome back. Welcome to the second part of this video. In this part, we are going to plot some graph. We will plot the graph with respect to temperature, with respect to doping concentration, and all these kind of things. So what all parameters we have seen? So first parameter we saw, that was carrier concentration, right? Intrinsic carrier concentration. Then we saw about mobility. Then we saw conductivity. Then current density, current, all these parameters we saw. So we just need to plot the graph with respect to temperature. Then some other graphs also we will draw. So you need to have patience in this part of the video. Okay, just keep on looking whatever that I am telling. Now you let me know one thing. What we are doing firstly, we are taking an intrinsic semiconductor and we are plotting intrinsic carrier concentration versus the temperature. Intrinsic carrier concentration versus the temperature. But it will have an effect on Eg as well and temperature as well. So first let's understand by our simple concept. What was our concept? At 0 Kelvin, what was the condition? This was your valence band, this was your conduction band. I am talking about intrinsic semiconductor. That means I am talking about pure silicon. So valence band was filled with electrons and conduction band was empty. As the temperature increases, at 300 Kelvin, what really happened? Some electrons from here went to conduction band. Some electrons from here went to conduction band. So in conduction band, there were some free electrons and here there were some holes. These electrons and these holes were known as intrinsic carrier concentration. At the beginning, at 0 Kelvin, there were electrons, but these electrons were bound electrons. So you were not calling it intrinsic carrier concentration. No, these were the intrinsic carrier concentration. These two electrons and these two holes are known as intrinsic carrier concentration. They are not carrier concentration, right? Because they are bound. Since they have become free now, since they have a vacancy here, they are known as intrinsic carrier concentration. So as the temperature increases, here how much intrinsic carrier concentration was there? 0. But as the temperature increases, you are having 2 electrons and 2 holes, and that is known as intrinsic carrier concentration. So as the temperature was increasing, what was happening? The covalent bond was breaking up, and because of that you are getting free electrons and holes. So intrinsic carrier concentration increases with increase in temperature. So what will happen? At 0 Kelvin it was 0 only, then slowly it will keep on increasing. So the graph will, just a second, the nature of a graph will go somewhat like this, like it will keep on increasing. Okay, just like you can never make the perfect graph that sir this is how it will go for all the semiconductor. For some semiconductor it can be different, for some semiconductor it could be different, but one thing I surely know that it will be just keep on increasing. It will have increasing nature. Now how it will be increasing, sir? In this manner it is increasing, but just only one thing I know, that it will have increasing nature, that carrier concentration will never decrease with respect to the temperature. Okay, so in the examination if these kind of graphs are given in the options, so only thing you need to notice is that whether it is having increasing nature or not. So whichever the graph is having increasing nature, that would be your answer. That's it. Okay, but now this graph we have drawn, but there is an expression. There is an expression which will relate your intrinsic carrier concentration, temperature and Eg value. What is Eg? Eg is band gap. So there is a particular expression which will relate intrinsic carrier concentration, temperature and band gap. What is that expression? So that expression formula I am going to write down. Sir, how that formula came? That derivation we will see later on. In this chapter only we will see the derivation later on, but as of now you need to remember this particular expression. So your Ni square is given as some constant A naught T to the power 3 e to the power minus Eg by Kt, where A naught is a material constant. It will depend on the material. It is a constant value. T is the temperature in Kelvin. Eg is the band gap at a particular temperature. Eg is the band gap at a particular temperature. K is the Boltzmann constant and T is the temperature again. What is the value of Kt at room temperature? What this Kt is known as? Thermal energy. So what is the value of Kt at room temperature? Do you remember the value? If you don't remember, then it is not good. I told you to remember. What is the value? Although in examination there is very high chance that this value will be given, but still at least at the room temperature you need to remember it. 0.0259 electron volt, right? Say yes or no. Okay, or it can be written as 25.9 milli electron volt, or it could be written at 26 milli electron volt as well. So at least remember this value, 26 milli electron volt. Yeah, so don't write down anything, like everything is already written. I will just remove this slide and then I will show you that everything is already written. Now this is the expression between Ni square, temperature and Eg. How this formula came, that derivation we will see later on, but as of now you remember it. From here, how can you find out the value of Ni? So this power can go here. So A naught to the power 1 by 2. What it will become? A naught to the power 1 by 2. This will also be a constant only. So can I write down as B naught? Can I write it down as a B naught? Basically whatever the constant was there, this constant is different, but again it is a constant only, right? T to the power 3 by 2 e to the power minus Eg by 2 Kt. So either you remember this expression or you remember this expression. Any of the expression you can remember. Secondly, this is the Eg at a particular temperature. This is the band gap at a particular temperature. What is the relation between band gap and the temperature? So band gap reduces with increase in the temperature. Do you remember that? Band gap will reduce with increase in the temperature. So Eg was given as Eg naught minus beta naught T, where Eg naught is the temperature, Eg naught is the band gap at 0 Kelvin. So as the temperature increases, this value will decrease. So now in place of Eg, if I replace this Eg naught minus beta naught T, what I will be getting? Minus Eg naught plus beta naught T. Why plus beta naught T? Because there is a negative sign, divided by 2 Kt. Now e to the power minus Eg naught divided by 2 Kt, e to the power minus, plus sign is there, e to the power beta naught t divided by 2kt. So t and t get cancelled out. So what you are getting, e to the power beta naught divided by 2k. I am only looking at this expression, e to the power beta naught divided by 2k. Is this a constant? K is a Boltzmann constant, beta naught was a constant value only, 2 is also a constant. So this is also constant only. So this particular part is constant only. B naught is a constant, multiply with the constant. It will be a constant only. Are you able to understand this point, what I am saying? So what you got to know here is that B naught multiply with the constant, what that would be, some new constant C naught, t to the power 3 by 2 e to the power. Now in place of Eg what I can replace, Eg naught by 2kt. So in place of Eg what I can replace, Eg naught. So e to the power minus Eg naught by 2kt. So either here you can write down Eg or you can write down Eg naught as well. Anything you can write down, because you know that there is a linear relation between Eg and the temperature. As the temperature increases, Eg goes down. So in some textbook you will find out that a particular band gap at a particular temperature is written, and in some textbook you will see that band gap at 0 Kelvin is written. Okay. So band gap at 0 Kelvin they can write down, band gap at a particular temperature also they can write down anything. So don't get confused. Okay. Particularly we will write down the band gap at a 0 Kelvin. So what I will write down, some constant t to the power 3 by 2 e to the power minus Eg naught divided by 2kt. So this is the relation, this relation you need to remember. So I will just remove everything that I have written and then I will show you what has been written under the slide. So this is written. The intrinsic carrier concentration Ni of a semiconductor depends on the band gap and the temperature in this manner. Ni square equals to a naught t to the power 3 e to the power minus Eg naught by kt. From here if I want to find out the value of Ni, that would be a naught to the power 1 by 2, so that will be some constant b naught t to the power 3 by 2 e to the power minus Eg naught divided by 2kt, right, where Ni is the intrinsic carrier concentration, a naught is material constant, T is the absolute temperature, Eg naught is the band gap at 0 Kelvin and K is the Boltzmann constant. You don't need to remember the value of Boltzmann constant, you just need to remember what is the value of Kt at 300 Kelvin. The value of Kt at 300 Kelvin is 26 milli electron volt. Well and good. Okay. And now in this expression if you see, if temperature increases then what will happen? This value will increase. What I am saying, again let me write down here. Some constant, again I am writing down some constant as a naught only. Whatever the constant is there, don't look at this constant. Only matter of concern is t to the power 3 by 2 e to the power minus Eg naught divided by 2kt. So if temperature increases, then this value will increase. This value will also increase. 2kt will also increase. If 2kt is increasing, that means this particular value is decreasing. If 2kt is increasing, that means this particular value is increasing. So on e to the power minus x, so this x is decreasing. X is decreasing. What does that mean? Then this value will increase. What do you know? E to the power x. If x increases, then e to the power x increases. You know that, right? What about e to the power minus x? What is e to the power minus x? E to the power minus x is 1 upon e to the power x. So if x increases, then this whole value will increase. 1 upon something is increasing, that means this value will decrease. Right? But what is happening here? In our case, what is happening? X is actually decreasing. Eg naught divided by 2kt. If temperature increases, this whole value decreases. So x is actually decreasing. If x is decreasing, that means this value is decreasing. If this value is decreasing, that means this whole value is increasing. So e to the power minus x is actually increasing. So this part is also increasing, this part is also increasing. So the whole part will increase only. Are you able to understand this point or not? Very, very simple thing. Right? Just mathematics. If temperature increases, this part increases. If temperature increases, then this whole part also increases. Because here, if temperature increases and this part increases, this whole part decreases. If this whole part is decreasing, that means e to the power minus x is increasing. So if temperature is increasing, then Ni is also increasing. So from the formula also you can prove it. Right? So if temperature increases, Ni increases. So if temperature increases, Ni increases. If Eg increases, then what will happen to Ni? Do it on your own. This is simple mathematics, you should be able to tell it. If Eg increases, what is the formula? Some constant t to the power 3 by 2 e to the power minus Eg by 2kt. So forget about the temperature. Who is increasing now? Eg is increasing. So if this value increases, Eg value increases, then what will happen? E to the power minus x will increase. If e to the power minus x is increasing, that means this whole value will, sorry. If Eg is increasing, that means this x is increasing. So if x increases, then e to the power minus x decreases. If Eg is increasing, that means this whole value is increasing. That means e to the power minus this whole value will decrease. That means if Eg increases, then Ni will decrease. And it is pretty obvious as well. Why it is obvious? Because if the gap between conduction band and valence band increases, if this gap increases, then this electron will require more energy. This electron will require more energy to go here. So let's just say at room temperature it was going here. So at room temperature you were getting one electron and one hole. But if Eg gap is very large, then it may happen that this electron is not able to cross this much of energy. So you will not get any electron. Are you able to understand this point? So if Eg is very large, then you will not get free electrons and holes. So to get the free electron and holes, Eg should be low. So if you are increasing the Eg, that means intrinsic carrier concentration will decrease. Very simple point. Within 10 seconds you should be able to revise it. Only formula you need to remember is Ni equals to A naught T to the power 3 by 2 e to the power minus Eg naught divided by 2 kT. If temperature increases, Ni increases. By the concept as well you can understand, by the formula as well you can understand. Because temperature increasing, T to the power 3 by 2 increases. Temperature increases, then Eg naught by 2 kT decreases, e to the power minus, if x is decreasing, that means e to the power minus x is increasing. So increasing, Ni will increase only. By the concept also you can understand, at higher temperature, more covalent bond will be broken. If more covalent bonds are broken, that means more electrons will be there, more holes will be there. That means carrier concentration will increase. Now if Eg increases, that means the gap between conduction band and valence band will increase. So at lower temperature, it might happen that electron is not getting enough energy to go from valence band to conduction band. That means the carrier concentration will decrease. That's it. Or from the formula as well you can see it. Very simple. Within 10 seconds you will be able to revise it, and this is the graph which can be coming in your examination. So this was about our intrinsic carrier concentration. Let's go to our electron concentration in n-type semiconductor. So previously we were studying about intrinsic semiconductor. Now we will study about n-type semiconductor. In n-type semiconductor we will be particularly looking at electron concentration. Okay, so look at the screen very carefully. At 0 Kelvin what was happening? Because of the pentavalent atoms, because of the impurity, just below the conduction band, you are having a donor energy level. But at 0 Kelvin, none of the electron is having any energy to go from donor level to conduction band or to go from valence band to conduction band. So no electrons are there in the conduction band. What does that mean? That charge carriers are, number of electrons are 0. When I say electron, that means I am talking about free electron. And what do you mean by free electron? Free electron means electrons in the conduction band, right? At least 20 times I have repeated this line. Electron means free electron. Free electron means electron in the conduction band. So at 0 Kelvin there is no electron in the conduction band. Just as the temperature increases. So just as the temperature increases, what will happen? From here electron will start going. Along with that, some covalent bond will also be broken. So slowly, yes, the number of electrons are increasing here. But at mid temperature what will happen? All these will be completely ionized because this gap is very low. So they will be completely reaching here. They will be completely reaching here. From here hardly, previously 2 electrons were coming, so now here 3 electrons would be coming. So let's draw the graph from 0 Kelvin till mid temperature. So what was happening? At 0 Kelvin there was nothing. At 0 Kelvin there was 0 electrons. But slowly the electrons started increasing. At one particular point it will become constant. At the mid temperature it will become constant. Why is that so? Because all these have been already ionized. At the mid temperature what happens is that whatever the Nd we doped, because of one Nd we were getting one electron. So all the electrons are ionized. That means all the electrons have reached to the conduction band. Now hardly some 2 or 3 electrons are coming from the valence band. So almost it has become constant, or you can say that it will rise slowly. Here it is rising fastly. Why is that so? Initially why it is rising fastly? because these are being ionized. Nd is a lot more than the intrinsic carrier concentration. I hope you remember that Nd will be much more than the intrinsic carrier concentration. Let's just say intrinsic carrier concentration was 10. So Nd would be somewhere around 100. So those hundreds have already reached here. Now out of these 10, let's just say 9 have already reached. So 9 plus 1, 10 will come. With the increase in temperature, only a few electrons will be coming from the valence band, because till the mid temperature all these have been already ionized. Are you able to understand this point? At low temperature only they will get enough energy to get ionized. So till the mid temperature all these are already ionized. If you are increasing the temperature, what will happen? Some of these will also come here, but in a very few amount, because donor atoms are already very much higher. So these donor electrons are already very much higher. So almost it will become constant at the mid temperature, almost it will become constant. But now what you are doing, you will keep on increasing the temperature. What you are doing, you will keep on increasing the temperature. So these are already there. These have already reached here. These electrons have already reached here. But now what will happen is that because the temperature is very high, so all of these covalent bonds will start breaking up. So a lot of covalent bond will start breaking up. So a lot of covalent bonds are breaking up. So from valence band as well, a lot of electrons are coming now. So now what will happen is that the number of electrons will increase drastically after a particular temperature, at a very high temperature. So a very interesting graph. Usually people don't understand this graph, they don't know what is actually happening, but I have given you the whole condition that what is actually happening. At 0 Kelvin, no electron is reaching, no charge carrier. At low temperature, these guys have got enough energy, so they are increasing. So here number of electrons are increasing. From the valence band as well, some electrons are coming, but at the mid level temperature, when you have reached already here, when you have reached already at temperature T1, at this T1 temperature, all of these electrons have been already ionized. Only a few electrons are coming, which are hardly increasing any number of electrons, right? So number of electrons are almost constant. But if you keep on increasing the temperature, at very high temperature, what will happen is that a lot of covalent bonds will break and a lot of electrons will come into the conduction band. Okay, so this region, this particular region will be known as which region? Ionization region. Ionization region. Why ionization region? Because in this particular region ionization is happening. These electrons from the donor level is going into the conduction band, and this is known as extrinsic region. This is known as extrinsic region. Why extrinsic region? Because in this region already all of these electrons have been ionized. In this particular region, all of your donor energy level electrons have been ionized, or whatever the electrons that are coming from the donor atom, all these electrons are ionized in this region. So that's why it is known as extrinsic region. Basically you wanted your electron region to be this, right? You wanted the number of electrons to be this only. But when you kept on increasing the temperature, at very high temperature, what really happened? That a lot of electrons are coming from the valence band as well. What does that mean? If a lot of electrons are coming from the valence band, so this kind of mechanism was happening in which kind of semiconductor? In the intrinsic semiconductor, no. Initially you were having intrinsic semiconductor. You know that Ni value was very low. So for that what you did? You did the doping of donor atoms. Because of the donor atoms, you got some electrons, right? But if you kept on increasing the temperature, how you were getting this Ni? This Ni you were getting because from here some electrons were going, right? And why these electrons were going? Because of the temperature only. And if you have increased the temperature very high, that means all of them got thermal energy. So a lot of electrons have got the thermal energy. So these electrons are excited because of the thermal energy, not because of the donor level, not because from here. These electrons are coming from here, and if the electrons are coming from the valence band, what does that mean? That means they are coming because of the thermal energy. And this thermal energy phenomena happens majorly in which kind of semiconductor? Intrinsic semiconductor. So this particular region is known as intrinsic region. So what did you understand here? At very high temperature, At very high temperature, the extrinsic semiconductor will start behaving as intrinsic semiconductor. That's why you do not operate your semiconductor at a very high temperature. You will operate your semiconductor in this particular region. This is your working region. A very important graph, and I am expecting this graph to be coming very soon in your examination, very soon. Okay, so this is your electron concentration with respect to temperature, and this particular point is known as freeze out point, because here there are no free electrons. So this particular point, or sometimes in some textbook as well, you will see that this region is known as freeze out region. So you can call it freeze out region or freeze out point, whatever you want to call it, but important parts are these two regions, extrinsic region and intrinsic region. So at a very high temperature, what will happen is that a lot of valence band electrons will get thermal energy, or you can call it a lot of covalent bond electrons will get enough thermal energy, and they will create electron hole pairs, and this phenomena happens in intrinsic semiconductor. So your semiconductor, your n-type semiconductor is working as an intrinsic semiconductor only. So you don't operate your semiconductor at a very high temperature. Now you would say that sir, at very high temperature, sir, we are getting a lot of electrons, so it is good. The device may burn out. Okay, what you will say that, sir, I will operate my semiconductor at a very high temperature. So do you operate your mobile when it is very heated? No, you operate the mobile at the working condition, no, at the temperature, at the room's temperature only, no. Like if your mobile is very heated, then you will be tensed, right? Because your device may burn out. The chips inside your device, the chips inside your mobile may burn out, and your mobile may start and your mobile may stop working, right? So that's why you do not operate any semiconductor at a very high temperature. Although the number of electrons are very high, but the device will be burning out, and actually there has been no use of these donor atoms. Since a lot of electrons are coming from here, the donor atom will become minority only. I should not say minority, that means what I mean to say is that these numbers, let's just say these numbers Nd was 100, but at very high temperature what will happen is that these electrons will be very large. These electrons will be roughly around 1000. So this 100 will not look anything around these 1000. So there was no use of this doping. Even if you haven't done the doping, still it would be the same only. Are you able to understand this point? Even if you did not do the doping, then also these 100 will not make any sense. This will become 10,000, 1 lakh. So in 1 lakh, if you add 100, what does that mean? Nothing, right? So almost it is working as an intrinsic semiconductor only. Are you able to understand this point? Right? So at very high temperature, we will never operate our devices, because device will be burning out. Now what may happen is that in the examination, although this graph we have plotted n versus t, but in the examination they can ask you the graph n versus 1 by t. I don't know why. Basically a lot of curves in our industry as well, when you go into the industry, you will draw a lot of curves with respect to 1 by t, not with respect to t, with respect to 1 by t. So n versus t graph is given. Can you draw the graph of n versus 1 by t? Simple mathematics. You should be able to do it on your own. Here 1 by t value is low. This is the axis of 1 by t, right? So here 1 by t value is low. What does that mean? That t value is very high. So at very high value, number of carriers are also very high. And then if 1 by t increases, if you go here in this direction, 1 by t increases. If 1 by t increases, that means t decreases. And if t is decreasing, that means you are moving here. Basically in this graph, if you are moving here, that means in this graph you are moving here. So basically you are starting this graph from here. So how the graph will go? The graph will go somewhat like this. I will just draw the graph completely, and then you tell me whether you are able to relate or not. So this is how the graph will go. Say yes or no. This will be our 1 by t2, and this would be our 1 by t1. I hope you are able to relate this graph, how this graph is happening. If 1 by t is very low, that means t is very high. T is very high, that means a lot of charge carriers are there. Now if 1 by t increases, that means t decreases. If t decreases, that means you are moving here. So just this graph was made like this. Now you just go opposite. So increasing to decreasing, then constant, then decreasing. What I am saying, increasing to decreasing, constant, decreasing. So increasing to decreasing, constant, then decreasing. This is just, this graph just made opposite, because in the examination, usually in the textbook you will see that this graph is made. So that's why in the examination what they can ask, number of electrons versus 1 by t. They will not ask number of electrons versus t, they will majorly ask number of electrons versus 1 by t. Because in the textbook in Niemann this graph is made. Semiconductor Physics by Donald A. Niemann, one of the best book for EDC. In that particular book this graph has been made. So n versus 1 by t also you should be able to make. So usually in the examination what I will do is that I will make the graph of n versus t. Now if I need to make n versus 1 by t, what I will do, from here I will start and just make it opposite. So increasing, highest to decreasing, constant, then decreasing. So highest to decreasing, constant, and then decreasing. All good, all fine. So yeah, a very important graph, a very important, and I can expect that it is coming in the upcoming GATE examination very soon. Either this graph or this graph. Since it is given in the Niemann, so high probability is that they will ask this particular graph. Okay. So the complete theory is written. Let's read it. N-type semiconductor 0 Kelvin, all donor atoms are neutral and electron will occupy the valence band. So the conduction band is completely empty and the electron concentration in the conduction band is essentially 0. At low temperature 0 Kelvin, a very few electrons gain enough thermal energy to move to the conduction band. So electron concentration increases slowly. This is called freeze out region. In the mid temperature range, even though thermal energy is available to ionize most of the donor atom, so almost all the donor atom will contribute to the conduction. Here the electron concentration in the conduction band is roughly equal to the donor concentration Nd. Did you understand this point? At mid temperature what really happened is that all the donor atoms have been ionized. So started increasing, here it will become constant and is almost constant, forming the extrinsic region. So it is known as extrinsic region. At very high temperature, intrinsic carrier regeneration becomes significant because of the thermal energy. Because thermal energy is sufficient enough to excite the electrons from the valence band to the conduction band. So electron concentration will start increasing rapidly with temperature, and this is known as intrinsic region, where the conduction is dominated by thermally generated electron hole pairs. So you are able to understand every single line that has been written here. Say yes or no. Okay. Now the same plot you can draw for number of holes in the p-type semiconductor versus temperature. Although in our textbook this curve is given, but they can ask the same kind of plot for number of holes in p-type semiconductor versus temperature. So the same analogy you will make, 4 kind of graphs you will make, and you will be able to draw the graph. The same graph you will get. Initially what will happen? There are no holes. Slowly holes will start ionizing. Then what will happen? They will become constant, and after that, because of the thermal energy, they will start increasing rapidly. And if you need to draw it versus with respect to 1 by t, then this is how the graph will go. All good? All fine? Okay, so you can draw the graph on your own. Let's see the next graph. Before going to the next graph, we need to understand one term that is known as scattering. So you already know everything about scattering. What is scattering? Let's just say there is an electron. This electron has to move. Where it will be moving? It will be moving in the silicon crystal. So silicon, 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 silicon. There can be some impurity as well. Let's just say there is some donor impurity, or there can be some acceptor impurity as well, right? Acceptor impurity as well. And these atoms can vibrate as well. These atoms can vibrate as well, because if the atoms are getting thermal energy, then they will start vibrating. If atom will get thermal energy, then they will start vibrating. So this electron cannot move freely, right? Just as this electron gets into the crystal, it cannot move freely because atoms are vibrating. So what they will do? They will collide with the electron. These atoms and electron will collide. Or what may happen is that, like, somehow electron has reached here. So what will happen? This positive charge can attract this electron. So it will also affect the motion. And what may happen? Let's just say electron has reached here. So this negative charge can repel this electron. So this will also affect the motion, right? So electron is not moving freely. It is colliding, or it is being affected by some impurity or anything. This phenomena is known as scattering. So electron is getting scattered, right? Are you able to understand this point? And because of the scattering, what will happen? Mobility will decrease. Do you remember this point? That if there are a lot of these kind of phenomena, that electrons are, there is impurity, there is this lattice vibration. Because of that, what will happen? Impurity will decrease. Do you remember that particular thing? Okay. So when I was explaining you mobility, at that time also I told you that electrons cannot move freely. When I was explaining you effective mass, at that time as well I said the same thing, that electrons cannot move freely. So electrons are actually being scattered. So one line, in one word, if you want to call this phenomena, that is known as scattering. So electrons will be scattering. So there are mainly two kind of scattering. So first let's remove it and read the definition of scattering. So scattering, in a semiconductor, electrons or holes move through the crystal, but they do not move in a straight line forever. They keep on bumping into the things like atoms, ions, or impurities. This bumping is called as scattering, and it will slow down their motion. Very simple thing. You understood the meaning of scattering. Now there are two kind of scattering. One is impurity scattering, and other one is lattice scattering. What do you mean by impurity scattering? So impurity scattering. Impurity means it will be coming because of the impurity. So we have two kind of impurity: donor impurity and acceptor impurity. Donor impurity is positively charged, acceptor impurity is negatively charged. So if an electron started moving, it was going, but this positive charge attracted the electron. So it is affecting the motion, and this negative charge will repel the electron. So this is also affecting the motion. So that's why the electrons are getting scattered. So the scattering that is happening because of these impurities, the scattering that is happening because of these impurities, that is known as impurity scattering. You understood? Now just tell me one thing, this scattering will be dominating at lower temperature or higher temperature? This scattering will be dominating at lower temperature. Why is that so? Because at low temperature means you are having low thermal energy. And if thermal energy is low, that means electrons are moving slowly. If electrons are moving slowly, then these positive charge or negative charge can attract or repel the electron. Let's just say if I am moving very fast and there is some guy standing and he wants to attract me. If I am moving slowly, then he will be able to attract me. But if I move very fast, then he will not be able to attract me, right? He will be standing just there. I just need to pass in front of him. So he is just standing, I am just passing. If I am passing very slowly, so he will catch me, or attract me or repel me. But if I am moving very fastly, then he will not be able to attract me, right? So this is dominating at lower temperature. Impurity scattering, listen to my statement very carefully. Impurity scattering is dominating at low temperature only. As the temperature increases, impurity scattering decreases. As the temperature increases, because if temperature increases, then thermal energy will increase, electrons will move very fastly. If electrons are moving very fastly, then they will not be able to attract me, right? Basically, if I am electron, if electrons are moving very fastly, then these positive ions or negative ion will not be able to attract or repel the electron. So the effect of impurity scattering will be reducing with increase in temperature. Everything you are able to understand, right? So all these things you should keep on revising, otherwise you will be forgetting it, right? So everything I have explained, everything is written here as well. That's why I have made the notes in a manner that whenever you read the notes, everything will come to you. Or whatever the phenomena that I am explaining, in your notes you can write it down in some side, right? Let's just say I explained why that if I am moving very fastly, then they will not be able to repel or attract me. So you can write it down in some brief manner, you can write it down in your notes only. Okay, so let's read the definition. This happens when electrons collide with impurity atoms. In the semiconductor, these impurities have extra charge that can deflect the electrons. It can either attract it or it can repel it. Impurity scattering is stronger at lower temperature because electrons move more slowly and spend more time being affected by the impurity electric field. Okay, is that clear to you? So it is dominating at a lower temperature only. As temperature increases, the thermal energy will also increase. If thermal energy increases, what does that mean? Impurity scattering also decreases, right? So this is the meaning of, this is your impurity scattering. Other scattering is lattice scattering or phonon scattering. So here what will happen? Atom, silicon atoms are there. Electron tried to move. If you give high temperature, then what will happen? These atoms will start vibrating. these atoms will start vibrating. So this atom vibration happen because of the temperature only, and it happens at the higher temperature. On low temperature, they will vibrate very slowly. Let's just say this is my hand. I keep this hand on fire. Then what will happen? My hand will vibrate, no? But if temperature is very low, then it will vibrate very slowly. But if temperature is very high, then it will start vibrating more and more. As I keep on increasing the temperature, it will start vibrating. So similar thing will happen with the atoms. When you boil the water, what happens? When water is being boiled, so you would see that water will keep on vibrating, right? Similar thing will happen with the atoms. So as you give more temperature, it will start vibrating more. And since they are vibrating at their place, this electron will be colliding with them. This electron will be colliding with the vibrating atoms. Electron will be colliding with the vibrating atoms. And if it is colliding, that means it is affecting their motion. So this is known as phonon scattering, or it is known as lattice scattering. So here it would be written lattice scattering, but other name is phonon scattering. Okay, other name is phonon scattering. Okay, it is written. So lattice scattering or phonon scattering. So this happens when electron collide with the vibrating atom of the crystal lattice. At higher temperature, the atom vibrate more. So electrons are scattered more frequently because of the atoms the moving atoms act like obstacle in their path. Right, moving atoms, those silicon atoms, those are moving, they will be working as a hindrance in their path. This is why lattice scattering is more dominant at the high temperature. Did you understand this point? Lattice scattering is more dominant at the high temperature. Why is that so? Because as the temperature increases, vibrations will increase. Lattice vibration will increase. Lattice vibration means atom vibration. If lattice vibration is increasing, that means lattice scattering also increases. So two kind of things are there, impurity scattering and lattice scattering. So when the temperature was low, at that time lattice scattering was dominating. As the temperature started increasing, the effect of lattice scattering is being less, but the effect of impurity scattering is being less, but the effect of lattice scattering is increasing. Are you able to understand this point, what I am saying? Let's just say this is the temperature line. At lower temperature, impurity scattering is dominating, but lattice scattering is not dominating. As the temperature increases, the effect of impurity scattering is going down, but the effect of lattice scattering is increasing. And at higher temperature, only the lattice scattering will be dominating, because electrons will be moving very fastly. So impurity will not be able to attract or repel them. Is that clear to you? I hope you are able to understand. If you are listening to me with the clear mindset, then you will be able to understand. There is nothing tough. Otherwise, you will not be able to understand a single line. So in the best possible manner, I am giving the explanation, and in the easiest language, I have written the theory as well. So don't think that this theory is written by ChatGPT. You go to ChatGPT and ask them what is impurity scattering. They will write down very tough language. But it's me who will give prompt to ChatGPT again and again that this is how you reduce the complex part of your language. Then I give them prompt that this is how you should write down the language. So I like all these things, all this material is made after a lot of efforts. Okay, it feels like that, sir. Okay, just you go to ChatGPT, what is scattering? They will give the definition, you put it down, or you simply copy it from textbook. No, if I do that, then what will be the difference? Everything is written in the textbook. No, you can read the textbook, but all these will take a lot of effort. Only thing you need to do is that you need to listen to me carefully. That's it. Just listen to me carefully, and everything you will be able to understand. And notes are also there in the easiest possible language. Okay. So I will make sure that in the EDC, the most difficult part is that you don't get easy language. There are a lot of terms, sir. Lattice, electrons collide, impurity, low temperature, high temperature, then phonon, all these things are there. So what is the meaning of all these things? So slowly you need to build up the concept. So you are able to understand the meaning of every single thing now. Phonon means heat. From phonon you will just understand that heat. Look, when these atoms vibrate, when these atoms are vibrating, so this is known as phonon. And because of this vibration, heat is generated. So I will again explain the meaning of phonon when we study direct bandgap and indirect bandgap semiconductor. So at that time phonon word will again come into action, and that we will study in the next lecture. But as of now you ignore this word phonon. There are two things, photon and phonon. Photon and phonon. Photon means light, phonon means heat. That's it. Photon is light, phonon is heat. So as of now if you feel like that, sir, what is this phonon? So ignore this word as of now. You just remember it is known as lattice scattering. Okay. Other things are written. Temperature dependence. So impurity scattering decreases with temperature because electrons will gain more energy, they will move faster and are less affected by the electric field. Which electric field? Impurity is electric field. Impurity electric field means this is a positive charge, this is a negative charge. This is coming because of the donor atom, this is coming because of the acceptor atom. So this electric field I am talking about. And your lattice scattering will increase with the increase in temperature because at the higher temperature atoms will vibrate more. So if atoms are vibrating more, then electrons will be colliding more. If they are colliding more, that means they will be scattered more. So at higher temperature lattice scattering will increase, at lower temperature impurity scattering will decrease. As the temperature increases, impurity scattering will decrease. Now a very important part is about to come. Okay, very important part. In the beginning only I told you, because of the scattering mobility will always decrease. Because what is the meaning of scattering? Scattering means electrons are not able to move freely. They are not able to move in the straight line. That means they are being scattered. They are having some hindrance, or they are not able to move freely. That means because of the scattering, always mobility will decrease. Because of the scattering, mobility will always decrease. Is that clear to you? So this line I have written here. Scattering always reduces the mobility of charge carriers because every collision slows them down and make their motion less smooth. So if scattering increases, then mobility decreases. Now our task would be to draw the graph between mobility and the temperature. Try doing it on your own. A rough graph I am expecting, that it will increase, it will keep on increasing, it will keep on decreasing. What will happen? What do you think? Just think about two temperature range, low temperature range and high temperature range. Let's just say this is a temperature T1, this is a particular temperature T1. So before T1 you are thinking low temperature range, after T1 you are thinking high temperature range. So let's talk about low temperature range. From 0 to T1, you are going from 0 to T1. That means you are in the low temperature range. In low temperature range, who is dominating? Impurity scattering is dominating, right? So only you need to think about impurity scattering. Now in this low temperature range, if I am increasing the temperature, then what will happen? Impurity scattering is going down. That means this impurity scattering is going down. If scattering is going down, then what will happen? Mobility will increase. Here I have written that more scattering means mobility will decrease, and if scattering is less, then mobility will increase. Scattering will always reduce the mobility. So if scattering is less, then mobility will increase. So what really happened there? Think about it again with the clear mindset, otherwise you will not be able to understand. At lower temperature, who is dominating? Impurity scattering is dominating. So till T1 I will only think about impurity scattering. Okay. Now in the lower temperature, if I increase the temperature, then what will happen? Impurity scattering will go down. That means electron will not be affected by the impurity. So if scattering is going down, what does that mean? Mobility will increase. So in the lower temperature range, mobility will increase. Now you have reached a particular temperature. After T1 you will say that this is high temperature range. After T1 you will say that this is high temperature range, from T1 to infinity. So in high temperature, who is more dominating? Lattice scattering, right? Lattice scattering is dominating. Now in the higher temperature range, if I increase the temperature, then what will happen? If I increase the temperature, then lattice scattering will increase. If I increase the temperature, that means atoms will be vibrating more, and if they are vibrating more, that means there will be more hindrance. So lattice scattering will increase, and if lattice scattering is increasing, what does that mean? Mobility will go down. So after T1 at a particular temperature, mobility will go down. So initially it was supposed to go in this direction, and if I increase this graph, this was also supposed to go in this direction. But in the lower temperature range, impurity scattering was dominating. In the higher temperature range, lattice scattering was dominating. In the higher temperature range, if I increase the temperature, lattice scattering will increase, and because of that mobility will decrease. But in the lower temperature range, impurity scattering is dominating. In the lower temperature range, impurity scattering is dominating, and in the lower temperature range, if I increase the temperature, impurity scattering will decrease. That means mobility will increase. So this is how the graph should have gone, and in between this temperature, both of the scatterings are dominating. Like at the mid temperature, both of the scatterings are dominating. So this kind of graph you will get. Arey bhai yaar. So this kind of graph you will get. So I'm not going to write down anything. It's just that you need to think about it. If you are not able to think about it, then at least mug up this graph. The graph will go like this. That's it. Just remember it. If you are not able to understand, hopefully you should be able to understand, because I have spent roughly around 20 to 25 minutes just to explain all these phenomena and only this graph. Our target was to make this graph only. Just to make this graph, I had to explain everything, all these things. So just to make this graph, we have understood these scattering, impurity scattering, lattice scattering, and how it is depending on the temperature. And based on that, I hope you should be able to draw this graph on your own. So in the low temperature range, with the increase in temperature, mobility will increase. But in the high temperature range, with the increase in temperature, mobility will decrease. What is this high temperature? What is this particular temperature T1? It could be 100 Kelvin. For some, it could be 200 Kelvin. But for any material, it will never be greater than 300 Kelvin. What I am saying? For any kind of material, it will be always lesser than 300 Kelvin. This temperature T1 that I have written, it could be 100 Kelvin. For some material, it could be 200 Kelvin. For some material, it could be 300 Kelvin. It will never be greater than 300 Kelvin. So if I am at the room's temperature, by default, I will be at the room's temperature only. If I am at the room's temperature and I try to plot mobility versus temperature graph, what I will see? That just as I increase the temperature, my mobility will decrease only. Are you able to understand what I am saying? A very important point. This temperature T1 will depend on the material. For some material, it would be 100 Kelvin. For some material, it would be 200 Kelvin. But for none of the material, it would be greater than 300 Kelvin. That means for none of the material, it would be greater than room's temperature. So if I am at the room's temperature, which is by default, you will be at the room's temperature only. So if I am at the room's temperature and I try to increase the temperature of my room and I see how my mobility is going, so what do you see? Mobility will decrease. Say yes or no. Are you able to understand this point? So with the increase in temperature, mobility will decrease only if you are at the room's temperature or if temperature is not given. By default, if you need to take one temperature, what that would be? That would be room's temperature. So at the room's temperature, if you are already at the room's temperature, and after that someone asks you what will happen to mobility if you increase the temperature, then it will decrease only. So with the increase in temperature, mobility will decrease after the room's temperature, and before the room's temperature, it can increase. So this relation is, here mobility is proportional to T to the power 3 by 2, minus 3 by 2. Why minus 3 by 2? Because with the increase in temperature, mobility is decreasing, and here it will be proportional to T to the power plus 3 by 2. With the increase in temperature, mobility will increase. So mu is proportional to T to the power 3 by 2, and here it is proportional to T to the power minus 3 by 2. Is this graph clear to you or not? Okay. Shall I repeat everything that I said? Or you can go back to the video and watch it again. Again, in a quick manner, I will repeat. In low temperature range, impurity scattering is dominating. In low temperature range, if I increase the temperature, then impurity scattering will go down. Why impurity scattering is going down? Because electrons are moving faster and they are not being affected by the impurity electric field. That's why impurity scattering is going down. If impurity scattering goes down, then mobility increases. After a particular temperature T1, in high temperature range, lattice scattering will be dominating. The atoms will be vibrating at their place, and since they are vibrating, electrons will be colliding with those vibrations. As the temperature increases, the vibration will increase more. Electrons will collide more. That will increase the scattering, and since the scattering is being increased, mobility will decrease. That's it. This is the explanation. Within 1 minute, you will be able to revise it. By default, we will be at the room's temperature only. So as the temperature increases, scattering will always decrease, by default taking room's temperature. I have drawn the graph of mu versus T. You draw the graph of mu versus 1 by T. Mu versus T goes in this direction, mu versus 1 by T will go in this direction. So what will be the nature? This will be the nature only. The same kind of nature you will get, right? So in a rough way, I have drawn the graph, because in the examination they can ask the graph of mu versus 1 by T as well. Okay. Same graph you will get, no? From decreasing to increasing and then decreasing. From decreasing to increasing and then decreasing. So from decreasing to increasing and then decreasing. So low to high and then decrease. Low to high and then increase. Sorry. Low to high and then decrease. Low to high and then decrease. You will be able to relate it. Or you can think that if 1 by T is low, that means temperature is high. So you can think in this phenomena as well. Or just I have told you a trick that just go opposite in the graph. Low to high and then decreasing. So low to high and then decreasing. So this will be the graph of mu versus 1 by T. So anything they can ask, mu versus T also they can ask, mu versus 1 by T also they can ask. In some textbook, if you find that, sir, always in the textbook, sir, I saw that this was the graph given. So they are considering that they are starting from some particular temperature. They are not starting from 0 Kelvin. They might be starting from some 100 Kelvin or some 200 Kelvin or from room's temperature. So with the increase in temperature, it will decrease only. It could be anything. For different material, it will be different. 0 Kelvin means minus 273 degrees Celsius. So they might not be starting from minus 273 degrees Celsius. They might be starting from minus 100 degrees Celsius. So after that, it will always decrease. Because this T can be 100 Kelvin as well. What is the meaning of 100 Kelvin? 100 Kelvin means minus 173 degrees Celsius. Right? So it is different with respect to different materials. Right? And with respect to different conditions as well. It will depend on doping and all these kind of things as well. Okay, so it can be different, but it will never be greater than room's temperature. So no matter whatever the semiconductor that you are having, if you are at the room's temperature, then always with the increase in temperature, your mobility will decrease. So what may happen is that in longer run, you might forget, sir, what this was. Because this is complete theory, no, this is not numerical. So in longer run, you might forget that, sir, what I studied. Then what you can do is that you can again come back to this video and revise it. What I am saying, in longer run, you might be forgetting, look, this thing you will not be forgetting. This graph you will not be forgetting in longer run. But this graph you will be able to remember that, sir, this was the graph. But how it came, I forgot, sir, at lower temperature, who was dominating, which was dominating, everything you will forget. And you will try to read the theory. It might happen that you are not able to understand the theory as well. It happens with EDC. Every time you study EDC, you will feel like that it is a new subject. This thing I have always said about EDC. Every time you study EDC, it will feel like that it is a new subject if you don't revise it. Revision is very important in the EDC. So if you, in the worst case, if you have already forgot it, then what you can do is that you can again come back and watch this video and you will be able to understand everything. Okay? Fine. So at low temperature, impurity scattering dominates because electron collide mostly with the dopant atoms. Mobility is low, but as the temperature increases, impurity scattering decreases with temperature. So mobility also increases. At higher temperature, lattice scattering dominates because atoms vibrate more. Mobility decreases with the increasing temperature since lattice scattering increases with temperature. Okay, well and good. Yeah, there is one more formula. So let's just say because of the lattice scattering, when you are considering only lattice scattering, at that time your mobility was mu L. When you were considering only impurity scattering, at that time your mobility was mu Im. When you were considering only surface scattering, at that time your mobility was mu surface. What is surface scattering, sir? You don't need to worry about that. Only two important things are there, impurity and lattice. Those I have explained. There could be a lot of different kind of scattering as well. Those you don't need to study. So with respect to different scattering, at some point of temperature, only lattice scattering will be dominating. At some point of temperature, only impurity scattering will be dominating. At some point of temperature, only surface scattering will be dominating. So because of only the lattice scattering, your mobility is mu L. Because of only the impurity scattering, your mobility is mu Im. And because of only the surface scattering, your mobility is mu surface. Now they ask you what is the total mobility. So for that, this formula you need to apply. 1 by mu total will be 1 by mu impurity plus 1 by mu lattice plus 1 by mu surface and so on. Let's solve a numerical on this, you will be able to understand. Okay, so this is the numerical, although very rare chance that these kind of question they will ask. What they have given in a semiconductor, two scatterings mechanism are existing: surface scattering and phonon scattering. What is phonon scattering? Lattice scattering only. What is surface scattering? You don't know. Okay, surface scattering you don't know. If you want to know, like, because of the rough surface, electrons will not be able to move in a free manner, right? The surface could also be low. The surface could also be rough. So this is the scattering that will come because of the surface. Because of the rough surface, if electrons are not able to move in a good manner or in a perfect manner, then it is known as surface scattering. But you don't need to study about it. Just it is some kind of scattering that you don't know. So because of the surface scattering and phonon scattering, two kind of scattering are present. Because of the surface scattering, the electron mobility is 400. And because of the lattice scattering or phonon scattering, the mobility is 600. So effective mobility you need to tell. So what will be the effective mobility? So effectively I will use this mobility. So in some of the previous question you saw that sir electron mobility is mu n, some certain value was given, some certain value was given, mu p, some certain value was given. So they were giving this value at a certain temperature. So they have considered all these things, surface scattering, lattice scattering. After that they were giving this value. So that value 1 by mu would be 1 by 400 divided by 1 by 600. So you can simply do it. It would be from here 3 to 5 yeah, so value of mu will come out to be 240, right? It will be simply 400 into 600 divided by 1000. Yeah, so 240 centimeter square volt into second. So you can solve this equation, you will get the value of mu as 240 centimeter square upon volt into second. So this is your total mobility. All good. So very rare that these kind of questions will be asked, but still in some test series, if you see these kind of problems, you will be able to solve it. Just take the reciprocal and add it. Well and good. Okay. So this graph is also clear. Mu versus T graph is clear. N versus T graph is clear. P versus T graph is also clear. Number of holes versus temperature graph is also clear. And intrinsic carrier concentration versus temperature graph is also clear. So these graph we have seen. Now who comes into action? Carrier concentration done. Mobility done. Now who will come into action? Conductivity. So what you will see? Conductivity versus temperature graph for intrinsic semiconductor. So first we will see the conductivity of intrinsic semiconductor versus temperature graph. So what is the conductivity of intrinsic semiconductor? That is NiQ mu n plus mu p. Now how Ni is related with respect to the temperature? So that is some constant T to the power 3 by 2 e to the power minus Eg naught by 2 kT. Sir, Q is also a constant. A naught is a constant, Q is also a constant. So multiply with Q. What about sir mu n and mu p? Now sir, for mu we know two things. Mu is proportional to T to the power 3 by 2 and mu is proportional to T to the power minus 3 by 2. This will work in the low temperature range and this will work in the high temperature range. So mu is proportional to T to the power 3 by 2. So can I write down as mu is equals to mu naught T to the power 3 by 2 and mu is equals to mu naught, here mu naught 1 I am writing, here mu naught 2 I am writing, because I need to remove this proportionality sign. So if I remove this proportionality sign, some constant will come. So this is low temperature and this is high temperature. So no matter whether you put low temperature or high temperature, in both of the cases you will see that conductivity will increase with the increase in temperature. What I mean to say is that, let's just say I put a low temperature here. If I put low temperature, that means this formula I need to put. This formula I need to put. So what I will do is that Say yes or no. You agree to this point? So this we are doing at low temperature, right? This I am doing at low temperature. So what will happen is that T to the power 3 by 2 will come outside. T to the power 3 by 2 will come outside. So what I will be getting? A naught T to the power 3 by 2, 3 by 2, right? T to the power 3 by 2, 3 to the power 3 by 2, both will be added T to the power 3. A to the power minus Eg naught by 2 kt. Q is a constant, mu n naught, mu p naught, these are also constant. A naught is also a constant. So constant multiply with constant, multiply with constant. What you will get? Another constant. So this you are doing at low temperature. Low temperature. So let me know what really happened here. At low temperature as well, what do you see? At low temperature as well, what I see is that if your temperature increases, if temperature increases, this value will increase and this value will also increase. Why is that so? Because if temperature increases, this will decrease, e to the power minus x. X is decreasing, that e to the power minus x will increase. So your conductivity will increase only. Right? So your conductivity will be increasing only. So at low temperature range also it is increasing. Let's check at high temperature. So at high temperature, what I will do? E to the power minus Ag naught by 2 kt Q mu n naught T to the power minus 3 by 2 plus mu p naught T to the power minus 3 by 2. This is what you will do at the high temperature, right? Now T to the power minus 3 by 2 will come outside. T to the power plus 3 by 2 and T to the power minus 3 by 2. What that would be? T to the power 0. That would be 1 only. So A naught is constant, 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 constant. So everything is constant only. So what you are getting? Some B naught T to the power plus 3 by 2, T to the power minus 3 by 2, T to the power 0 only. So that term is gone. T to the power 0. That term is gone. What you are left with? E to the power minus Ag naught divided by 2 kt. So this is happening at high temperature. Here also you can see if temperature increases, then this value will decrease, right? And if this value is decreasing, then whole value will increase. So even at the low temperature range or high temperature range, you put the values in the formula. In both of the cases, if temperature increases, your conductivity is increasing only. Now what kind of graph you will get, that is very complex. You cannot tell. Only the nature you can tell. So how I will make the graph? I will just make the graph in this manner. A very rough graph, that's it. What it shows? That with increase in temperature, mobility will increase. Sorry, not mobility. Sorry. With increase in temperature, conductivity will increase. That's it. Okay. Nature of the graph is not very straightforward. You can see that exponential relation is there, t to the power 3 relation is there. Here only exponential relation is there, so here you can make it, but in the low temperature range as well, it will be very difficult to make. So just I have made the graph in this manner. It is just telling that it is increasing, nothing else. That's it. So your conductivity with the increase in temperature is increasing. Is that okay for you or not? Conductivity of intrinsic semiconductor. So what I did, I wrote down the formula. Whenever it comes to conductivity or resistivity, what you will do, you will write down the formula. For Ni, what I did, I wrote down the formula with the concept as well, I explained it. For mobility, what I did, I explained the scattering and then I made the graph. When it comes to conductivity, what you will do, you will write down the formula. Whether it is for N type, P type, or it is for intrinsic. Always you will write down the formula. Now you know that this guy increases with temperature. What about these two guys? So these two guys are different. First they increases, then decreases. So both of the cases I consider. When I consider the both of the cases, I got to know that in both of the cases only, my conductivity is eventually increasing only. So Ni versus T when I am making, it will be a increasing graph. Okay. What will be the nature? We don't care. If 4 options are given, we will just see that in which graph my in which graph my conductivity is increasing. So that will be the answer. Okay. So yeah, this is the graph, but another point is there. Ln rho I versus 1 by t graph I will make. What will be the significance of the slope of this graph? What I am asking, what will be the significance of the slope of this graph? Temperature is not mentioned, so by default I will take room's temperature. Room's temperature. So what is the significance of the slope of ln rho I versus 1 by t? So first, can you comment that whether it will increase or decrease? Think about it and comment whether it will increase or decrease. Like the nature will be like this or it will be like this. And then what will be the slope representing? That also you need to tell. So let's write down the formula of rho I first. What is the formula of rho I? That is 1 by sigma I, and 1 by sigma I is 1 by ni q mu n plus mu p, right? Just 1 second, guys. Yeah, sorry for the interruption, guys. So where were we? We have written down the expression of rho I. We need to find out the slope between the curve of ln rho I versus 1 by t. Okay. So this is the expression of rho I. So what I will do is that first I will solve with respect to sigma I, because for sigma I have already written down the expression, and we need to go for room temperature, right? For the room temperature, high temperature means here room temperature only. So this expression we have derived for room temperature only, no? So we need to consider the case of room temperature. So at the room temperature, if I write down the expression of sigma I, that is ni q mu n plus mu p, right? Now what is the expression of ni? A naught t to the power 3 by 2 e to the power minus eg naught by kt q mu n plus mu p. What is the value of mu n? At room temperature. So for the room temperature, what will be the scenario? Mu n will be proportional to t to the power minus 3 by 2, because after the room temperature, mobility will decrease only. Mobility will decrease only, right? So this is the expression that we are going to use. So mu n naught t to the power minus 3 by 2 plus mu p naught t to the power minus 3 by 2. So t to the power minus 3 by 2 will come outside, and this will get cancelled, and mu n naught, mu p naught, they will be constant only. So what you are left with? Some constant c naught e to the power minus q is also a constant, mu n naught, mu p naught also constant, a naught is also a constant, and t to the power 3 by 2 and t to the power minus 3 by 2 has been cancelled, right? So only you are left with some constant Eg naught divided by 2 kt. This is what you are left with. This is your sigma I. What will be your rho I? Rho I will be 1 by sigma I. That would be 1 by c naught. And if you take the reciprocal of e to the power minus x, reciprocal of e to the power minus x, what that would be? E to the power x. So 1 by c naught e to the power Eg naught by 2 kt, right? What is 1 by c naught? Again a constant. So can you write it down as rho I is coming out to be some constant, here a naught, c naught I have written. Let's write down the constant as b naught. Some constant e to the power Eg naught by 2 kt. What I need to do? ln rho I need to introduce. So both of the side I will take ln. Again ln b naught will also be a constant. What I am doing? ln b naught multiply with e to the power Eg naught by 2 kt. So ln m into n, what that would be? ln m plus ln n, right? So ln b naught plus ln e to the power Eg naught by 2 kt. So what do you see here? What you are getting? ln rho I is equals to ln b naught is a constant value that I am writing down as k naught plus ln and e will cancel each other. So what you are getting? Eg naught by 2 kt. So what do you see here? ln rho I versus 1 by t. What I need to do? ln rho I versus 1 by t. So what I can see here is that ln rho I Eg naught by 2k, Eg naught by 2k into 1 by t plus some constant. Isn't it like y equals to, this is our y axis, this is our slope, this is our x axis plus some constant. So this is the relation that I am getting. So what is our slope? This is the slope, right? The slope is representing Eg naught by 2k. 2k is a constant value, right? So the slope of ln rho I versus 1 by t represents the band gap. So if you know the slope of ln rho I versus 1 by t graph, then you will be able to know the band gap. So what is the significance? Significance is band gap. So if someone asks you with the use of the slope of L and y versus 1 by t graph, what you can find out? You can find out the band gap of the material. Are you able to understand this point? And now you can see that L and y versus 1 by t graph I am making. So if 1 by t increases, let's look at this particular expression. If 1 by t increases, 1 by t increases, not t increases, 1 by t increases. If 1 by t increases, so this 1 by t is increasing. That means this whole value will increase. Are you able to understand this point? 1 by t is increasing, not t is not increasing, 1 by t is increasing. That means actually t is decreasing. If 1 by t increases, that means t decreases. So if t decreases, then this whole value will increase. And now in e to the power x, if x is increasing, then this whole value will increase. So if 1 by t is increasing, then rho I will increase. Or you can say ln rho I will also increase. From this expression also you can see that if 1 by t increases, then this value will increase. Basically this whole term will increase. And if this whole term is increasing, then ln rho I will increase. So kind of this graph, you are not sure about the nature of the graph, but this is how you can make it. And if someone asks you at this point, if you draw the slope, at this point, if you draw the slope, what this slope will represent? So this slope m will represent Eg naught by 2k, where 2k, k is a constant, k, what is k? K is Boltzmann constant, right? 2 is a constant value. So what is this Eg naught? Eg naught is the band gap. So the slope of this particular graph is helpful in finding the band gap. This question has been asked in the examination 2 times. Ln rho I versus 1 by t graph. How it is useful? It is useful to find out the band gap. So if you just know this expression, if I have just explained you this particular graph, then would you be able to write down all these things? So don't mug up any graph. Are you going to mug up ln rho I versus 1 by t? It will be increasing. No, just write down the expression. Very simple mathematics it is. Very, very simple. So you will be able to do every calculation there, right? Let's see this question. Ln rho I versus 1 by t graph is given. Which semiconductor is having more band gap? Semiconductor A or semiconductor B? So you know that ln rho I versus 1 by t slope of ln rho I versus 1 by t curve represents the band gap. Right? So who is having more slope? A is having more slope, right? The slope of curve A is more than slope of curve B. I hope you know basics of signal system. This much basic you should know. This is the slope, this is the slope. Who is having more slope? If you move in this direction, the slope will keep on increasing, right? So the slope of A is more than the slope of B. If slope of A is more than the slope of B, what does that mean? Eg naught by 2k will be more than the, one second guys. Eg naught of A will be more than Eg naught of B. Yeah, so what I was saying, the slope here is more. Slope for curve A is more than the slope for curve B. If slope here is more, what does that mean? That means Eg naught of band gap of curve A will be more than the band gap of curve B. Right? Very, very simple thing. Very straightforward. Band gap is more. Okay. So from here you can see that ln y versus 1 by t will represent the band gap. If slope is more, that means band gap is more. So here the slope is more, here the slope is less. So if this slope is more, that means band gap of A will be more than the band gap of B. This is also a gate VIQ only. Okay, let's write down in a better manner. Band gap of A will be more than the band gap of B. And here I will write down Eg naught of A will be greater than Eg naught of B. Now this graph is very, very interesting. You need to keep your concentration again here, and then only you will be able to understand. What we are going to do? We are going to plot conductivity versus temperature graph only, but for n-type semiconductor. For n-type semiconductor, we are going to draw conductivity versus temperature graph. So for n-type semiconductor, n is mostly very, very greater than P. What does that mean? That means sigma will be n q mu n mostly. Say yes or no. So you know the graph of n versus t, you know the graph of mu n versus t as well. What I mean to say is that, have you drawn the graph of n versus t? Yes, where I have drawn? N versus t. This is the graph of n versus t. Have you drawn the graph of mu n versus t as well? Yes. This was the conductivity for holes as well, for the electrons as well. For both of them, the same graph will happen. And when it comes to conductivity, there is no difference between intrinsic or extrinsic. Intrinsic semiconductor or n-type semiconductor or p-type semiconductor, everyone will have the same mobility, right? All the holes will have the same mobility, all the electrons will have the same mobility. So here I did not say that it is intrinsic or extrinsic, but for the electrons, for electron concentration, here I said that it is n-type, right? Here I said that it is intrinsic. So here I have to differentiate between intrinsic and n-type, but when it came to mobility, I do not have to differentiate. Then I came to conductivity. So in conductivity, here we talked about intrinsic. So this was also about intrinsic only. Ln rho I. Rho I means intrinsic only. So everything is going for intrinsic only as of now in this particular scenario. Now we will move to extrinsic. So in extrinsic, we are talking about n-type semiconductor where n is very greater than p. So sigma is equals to n cube mu n. So do you know the graph of n versus t? Yes. So in a rough manner, I am making the graph. This is graph of n versus t. And do you know the graph of mu n versus t? Yes. So this was a certain temperature, and I am saying that at room's temperature, this thing is happening. After that, it is reducing. So where will be room's temperature? This will be the room's temperature, because you know that at room's temperature, most of the electrons will be ionized. Most of that donor level electrons will be ionized. So if this is the T1 temperature in this particular graph, then in this particular graph, this will be the T1 temperature. This T2 temperature is very high. This T2 temperature is very high. So this is the T1 temperature here, and this is the T1 temperature here, right? All good. So in the initial, what will happen? If the temperature increases, n also increases and mu n also increases. So both are increasing, so graph will increase only. Aggressively it will increase, right? After that, what is happening? After T1, here this is decreasing, mu n is decreasing, and this is constant. One factor is constant and one factor is decreasing. What does that mean? Decreasing graph multiply with constant. What does that mean? The graph will decrease only. After that, what is happening? Increasing graph and decreasing graph. I am talking about at T equals to T2. This is the T equals to T1 at room's temperature. But if the temperature becomes very high, so if the temperature becomes very high, then what will happen is that your semiconductor will become intrinsic semiconductor. And in the intrinsic semiconductor, the conductivity always increases. So conductivity will always increase. Did you understand this graph or not? Conductivity of n-type semiconductor we are putting. Conductivity of n-type semiconductor we are putting, which is n q mu. For n versus temperature graph, we already know. What is n? N is the concentration of electrons. So how the concentration of electron will increase with respect to the temperature? So first they will get ionized and then they will become constant. So when they are getting ionized, along with that mobility is also increasing. So this is how the graph is going. After a certain temperature, at a particular certain temperature, after that what is happening? After that temperature, mobility is decreasing, but your ionized concentration becomes constant. So mobility, this factor is decreasing, this is constant, Q is already constant, so this will decrease. At a very high temperature, what happens? At very high temperature, what it will become is that it will become intrinsic, right? What was this, John? This was the intrinsic, this was intrinsic region. What this was? This was the extrinsic region. And what this was? This was ionization region or freeze out region. So mostly your device will be working in this particular region. So for n-type semiconductor, your conductivity will decrease with increase in temperature. If temperature increases, your conductivity will decrease because you will be working in this extrinsic region only. This is the extrinsic region, and what this was? This was your ionization region. Did you understand this point or not? For T greater than T2, I am not writing down the theory for this. Okay, I am not going to write down the theory. You have to understand on your own. So what I will do is that I will make rough graphs so that you would be able to relate. So what I will do here, only I will make the rough graphs. So n versus T graph I will make, and mu versus T graph I will make. So n versus T graph if I make, I know that it will increase, then saturate, and then increase drastically. This temperature was T1 and this temperature was T2. And here at T1 temperature only, this was n versus T, and this was your mu n versus T. So here at till T1 temperature it increases, but after that it will decrease only. Always it will keep on decreasing. Always it will keep on decreasing. So it will just keep on decreasing. Mobility will keep on decreasing, because if temperature increases, the atoms will vibrate more, scattering will be more, and mobility will decrease. So here it will keep on decreasing, but after T2 temperature, what will happen? A lot of carriers will be there. A lot of carriers will be there. A lot of electrons will be there. And since there are a lot of electrons, then conductivity will keep on increasing. And we are actually going into intrinsic region. And for intrinsic semiconductor, we know that conductivity always increases with respect to the temperature. So basically this relation we will start to follow. So this kind of graph we will get. What about this graph? Versus 1 by T. So how will you start? From the top, go down, from the top go down, and then again increase. I am working in this direction, right? When I am making sigma versus T, I will work like this. When I am making sigma versus 1 by T, now I will work like this. So from the top, starting from the top, go down, starting from the top, go down. Once you have reached to the below point, then again you increase, then again you increase, then again you reach to a 1 point, again you reach to 1 point, and after that again you decrease, after that again you decrease. So in this manner it will decrease. It will not decrease very drastically, slowly it will decrease. So this kind of graph you will get. Again, very important, very soon this graph is coming in your examination. Sigma versus 1 by T for n-type semiconductor, very soon it is coming, because it is given in Donald A. Neiman. And from that particular book, all the question comes. So whatever that is there, unsolved example, solved example, whatever that is there, whatever that is useful for us, everything we are going to study in this course. Don't worry about that. So you will not have to read that book, but whatever that is available in that particular book, I will make sure that comes in your notes. Okay, so this kind of graph is already given there, so surely it is coming in your examination very soon. Is that clear to you or not? All good? All fine? So yeah, I hope that graph is clear. Similar graph will happen for p-type semiconductor as well, that we are not making. For p-type semiconductor, what will happen? P, Q, mu P. So this graph will be same. Sorry, which graph? This graph will be same. In place of n, you just need to replace P, and mu P, this graph will also be same. So ditto the same graph you will get. Ditto same graph, everything will be same. So we are just studying for n-type semiconductor. For p-type semiconductor, everything will be same. Just in place of electrons, you will replace holes. That's it. Because their majority charge carriers are hole, not electrons. All good? All fine? So this graph is also done. Now mobility versus doping concentration. Mobility versus doping concentration. So this was our n-type semiconductor. So now what we are doing, we will just keep on increasing that doping. So let's understand with the example of n-type semiconductor. So what we are doing, more and more impurity we are putting. So if we put more and more impurity, what will happen? More and more positive charge will come. And if more and more positive charge will come, that means impurity scattering will increase. And if impurity scattering increases, or what may happen, a lot of atoms will also come. Like if I am putting Nd, that means I am putting more atoms. If more atoms are coming, that means phonon scattering will also increase. You are putting the impurity. If you are putting the impurity, that means because of the positive sign, what will happen? Impurity scattering will increase. You are putting the atom as well, right? You are putting the phosphorus atom. Because of that, what will happen? The phonon scattering the lattice scattering will also increase. So effectively, more atoms means more scattering. And if there is more scattering, what does that mean? Mobility will decrease. So mobility will decrease. There you go. Understood? More doping means more atoms. More atoms means more scattering. And if there is more scattering, what does that mean? Mobility will decrease. So scattering will always reduce the mobility. Scattering will always reduce the mobility. So this is what have been written. Initially from low to medium doping, impurity scattering keeps on increasing, so mobility falls. At very high doping, impurities are already everywhere. Adding more doesn't change much of scattering. So yeah, so scattering will saturate basically. If you keep on adding up, impurities, then already impurity scattering is already very high. So mobility will keep on decreasing, and then after that it will saturate. Almost it will saturate. Okay. Basically what I am doing is that I am adding up the impurities. More and more impurities. So at some point the impurity scattering will not be increasing more. Like already it would have reached to its peak. So if scattering has reached to its peak, that means scattering is not increasing more. it is already very high. That means mobility is already very low. So it will keep on decreasing, and after that it will, at some point it will saturate. Okay, so this kind of graph you will get. Just remember the graph, that's it. In the examination, what will happen is that they will make some graph and then they will ask which of the following graphs are correct. That's it. So mobility will decrease with respect to doping concentration. All good, all fine. Resistivity and conductivity versus doping concentration. So we have seen the mobility. We have seen the mobility. Now we are going to see resistivity and conductivity. So what is the formula of conductivity? This is conductivity, this is resistivity. That is NdQ, or you can write down NQ mu. NQ mu. We are taking the example of n-type semiconductor. Okay, we are taking the example of n-type semiconductor. Now someone will be saying that, sir, why you are not studying it for intrinsic semiconductor? We will not study these graphs for intrinsic semiconductor because doping concentration, doping will be done in extrinsic only, no? So you can study these graphs for n-type or p-type. This graph also for n-type or p-type. The graphs which could be understood for n-type, p-type and intrinsic, those are these graphs. So here sigma versus 1 by t, and here also you can see that sigma versus t. So this was for intrinsic, this was for n-type. Similarly also here also for mobility, for all three kind of semiconductor, the graph will be same. Intrinsic, n-type, p-type, for all of them mobility graph will be same. Here this was for n-type and this was for, this graph was for intrinsic. So intrinsic, n-type for everyone, intrinsic, n-type for everyone. For everyone means for n-type and p-type only, because we are looking at doping concentration. That means doping is done only in n-type and p-type. So this is the graph of mobility. Let's just say this is for n-type. This is for n-type. How will I make the graph for p-type? Will it be from here to here, or it will be from here to somewhat like this? Basically it will be starting from here more than this or lesser than this? Lesser than this, right? Because mu n naught value is always greater than mu p naught value, because mobility of electrons is greater than the mobility of holes, right? In this graph as well you can do the same thing. In which graph? In this graph. If I say this graph I am making for electrons, if this graph I am making for electrons, then the graph of holes will go like this, or it will go like this. It will go like this, right? Because mobility of electrons are more than the mobility of holes. So here also you can say that, so this particular graph is for n-type semiconductor and this particular graph is for p-type semiconductor. Okay. Next, what we were seeing? We were seeing conductivity versus doping concentration. Conductivity versus doping concentration. So here I will make the graph only for n-type, not for p-type. Sir, why not for p-type? We will tell you later on. In the next lecture, you will understand why we are not drawing for n-type here. Sorry, why we are not drawing for p-type here. Okay, only for n-type we will draw. So what will happen? As the doping concentration increases, this n value will increase, right? As the doping concentration increases, this n value will increase, but this mu n value will decrease. This mu n value will decrease. As the doping concentration increases, this mu n value will increase and this value will increase. This guy is more dominating. Okay, who is more dominating? N is more dominating. So increasing is more, decreasing is less. Sir, why it is more dominating? Practically it is found that this guy is more dominating. So basically your conductivity will increase. And just think about it, no? If we are doping, why we are doping? To increase the conductivity only, no? So if we are doping, then conductivity should increase, no? And what about the resistivity? They are inverse of each other, so resistivity will decrease. A very rare chance that these graphs will be asked, because they are not completely correct. They are true only for n-type semiconductor. N-type. This is also true for n-type. Sir, why you are making it then? Because it is given in Niemann's book. That's why we are making it. Otherwise, I would have surely avoided this graph. Or some people will also have a doubt that, sir, if you have given the graph of mu versus doping concentration, why you did not give the graph for sigma versus doping concentration? Why you left that graph? It is given in the Niemann's book as well, and people will have a doubt as well. That's why I am making this graph. There is very rare chance that this graph will be asked, because for p-type semiconductor it would be different. In the next lecture, we are going to study a topic which is called as minimum conductivity condition. So in that minimum conductivity condition, you will see that in p-type semiconductor, if I do the doping, so at a certain doping you will get the minimum conductivity, and after that it will increase. But in n-type semiconductor, always the conductivity will keep on increasing. Okay, why we were doping? We just go to the first lecture. In first lecture I told you why we are doping, because we wanted to increase the conductivity. So if we wanted to increase the conductivity, yeah, it will increase, right? So someone will say that, sir, with the increasing of doping concentration, mu n is going down. No, but n is increasing. So who is more dominating? N is more dominating. Sir, what is the reason? No reason. There is no particular reason that, sir, why n is dominating. No particular reason is there. It is just dominating, so it is dominating. This is what have been written here. At low doping, Nd is very small, so conductivity is very low. At moderate doping, Nd increases, so conductivity increases rapidly, even though mobility decreases somewhat. At very high doping, mobility drops strongly due to impurity scattering, so conductivity rises slowly or even can saturate. Basically, at very high doping, what will happen is that this mobility can drop, right? This mobility can drop, but N will keep on increasing. So what may happen is that it can even saturate, or it may rise slowly, but it will never happen that conductivity is going down. What I am saying is that at very high doping, this mu n will rise, this mu n will drop significantly. At very high doping, this mu n will drop very significantly, but this n will keep on increasing. Again, this n is dominating only. Okay, so it will not happen that, sir, conductivity will decrease. No, conductivity will not decrease, but the rise will be slow. Rise may be slow. The rise may be slow. At very high temperature, the rise may be slow. Here it is rising rapidly, but at very high temperature, the rise may be slow. But it will never decrease, that I am telling. Here also, the decay may be small. The decay may be slow. But it will always be decaying. It will always be increasing. That's it. Is that clear to you? Look, these graphs are very practical. Like understanding it with respect to theory is very difficult. Although somehow we are understanding it. But these are very practical graph. For different material, different kind of graph you will be getting. But only thing is you can comment on the nature. The nature is always increasing. That's it. This is the nature. Here the nature is always decreasing. Why is that so? Because conductivity and resistivity both are inverse of each other. So in our book, in Niemann, these two graphs are made. That's it. So directly I have made these graphs. Okay. But very rare chance that this will be asked. So don't focus much on this. Focus on the previous graph that we have made. This graph is very important. This graph is very, very important. This particular thing is very important. This graph also very important. These graphs are very important. Scattering is also very important. These graphs are also important. So one of the graph can be asked. If they are framing good question from basic semiconductor physics, then they can ask questions on the graph. More graphs are there, but that we will see in the next lecture. Okay. So which graph is left? Vd versus mu e. This expression we have written. So Vd versus E graph I will make. Mu versus E graph I will make. So a few more graphs are left, but majorly whatever the graphs are there, that we have already seen. So don't feel like that, sir, how we will remember. Concepts are there. Try to remember the concepts. Okay. And these are some good concepts that, okay, for a particular temperature it will rise and then saturate and then again rise. So these are like good graphs. This graph is very good. This graph is also very good. And if you know these two graphs, then surely very easily you will be able to make the graph of conductivity as well. Similarly for intrinsic type of semiconductor. So I have spent more than enough time, 1.5 hours on these graphs. So I hope you would have understood everything. Just in the last graph here I said that it will increase always, but no, not always increase. Basically it will never decrease, it will always increase only, but the speed of increase may be slow. Okay, so what it is written is that at very high doping, mobility drops strongly. Mobility will drop strongly due to impurity scattering. So conductivity rises slowly or even can saturate. But notice the word rises. So it will always rise. It can saturate or it can rise, but it will never decay. So if this kind of curve is coming in the examination, you will only see that in which of the graph there is no decay. So if there is no decay, that answer will be correct. All good, all fine. let's meet in the next lecture. I hope there is nothing else. Yeah, let's meet in the next lecture, and in the next lecture we will see some graphs and whatever the topic is left that we are going to cover. After that we need to study Fermi direct distribution, and after that we will study low level injection and continuity equation, and after that our chapter will be completed. Okay then, yeah, so let's meet in the next lecture. Thank you very much. Happy learning. Hi everyone, welcome back. So in the last lecture we were looking at some graph, right? So with respect to conductivity, carrier concentration and mobility versus temperature graph we have made. Along with that, mobility and conductivity versus doping concentration graph also we have made. Now another expression we studied, what that was? Drift velocity versus electric field. So what we studied, that your drift velocity is proportional to electric field, and when you remove this proportionality sign, what do you get? Mobility. So this expression we have already studied, right? Vd is equals to mu e, and Vd is proportional to E. What does that mean? That means between Vd and E there should be a straight line. Between Vd and E there should be a straight line, and since mu is a proportionality constant, so mu should be constant. But your happiness will stop here, because initially when you give more electric field, let's just say this was your semiconductor and there was an electron. We are talking with respect to electron, so we will be talking about the drift velocity of the electron. So if I give more electric field, if I was increasing the voltage here, if I am increasing the voltage, what does that mean? Electric field will also increase. Why is that so? Because E is equals to dV by dx, or you can call it V by L, right? If the length is L. So if V is increasing, electric field will also increase. All these formula we have already seen, right? So if voltage is increasing, then electric field is also increasing. If electric field is increasing, that means what is the force? F equals to QE. That means this electron is going through more force, because electric field increases, then force increases. So in this opposite direction, this electron is feeling more force, and if it is feeling more force, what does that mean? Its velocity will be more, right? Because if electron is feeling more force, then its velocity will be more. It will generate more velocity. So yes, with the increase in electric field, that means with the increase in voltage, your velocity of the electron will increase. Your drift velocity of the electron will increase, right? And it will increase proportionality. Vd is proportional to E. In that manner, it will increase. But since electric field increases, what will happen? More and more electric field means more and more velocity. But there is some scattering, because this electron is not free. There are silicon atoms. If your electron is gaining more energy means voltage is more, electric field is more, force is more. If force is more, that means energy is more. So if your electron gets more energy, then what will happen is that it will try to accelerate faster. So if it tries to accelerate faster, what will happen is that there are silicon atoms. Now this electron will collide through these silicon atoms. So eventually it tried to go linearly, although velocity will increase only, because you are increasing the electric field. Although the velocity will increase only, but it will increase slowly now, because the scattering has increased. Are you able to understand this point? So it will increase slowly. In that manner it will increase. And if you just keep on increasing the electric field, at some time the velocity will saturate. So velocity will say that I cannot increase beyond a certain limit. Like, it's not that, sir, velocity will reach infinity. Velocity cannot reach infinity. Velocity will not keep on increasing, because as you apply more and more electric field, more and more collisions will happen, and more collision will happen. That means what will happen is that your velocity tried to increase so much faster, but it was not able to increase so much faster, because actually this mobility is going down. Why mobility is going down? Because scattering is increasing. If electron is trying to move faster, scattering will increase, so mobility will go down. So although this part is increasing, electric field is increasing, but mobility is going down. So what will happen is that slowly it will increase, but it will increase slowly only, and after some time it will saturate. So Vd will increase, then increasing slowly, and after some time it will saturate. So till this particular point it was rising linearly. After that, what really happened was, it was rising in under root manner. Basically here Vd was proportional to E. What I would say, here Vd was proportional to E. Here Vd became proportional to under root E. and here Vd became proportional to, I would write down E in the other manner. So here Vd was proportional to e to the power 1. I would call it e to the power 1. And here Vd was proportional to e to the power half. And here your Vd is proportional to e to the power 0. Why to the power 0? That means with the increasing E, there is no effect in the drift velocity. Even if your E is increasing, even if your E increases, Vd remains constant. So slowly your drift velocity will saturate. Is that clear to you? So in the first scenario, Vd is proportional to E. What I am saying? Vd is proportional to E. Vd is proportional to E. So mu will be constant. Mu will be constant. In the second scenario, Vd is proportional to e to the power 1 by 2. Then mu, what will be the relation between mu and electric field? What I am saying, Vd is equals to mu E. Vd is equals to mu E. In this particular region, I am saying that Vd is proportional to e to the power 1 by 2. So Vd is proportional to e to the power 1 by 2. When I remove the proportionality sign, I am taking one constant, that is k. So Vd is proportional to e to the power 1 by 2. That would be mu E. So this is e to the power 1, this is e to the power minus 1 by 2. So what you are getting? Sorry, this is e to the power 1 by 2 and this is e to the power 1. So what you are getting? E to the power minus 1 by 2. So mu is equals to k into e to the power minus 1 by 2. So mu is proportional to e to the power minus 1 by 2. So basically mu will decrease. Mu will decrease. In what manner it will decrease? It will decrease in this manner. So here your mu was not depending on electric field. So mu was proportional to e to the power 0. But now your mu is proportional to e to the power minus 1 by 2. And here what is happening? Vd is proportional to e to the power 0. So what is the expression? This is the expression. Vd is proportional to e to the power 0. So if you remove the proportionality sign, some constant will come. Mu is equals to e. E to the power 0 is 1 only. So basically you can say that Vd is constant. So if Vd is constant, that means it is some constant value. So what you can see? Mu is equals to k by e. So mu is equals to k e to the power minus 1. So you can say that mu is proportional to e to the power minus 1. So after that mu will keep on decaying because scattering is increasing. If scattering increases, then mu will keep on decaying. So now mu will become proportional to e to the power minus 1. And here, if we write down with respect to Vd, then how we will write down? So first Vd was proportional to E, then Vd became proportional to e to the power 1 by 2, and then Vd became proportional to e to the power 1 by 2, and then Vd became proportional to e to the power 0. So 1 by 2 0, 0 minus 1 by 2 minus 1. So this graph will be very easy to remember. Vd versus E graph. Vd first it will rise linearly, but after some time what will happen is that scattering will increase, so it will rise sublinearly. What this is known as? This was your linear region. Okay, linear region. This is known as sublinear. Sublinear. It tried to become linear, but now it is increasing slowly, not in a linear manner. Because if it was linear, then it would have gone somewhat like this. But now it is not going somewhat like this. It is going in the slower manner. So slower manner means Vd is proportional to e to the power 1 by 2, and this is known as saturation. This region is known as saturation. So this graph is very important. Okay, very important graph to understand any IV characteristics. So IV characteristics also we will discuss. So any particular device that you are having, whether it is a semiconductor, it is diode, MOSFET, VGT, any kind of device that you are having, without this particular graph, you cannot understand any device. For understanding any device, you need to know this particular graph. So you remember the logic or not, I don't care. What is the logic? That first it will rise linearly, then scattering will increase, mobility will decrease. Even if you forget this logic, it is fine, but the nature of graph should be clear. Rises linearly, then sublinear, and then constant. Whatever the logic is there, after 5 days you will forget it. If you don't revise it, then after 5 days you are going to forget the region. That what was the actual region, why it was rising linearly, then sublinearly, and then saturate. You will forget the region, scattering and everything you will forget. But the nature should be clear to you, that how the graph will rise, linear, sublinear, and then saturate. So that nature you are not going to forget. Okay, what was the reasoning, what was the theory, all this theory will be written and you will be forgetting it. I know that. Okay, I have also been a student. If you don't revise EDC, then all this theory you will forget. but this waveform you are not going to forget. You cannot forget the waveform. Okay, and reasoning also is clear. What is the reasoning? The only reasoning is that if you keep on increasing the electric field, that means electron will feel more force. If they are feeling more force, they will try to accelerate very faster, and if they try to accelerate very faster, they will scatter more, and since they are scattering more, so mobility will decrease. So if in the initial manner mobility was constant, but since your electron tried to go very fast, your mobility started decreasing. Although electric field is increasing, but mobility is decreasing. So now initially it was rising linearly, but now it will rise sublinearly, and eventually what will happen is that electron will gain so much of energy that mobility will start decreasing so much. So eventually your velocity will saturate. So increase, sublinear, and then saturate. A very, very important graph, and all the reasoning and everything have been written here. Okay, so this graph, when you are making this graph in your notebook, just make sure that you make it in a very good manner. Now let's write down the typical values. So this value is for silicon, this is roughly around 10 to the power 3 volt per centimeter. You don't need to mug it up. Okay, if you can remember, you can remember, but no need to mug up. If some question is coming, they will give this data, and this value is roughly around 10 to the power 4 volt per cent. 10 to the power 4 volt per centimeter. Okay, so when your electric field is 10 to the power 3 volt per centimeter, till that point it is rising linearly. When it is between 10 to the power 3 to 10 to the power 4 volt per centimeter, at that time it is rising sublinearly. And when your velocity becomes, when your electric field becomes 10 to the power 4 volt per centimeter, after that it will saturate. Okay, and another thing is that this velocity is 10 to the power 7. As far as I remember, it was 10 to the power 7 only, right? 10 to the power 7. So this saturation velocity is, for silicon it is 10 to the power 7 centimeter per second. Again, you don't need to mug it up. These values, even if you forget, no need to worry about that. But the nature should be clear. Vd is proportional to e to the power 1, e to the power half, e to the power 0. If you are able to write down this one, then surely you will be able to write down this one as well. All good, all fine. Let's read out the theory. You can read the theory on your own. In silicon at a low electric field, the drift velocity of carrier increases linearly with the applied electric field according to Vd is equals to mu e, where mu is constant. Mobility remains nearly constant in this region. As the field increases beyond 10 to the power 3 volt per centimeter, carrier will gain higher kinetic energy because between the collision and undergo more frequent scattering with the lattice through optical phonon emission. Now you are not able to understand this optical phonon emission. What is the meaning of this optical phonon emission? You will just understand that it is nothing but lattice scattering. Okay. Optical phonon emission means it is nothing but a lattice scattering. So there will be more and more lattice scattering. Okay, because electrons are trying to move fast, but atoms are vibrating. Since they are vibrating, they will collide. If they are colliding more, then mobility will decrease. So this is what has been written. This enhanced scattering effectively reduces the mobility. So drift velocity is no longer rising linearly, but instead it will rise more slowly, approximately proportional to under root E. When the field is reaching above 10 to the power 4 volt per centimeter, the scattering rate will become so strong that additional energy means even if you are increasing the electric field, even if you are increasing the potential, the field is quickly dissipated to the lattice via phonon emission. That means there is no effect of the increasing of the field. So what will happen is that there is no further acceleration. As a result, the drift velocity will be saturating at nearly constant value of 10 to the power 7 centimeter per second, known as the saturation velocity. Okay, so this is the complete theory that has been written. So this graph is clear to you, Vd versus E graph. All good, all fine. Let's solve some question. So for a silicon semiconductor, electric field is changing from 4000 volt per centimeter to 8000 volt per centimeter. The mobility of electron will be multiplied with the factor of what? Silicon is given. Electric field is changing from 4000 to 8000. So when your electric field is between 10 to the power 3 volt per centimeter to 10 to the power 4 volt per centimeter, right? Although data should be given in the examination, data would be given, but all these data I have written for silicon, so I asked the question on silicon only. So here I did not give the data, but in the examination they will give the data that in this particular region the electric field is rising sublinearly. What does that mean? That your mobility will be e to the power minus half. Say yes or no, right? Your mobility will be proportional to e to the power minus half, right? In this region, mobility will be proportional to e to the power minus half. So now what they are saying, electric field is changing from 4000 to 8000. So mobility of electron will be multiplied with what factor? So your mu2 is the later on mobility. Basically, when electric field is 4000 volt per centimeter, at that time your mobility is mu1. When your electric field is, this I will call E1, this I will call E2. When your electric field is 8000 volt per centimeter, at that time your mobility is mu2. Your mobility of electron will be multiplied with what factor? So what I will find out? Mu2 by mu1. That will be equivalent to E2 to the power minus 1 by 2 divided by E1 to the power minus 1 by 2. So that can be written as under root E1 by E2, because this is 1 by under root E1 and this is 1 by under root E2. So E1 will go upward, E2 will go downward. So mu2 by mu1 is coming out to be under root initially 4000 divided by 8000. So what we are getting, 1 by 2, 1 by under root 2. So mu2 is mu1 by under root 2. So this is the answer. So basically your mobility is multiplied with the factor of 1 by under root 2. Your mobility is multiplied with the factor of 1 by under root 2. That would be the answer. All good? All fine? Very easy question. Although this data should have been given, but since we have wrote down the data for silicon only, so I use this data here directly. Let's solve more questions. A DC volt of 10 volt is applied across a n-type silicon bar having a rectangular cross section area. Having a rectangular cross section. Length is 1 centimeter shown in the figure. The donor doping concentration is Nd and mobility is given. Find the average time taken by electrons to move from one end to the other end. What you need to find? Time you need to find. Average time from here to here. What is time? Time is equals to speed upon distance. Oh, sorry. अरे भाई, I am a Hindi medium student. Distance upon speed. Time is equals to distance upon speed. Like very, very disappointing, right? I have to write down the formula. Time is equals to distance upon speed, or you can call it velocity. So you know that the electron, if the electron is going from here to here, it needs to cover the distance of 1 centimeter. But you need the velocity. So can you find out what you need to find? Average time. So distance upon average velocity. So can you find out the average velocity? Yes. What is average velocity? Average velocity is Vd. What is the formula of Vd? You know. Vd is equals to mu e. This is the only formula we know. Mu we are having. Do we have electric field as well? Yes. Because what is the potential? 10 volt. What is the length? 1 centimeter. So what will be the electric field? V by L. I told you. Across, what is electric field? Electric field is minus dV by dx, right? Minus dV by dx. So let's just say this is your x equals to 0 and this is your x equals to L. So when you are going from x equals to 0 to L, how much your voltage is changing? From 10 to 0. And you are going from 0 to L. So minus L you will put here. So 10 by L, right? So 10 by 1 centimeter. 10 by 1 centimeter. So 10 volt per centimeter. This is your electric field. Okay, and are you having the value of mobility as well? Yes, mobility value is also there. So what will be your Vd? Vd will be, mobility is also given in centimeter square, electric field is also in centimeter square only. So mobility is 10 to the power 3 into 10. And what will be the unit? Meter per second, centimeter per second, right? So what you are getting? 10 to the power 4 centimeter per second. This is your drift velocity. So here what you will do? 1 by centimeter upon 10 to the power 4 centimeter per second. So what is the answer you are getting? 10 to the power minus 4 seconds. This is the average time. This is the time taken. Microsecond they are asking. So in microsecond what it would be? Your answer is 10 to the power minus 4, right? So in microsecond can you convert it? Yes, I will multiply by 100 and divide by 100. So what I will be getting? 100 microsecond. because if I multiply by 10 to the power minus 2, I will have to divide by 10 to the power minus 2 as well. So 1 by 10 to the power minus 2 will become 100 and 10 to the power minus 6 will become micro. Answer is 100 microseconds. So this will be the answer. Very, very simple question. In the EDC, always you just see that, sir, what we need to find. We need to find the time. Time is distance upon speed. Distance I already know. This is not the collision time. Don't feel like collision time or anything. No, nothing is there. Collision time, all these things are not there. Collision time is a separate, different thing. What they are asking, they are just asking that average time taken by the electron to reach from one end to the other end. So distance is 1 centimeter divided by the drift velocity. Drift velocity will be mu e. What is the value of mu? Mu value is 10 to the power 3. What is the value of electric field? That is 10 centimeter per second, right? So 10 to the power 4, and then then I put it, I get the value of 100 microsecond. Let's solve next question. You try doing it on your own, you will be able to do it. A piece of silicon is doped uniformly with phosphorus with donor concentration of 10 to the power 16. Donor concentration is given as 10 to the power 16. The expected variation of mobility versus the donor concentration is given. I told you, mobility versus donor concentration. As the donor concentration increases, the mobility decreases. So yeah, this is happening. So the graph for electron is also given, the graph for hole is also given. Now what they are saying, assuming full dopant ionization at 300 Kelvin, the graph is given. Using this data, determine the approximate value of mobility mu n at Nd 10 to the power 16. Okay. When your Nd is 10 to the power 16, 1 e plus 16, what is the meaning of that? 10 to the power 16 only. Okay, this is your 10 to the power 16. When your Nd is, when your doping concentration is 10 to the power 16, at that time, what is the value of mobility? The value of mobility is 1200, 4 electrons, and 4 holes, it is 400. Okay. And calculate the conductivity sigma of the silicon crystal. Assume electrons are the majority charge carriers and holes can be neglected, and yeah, okay. So what is the formula of conductivity? I know that this is an n-type of n-type semiconductor. In n-type semiconductor, electrons and holes will be drifting in the opposite direction. So because of them, the current will be in the same direction. So effective conductivity I can write down nq mu n plus pq mu p. Now you know that what is the formula of n? Sir, the formula of n is nd by 2 plus under root nd by 2 whole square plus ni square. Now in this question, ni value is given? No. So by default, if ni value is not given, you will assume that ni is pretty low. Ni is very lower than nd. If ni value is not mentioned, by default you will take that doping concentration is very high. So n will be approximately equals to nd only. And second line they have given that holes can be neglected. Or how you would have find the holes? Ni square by nd. But again you are not having ni value, so you will have to ignore the minority carrier concentration. So if ni value is not mentioned, then you will only consider the majority charge carriers. You will not consider this particular value. This particular value you will put to 0. Basically you will say that, sir, minority charge carrier concentration will be 0. Holes will be 0. I will only consider the electrons. Now how many electrons would be there, sir? So the number of electrons will always be equals to the dopant concentration, considering 100% ionization. Here it would be written full dopant ionization. So what they have considered? They have considered full dopant ionization. That means all that 10 to the power 16 atom, all that 10 to the power 16 atoms is giving you one free electron. So forget about the intrinsic carrier concentration, forget about everything. Whatever that donor atom that you are putting, all those donor atoms are giving you free electrons. That's it. This is what you will assume. So this 10 to the power 16 free electrons you are having. So your n is equals to nd here. So what will be the answer? Answer will be nd q mu n. What is the value of nd? 10 to the power 16. Everything is going into centimeter. What is the value of q? 1.6 into 10 to the power minus 19. And what is the value of mu n? Value of mu n, from here I can see that it is 1200. Okay, so what you can see is there here 10 to the power 3, 10 to the power 19, 1.6 into 1.2. That answer you are getting. 1.6 into 1.2. So 1.92. So from here, conductivity you are getting 1.92 Siemens per centimeter, because everything is there in the centimeter. Just I am putting the value. What is the value of Nd? 10 to the power 16. What is the value of Q? 1.6 into 10 to the power minus 19. What is the value of mu n? 1200. So what you are getting? 1.6 into 1.2, that would be 1.92. So this would be the answer. Do we have more questions? No. Let's see the IV characteristics. So this is any random type of semiconductor. It could be intrinsic, it could be N type, it could be P type. So any random type of semiconductor is there. Across this semiconductor, you have put a battery of V, and now you are measuring this current. So with respect to this voltage V, how this current will go? Any kind of device that you make, whenever you go into the industry, wherever you go, any kind of device that you are having, your first target will always be to measure this IV characteristics. That if I increase my supply, this is the supply, that means this is your power. If I increase my power, how my current will increase? This is not about semiconductor. Even if you make diode, you make BJTs, you make MOSFET, or you make FinFETs, you make any kind of devices in your industry, wherever you go, I create something out of the box. My first target will always be IV characteristics. That with respect to the voltage, how much current I am getting. So let's try to find out the answer here. So what do you know? What is J? J is equal to sigma I. So we are considering any random semiconductor, not N type, P type, nothing. For any particular random semiconductor, J is equal to sigma I. What is your I? I will be J into A. So that would be sigma E into A. What is the formula of sigma? N Q mu E. What is N here? Number of electrons? No. N is charge carrier. It could be anything. N is simply charge carrier, right? Here, what is the N? N is charge carrier. It is not free electron. It could be anything. Any charge carrier it is. Okay. So this is your I. Now what do you see? I is equal to NQ. Can I put this as VD? Yes. So number of charge carriers for a particular semiconductor, that would be constant, right? If it is intrinsic, then N will be equal to Ni. If it is N type, then N will be equal to approximately equal to Nd. And if it is P type, then N will be approximately equal to Na, right? So there my majority will be holes. In N type, majority will be electrons, and in intrinsic, holes and electrons will be constant. Both will be same, right? So this will be a constant value. Q is already a constant, and cross section area will also be constant. Basically, you are not changing the semiconductor, no? So for the semiconductor, cross section area will also be constant. So you can directly see that I is proportional to VD. So this is the first relation that I am getting. I is proportional to VD. Now what is the next thing? What is V? V is equals to E by L. Let's just say the length of this particular semiconductor is L. So V is equals to E by L. So can you say that your V is proportional to ED? Sorry, V is proportional to E. This is the second equation we are having. Have we drawn the graph of VD versus E? Have you drawn the graph of VD versus E? Yes. So similar kind of graph you will get for I versus V. That's why I said that this graph is very, very important. Because I know the graph of VD versus E. If I know the graph of VD versus E, I can directly comment on the graph of I versus V. So VD is proportional to I, E is proportional to V. Or you can just think that if V increases, then E increases. If E increases, VD increases. If VD increases, I will increase. So there you go. If V increases, E increases, E increases, VD increases, VD increases, I increases. So there you go. It will increase. But after some time, what will happen is that if V increases, E will increase, but VD will increase, but slowly. So if VD is increasing slowly, then I will also increase slowly, or you can call it sublinearly. And after some time, what will happen is that if V increases further, then E increases further, then VD doesn't increase further, it will become constant. So I will also become constant. So this is the graph we will get. Now what I will do is that I will make two more graphs. I will make two more graphs, and then I will ask you a question. Let me make the graph and then wait for my question. I hope that some students would have already understood what the question would be. What do you think? What will be the question? I will be asking you that three graphs I have made. Which of the graph is for intrinsic semiconductor? which of the graph is for extrinsic semiconductor, which of the graph is for n type, and which of the graph is for p type. So 3 graphs I have made, I versus V graphs I have made. Which of them is for intrinsic, which of them is for p type, and which of them is for n type. So who is having the maximum current at a certain voltage? Let's just say this voltage was 2 volt. So at a fixed voltage, who is having the maximum current? So maximum current this particular graph is having. And who will have the maximum current? N type semiconductor will have the maximum current. Why is that so? Because mu n is greater than mu p. So this would be your n type. And between extrinsic and intrinsic, which semiconductor will have more current? Extrinsic semiconductor will have more current, or intrinsic semiconductor will have more current? Extrinsic will have more current. So this has to be p type, and this has to be intrinsic. There you go. This IV characteristic graph also we have made. All good? All fine? Okay. Again, a very important graph. Very, very important graph. Yeah. So this particular graph things are completed now. Okay. So on graphs only we have spent, I guess, 2 hours. So all the graphs we have spent, all the graphs we have seen in 2 hours. So graphs and some numerical problem also we have seen. So in the examination, what may happen is that directly they can make some graph and they can ask you which of them will represent the correct graph, or they can ask some questions as well. Okay. So I hope you have understood these particular analysis in a very good manner. Next, we need to study about diffusion current. Before that, we need to build up the base. So here we will be building up the base, but we are going to understand about diffusion current now. So till this point, what we were doing? This was your intrinsic semiconductor. In this intrinsic semiconductor, let's just say I am doping donor concentration. So if I am doping donor concentration, then how I was doping it? How I was showing it? That's a positive sign, positive ion giving you an electron, 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 positive ion giving electron, positive ion giving electron. So your electron concentration, if I say this is your x equals to 0 and this is your x equals to L. So whatever the electron concentration I get at x equals to L by 2, the same concentration I am getting at x equals to 0, the same concentration I am getting at x equals to L by 4, the same concentration I am getting at x equals to 3L by 4. So your electron concentration with respect to x was constant. It was always constant. And now what I used to do is that I used to apply some electric field, then your electron would have moved opposite to the electric field and the current would flow. This was the scenario I was doing. But now what I am doing is that I am doing non-uniform doping. So this was known as uniform doping. So now what I am doing is that here I am doping more. What I am saying, here donor atom is more. Here donor atoms are more. But at this side donor atoms are less. Are you able to understand this point? Here donor atoms are more, but here donor atoms are less. So now if I plot the graph of doping concentration versus x, then it will not be straight line. Just in a rough manner I am making the graph. Like let's just say here doping concentration is, here the donor atoms are more. Basically here the number of electrons are more, but with the distance it is decreasing. It can decrease linearly or it can decrease exponentially, or in whatever the manner it is decreasing, it is actually decreasing. So at x equals to 0, whatever the number of electrons you are getting, at x equals to L, the number of electrons are not same. At x equals to L by 2 as well, the number of electrons are not same. So they can decrease linearly or they can decrease exponentially. Whatever the graph is there, I don't care. But I just know one thing, that there is some gradient. What is the meaning of gradient? Gradient means that at this particular distance, at this particular point, the number of concentration is more, and at this particular point, the concentration is less. So here the number of electrons are more, here the number of electrons are less. Now I am having a spray. If I press this button, what will happen? So you can see that these, you cannot see actually, but what you already know that the particle of these spray, whatever the particle that is getting out of this spray, what will happen is that they will move in the whole room. Those particles will move in the whole room. So wherever there is high concentration, it will always move from the low concentration. Let's just say there is this tank. There is this tank which is completely filled. This tank is completely filled with water. Now what I did, I put another tank here, and here I did some hole. Okay, what I did, I made some hole. The tank was already filled with water. So here there was more concentration of water, here there was no concentration of water. So what will happen? The water will flow from here to here. So always it is the nature of the particle that it will always go from higher concentration to the lower concentration. Only the moving particle. Only the moving particle. Out of these two guys, positive charge and electron, who can move? This positive charge can move? No. I told you this is not important for your current to flow. Who are responsible for the current to flow? Electrons and holes. So who can move? Electron and holes can move. So this positive charge cannot move. Who can move? Electrons can move. And you can see that here there is more concentration of the electron. Here there is more concentration of the electron, but here there is less concentration of the electron. So what will happen is that electrons will move from here to here. So what I can see, I will see that this particular electron is moving from x equals to 0 to x equals to L. From x equals to 0 to x equals to L. Now if the electron is moving in this direction, because of the movement of electron, what will happen? Some current will flow. Some current will flow. Now for the movement of this electron, did you apply any electric field? No. I did not apply any electric field. Here in this particular scenario, did I apply any electric field? No. So this electron is not moving because of the electric field. So you cannot call it drift current. What you will call it? Diffusion current. So what you will say that electrons are diffusing from x equals to 0 to x equals to L. So what you will call it? Diffusion current. Now you will say that, sir, without even applying the battery, I am getting some current. What you are thinking that, sir, without even applying the battery, I am getting some current. Is it ever possible? This material, I don't apply any battery. Will it give me some current? No. So it is not possible. That means you are missing out on something. So what you are missing out? You are missing out that if these electrons are moving here, then they are leaving behind a positive charge. What really happened is that at x equals to 0, the positive charge has been accumulated, and at x equals to L, although the electrons will move and they will make sure that electron concentration becomes similar at everywhere, but what will happen is that at x equals to 0, there has been an accumulation of the positive charge, and here there are electrons. At this side there is an electron, and here there are positive charge, and this is positive charge is positively charged and electrons are negatively charged, and because of positive charge and negative charge, what will happen is that there one electric field will be built up, and this electric field is known as built-in electric field. What this electric field is known as? Built-in electric field. Again, let me explain it. The doping was non-uniform. Here there was more concentration of electrons, here there was less concentration of electron. Electron will move from higher concentration to the lower concentration, higher concentration to lower concentration. Since electrons are moving, there will be a current flow in the opposite direction of the electron flow. So electrons are moving from x equals to 0 to L, so current will flow from x equals to L to x equals to 0. This current is known as diffusion current because it is not flowing because of the electric field. It is flowing because of the concentration gradient, or you can say that electrons are diffusing, that's why this current is flowing. If the electron diffuses, what really happens is that at x equals to 0, there is positive charge that is being accumulated, and at x equals to L, you are having some electrons, some negative charge you are having. So positive charge and negative charge, because of that there will be one electric field from the positive charge towards the negative side. So this is the built-in electric field. Now in this built-in electric field, in this particular built-in electric field, this built-in electric field has been built up. In this particular built-in electric field, who are there? Electrons are there. There are electrons available. So because of this built-in electric field, electrons will move in which direction? Because of this built-in electric field, electrons will move opposite direction to the electric field. This is the direction of the electric field. So where the electrons will move? Electrons will move opposite. So electrons will move opposite. Electrons will move opposite. Is it clear to you? First electron started diffusing. Because of the diffusion, what really happened was there was some electric field build up. Because of this electric field, again the electrons will feel another force, and that force will be opposite to the direction. That force will be from x equals to L to x equals to 0. So again these electrons, this was also electron, this was also electron. So again these electrons are drifting. Here electrons are diffusing. But here I will use the word electrons are drifting. Why is that so? Because these electrons are moving because of this built-in electric field. And I told you, if there is an electric field, that means drift word will come into action. So here electrons are diffusing because of the potential gradient, and here electrons are drifting because of the built-in potential, or you can say built-in electric field. And if electrons are drifting in this direction, then there will be a current flow in the opposite direction of the drift, and that current flow will be in this direction, and this current will be known as J drift. So you can see that this is the direction of diffusion current, this is the direction of drift current, both will cancel out each other. There you go. Did you understand this point or not? Let me explain everything again. It is not tough. At one go, in the initial phase, it may feel like that's a really tough, but slowly you will be able to grasp it. What we did, this was a semiconductor, it was non-uniformly doped. At one side, we were having more concentration, at the other side, we were having lesser concentration. So electrons started moving from more concentration towards the lesser concentration. Since they are moving, they are moving not because of the electric field, but they are moving because of the concentration gradient. Okay, because more concentration, less concentration. So electrons are diffusing from x equals to 0 to x equals to L. So this was your x equals to 0, and this was your x equals to L. So electrons are diffusing from x equals to 0 to L, and since they are diffusing from x equals to 0 to L, there will be a current flow in the opposite direction. That current is known as diffusion current. Here you felt like that, sir, I have created the current. But actually, what really happening is that since the electrons are diffusing, there has been some positive charge build up here, and there has been some electrons have been built up here. Because of the positive charge, negative charge, there is a built-in electric field that has been built up. This electric field we are not applying. This electric field has been built up in the semiconductor itself. So this electric field has been built up from x equals to 0 to x equals to L. Because of that, electrons will be drifting in the opposite direction of the built-in electric field. So electrons are drifting in the opposite direction, and since they are drifting in this direction, there will be a drift current flowing from x equals to 0 to L. So direction of diffusion and drift current are opposite to each other, so they will cancel out each other, and the total current will be 0. Because it is pretty obvious that in a semiconductor, if you are not applying any external electric field, then how the current can flow? Current cannot flow, right? For the current to flow, external electric field is important. So if you haven't applied the external electric field, first you felt like that some current is flowing, but actually there has been some built-in electric field. Because of that, electrons are drifting in the opposite direction, and the current is also flowing in the opposite direction. So they are cancelling out each other, and the total current is 0. Now you know the expression of drift current, but you don't know the expression of diffusion current. So that expression I am going to write down. So the diffusion current density due to electrons is given by J diffusion. What I am writing? J and diffusion I should write down. J and diffusion. So that is given by, you have to remember the formula. Okay. So that is Q dn dnx by dx. Sir, what is this dn? I will tell you everything. But just let me know one thing. Here there is a concentration gradient. That means whatever the concentration you are having at x equals to 0, at x equals to L, you are having different concentration. So I am making any rough graph. The nature could be anything. The nature could be linear. It could be exponential as well. So we don't know what is the nature. Whatever the nature is there, we don't care about that. Basically, whatever the nature is there, we don't care about the nature. But I just know one thing, that the concentration is changing with respect to x. That thing I know. Okay. So there will be, here if I put, here if I ask you to find out the value of dnx by dx, what that would be? 0. So what will be the diffusion current? 0. So Q into dn into dnx by dx. What is this dn? This dn is known as diffusion constant or diffusivity. What it is known as? Diffusion constant. Diffusion constant or diffusivity. Diffusivity. What is this nx? You already know, right? Concentration of electron, nx, electron concentration at a particular point x. Concentration of electron with respect to x, or concentration of electron at a particular x, that is nx. And this is just the differentiation Q, already you know. Now sir, what is this dn? So dn, formula of dn would be mu n into Vt. This is the formula. D is equals to mu into Vt. The similar formula we will write down for the holes as well. So what will be that formula? dp is equals to mu p into vt. How will you remember? Do you remember ABCD? Do you remember the alphabet? So d will come first, then u will come, and then v will come. So d is equals to uv. So dn is equals to mu n vt. People actually, like, usually they will forget that, sir. Some will write down, sir, mu n is equals to dvt, and like usually they can forget the formula. So how do I remember? I remember the alphabets. So a b c d u v. So dn is equals to mu n into vt. So this formula you are going to remember. This expression, this relation was given by Einstein, but you don't need to remember the name of Einstein. This relation was given as Einstein, so this is known as Einstein relationship. But you don't need to write it down. You just need to remember dn is equals to mu n into vt. Okay, all good. So will you be able to remember the formula of diffusion current density? So this is your diffusion current density, q into dn into dnx by dx. Now when we write down this formula for the holes, when I write down this formula for the holes, here I have written down for electrons. So when I write it down for the holes, there will be, I will be putting one negative sign here. When I write it down for the holes, I will be putting one negative sign. Why I will be doing so, that I will explain later on. As of now, you just remember this is the formula. Okay. Now another thing you can notice, at equilibrium, equilibrium means no external electric field applied. At the equilibrium, that means under no external electric field. What is happening? Under no external electric field. Under no external electric field, let me again draw the diagram. What was happening here is that there was electrons were diffusing. Here there were more electrons, right? Here there were more electrons. Here there were lesser electrons. So electrons were diffusing in this direction. So there was a diffusion current in this direction. So there was diffusion current in this direction. And since there has been a lot of positive charge and there has been lesser positive charge, so there has been an electric field build up in this direction. So there has been an electric field build up in this direction, that was known as E built in. From now onwards, I will write it down as EB. So this is the built-in electric field. Because of this built-in electric field, electrons started drifting in the opposite direction, and because of that you get a diffusion current in this direction. So you are getting, drift current in this direction. So can I write it down in this manner that your J diffusion is equals to minus of J drift if there is no external electric field applied. So J diffusion is equals to minus of J drift. So what will be the expression of J diffusion? That would be Q into dN into dnx by dx. Look, how do I actually remember? What was the formula of a drift? NQ. What was the formula of drift current density? What that was? Sigma E NQ mu E. So look, Q same. In place of mu, what is coming? dN is coming. Just a way to remember. Q same. In place of mu n, who is coming? dN is coming. When it comes to diffusion current, there is no electric field. So forget about the electric field. Who is left? N is left. But here, what is happening? There is a concentration gradient. So that's why I will put dnx by dx. Just a way to remember I am telling. If I remember the formula of a drift current, which is sigma E NQ mu E. So Q same. In place of mu n, what is coming? dN. Electric field is not there. Now in place of n, what will come? dnx by dx will come. Because there is a concentration gradient. Just a way to remember I am telling, nothing else. What is drift? What will be the formula of drift current? What will be the formula of this drift current? So which particles are moving? Electrons are moving. What is the formula of drift current? That is sigma E. Sigma E is NQ mu E. In place of n, what I will put this time? Nx I will put. Why is that so? Because electron concentration is not same at all the places. It is varying with respect to n. So Nx I will put. Negative sign is already there. Q I will put. In place of mu I will put mu n and E. In place of E, what I will put? E built in I will put. Because electrons are moving because of this built-in electric field. So is this relationship clear to you or not? All good? All fine? Right? So what will happen? Q and Q will get cancelled out. Now EB is equals to minus dN by mu n minus dN by mu n into 1 by nx dnx by dx. This is the formula of built-in electric field you are getting. Now what is this dn by mu n? What did I tell you? D is equals to uv. A, B, C, D, D is equals to uv. So mu n into Vt. From here you can see that dn by mu n is Vt only. So what is your built-in electric field? What is the formula of built-in electric field you are getting? That you are getting as minus Vt by nx dnx by dx. When you are watching this lecture, you are not going to forget this formula, because again and again we will be solving a lot of question on this particular formula. But in longer run you might forget it. What I am saying, when you are watching this lecture, you will not forget this formula, but in longer run you might forget it. So concept should be clear to you. Within seconds you will be able to derive it. So drift and diffusion will be equal and opposite to each other. So diffusion is equals to drift. Write down both of the formula. Within second you will be able to derive it. So minus Vt by nx dnx by dx. That's it. Okay. Just another way I am telling. Just one another way of looking at it. What I am doing is that, so formula of built-in electric field you have got minus Vt by nx dnx by dx. In longer run you might forget it, so what you will do is that you can derive it as well. So what you will see, can I write it down in this manner? What will be the value of this particular thing? 1 by nx dnx by dx only. So 1 by nx dnx by dx I am replacing by this particular value. What is the differentiation of ln fx? That would be 1 by fx into differentiation of fx. So 1 by nx differentiation of nx, right? So another formula for the built-in electric field I have written down here. And this built-in electric field could be a function of x as well. What I am saying is that it could be constant or it could be a function of x as well, because this is also a function of x. If you do the differentiation, who knows that it might be a function of x only. This is also a function of x. So built-in electric field could be a function of x. So this is the answer that you are getting. Now from here, if you want to find out the potential difference, like this is your built-in electric field, this is the built-in electric field is built up. If there is electric field, that means there will be electric potential as well. So this built-in potential, what this is known as built-in potential. So if you want to find out the built-in potential, that built-in potential is given by, how did I write it down? I have already explained it, right? Because Ex is equals to, here I have already told that Ex is equals to minus dV by dx. So from here Vx would be equals to minus Ex dot dx. So don't mug up anything, we will solve the numericals, you will understand how to utilize these kind of formula in the questions. If you want to remember something, you can remember this one, that's it. Sir, how I will use it in the questions, don't worry about that. So as of now, we have started studying about our non-uniform doping, that means we have started studying about diffusion current. So we took a semiconductor, then we doped it with donor atoms. We are not applying any external bias. Diffusion current and drift current are opposite to each other, they are cancelling out each other and total current is 0. Then only thing I need to remember is this formula of the diffusion current. Diffusion current because of the electrons. What is that? Q into dn into dnx by dx. dn is that diffusion constant or diffusivity. Value of dn is given by mu n into Vt. And now what is Vt? I forgot to tell what is Vt. Vt is thermal voltage, right? Vt is thermal voltage. Voltage at room temperature. Voltage because of the temperature, right? Vt is thermal voltage, and that is given by Kt, right? This thermal voltage is given by Kt by Q. So value of Vt at room temperature, Vt at 300 Kelvin. What is the value? 0.0259 volts, right? So I forgot to tell what is this Vt. Vt is thermal voltage. Thermal voltage at room's temperature is 0.0259 volt, right? So you don't need to remember the value of Kt, nothing you need to remember. Only thing you need to remember is that Vt is proportional to T. Vt is proportional to temperature. Vt is proportional to temperature. From here you can see that Vt is proportional to temperature, and the value of Vt at room's temperature is 0.0259 volts. All good? All fine? And then we saw that at equilibrium under no external bias, what will happen is that drift current and diffusion current are same and opposite to each other. Then what we can do is that J diffusion is equals to minus J drift. If I do that, I will get this particular expression, that is minus Vt by Nx d by dx Nx. This particular expression can be written as minus Vt d by dx ln Nx. Using this expression, it will be easy for me to find out the built-in potential. But as of now, only thing you need to remember is this formula. Using this formula, how will you find out the built-in electric field? How will you find out the built-in potential? Everything we will see, don't worry about that. All good? All fine? Similar analysis you can do for the holes as well. And similar analysis, like let's go back to this slide. Here I said that at x equals to 0 there was more concentration, and at x equals to L there was lesser concentration. Opposite can also happen. What I am saying is that it may happen that here there is more concentration and here there is less concentration. So in this scenario, what will happen? Electrons will diffuse here. If electrons are diffusing here, that means this will be the diffusion current, right? Electrons are diffusing here, this will be the diffusion current. Since electrons are diffusing here, there will be more positive charge, there will be less negative charge. So electric field will build up in this direction. So this will be your built-in electric field. Since this is the built-in electric field, the electrons will move in this direction. So electrons will be moving in this direction. That means you can say that electrons are drifting in this direction. So if electrons are drifting in this direction, then drift current will be opposite. There you go. Drift current will be opposite. So diffusion and drift are opposite to each other. So it's not necessary that, sir, at x equals to 0 there will be more concentration, at x equals to L there will be less. Opposite can also happen. At x equals to L there is more concentration, at x equals to 0 there is lesser concentration. So opposite thing can also happen. The similar kind of analysis you can see in the p-type semiconductor as well, where I have said that at x equals to 0 there is more concentration and at x equals to L there is lesser concentration, but let's do it opposite. Okay, just for the thrill, let's do the opposite, that at x equals to 0 you are having lesser concentration, but at x equals to L you are having more concentration. All good? All fine? So holes will diffuse from here to here. Holes will diffuse from x equals to L to 0. If holes are diffusing in this direction, the diffusion current will also be in the same direction. So this will be your diffusion. And since holes are diffusing here, what will happen is that there will be negative charge, and holes have diffused here. So here there will be holes. So this is negatively charged, holes are positively charged. So what will happen is that there will be a built-in electric field from holes to negative charge. So this will be the built-in electric field. This is the built-in electric field. Now where the holes will move? Holes will move in the same direction to the electric field. So this was holes are diffusing. Now because of this built-in electric field, holes will drift. Holes will drift in the same direction as the electric field. So holes are drifting. And what will be the direction of current? Direction of current will be in the same direction of the hole drift. So if holes are drifting, holes are drifting in this direction, so what will be the direction of drift current? This will be the direction of drift current. So you can see that diffusion current and drift current are opposite to each other and they will cancel out each other. I hope you have understood. Holes will diffuse. Since they are diffusing here, this will be the diffusion current. Because of that, electric field is built up. Holes are drifting in this direction. Drift current is also in the same direction. So diffusion and drift current are opposite to each other and they will cancel out each other, right? So what we have done is that at x equals to L there is more concentration and at x equals to 0 there is lesser concentration. So x equals to L to x equals to 0. Oh, sorry. At x equals to 0 there is lesser concentration, at x equals to L there is more concentration. So this is how I can make the graph. It can be exponential as well. I don't care. The nature could be exponential as well. Whatever the nature is, I don't care. It could be exponential, it could be linear. I just know one thing, that at x equals to 0 lesser concentration, at x equals to L there is more concentration. What will be the formula of diffusion current? So diffusion current for holes. Here I write down diffusion current for electrons Jn. So I am writing diffusion current for holes Jp. That is given by minus q dp dpx by dx, where your dp is mu p into vt. Sir, why this negative sign? Sir, here there was no negative sign. Why this negative sign? So let's understand. Here the diffusion current is in the same direction as the diffusion. What I mean to say is that, what is the direction of diffusion current here? This is the direction of diffusion current. If I make the diffusion current is from x to x equals to L to x equals to 0, right? But if you are going from x equals to L to x equals to 0, your slope is negative or positive? If I go from x equals to 0 to x equals to L, then my slope is positive. But if I am coming from x equals to L to x equals to 0, then my slope is negative, no? Are you able to understand this point? So slope will be negative, dpx by dx will be negative. And if slope is negative, so my current Jp, that will also be negative. Basically current can never be negative or positive. If 2 ampere current is flowing, 2 ampere current is flowing. So this negative sign is just showing the direction. It is showing that this negative sign is showing that in whatever the direction holes are diffusing, in the same direction diffusion current is there. So even if you forget the negative sign, no need to worry about that. What you can do, you can analyze the condition that, sir, here there are more holes, here there are less holes. So where the current will be flowing? From more holes to the less holes. So holes are diffusing in this direction, so this will be the direction of a diffusion current. So this is just for the sake of direction. What I mean to say is that if I put the value of dp by dx here, what I will do? dp by dx, with the increasing x, my concentration is increasing. So this value will be positive. dp by dx will be positive. With the increasing x, my concentration is increasing. So here the slope is positive. So this value will be positive. Q dp. dp will be positive, q will be positive. Now the total answer is becoming positive. What does that mean? So what people will think that in the direction where px is increasing, in the same direction current is flowing. But no, the diffusion current is flowing in the opposite direction. The diffusion current is flowing where px is decreasing. Px is decreasing from x equals to L to x equals to 0. Your whole concentration is decreasing from x equals to L to x equals to 0. And diffusion current is also flowing from x equals to L to x equals to 0. Again, let me repeat the statement. Your whole concentration is decreasing from x equals to L to x equals to 0, right? And your diffusion current is also flowing from x equals to L to x equals to 0. So your diffusion current is flowing in the decreasing direction of whole concentration. That's why there is a negative sign here. What is the direction of diffusion current? This is the direction of diffusion current, right? This is the direction of diffusion current. In this direction, your electron concentration is increasing, because here there were more concentration and here there were less concentration. What was the direction of diffusion current? This was the direction of diffusion current. So the direction of diffusion current is in the increasing direction of electron concentration. But in case of holes, what was happening? Let's just say there were more holes. Here there were more holes and here there were lesser holes. So what will happen? Holes will diffuse here, and since holes are diffusing in this direction, so diffusion current will be this as well. So in case of holes, what happens? The diffusion current is in the decreasing direction of the whole concentration. But in case of electrons, the diffusion current is in the increasing direction of the electron concentration. So that's why when I write down the equation for electrons, I don't use any negative sign, but when I write down the equation for holes, I use the negative sign. Even if you forget the negative sign, there is no use of that. They will ask the magnitude of current, okay? And if somewhere the sign is being used, you will be able to do the analysis. Don't worry about that. So don't worry about this sign, only you remember this particular thing, q dp dp by dx. Here as well, sir, do I need to remember this sign? Don't worry, don't remember this sign. We will solve the numerical and you will get to know that there is not much importance of this sign. Without even remembering this sign, you will be able to solve the problems. Here also you don't need to remember this negative sign. All good, all fine. So your drift current is q dpx by dx. Drift current density. It is your drift current density, where this is the formula of your dp. Can you find out at equilibrium what will happen? At equilibrium. Equilibrium means no external bias. So diffusion and drift current will be opposite and equal to each other. So J diffusion will be J drift. Okay. So what is the formula? This formula is minus Q dp dpx by dx, and here minus charge carrier Q mu p and built-in electric field, which could be a function of x. So Q and Q will get cancelled out. So eventually your EBX will come out to be the similar answer, just here negative sign and negative sign will get cancelled out. So answer would be Vt divided by Px dpx by dx. Sir, in this formula there is no negative sign, but sir here there was a negative sign. So sir, will I mug it up that in the electron, if I write down the formula of electron current, then there will not be any negative sign. When I write down the expression of built-in electric field, then there will be negative sign. But here there will be negative sign, here there will not be negative sign. Forget about the negative sign, positive sign. Always you will take positive sign. No numerical will be wrong, because we will be solving the numerical. We will be making the direction with respect to the concept, not with respect to these signs. So we will solve the question with the concept. We will draw this diagram. We will see that where there is more concentration, where there is less concentration. Based on that, we will be able to know what is the direction. So when we solve the numerical, we don't need to care about these negative positive sign. Just the formula should be clear. What is that formula? That what would be the formula of diffusion current? That would be Q into Nx dnx by dx, Q into dp dpx by dx. And what will be the formula of built-in electric field? Vt by px dpx by dx, Vt by nx dnx by dx. That's it. Just if you remember the formula, and even if you forget this formula, you will be able to derive it within seconds. So don't worry about the signs. Okay, positive sign, negative sign, you don't need to worry about that. All good, all fine. So now we are going to see the numericals. So this question we are going to solve, this question we will solve, this problem we will solve, and this problem, and then this question. So I have put 5 questions here. With 5 questions, everything will be revised, whatever that we have studied. Every single thing will be revised. So let me take a break. You try solving these problems. You try solving this one. Then you try solving this one. This is a very good question. So here you need to take care of something. Temperature you see, 400 Kelvin. Okay. Try solving this one as well. You need to find out the built-in electric field, and you need to find out the potential difference as well. Then built-in electric field and the potential difference. And this is the best question. Like best question ever that can be asked on this particular topic. And if you are able to solve it, for me you are under 100 any day. No matter whatever the rank you get in your GATE examination, but if you are able to solve it, for me you are any day GATE AIR under 100. Even if you get 1000 rank, for me you will always be under 100. For IITs it will be 1000 only. They will give you admission based on your 1000 rank only. But if you are able to solve it, that means you have understood everything. Okay. These questions are from Niemann only. This is from Niemann. This is also from Niemann directly. This is also from Niemann. These are also from Niemann, but I just changed some data so that I could make it more complex. This is also from Niemann only. This is directly from Niemann. Okay. But here I changed the data just so that I could make it more complex. Yeah. So you try solving it. I will take a break and then I will come back. And with that, this topic will also be completed. So yeah. Just let me take a break and then I will come back and we will start solving these questions. Yeah, hi everyone, welcome back. So did you try this question? In this question, what is given? The electron concentration is varying with respect to x. So a particular expression is given, Nx is equal to 10 to the power 15 e to the power minus x by ln, and value of ln is also given. So your electron concentration is varying with respect to x in this manner, that at x equals to 0, it is 10 to the power 15. And at x equals to infinity, what it will happen? E to the power minus infinity, that would be 0. So basically it is decreasing with respect to x. So in this manner it is going from 10 to the power 15 to it will decrease. Value of ln also they have given. What is, sir, what is this diffusion length? So when we study about low level injection, at that time I will take this particular thing into action. What is the meaning of diffusion length? As of now, you just understand that value of ln is 10 to the power minus 4 centimeter. That's it. Okay, so this is this kind of concentration gradient is there. What does that mean? That means let's just say this is your semiconductor, this is your x equals to 0. What is this? X equals to something that you don't know. You don't know the length of your semiconductor, but you know that at x equals to 0 you are having the maximum concentration. That means here you are having the maximum concentration of electrons. But with respect to the distance, it is keep on decreasing, and when you reach at x equals to infinity, the electron concentration will be 0 only. But the length will not be surely infinity, it would be some centimeter or whatever it is. Right? So diffusion coefficient is also given, the value of dn is also given, that is given as 25 centimeter square upon second. How can you write down the unit of dn? You know that d is equals to mu into vt, right? What is the unit of mu? Centimeter square volt into second. What is the unit of vt? Volt. So volt will get cancelled out, centimeter square upon second. This will be the unit. Okay. Charge also you know, you just need to find the diffusion current density. So diffusion current density, because of the concentration gradient it is coming. Now you will say that the total current would be 0. Yeah, total current would be 0. But one component will be of diffusion, one current component will be of drift. And drift current is coming because of the built-in potential. They are just asking you the diffusion current. They are just asking you the diffusion current density. Only the diffusion component you need to tell. I know that total current would be 0, but here you will not say that sir total current will be 0. You will say that sir one component is diffusion, one component is drift. They are asking us the diffusion component. So diffusion current will be coming because of the concentration gradient. So your diffusion current would be, this is your diffusion current. So Jn of x I am writing down because it could be a function of x as well. Why it could be a function of x? Because what was the formula? Q into dnx by dx. So if you solve this particular value, this could be a function of x as well. So that's why I am writing down Jnx. It could be a function of x. So what is the value of q? 1.6 into 10 to the power minus 19. What is the value of dn? 25. Everything is going in centimeter square. And dnx by dx, can you differentiate it? What is your nx? Nx is given as 10 to the power 15 e to the power minus x by ln. So if I differentiate it, what I will be getting? Sir, you will be getting 10 to the power 15 e to the power minus x by ln, 1 by ln and another negative sign as well. So your answer would be 10 to the power 15 upon ln e to the power minus x by ln. What is the value of ln? Value of ln is 10 to the power minus 4. So here I will put 10 to the power minus 4, here also I will put 10 to the power minus 4. Sir, negative sign will also come, but I will not care about the negative sign. Surely the negative sign will come, but you know that they will just be asking the current density. Answer will never be negative. If I say the current is minus 2 ampere, what does that mean? That means current, let's just say this direction I am taking as positive, and now I say that current is minus 2 ampere, that means current is flowing in this direction, that's it. So minus sign and anything, you don't need to care about that. So you let me know in which direction diffusion current will be flowing. So electrons will be diffusing in this direction, so the direction of diffusion current will be opposite to that. So this will be your diffusion current density. So if they ask you what is the direction of diffusion current, so it will be from right to left, that's it. Okay, so this is the expression of Jnx you are getting. Let's add up another page as well. So I will have to add the pages anyway. So Jnx I am getting as, so this would be 10 to the power 19 only, this will get cancelled out, 25 into 1.6, 25 into 1.6, 25 into 1.6, so that would be 40, right? 40, and this would be 10 to the power 19, this would be cancelled out. So 40 e to the power minus x by 10 to the power minus 4, everything is going in the centimeter, and what will be the unit here? Ampere per centimeter square. Okay, so this is the answer. Minus sign also you can take into action because everything is SI, only the length is in centimeter, rest everything is okay. Now you need to find at x equals to 0, x equals to 10 to the power minus 4 and at x equals to infinity. So first one is at x equals to 0. So your value of current density at x equals to 0. If you put x equals to 0 here, minus 40 ampere per centimeter square. Next, if you put x equals to 40, not 40, sorry, 10 to the power minus 4 centimeter, right? X equals to 10 to the power minus 4 centimeter. So you can see that this is also in the unit of 10 to the power minus 4. So this will also be in the unit of, this is in the unit of centimeter. So this x will also be in the unit of centimeter, and this would have been mentioned in the question as well, that x is in the centimeter. They did not write it down. It should be given in the question that x is in the centimeter, because ln is in the centimeter, no? So this x will also be in the centimeter only. So your Jn at 10 to the power minus 4 centimeter, that would be minus 40 e to the power 10 to the power minus 4 divided by 10 to the power minus 4. This is also in centimeter, this is also in centimeter. So your answer is coming out to be minus 40 by e. So you can solve it, minus 40 by e, you can do it and you will get your answer. (14.71). What this negative sign is representing? Negative sign is representing that the current is flowing in this direction. So where the holes are diffusing, where the electrons are diffusing, in the opposite direction the current is flowing. That's why the negative sign is coming in the final answer. And at x equals to infinity, what will be the scenario? At x equals to infinity, Jn of infinity. So minus 40 e to the power minus infinity. What will be the answer? E to the power minus infinity will be 0 only. So current will be 0 ampere per centimeter square. Very easy question, very straightforward. Just you need to apply the formula and you will get the answer. Nothing was there, only formula based. Free marks, I would say, free marks. If you just remember the formula, q into dn dnx by dx, your job would be done. And forget about the negative sign, don't care about the negative sign. Let's go to the next one. A non-uniform doped p-type semiconductor is maintained at 400 Kelvin. So your semiconductor, p-type semiconductor, is working at 400 Kelvin. The hole concentration is decreasing linearly from x equals to 0 to x equals to 0.1 centimeter. What does that mean? They have given the graph of hole concentration. Your hole concentration is decreasing linearly from x equals to 0 to x equals to 1. This is how it would be. X equals to 0 to x equals to 0.1 centimeter. This is how it would be decreasing. At 400 Kelvin, the diffusion current density is measured to be 20 ampere per centimeter square. The diffusion current density at 400 Kelvin. This is constant. It is not a function of x. I told you it could be a function of x. It could not be a function of x as well. And just tell me one thing. What would be the formula of diffusion current density? Just tell me what would be the formula of diffusion current density. That would be q dp dpx by dx. Right? This would have been the formula. And another negative sign also you can add. Even if you forget the negative sign, don't care about that. Now you just let me know the slope of this graph, what it will represent. The slope of this graph, what it will represent. Dpx by dx only. And will that be constant? Yes, the slope of this graph will be a constant value. Are you able to understand this point? The slope of this graph is constant, but slope of this graph would be different. This is simply y equals to mx plus c. So what will be the slope here? Slope will be some constant value m. So slope will be constant. For this graph, the slope will be constant. So if this slope is constant, this dp is constant, and q is also constant, that means this current density has to be constant. So yes, current density is constant, that is given 20 ampere per centimeter square. So just remember that everything is going in the centimeter. Now what they are actually asking, if the hole concentration is given at x equals to 0, they have given the hole concentration. What is the hole concentration at x equals to 0? They have given the hole concentration at x equals to 0 as 3 into 10 to the power 18 centimeter cube. You need to find the hole concentration at x equals to 0.05 centimeter. This is what you need to find. I know the Jp value, I know the Q value, I can find out the Dp value as well. How can I find out the Dp value? Because I have the mobility value. So what is the relation between dp and mobility? That is mu p into Vt. But now here something interesting will come out. You need to find out the value of dp. You need to find out the value of dp, which is equals to mu p into Vt. So if I put the value of dp, if I put the value of q, if I put this value, then what I would be able to find out? Dpx by dx. And if I am able to find out dpx by dx, then I can find out the hole concentration as well. So my major concern would be to find out the value of dpx by dx. For that I would require the value of dp. So value of dp, diffusion constant, that would be mu p into Vt. But it is working at 400 Kelvin. So you need to So you need to find out the value of dP at 400 Kelvin only. And you are given mu p value at room's temperature. What it is given? Mu p at 300 Kelvin is given. What is that? 550 centimeter square volt into second. So how will you find out the mu p value at 400 Kelvin? Because everything you require at 400 Kelvin. So you require mu p value at 400 Kelvin, you require Vt value at 400 Kelvin. So now you know that after room's temperature, what you know? What is my target? My target is to find this particular thing. And you know that after room's temperature, mu p is proportional to T to the power minus 3 by 2. So mu p at 400 Kelvin divided by mu p at 300 Kelvin would be equals to what? Temperature 400 Kelvin to the power minus 3 by 2 divided by temperature 300 Kelvin to the power minus 3 by 2. So what you are getting? Mu p at 400 Kelvin. Mu p at your 400 Kelvin is coming out to be 3 by 4 to the power 3 by 2, right? 0 will get cancelled out and this will go upward, this will come downward to the power 3 by 2 into 550. So this would be the answer. Basically it should decrease, that I already know. So 3 by 4 to the power 1.5, right? Into 550. So 357.23. So this was the best thing of this question. Actually in Niemann here 300 Kelvin was given, but just to make the question a bit complex, I changed it to 300 Kelvin. So what you are getting? This much you are getting. So this is the value of your mobility. And what about the Vt value? Sir, for Vt value I would require the Boltzmann constant. No, you know that Vt is equals to Kt. From here what you can see is that Vt is proportional to temperature. What does that mean? Vt at 400 Kelvin divided by Vt at 300 Kelvin will be equals to Vt at 400 Kelvin, you don't know, right? Basically Vt at 400 Kelvin you don't know, but Vt at 300 Kelvin you already know. Since it is proportional to temperature, so it would be 400 divided by 300. Say yes or no? Are you able to understand this point? So Vt at 400 Kelvin will be equals to 4 by 3 times of whatever Vt at 300 Kelvin. What is that? 0.0259 volt. Are you able to understand this point? So 0.0259 into 4 by 3. So 0.0345. 0.0345 volt. So this is your Vt value at 400 Kelvin. Now what I need to find? I need to find the dP value at 400 Kelvin. That would be mu p value at 400 Kelvin multiply with Vt value at 400 Kelvin. So mu p value at 400 Kelvin, what that was coming out to be 357.23 into 0.0345. And what will be the unit? Unit will be centimeter square upon second. 0.0345 whatever it is written into 357.23. So this answer is coming out to be 12.33 centimeter square into second. So this is your dP value now. So this was the best part of this question. So dP value we have find out now. Now I can solve the question, right? So here also let's solve it. 1.6 into 10 to the power minus 19. Let's take it negative because this negative sign I have put here. Okay, but negative sign, even if you forget, don't care about that. Now what is the dP value? Let's just say I have forget the negative sign. Forget about the negative sign. I told you negative, positive, just forget about everything. Just put down the values. What is the dP value I am getting? 12.33. 12.33 dpx by dx. Okay, so 12.33 into 1.6 into 1.6, then you take the reciprocal and then multiply with 20. So 1.01 into 10 to the power minus 10 to the power minus 19. So your dpx by dx, you are getting 1.01 into 10 to the power 19. Or you can write down 10.13. 10 to the power 18. I will write it down in 10 to the power 18. So after doing the calculation, I am getting 10.13. 10.13 into 10 to the power 18. Okay. Now you know that the slope is negative only, no? From the graph only you could see that slope is negative. Basically, whatever the value at 0 you are getting, the value at 0.05 would be lesser than that. Because it is saying that it is decreasing linearly from 0 to 0.1 centimeter. That means at 0.05, the value will be lesser. So you already know that slope will be negative. So even if you had forget this negative sign here, directly you can put the sign negative here. Now from here, can you find out the value of px? Just take this dx at this point and then just px would be, just integrate. What I mean to say is that dpx would be minus 10.13 minus 10.13 into 10 to the power 8 dx, and you will integrate. How you will integrate? You can integrate from 0 to a particular x, right? And here also you can integrate from 0 to a particular x. On both of the side I am integrating. So what I will get, here I am writing down. So that would be equivalent to px minus p of 0, 0 to a particular x I am integrating. And here what you will get, minus 10 to the power minus 10.13 into 10 to the power 8x, right? So value of px is coming out to be p of 0 minus 10.13 into 10 to the power 8 or 18, 10 to the power 18 into x. And you can see that if I put x equals to 0, I am getting p of 0 only. So p of 0 value I already know. Now this is the final answer that I am getting. This is the final expression that I am getting. Now what I need to find? I need to find the value at 0.05 centimeter. 0.05 centimeter. So p of 0, concentration, where is the p of 0 value? 3 into 10 to the power minus 18, everything is going into centimeter only. So don't worry about the unit. 3 into 10 to the power 18 minus 10.13 into 10 to the power 18 into 0.05. I will not convert it into the meter. Why I will not convert it into the meter? Because everything is going into centimeter. So that's it. This would be the answer. So 10.13 it is, 10.13 it is, multiply with 0.05. Multiply with 0.05, that is 0.5, and that will be subtracted from 3. So what you are getting? 2.5, roughly around 2.5 into 10 to the power 18 per centimeter cube. So this will be the concentration. Is that clear to you or not? Very simple thing. Here also the expression for the value of current density was given. I know that I know the value of Q, I know the value of dP as well. From there I can find out how my whole concentration is decreasing. So if I know the expression of dP by dx, then from there directly I can find out the value of P of x just by integrating it. So here if my x is going from, here you should write down from P of 0 to P of x, because here you are putting the limit of Px, no? So from P of 0 to, if I am going P of x, that means I am going from x equals to 0 to x equals to x, right? So I can simply integrate, I will get this value. Till this point I was doing something else. Or you can simply know from here only the slope is minus 10.13 into 10 to the power 18. That means if you move for 1 centimeter, then this much will be reduced. So if you move for 0.05 centimeter, then how much will be reduced? This much will be reduced. So if I am an intelligent student, what I would do is that I know the slope, I know the meaning of slope. If I have studied signal system, then I would know that what is the meaning of slope. That if you work for 1 centimeter, because the unit are The units are there in the centimeter only. So if I move for 1 centimeter, then my whole concentration will be decreasing for 10.13 into 10 to the power 18. But I need to move for 0.05 centimeter. That means I will multiply with 0.05 centimeter. That means my whole concentration will be decreasing by 10.13 into 10 to the power 18 into 0.05. So what was the concentration at x equals to 0? This was the concentration at x equals to 0. And how much it will be reduced? This much it will be reduced. So your approximate answer would be 2.5 into 10 to the power 18. That's it. The best thing was here the temperature was 400 Kelvin. So if different temperature is given, people will be thinking that you need to remember the formula of you need to remember the Boltzmann constant, but you don't need to remember the Boltzmann constant. You just know that Vt is proportional to temperature and your mobility is proportional to 10 T to the power minus 3 by 2. So it will decrease and this will increase. So this value has decreased and this value has increased. All good? All fine? Okay then. Let's move to the next question. The electron concentration in the silicon is given by this thing. This is how the electron concentration is varying. X is measured in micrometer. So this they have given. X is measured in micrometer. So this 18 would also have been in micrometer only. The question is not written in the correct manner. This would also be in micrometer. So here they should have written minus x by LP. Then they would have said that LP is 18 micrometer. Okay. So this would also be in micrometer. And your semiconductor is limited between 0 to 25 micrometer. What does that mean? What do you understand by this? I understand that this is my semiconductor which is going from x equals to 0 to x equals to 25 micrometer. Okay, this is the length of my semiconductor, and at x equals to 0 I am having the maximum concentration, and with the distance it is decreasing. With the distance it is decreasing. With the distance this concentration is decreasing. So what do you think? Here there would have been more concentration, and at this point there would have been lesser concentration. If I say this is my x equals to 0 and this is my x equals to 25, right? That means electrons will diffuse here. So on this side there will be positive, 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 and this side there will be negative. So what will be the direction of electric field? This will be the direction of electric field. This will be the direction of E field, right? This is your x equals to 0 and this is your x equals to 25. So your direction of electric field is from x equals to 0 to x equals to 25 micrometer. Okay. Diffusion constant, mobility, all these things are given. Temperature is not mentioned. Temperature is mentioned 300 Kelvin only. Everything is fine. The total electron current density is given as minus 40 ampere per centimeter square. The electron has both diffusion and drift current component. Determine the electric field as a function of x, which must exist inside the semiconductor. So inside the semiconductor, which electric field will exist? That would be built-in electric field. So what they are asking? Built-in electric field. So even if you forget the formula, then you can derive it. I told you the diffusion current and the drift current will be opposite to each other and they will be cancelling out each other. So what would be the scenario here? What is the diffusion current? Sir, Q into dnx by dx minus nx q mu n and built-in electric field, right? Q and Q will get cancelled out. What you are getting? Built-in electric field you are getting as dn by mu n into 1 by nx dnx by dx. This is your built-in electric field that you are getting. Sir, negative sign, forget about the negative sign. Don't worry about the negative sign. Okay. What is dn? dn is 25. What is mu n? 960. Everything is going in centimeter square. So dn is 25, mu n is 960. 1 by nx. What is the value of nx? Value of nx is 10 to the power 16 e to the power minus x by 18. 10 to the power 16 e to the power minus x by 18. Right? This is in micrometer. This is also in micrometer. Can you differentiate the nx? Can you differentiate the nx? Yes, surely I can differentiate. This is your nx. 10 to the power 16 e to the power minus x by 18. So if I differentiate it, what you will be getting? 10 to the power 16 divided by 18 e to the power minus x by 18. So 10 to the power 16 e to the power minus x by 18 divided by 18. So negative sign will also come. Forget about the negative sign, I am telling you. Okay, here also negative sign would have come, here also negative negative, so that would have been positive, right? So negative sign, positive sign, we don't care. We just need to find out the value of built-in electric field. We also know the direction as well. So what we can see here is that this part and this part is getting cancelled. So what you are getting? 25 divided by 960. But this 18 is in micrometer, right? But everything was going in centimeter. Here centimeter, centimeter, dn value centimeter, 960 centimeter, and jn is not useful for us. Although it is given, but it is not useful. So what did you get to know? That this is in the micrometer. But I need to convert it into the centimeter. So what I will do? 18 into 10 to the power minus 4. This was the important part, because everything is going to centimeter, so I will take this also into centimeter only. Although here also I should have taken centimeter, but this is getting cancelled. But here it is coming in micrometer. 18 is coming into the micrometer, so 10 to the power minus 4. Then it will be into the centimeter. So now it will be okay for me. So what I would do is that 25 divided by 960 divided by 18 multiply with 10 to the power 4. So 14.46, 14.46 volt per centimeter. So this is your built-in electric field that I am getting. So what is the value of my built-in electric field? 14.46 volt per centimeter. It is coming out to be constant. It could be a function of x as well. Here I should have written it could be a function of x, right? It could be a function of x, but it is coming out to be constant. Right? Now what I need to find? I need to find the built-in potential. What is that? Dot dx, right? Now what you need to find? Calculate the potential difference between x equals to 0 to x equals to 0 and 25 micrometer. That means from 0 to 25 micrometer you need to integrate. So what you will be getting? E built in, this is 14.46, that is constant. Forget about the negative sign. What you can see, from 0 to 25 micrometer, this is what they are saying. So what is the differentiation of a dx? That would be x only. From 0 to 25 micrometer, right? Micrometer. This is your micrometer. So what I would do, I will put 10 to the power minus 4, because this is in the centimeter, so this will also be in the centimeter only. So what will be the answer? 14.46 into, basically what was your V? Sorry, what was your electric field? Electric field was potential divided by the length. So what will be your potential? That will be electric field into the length. What is the length? Between 0 to 25 micrometer. So in the length I will put 25 micrometer. Or you can do in this manner, that E built in will come constant. You are integrating from 0 to 25 micrometer. Sir, you have forget the negative sign. Forget about it. Just hold on. Okay. We will get the answer. Just hold on. So 14.46, 25 into 10 to the power minus 4. So 14.46 into 25. So you are getting divided by 10 also I can do. So 13.16, 13.16 millivolt. (14.46 into 25). 14.46 into 25. Yeah, and divided by 10 to the power 4. So 36.15 millivolt. Yeah. So this is the answer you are getting. Now sir, plus minus sign, how I will decide? So what they are saying, calculate the potential difference between x equals to 0 to potential difference between x equals to 0 and x equals to 25 micrometer. Let's just say this is 1 point. This is your VA potential, which is at 2 volt, and this is your VB potential, which is at 1 volt. If I ask you find the potential difference between VA and VB, what you need to find? VA minus VB. What would be your answer? 1 volt. Right? VA minus VB, 2 minus 1, 1 volt. If I ask you find out the potential difference between VB and VA, so you need to find out VB minus VA, that would be 1 minus 2 minus 1 volt. Here what you can see, x equals to 0 is at higher potential or x equals to 25 is at higher potential? X equals to 0 is at higher potential, no? because at x equals to 0 you are getting positive charge. So that means this is the higher potential. So if I am finding the potential difference between x equals to 0 to x equals to 0 and x equals to 25, that means x equals to 0 is at higher potential. So final answer will be positive or negative? It will be positive only. So forget about this negative sign here, negative sign, wherever negative sign is coming. Don't care about those negative sign. If they are asking electric field, that means a negative sign will not come. But in the potential, in the answer, negative sign may be there. What I mean to say is that if they are asking electric field, then all the 4 options will be having different values. There is no meaning of a negative sign there. In the electric field, they can say that, okay, the direction of electric field will be from x equals to 0 to x equals to 25. Or in one of the option, they will say that direction is there from x equals to 25 to x equals to 0. So you would know that the direction is from x equals to 0 to 25. So with this particular answer, they can give the direction. Direction is from x equals to, direction is positive x. What I am saying? Positive x. Positive x. What do you mean by positive x? That means you are working in the positive direction of x from 0 to 25. This is your 0. This is your 25. So if, and this is my x axis. So if I am working in this direction, this is my positive x, and if I am working in this direction, this is my negative x. Because from 25 to 0 if I am going negative x, from 0 to 25 if I am going positive x. So direction here is positive x. This is what they can say. Here plus minus sign could be there. The potential difference could be positive or negative. So how will you determine that, sir, x equals to 0 is at higher potential, x equals to 25 is at lower potential. And what they are asking, the difference between 0 and 25. So since this is at higher, this is at lower, so answer will be positive only. There you go. Okay. So this was the question. Here luckily our calculation was easy because this was not a function of x. But if it becomes a function of x, then finding the built-in potential by this formula will be a bit difficult. Are you able to understand this point? Which we are going to solve in the next question. But let's find out the value of built-in potential using a different formula. This is the answer, but let's use a different formula. In this problem only, what I am saying is that I am gonna find out the value of built-in potential using some different formula. So what is the formula of my E built-in? That is minus Vt by Nx. Forget about the negative sign. Just forget about the negative sign. dnx by dx. And I told you, you can do something like this. Okay, this is your built-in, and it could be a function of x as well. It could be a function of x. What I need to find? I need to find built-in potential, and that I know that it would be E built-in dot dx. Negative sign, anything, everything I am forgetting because I know that in the final answer I can change it. So what I will be getting? Vt. What is my E built-in? This is d by dx ln nx dot dx. Basically I am just putting this value, E built-in x. E built-in x I am putting dot dx. So you can see that dx and dx is getting cancelled out. Vt is a constant value. Vt can be outside. So basically d ln nx. What is the answer of d of ln x? And you are integrating it. What would be the answer? If you don't know by this, so what would be the answer of d of fx? If you are integrating it, what is the answer of d of x? If you are integrating from 0 to x. So answer would be 0 to, let's integrate it from 0 to alpha. So answer would be, sir, x integrating from 0 to alpha. So what would be the answer of d of fx? Basically this and this will get cancelled out. So answer would be fx, but you need to put the limit. You need to put the limit of fx. Are you able to understand this point? So similarly here as well, d of ln x. So this and this will get cancelled out. Answer will be ln x. But I need to put the limit. I need to put the limit of whatever that is inside. I need to put the limit of whatever that is inside. So now in our case, what is there? Ln of fx. Ln of fx. So this and this will get cancelled out. Ln of fx. But now I need to put the limit of fx. So from fx, f1 of x2, I am going to f2 of x. I'm not putting the limit of x, I'm putting the limit of fx. Are you able to understand this point? This and this was getting cancelled out. Here you are putting the limit of x. Let's just say it was d of sin x. So what you will say, sir, this and this will get cancelled out, so answer will be sin x. And if I am doing the indefinite integration, then I need to put the limit. So you will put the limit of x. So in place of sin x, if I am putting fx, so I need to put the limit of x. Similarly, here my function is ln, but inside ln there is another function. So I will put the limit of this fx. No, are you able to understand this point or not? Mathematics, again mathematics. Okay, mathematics only. D of ln x, this and sir, this will get cancelled, but since this will be a indeterminate this will be an indeterminate integration, so I need to put the limit of nx. So here this is how I am writing down the formula, that you will put the limit of nx. So this will be your final answer of built-in potential. So I need to find out the built-in potential. I need to find out the built-in potential from built-in potential between x equals to 0 to x equals to 25 micrometer, right? So what do you think, what should be my answer? V built-in, Vt, your answer was ln nx. This and this was getting cancelled, answer was ln nx. But now you are putting the limit. You are putting the limit from value of your electron concentration at x equals to 0 to the value of your electron concentration at x equals to 25 micrometer. So if I put this value, what I will be getting? Ln of nx at 25 micrometer minus ln of at 0 meter. Say yes or no. Did you understand this point? I am just putting this guy here. If the limit is given like this, fx going from x equals to 0 to x equals to 1, what would have been the answer? F of 1 minus f of 0, right? You agree to this point? Similarly, f of nx, and limit is also of nx only. So f of n of 25 minus f of n of 0. Is that clear to you? So what would be your final answer? Final answer will be Vt ln concentration at 25 divided by concentration at 0. So what is the value of Vt? From here Vt was actually dn by mu n, right? Dn by mu n ln concentration at 25 micrometer, that would be 10 to the power 16 e to the power 25 by, that would be 10 to the power 16 e to the power minus 25 by 18, because this is also in micrometer, this is also in micrometer, so micrometer is getting cancelled. This will be a certain value divided by concentration at x equals to 0. So if you put x equals to 0, e to the power 0 will be 1, so divided by 10 to the power 16. So what you are getting, this and this will get cancelled out. Ln e to the power something, ln e to the power x, what is the answer? X only. So 25 by 18 you will be getting. Now sir, negative sign will come, but you know that answer should be positive. My built-in potential will be positive. Here I have explained it. So what will be the answer? dn by mu n, this is your dn by mu n. So 25 by 960, dn by mu n, 25 by 960, 25 by 960. E to the power minus 25 by 18. Sorry, ln and e has been cancelled out, so 25 by 18. Answer will be positive only. I have forget this negative sign. At a lot of places, here also I forget the negative sign, right? At a lot of places I am forgetting the negative sign. So from here only the negative sign will come out, but I don't care about the negative sign. I even don't care about the limit, that sir n equals to, sir from here x equals to 0 to 25 you are going. You should have gone from 25 to 0. I don't care about all these things. I know that eventually they are going to be subtracted The only difference I will get is that either my answer will be positive or negative, but I know that my answer has to be positive only. So if I solve it, I will get the same thing. 25 into 25. Sir, here you need to convert it into the micrometer, centimeter, anything? No. Why is that so? Because this was 25 micrometer, this was also micrometer. So micrometer, micrometer got cancelled. So here no conversion is required. So 25 into 25 divided by 960 divided by 80. So 0.036, again the same answer I am getting, 36.169 millivolt. So eventually what do you understand? Here I am writing down the formula of built-in potential. That is coming out to be Vt into, forget about the negative sign, Vt into ln some concentration divided by some concentration. Some concentration, it could be 25 micrometer or it could be 0. Whatever you want to put, you can put it. Divided by some other concentration. That's it. This would be the answer. Did you understand this point or not? Sir, N2 by N1, N1 by N2. Sir, what is N1? This is what is N2? N1 is the concentration at x equals to 0 or 25 micrometer. N2 is the concentration at x equals to 25 or at x equals to 0. Sir, whatever the answer you get, you know that answer would be positive only because they are asking the difference between x equals to 0 to 25. So don't care about what is N1, what is N2. You just know that I need to put the concentration at a particular point and at the other point. And then I just need to divide them and then take ln. You can see that this particular expression. Just keep your notice here. Keep your notice here. So what we have done is that from here we converted the formula in this manner. Then I know that if I differentiate, if I integrate, then dx and dx will come out and then I will integrate. So if I integrate, integration and d will get cancelled out, and what I would see is that limit of ln will go from one concentration to other concentration. So ln of one concentration to other concentration. So if I reach from this formula to this formula, there is only one thing involved, that is integration with respect to dx from one concentration to other concentration. The concentration at x equals to 0 or 25, the concentration at x equals to 25 or x equals to 0. I don't care about that because in the final answer only the sign will change, nothing else will change. I hope everything is making sense to you. Like when you study this particular topic, people will get confused in sign. Sir, positive sign would come, negative sign would come. I am telling that don't even remember the sign. Just remember the expression. ln, like in the PN junction as well, I will write down the same expression, and there also I will not tell that sir which value will come upward, which value will come downward. There also I will not tell. There also I will say the same thing, that you will solve the question there and just you will see the sign. You will draw the diagram in this manner. You will draw the diagram in this manner, and then you will get to know that whether where the potential is positive, where the potential is negative. And in most of the times in the examination, they will ask only the magnitude of the potential difference. They will not ask the sign. They will ask only the magnitude. And if they are asking only the magnitude, then you would know how to solve it. So better than focusing on these formula and everything, we should focus on the diagram. If I am able to make the diagram, most of my job is done. Then I can write down the formula of built-in potential, then my job is done. Simply the answer would be Vt ln one concentration divided by other concentration. And you know that answer of built-in potential will be in volts. So here also I will be having volt only, and this would be some certain answer because concentration divided by other concentration. So unit to unit will be getting cancelled out. So this is unitless and this is having a unit of volt. So answer will be in volts. So this is how you can remember as well. Although in this question it was not required because it was not coming out to be a function of x. But if it was coming out to be a function of x, then this integration would have been a bit difficult for you. But even if it is coming out to be a function of x, what I have done is that we don't even require the built-in electric field. Without even calculating the built-in electric field, I can directly tell the answer of built-in potential. How will I tell? Vt ln one concentration divided by the other concentration. That's it. And how did I derive it? The complete derivation I have solved it. Dx get cancelled out, Vt d ln x, integration to d gets cancelled out, then one concentration divided by the other concentration. So if you keep your concentration, if you just listen to my words, then surely you will be able to understand it, right? So let's see this. Determine the induced electric field in a semiconductor in thermal equilibrium given the linear relation of the donor concentration. So sir, here they have given that donor concentration. Here they did not tell that sir it is the value of your number of electrons. What I mean to say is that someone will say sir number of electrons will be, sir number of electrons nx will be equals to ndx by 2 plus under root, this doubt you may have, but what you can see that Ni value is not given. So if Ni value is not given, then you know that Ni value is very small compared to this doping concentration. So you know that Ni is not given, that means NdX is pretty larger than Ni. Okay. So from here what you would see is that Nx is approximately equals to Ndx only, right? So this number of electrons, this electron concentration per unit volume is given. The length x is in the micrometer. Just make sure that I will use the length in the centimeter whenever it is required. So this is given. What you need to find? You need to find the potential difference. Okay, you need to find the potential difference. You don't need to find the built-in. Okay, electric field also you need to find. Induced electric field, built-in electric field they can call it, or induced electric field they can call it. So you need to find the induced electric field in the semiconductor in thermal equilibrium. Thermal equilibrium means there is a constant temperature. At that particular temperature there is no recombination, there is no generation. This process I have already told. I have told the meaning of thermal equilibrium. Also there is no battery also applied. No battery is also applied. So in this thermal equilibrium you know that there will be some built-in electric field. That electric field you need to find. Also you need to find the potential difference as well. So let's do it. And here also you know one thing. If I draw the diagram, so you can see that if x increases, then this donor concentration is decreasing. So if this is your x equals to 0 and this is your x equals to 1 micrometer, then with the increase in x, donor concentration is decreasing. That means the number of electrons will also decrease. So here more number of electrons are there, and here less number of electrons are there, right? So what will happen is that electrons will diffuse. Electrons will diffuse. So here they will create the positive charge and here they will create the negative charge. So the direction of electric field will be again from x equals to 0 to x equals to 1. Okay, and what about the potential? This will be positive potential, this will be negative potential. So basically the answer again here will be positive only, because x equals to 0 is at higher potential and x equals to 1 is at lower potential, right? So let's find out the built-in electric field. So you can either derive the formula or you can simply write down the formula, that is Vt by Nx d by dx Nx, right? Negative sign is there, but I don't care about the negative sign. What is the value of, let's put the negative sign. What is the value of Vt at room temperature? It is going, so 0.0259 divided by Nx. Nx is 10 to the power 16 minus 10 to the power 19 into x, into the differentiation of this one, what that would be, minus 10 to the power 19, right? So what you are getting, 0.0259 10 to the power 19 divided by 10 to the power 16 upon 10 to the power 16 minus 10 to the power 19x. So this is coming out to be a function of x, right? So they can ask you what is the value of a built-in electric field at x equals to 0. So what will be your answer? So this and this will get cancelled out and 10 to the power 3 will be multiplied. So 25.9 volt per centimeters, because everything is going into the centimeter. Here you are not putting the value of x. Whenever you put the value of x, at that time you should be taking care, right? So if someone asks you what is the value of a built-in electric field at x equals to 0. So if I put x equals to 0, what I will do, 0.0259 into 10 to the power 19 divided by 10 to the power 16. So this will be gone, 10 to the power 16, 10 to the power 3. So what you are getting, 25.9. Answer will be in volt per centimeter. Now if I ask you what will be the value of a built-in electric field at x equals to 1 micrometer, what do you think, what will be your answer? I want your answer. I want to see what value you put here. So 0.0259 10 to the power 19 10 to the power 16 10 to the power 19. Here I need to put the value of x. What I will put? I know that everything is going into the centimeter. This is centimeter cube inverse, right? So only here only I need to use the value of centimeter cube. So here I am using centimeter cube only. So everything is going in centimeter. Now I need to put the value of x equals to 1 micrometer. So what I will do? X equals to 1 micrometer is equals to 10 to the power minus 4 centimeter. So in place of x, what I will put? 10 to the power minus 4. Are you able to understand this point or not? Okay. So 10 to the power minus 4, it would become 10 to the power 15. So it doesn't make much sense, right? 10 to the power 15, because 10 to the power 16 is larger than 10 to the power 15. If I want to make it 10 to the power, then 10 micrometer I would have to do. 10 micrometer is not even possible. So yeah, let's keep this only 10 to the power minus 4. So what we are getting? 10 to the power minus 4. I was just thinking to change the problem, but let's not change the question. So let's keep this question only. So what we are getting? 0.0259 10 to the power 19 divided by 10 to the power 16 minus 10 to the power 15, right? So 10 I can take common. Basically this can be replaced with 10 into 10 to the power 15 minus 10 to the power 15. So 10 to the power 15 is common. So 9 into 10 to the power 15. What you are getting? 0.0259 into 10 to the power 19 divided by 9 into 10 to the power 15. So what you are getting? 0.0259, 0.0259, 0.0259 divided by 9 into 10 to the power 4. So that would be 28.7 volt per centimeter. Okay. So this is your built-in electric field at x equals to 1 micrometer. Well and good. Fine. Now what I need to find? Built-in potential. So if I go by this formula, then calculation will be difficult. I will have to integrate. That integration will be a bit difficult. But I told you, I remember answer ln divided by, since it is the whole concentration, sorry, since it is the electron concentration, so one concentration divided by the other concentration. So value of Vt I already know, 0.0259 ln concentration at 1 micrometer or concentration at x equals to 0. So what will be the concentration at x equals to 0? That would be 10 to the power 16. And what would be the concentration at x equals to 1 micrometer? What I mean to say is that, what is my N1? N1 is the concentration at x equals to 0. I could have taken the concentration at x equals to 1 micrometer as well, but I am taking the concentration at x equals to 0. What is that? Concentration at x equals to 0, that is 10 to the power 16. Right? And what will be the concentration at x equals to 1 micrometer? 1 micrometer means 1 micro. What does that mean? 10 to the power minus 4 centimeter. Right? So if I put 10 to the power minus 4 here, so 10 to the power 15, 10 minus 1, 9 into 10 to the power 15. 9 into 10 to the power 15. 9 into 10 to the power 15. So 10 by 9. 10 by 9 ln into 0.0259. So 27.28. No, sorry, 2.7. 2.72 millivolt. This is the answer we are getting. Isn't it too less? Am I doing some mistake? 10 by 9. What is the value of ln 10 by 9? Yeah, 0.1, 2.72 millivolt. Answer will be positive only because this will be at the higher potential, this will be at the lower potential. So even if you had taken opposite, let's just say 9, let's just say if someone had solved in this manner, sir, I had solved in this manner, then sir, what you would have got? 9 by 10, so ln 0.9 you would have done, 0.9 ln. So just try to do it in the calculator. So same answer you are getting, just negative answer you are getting, nothing difference is there. Are you able to understand this point? What I am saying is that, let's just say if you have put this upward and the other, this would have been upward for you, someone would have taken N1 as value of electron concentration at 1 micrometer. Then only difference would be of negative sign, nothing else. Only difference would be of a negative sign, nothing else there. Okay. So answer would have been same only. Answer would have been same. So you are getting minus 0.1, then you will multiply with 0.0259, So answer you are getting is 2.72, but in the negative. But you would see that, sir, x equals to 0 will be at higher potential. So my answer would have been positive only. So you would put a positive sign here. So forget about the sign, don't care about the sign, sir, positive sign, negative sign, don't care about that. Just solve the problem using the formula without looking at the sign, and then eventually you would see that we can apply positive sign or negative sign as per our diagram. So x equals to 0 will be at higher potential, x equals to 1 will be at lower potential. That's why here the positive sign would come and here the negative sign would come. Okay, well and good. So yeah, this question also we have solved. Now this question, first you will try it on your own. Very very high chance that you will not be able to solve it. Just just try thinking, what is this 12 volt per centimeter? Okay, I am not saying that you have to solve it. It is a very good question. It will take 30 minutes to explain. I will take roughly around 30 minutes or 20 minutes for this particular question. So you you try doing it. If you are able to do it, very good. Like try everything about this question, that you let me know whether there is an external electric field or internal electric field, whatever it is, try everything and then try to solve it. From this question you will learn a lot of new things. Mathematics will also be used here. Okay, so try doing it. I have to take some break, I have to drink some water, and then I will come back and we will solve this particular question. Yeah, thank you. Yeah, welcome back. So did you try this question? So first what we will do is that we will make the diagram. Constant electric field of 12 volt per centimeter is existing in the plus x direction for a n-type gallium arsenide semiconductor. So there is a semiconductor of n type and there is an electric field in the positive x direction. Let's just say this is your x equals to 0, then this would be your x equals to 50 micrometer. So in this positive x direction there is an electric field. Now sir, this is a built-in electric field, this is an external electric field, we don't know. Only we know that there is an electric field which is having a value of 12 volt per centimeter. Sir, built-in electric field, external electric field, we don't know, right? Let's read the question again. The total current density is constant and it is equal to 100 ampere per centimeter square. Let's just say if there was no external source, if there was no external source, if E external was 0, then the current density has to be 0. If E external was 0, then current density has to be 0, but J is equals to 100 ampere per centimeter square, which is non-zero. What does that mean? That means surely some external voltage source have been applied. Surely some external voltage source have been applied. So yes, external source is there. That's why there is a current. No, otherwise current would have been 0. Now because of the external source only you are getting 12 volt per centimeter. It is not necessary, because in the semiconductor as well built-in potential could be there. Let's just say because of the semiconductor you are getting electric field in this direction and I have applied the battery somewhat like this. Then what will happen? This built-in potential will be opposing this battery, because this battery will say that my electric field should be like this. But built-in potential will say that my electric field will be like this. So external and built-in both will be opposing each other. So you cannot say that sir 12 volt per centimeter is coming because of the battery. No, you cannot say that. You just know that total is 12 volt per centimeter. This is what you know. That's it. Nothing else you can comment. So total electric field is 12 volt per centimeter. This is what I know as of now. Now read the next line, very important line. A lot of students would have ignored this line, I know that. At x equals to 0, drift and diffusion currents are equal. At x equals to 0, what is the complete current? It is not a function of x. It is a constant current. At all the points, the current is constant, 100 ampere per centimeter square at all the point. But what they are saying is that at x equals to 0, the drift current and the diffusion current both are same. Both are same. At x equals to 0, drift current and diffusion current both are same. Both are same. Adding up both of them, you will get 100 ampere per centimeter square. If they were opposite in the direction, what I am saying that let's just say drift current is in this direction and diffusion current is in this direction. If they were opposite in the direction and they are saying that both are equal, that means I'm not sure whether they are talking about the magnitude or whatever they are talking about. Let's just say that by this statement I understand that they are talking about only the magnitude. So if drift current is 50 ampere, then diffusion current is also 50 ampere only. If I am saying that if both were opposite, then total current would have been 0 at x equals to 0. If both of the currents were opposite at x equals to 0, then total current would have been 0, but total current is actually 100 ampere per centimeter square. So what do you understand by that? I understand that actually both of the currents are added. And if both of the currents are added, what does that mean? That means both of the currents are in the same direction. That means diffusion and drift currents both are having the same direction only. Do you understand this point or not? What they are saying is, what I will write it down, if drift and diffusion current, if drift and diffusion currents were in opposite direction, then total current at x equals to 0 would have been 0 only. But total current at x equals to 0, is given as 100 ampere per centimeter square. That means drift current at x equals to 0, is equals to diffusion current at x equals to 0 is equals to 50 ampere per centimeter square, and both in the same direction. So from here what you understand is that drift and diffusion currents both are actually in the same direction. So this is the conclusion that we have made. Now you let me know what will be the direction of a drift current. So what is the applied electric field? This is the eventually applied electric field. Like this is the total applied electric field. So let's just say there was an electron here. Because of this electric field, the electron will be drifting in this direction. And if it is drifting in this direction, then the direction of drift current would have been this. So this would have been the direction of drift current. I drift. Let me make it here. Since the applied electric field, this is your applied electric field, total electric field, not applied electric field, this is your total electric field. This is my total electric field. Since this is the total electric field, then electron would be drifting in this direction. And if electron is drifting in this direction, that means I drift would have been in this direction. And I know that the direction of I drift and I diffusion both are same. That means diffusion current will be in this direction as well. Did you understand this point or not? So if diffusion current is in this direction, that means where the electrons would have been diffused, would have diffused in this direction, because if electrons have diffused in this direction, then only the diffusion current would be in this direction, no? So this would have been the diffusion of electrons. This I am calling as x equals to 0, and this I am calling as x equals to L, or x equals to 50 micrometer. Let's start again from the beginning. What I am saying, in the beginning I started reading the statement. I got to know that total current is non-zero. That means surely some external battery is applied. I don't care what kind of battery is applied, what is the potential of that battery, that I don't care. Now the next statement if I read, I get to know that the total current is constant, and and at x equals to 0, drift and diffusion currents are equal. Now they are talking about the magnitude or they are talking about the direction, I am not sure. So one thing I am pretty sure, that drift current is also 50 ampere and diffusion current is also 50 ampere. If if they were opposite, then they would have cancelled out each other and answer would have been 0. but at x equals to 0, the current is non-zero. So what I have written, if drift and diffusion current would be in the opposite direction, then total current at x equals to 0 would have been 0, but actually the current is non-zero. It is non-zero. And since it is non-zero, that means both of the currents are being added. That means drift and diffusion currents both are actually in the same direction. So both currents are flowing in the same direction. This is the conclusion I have made. Now again I came back to this question. On this semiconductor, the external field is this direction. The external field is in this direction. Total electric field is in this direction. So now how my electrons will drift? So electrons will be drifting in the opposite direction. That means the drift current would be in this direction. So if this is the direction of drift current, then I have said that drift and diffusion, both currents are in the same direction. And since they are in the same direction, so this is the drift current, so this would be the diffusion current. And if this is the diffusion current, then electrons would have diffused in this manner. Electrons would have diffused in this manner. What does that mean? That means that here the electron concentration would have been more, and here the electron concentration would have been less. Did you understand this point or not? Okay. So only on this analysis only the question can be framed. That where the electron concentration would be more, where it would be less. Only on this analysis only the question can be framed. Are you able to understand this point? Now let's see next thing. Mu n value is given. You need to determine the expression of electron concentration Nx. Expression of electron concentration we need to determine. So what is given? Complete current is given. I know that both of the currents will be added. That I know both of the currents will be added. Plus J diffusion. Both of the currents will be added. This is equals to 100 ampere per centimeter square. I know that everything is going in ampere per centimeter square. Let's write down. What would be your drift current? Sir, what about the built-in potential and anything? I don't care about the built-in potential now, because I know that total electric field I already know. So if my electrons are drifting, those electrons are drifting because of this field. So can I write down the expression? Yes. N Q mu E. N Q mu E. E total. Here in place of E, what I am putting? E total. And what about the diffusion? Q dn dnx by dx. Okay. Mu n value is given. Did they give the value of dn? No, 300 Kelvin they are talking about. So I need to find out the value of dn as well. So what would be the value of dn? Dn would be mu n by, okay, sorry, d is equals to uv. So mu n into vt. So value of mu n is given as 8 into 10 to the power 3. 8 into 10 to the power 3, and vt is 25.9 into 10 to the power minus 3. Okay, so you can solve it, you will get the value of dn. Et value you are having, mu n value you are having, q value you are having, this q value you are having, dn value also you are having. So you will get the expression. Let's write down the values. 100 is equals to, I have written down the values, so it will not take much time. 100 is equals to nx, the value of q is 1.6 into 10 to the power minus 19. Value of mu n is 8 into 10 to the power 3. The total electric field is 12 plus q is 1.6 into 10 to the power minus 19. dn value, this calculation I will have to do, so that I will do it, so forget about it, just remove this calculation. So dn is simply, just I am writing down, dn is simply mu n into vt. So I will just put the value mu n 8 into 10 to the power 3, vt value I already know, 0.0259 into dnx by dx. Okay, so you solve it and you will get the you will get the relation somewhat like this. How you will get the relation? So you solve all this calculation, you do all this calculation. So dnx by dx plus 463.32 nx is equals to 301.64 into 10 to the power 16. So this is the differential equation I am getting. I will put this as A and this as B. So I just need to solve this differential equation that I would be able to solve. Okay. So what I am saying, now the beauty will come. Okay. Now we need to solve the differential equation, and I know that a lot of people will be doing wrong here. So how will you solve this differential equation? Mathematics. Sir, I will be thinking of Laplace transform. So sir, what I can do, dy dx can be replaced with s, nx would be replaced with ns plus a ns. Sir, b was a constant value, so it would be b by s, and this step is wrong. This step is wrong. Why so? Because where you have considered the initial condition you forgot, no? Right? What I am saying is that if f of t is having a Laplace transform of f of s, capital F of s, then dy dt of ft, what will be its Laplace transform? S f of s. Is that correct? No. Minus f of 0. So similarly here s ns, what I am saying is that Laplace transform of nx is ns. Okay, this is what I am saying. Laplace transform of nx is ns. So s ns minus n of 0. So this n of 0 also I need to consider, right? N of 0, can you find out? You can surely find out. How will you find out? Just think about it. Just think, how will I find out the value of n of 0? Now this is my equation, or let's solve it more. What I can do is that s plus a will come common. So from here if I find out, so b upon s into s plus a plus n of 0, and don't forget about this s as well, because a lot of people will write down Laplace transform of b will be b only, b by s. A lot of time it happens with a lot of students. Laplace transform of 3 is 3. No, 3 by s. S upon s plus a. So how will I find out the value of n of 0? So now n of 0 I need to find out. What do I know? Drift current at x equals to 0 is equals to 50 ampere per centimeter square. So what is the drift current? N q mu e, right? So nx value at x equals to 0, q mu and applied electric field E total will be equals to 50. Q value you know, mu value you know, Et value you know. So from here you can get the value of n of 0. So your n of 0 would be coming out to be 0.325 into 10 to the power 16 atoms per centimeter cube. So this is your n of 0. Did you understand how did I calculate this n of 0? Because initial condition was given, no? If you need to find out the initial condition, then you need to use the initial condition. What is the initial condition given? That at x equals to 0, the drift current is 50 ampere per centimeter square. So at x equals to 0, drift current is 50 ampere per centimeter square. So you use this condition and you got the value of n of 0. Now you will put it here. Okay. So now it is just mathematics. Anyway, I will have to add a page. So now it would just be mathematics. So n of s would be value of b. Can I put, or shall I solve it? So you know how to solve these equations, right? Laplace transform and anything, you know how to solve it. So I don't think I need to put up the full equation. So just if you have studied signal system, then you would be able to solve it. If you have studied mathematics as well, then also you would be able to solve it. Even if you are not able to solve as of now, don't worry. After studying mathematics and signal system, you will be able to solve these equations. Okay, very simple it is. So nx is coming out to be 0.65 into 10 to the power 16 minus 0.326 into 10 to the power 16 e to the power minus 463 0.32x per centimeter cube. This is the answer that you are getting. Although this kind of calculation will not come in the examination, very rare chance. Even if it is coming, then you are not going to solve it in the examination hall. But I'm just telling that what is the depth of this question. And from this equation you get to know that at x equals to 0, the concentration will be maximum. At x increases, what will happen? This whole value will go down, right? At x equals to 0, the n of 0 will be minimum. This will be minimum. Why is that so? Because as x increases, then this whole value will go down. If this is going down, then this whole value will go down. Something that is being subtracted, that is going down. That means this n of x will go up, right? If this value is going down, that means this whole value is going down. Or just calculate. No, just calculate. What they are asking? They are asking, they would have asked electron concentration at x equals to 0 and at x equals to 50 micrometers. So what is the value of electron concentration at x equals to 0? That is 0.65 into 10 to the power 16. Sorry, no. From here I will subtract. So what I will get? I will put x equals to 0 here. So what I will be getting? 0.65 minus 0.326. So that would be 0.325. Roughly around 0.325 into 10 to the power 16. Yeah. And if I put next, what they are asking, at x equals to 50 micrometer. So everything is going in centimeter only, ampere per centimeter square, everything is going in centimeter. So next, what they are asking, at 50 micrometer, so you can call it at 50 into 10 to the power minus 4 centimeter, right? So what I will be getting? 0.65 into 10 to the power 16 minus 0.326 into 10 to the power 16 e to the power minus 463.32 into 5 into 10 to the power minus 3. So let's do this calculation. Have I written down the answer? No. 463.32 into 5 divided by 1000 plus minus e to the power into 0.326 minus 0.65. So roughly around 0.6178 into 10 to the power 16. This much concentration I am getting. So concentration at x equals to 0, concentration at x equals to 50 micrometer. This is the answer I am getting. Okay, next what they are asking. Calculate that diffusion drift and diffusion current density is at 50 micrometer. So both of the components separately I need to find out. So what I would do? Third, so drift current I need to find out at 50 micrometer. Or let's write it down as the expression of x. So what that would be? N q mu e total. N q mu e total, and here mu n. So nx I am already having. Q value I already know, 1.6 into 10 to the power. Forget about it, I am not going to put the values. Simply I will write down the answer. J drift I need to find out at 50 micrometer, right? So at 50 micrometer, what is the concentration I am having? At 50 micrometer, concentration that you are having is 0.6178 into 10 to the power 16, 1.6 into 10 to the power minus 19, mu n value 8 into 10 to the power 3, right? 8 into 10 to the power 3, and total electric field is 12. External electric field is 12. Where is total external electric field? That is 12. Okay, so what you are saying, 16, 3, 19, this and this will get cancelled out. 0.6178 into 1.6 into 8 into 12. So 94.90. what I am getting, 94.90 ampere per centimeter square. Let me check it again. 0.61 into 1.6 into mu n, that is 8 into 12. Yeah, 93.6, 0.6178 into 1.6 into 8 into 12. Yeah, 94.9 or whatever it is, roughly around 94. This is what you are getting. So this is the value of a drift current here. So what will be the value of diffusion? You know that drift plus, you know that J total is equals to 100 ampere per centimeter square. So what will be your J diffusion at 50 micrometer? J diffusion at 50 micrometer, what that would be? 5.1, roughly around 100 minus 94.9, that would be roughly around 5.1 ampere per centimeter square. That's it. All good? All fine? So this is how I could have solved it. Calculation is complex, but you understood the conceptual part here, right? And just let me know one thing, what would be the direction of built-in electric field? This would have been the direction of built-in electric field. So now they are saying that total electric field is in this direction, which is 12 volt per centimeter. That means total electric field is going from x equals to 0 to x equals to 12. And built-in electric field inside going from x equals to 50 to x equals to 0. So what do you think, what will be the value of external electric field? That would have been greater than 12 volt or less than 12 volt. So external electric field would have been greater than 12 volt. It cannot be 12 volt, it cannot be lesser than 12 volt, it would have been greater than 12 volt. Why is that so? Because built-in electric field is opposing the external electric field. So you need to apply greater than 12 volt per centimeter so that this built-in electric field could be minimized. So external electric field would have been 12 volt per centimeter plus built-in electric field. If you want to find out the value of built-in electric field, that also you can find out. Okay, Nx value you are already having, Vt value you already know, and dnx by dx you can already do. So you can get the value of a built-in electric field as well. That would be a function of x. And similarly, you can find out built-in potential as well. So if you find out the built-in potential, then you can find out what should be the value of an external battery. Are you able to understand what I am saying? Basically, inside there would have been a battery like this, right? Positive side here, negative side here. So that's why this is the built-in electric field, no? Basically, externally you need to apply somewhat greater than 12 volt per centimeter. So there is something that is opposing. So if I find out built-in potential, if I find out a built-in potential, here if I find out built-in potential, can I find out the built-in potential? V built-in, what that would have been? Vt ln concentration at one point, concentration at the other point. So at both of the points I have find out the concentration. So 0.6178, 0.325, 0.6178 divided by 0.325, and Vt is 0.025. So let's find out this value. This is the built-in potential that I am finding. So 16.63, 16.63 volt. This is the built-in millivolt. Sorry guys. So I should write down 0.01663 volt. This is the built-in potential between what point? This is the potential between 50 micrometer, right? This is the potential between this 50 micrometer minus 0 micrometer. This is the potential between 50 micrometer minus 0 micrometer. This is the whole potential. Now you know that total external electric field is, total field is 12 volt per centimeter, right? total field is 12 volt per centimeter. So what do you think, what would have been your total voltage? That would have been 12 volt per centimeter multiply with total length. What is the length of this semiconductor? Total length is 50 micrometer. 50 micrometer, that would be, so this and this get cancelled out. So 60 into 10 to the power minus 4. So that would have been 0.06 volt. So this is the total here. No, it is not the thermal voltage, it is the total voltage. So this would have been the total voltage that semiconductor is feeling. So semiconductor feels like that across me this much total voltage is applied. How much total voltage is applied? This is what semiconductor is feeling. Semiconductor is feeling that across me 0.06 voltage is applied. I hope I have done the calculation correctly. 50 micrometer, so 10 to the power minus 4, so 600, 10 to the power minus 2. Yeah, 6 into 10 to the power minus 2. And here what I was getting? 1.6 into 10 to the power minus 2. And here I am getting 6 into 10 to the power minus 2. 6 into 10 to the power minus 2. So just let me know what should have been the value of external battery. That would have been 6 plus 1.6. That would have been 7.6 into 10 to the power minus 2 volt. This would have been your V external. I should have applied a battery of 7.6 into 10 to the power minus 2 volt. Why is that so? Because I know that there is something inside that is opposing it. Inside there is a battery of this much opposition. What is that? That battery is 1.6 into 10 to the power minus 2. But total, your semiconductor is feeling that I am having 6 into 10 to the power minus 2 volt. In this direction. Direction is also given, no? This is the direction of electric field. If this is the direction of applied electric field, then you know that this would be positive, this would be negative. But inside there is a built-in electric field which is in the opposite direction. So they are opposing each other. So total electric field came out to be 12 volt per centimeter. Why is that so? Because total voltage your semiconductor was feeling, that was 6 into 10 to the power minus 2. So externally how much you should have applied? Externally I should have applied 7.6 into 10 to the power minus 2 volt. And if they ask you what will be the external electric field, what would have been your external electric field? So that would have been 7.6 into 10 to the power minus 2 divided by 50 into 10 to the power minus 4 volt per centimeter. So you can solve it. 7.6 7.6 divided by 50 into 10 to the power 2. So 15.12 volt per centimeter. So externally I should have applied this much of battery, this much of electric field, so that it would have felt that, so that I should have applied a battery of 7.6 into 10 to the power minus 2 volt, because there is some built-in electric field which is in the opposite direction. Built-in electric field is in the opposite direction. So the external electric field and the built-in electric field are opposing each other. And since they are opposing each other, that's why the total electric field was 12 volt per centimeter. So from here I can find out the built-in electric field as well, because I have wrote down the this built-in potential for 50 micrometer. Built-in potential across these two terminals. Okay. Across the complete length, I have wrote down the built-in potential across the complete length, right? So across the complete length also I can find out the electric field as well, right? Okay then. So I hope you have understood the analysis here. Well and good. This part was not asked, but what I feel is that okay, like eventually in the examination, if they want to ask this particular part, then they have to give these values, right? In the examination, if they want to ask this particular part, they have to give these values, no? So in the examination, there is very rare chance that this kind of question would be coming, like this whole question would be coming. But in this 35 minutes of discussion, you would see that a lot of things we have discussed, and these things can be surely helpful in your examination. Okay, so you should be able to read the question very carefully, what they are saying, how the electric field is there, inside what would have been happening. So all these things cannot be discussed in theory. All these things could be discussed with the problem as well. It can discuss only with the problem. So this question was there and we have discussed it. So here our diffusion current gets completed. Now two more topics are there. One topic is minimum conductivity condition. Other topic is EK diagram. Okay. So these two topics we need to cover, but I need to take some break. So I will take the break and then we will study minimum conductivity condition. Okay. And this minimum conductivity condition will occur in P-type semiconductor only. So that also we will see. Do you remember the graph of conductivity versus temperature? Sorry, conductivity versus doping concentration. I told you that I am making it for N-type semiconductor only. The graph was like this. So for N-type semiconductor, this was correct. But in P-type semiconductor, something different will happen. So that we will see. Okay. So let me take some break and then I will come back. In that particular time, you revise this question again. That what all things are happening, sir, how everything is understood. Even if you are able to not do the mathematics, still it is fine. This is not the question of mathematics. This was the question of pure understanding. Okay. So let's meet in some time. Yeah, welcome back. So let's see this topic, which is minimum conductivity. So this is not related with diffusion current. This diffusion current has ended. Okay. Whatever you want to learn in the diffusion current, that you have already studied. This is a different topic, minimum conductivity, very simple topic. Till this date in the GATE examination, they never asked question on this topic, but who knows, they may ask in the future. So what we were doing in the beginning of the lecture, in the beginning of lecture 1, we had an intrinsic semiconductor. The conductivity of intrinsic semiconductor was low. Since the conductivity of intrinsic semiconductor was low, what we did was, we started doping this semiconductor. We could have doped it with donor atom or we could have doped it with acceptor atom, right, to increase the conductivity. Do you really think that always the conductivity will increase? In case of N type, always the conductivity will increase, but in case of P type, something different could be there. So let's check that out. So for any kind of semiconductor, what is the formula of conductivity? N Q mu N plus P Q mu P, right? Because both of the currents, because of the electron and current because of the holes, both will be in the same direction. So conductivity will be added. Now you know there is something called mass action law. N into P is equals to Ni square. So the whole equation I want in terms of N only. So what I am doing is that sigma is equals to NQ mu N plus Ni square by N Q mu P. Now what I will do, I will find the value of N. What this is, here sigma is a function of N, right? Q is a constant value, mu N is a constant value, Q is a constant value, mu P is a constant value, Ni square is a constant value. Only variable is N, because N will be in our hand. Doping will be in our hand. How much doping do I do? That will be in my hand, right? So what I will do is that I will find the number of N such that sigma is minimum. What I am doing, my target is find N such that sigma is minimum. This is the target. To find the maxima or minima, what do you do? D sigma by dn is equals to 0. So if I do d sigma by dn, if you differentiate this with respect to n, so what will happen? Q and mu n are constant. Q mu n are constant. Differentiation of n with respect to n will be 0. Here Q, mu p and Ni square are constant. Differentiation of 1 by n will be minus 1 by n square multiply with Ni square Q mu p, and that would be equals to 0. So value of n is coming out to be, Q and Qn will get cancelled out. From here you can see that value of n will come out to be Ni under root mu p by mu n. This is the value of n that you are getting. Similarly, if value of n you are having, then you can get the value of p as well. So what will be the value of p? Ni square by n. So what that would be? P would be Ni square by n if you do. So value of p will come out to be under root mu n by mu p. Now sir, you differentiated it and you equated it to the 0. Then how do you know that, sir, at this value of n or at this value of p, this is minimum? This could be maximum as well, no? What I am saying is that how could you tell that, sir, this value at this value of n or at this value of p, this is minimum, this could be maximum as well? Because if your graph is giving you differentiation equals to 0, so this could be maxima as well, this could be minima as well. You are not sure whether it is maxima or minima. For that you need to do the double differentiation. So you can do the double differentiation and you will get to know that it is minima only. So those who know mathematics, they would know that if I do the double differentiation, if I differentiate it twice, so here this term will be gone and you would see that double differentiation. Like, just if someone is having the doubt that, sir, why you are saying that at the differentiation you are getting minima only, you could get maxima as well. But actually this is minima only. When I do the double differentiation, what I get to know is that 2ni square divided by n cube q mu p I will be getting. And since this value will also be positive, this will be also positive, this will also be positive, this will also be positive. So here I can see that this double differentiation is coming out to be positive. If double differentiation comes out to be positive, that means this point was minima only. So at n equals to ni under root mu p by mu n and at p equals to ni under root mu n by mu p, your conductivity is minimum. So find out the electron concentration such that your conductivity is minimum. Answer would be ni under root mu n by mu p. Find out the hole concentration such that your conductivity is minimum. Answer would be ni under root mu n by mu p. These two are the answers there. Now just let me know one thing. You already know that generally our mu p is greater than mu n. So out of these n and p, which value will be larger? If mu n is generally, sorry guys, mobility of electrons is greater than the mobility of hole. So generally mu n is greater than mu p. So out of these two, which value will be larger? Mu n is greater than mu p. So this value will be larger than this value. So from here what you can see is that for minimum conductivity, number of holes should be greater than number of electrons. This relation I already know, and here for minimum conductivity, value of p is coming out to be ni under root mu n by mu p, and value of n is coming out to be ni under root mu p by mu n, right? From here I can see that mu n is generally greater than mu p. That's why this p value is greater than n. And this condition is achieved in which kind of semiconductor? In intrinsic semiconductor? No. In n-type semiconductor? No. In p-type semiconductor. So minimum conductivity condition you can achieve in p-type semiconductor. What does that mean? That means that this I was having an intrinsic semiconductor. I was having. Then I started doping it. When I started doping it, I would expect that my conductivity should rise. Let's just say when there was no doping, this was my conductivity. But I would expect that just as I start the doping, my conductivity should rise. But what will happen is that initially it will decrease, it will reach at some point, and after that it will increase. So in p-type semiconductor, conductivity actually first decreases and then it increases. We will understand it by an example as well. Don't worry about that. Okay. So this is only for p-type semiconductor. So in p-type semiconductor, what you can say is that you can achieve the minimum conductivity condition. In n-type semiconductor, what will happen is that just as you have started doping, let's just say this was your intrinsic conductivity. Just as you started doping, always it will rise up only. What will be the nature? I don't know. Nature could go like this or whatever it is, but surely it will rise up only. It will not decrease. But in p-type semiconductor, what will happen is that first it will decrease and then increase. And we will see with respect to example, it will be more clear to you. So for the numerical purpose, what values you need to remember? This particular thing you need to remember, this particular thing you need to remember, and you got to know that the minimum conductivity condition can be achieved in p-type semiconductor. So this I will write down. Minimum conductivity condition can be achieved in p-type semiconductor. Okay. Now what will be the value of minimum conductivity? Basically, what was your sigma. Sigma was n q mu n plus p q mu p. For minimum conductivity, your n was coming out to be ni under root mu p by mu n, and your p was coming out to be ni under root mu n by mu p. Okay. So what would be your sigma minimum? So just put these values, ni under root mu p by mu n into q into mu n plus ni under root mu n by mu p into q into mu p. So what you are getting? This and this, what it will give you? Under root mu p mu n, and this will also give you under root mu n mu p. So what you are getting? 2 ni into q under root mu n mu p. This is the value of your sigma minimum. Just remember these three expressions and you will be able to solve the problems. All good? All fine? Here I have written it can be achieved in p-type semiconductor, or it could be compensated p-type semiconductor as well. Basically the condition is the number of holes should be greater than the number of electrons. This is the condition. Number of holes should be greater than the number of electrons. So this condition I can achieve in compensated p-type semiconductor as well, no? So compensated p-type semiconductor. So this minimum conductivity condition can be achieved in p-type semiconductor or in compensated p-type semiconductor. Okay. So so number of electrons value you should remember, number of holes value you should remember, and this minimum conductivity formula you should remember. Even if you forget it, you will be able to derive it very easily. Okay, so formula is 2 niq under root mu n mu p. Okay, let's solve the question. A semiconductor is having intrinsic carrier concentration of 1.5 into 10 to the power 10 centimeter cube. The semiconductor is doped to achieve the minimum conductivity condition. So how will you dope it? So they have already given that ND value is 0. What does that mean? That means you are doping the acceptor atom, and it is pretty obvious as well, because you want to dope the acceptor atom only, then only you will get the minimum conductivity condition. So what they are asking, determine the required dopant concentration. That means you need to find out the value of Na. How much atoms you need to dope such that you achieve the minimum conductivity condition, and what would be the corresponding minimum conductivity. This is what you need to find. So for minimum conductivity, I remember the number of holes should be under root mu n by mu p. So I know that my holes should be 1.5 into 10 to the power 10. Mu n is 1300 divided by 500. Two point four two into 10 to the power 10. These many holes I require, and how many electrons I will have, because I know that mass action law will be valid. So how many electrons I will have? So forget about this formula. I will not remember this formula. I will just do Ni square by P. So what is my Ni square? 2.25 into 10 to the power 20 divided by 2.42 into 10 to the power 10. So what I am getting? Reciprocal into 2.25. So you are getting 0.93. 0.93 into 10 to the power 10 centimeter cube. So what I have done is that I started doping that donor atoms. At some point of time, the number of holes became this much, the number of electrons became this much. At that particular point, my conductivity was minimum. So now looking at this particular expression, you would say that, sir, number of dopant atoms should be 2.42 into 10 to the power 10. Absolutely wrong. No, you need to apply the charge neutrality equation. No, charge neutrality equation. Don't do this kind of error. That, sir, number of holes are 2.42 into 10 to the power 10. What does that mean, sir? The number of dopant atoms should be 2.42 into 10 to the power 10. Absolutely wrong. No. This is the value of P that you have got. Are you able to understand that P was actually equals to Na by 2 plus under root Na by 2 whole square plus Ni square, right? So from here you need to find the value of Na. You need to find the value of Na. But solving this equation will be difficult. So I'm not going to solve this equation. What I will do, from where this equation was derived? From the charge neutrality equation. Charge neutrality equation. What did this charge neutrality equation said? Positive charge equals to negative charge. So Na will be a negative charge plus electrons will be equals to P plus Nd. Positive charge, positive charge. Here Nd is 0. So what does that mean? Na would be equals to P minus N. So what will be the value of P minus N? 2.42 minus 0.93. So minus 2.42. So 1.48. 1.48 into 10 to the power 10. What do you think? Is this the final answer? Is this the final answer? No. Why is that so? Because only 60% ionization is done. So if I give this much of dopant, if I put 1.48 into 10 to the power 10 boron atoms, if I put 1.48 into 10 to the power 10 boron atoms, so only 60% of this will give me hole. But I need this to be fully ionized. What does that mean? That means there should be some value of X. There should be some value of X whose 60% should be equals to 1.48 into 10 to the power 10. Are you able to understand this point or not? 60% ionization is done. What does that mean? That means only 60% of this guy will be able to contribute. But actually you require acceptor atom to be acceptor atom to be 1.48 into 10 to the power 10. That means this much acceptor atom you require. But useful acceptor atom are some X, only 60% of that. If I say that I will dope only 1.48 into 10 to the power 10 acceptor atom, then only 60% of this will be helpful. What does that mean? 1.48 into 0.6. So I will be getting only 0.88 into 10 to the power 10 useful atoms. Rest all the atoms will be wasted. But what I require, this is my requirement. This is my requirement. If this is my requirement, this number is my requirement. That means there should be some number X whose 60% should be 1.48 into 10 to the power 10 centimeter cube, right? Centimeter cube inverse. So this is not the final answer. What you will do is that 1.48 divided by 0.6. So 2.46. So value of X you are getting is 2.46 into 10 to the power 10 centimeter cube. There you go. So what does that mean? 2.46 10 to the power 10 atoms per centimeter cube doping will make sure that you achieve the minimum conductivity condition. Are you able to understand this point or not? So I was doping. At this point, I was getting the minimum conductivity. So there was some conductivity I was getting. Then I was doping. I got the minimum conductivity, and after this, it will increase. And let's check. What I want to check is that this particular scenario I am having. What I will check is that I will check the conductivity. I will check the intrinsic conductivity. First, what I will check? First, I will check the intrinsic conductivity. What I am gonna do is that this is the number of dopant atom I have got. This is the answer I have got. Next, what I need to find out the value of minimum conductivity. But first, let's check what was the value of intrinsic conductivity when there was no doping. When there was no doping, then what was the value of conductivity? At that point of time, this was your conductivity, right? This is your when no doping was there. No doping was there. When no doping was there. Okay. So what would have been the answer? 1.5 into 10 to the power 10 into 1.6 into 10 to the power minus 90. I don't think mu n value is given. Okay, it is given. 1.5 into 10 to the power 10 and q value 1.6 into 10 to the power minus 19. Mu n mu p 1800. Okay, so you solve it and let's check what answer do you get. 1.5 into 1.6 1800. So 4.3 10 to the power 13 4.32 into 10 to the power minus 5 Siemens per centimeter. This is the answer we are getting. This is the intrinsic conductivity. Now at this much of doping, how many number of electrons and holes you are getting? At this much of doping, these number of electron and holes you are getting, right? At doping of Na equals to 2.46 into 10 to the power 10. 2.46 into 10 to the power 10 atoms per centimeter cube. At this much doping, what is the scenario? At this much doping, your conductivity would be, at this much doping, what is the value of N? Number of electrons are 0.93 and 2.42. 0.93 into 10 to the power 10 per centimeter cube, and here number of holes were 2.42 into 10 to the power 10. So now you apply the formula of sigma, although it will be minimum only, so I am already putting minimum. So I already know NQ mu n plus PQ mu P. Okay. So you put the value, this value will be surely less than this, or I already know that what will be the formula? 2Ni Q under root mu n mu P. Okay. So either you put this value of n here, Q value you put, mu n value you put, P value you put, Q value you put, mu P value you put. You will get the same answer, whatever the answer that I am going to get from this particular formula. So what I would do is that 1.5 into 10 to the power 10 into 1.6 into 10 to the power minus 19 under root 1300 into 500. So 3 into 1.6 into, get out it, 13 into 5, 13 into 5, then you take the under root, so 10 to the power 2, then you take the under root into 1.6 into 1.5 into 2. So you are getting 3.38 I have got into the power 12, and yeah, 3.86 into 10 to the power minus 5 Siemens per centimeter. So this is the value of your minimum conductivity, and this was the value of your intrinsic conductivity. So even after doping you are getting lesser conductivity, and just try checking, let's just say Na value I have taken as 10 to the power 10 only. So you take the Na value as 10 to the power 10, then you calculate the value of number of electrons, then you calculate the value of number of holes, and then you again check the conductivity. You would see that this conductivity is coming lesser than this. So what really happened was, there was a intrinsic conductivity. From intrinsic conductivity you are going down, and then you will increase. After this point you will increase. What I mean to say is that, let's just say you take the doping value Na value as 3 into 10 to the power 10. What I am saying, you take the doping value 3 into 10 to the power 10. From there, then you apply this formula. Out of this 3 into 10 to the power 10, only 60% are useful. So first you will calculate the 60% of 3 into 10 to the power 10. then you will put the value here, you will calculate the number of holes, then you will calculate the number of electrons, and then you will apply this formula of conductivity. You would see that now the conductivity is coming more than this. So this is the minimum conductivity condition. After that, conductivity will rise up. So this phenomena happens only in p-type semiconductor. Are you able to understand this point or not? So usually I have seen that people remember the formula of a minimum conductivity. They actually do not understand what is the meaning of minimum conductivity. So just this particular topic is saying that in p-type semiconductor, you have to, when you are doping, make sure that doping should be very larger than Ni. Because if you are doping just near to Ni, what was Ni? 1.5 into 10 to the power 10. And if I am doping 2.46 into 10 to the power 10, which is near to Ni only, then my conductivity is actually reducing. So I was doping to increase the conductivity, but actually it reduces. So in p-type semiconductor, I need to take care of this particular thing. Is that clear to you or not? Okay. So if any question can be framed from this particular topic, then it would be this particular question only. From here only every question can be framed. Just make sure that you are not going to find out the Na value from this particular formula. You will go to the charge neutrality equation. From there you would see that Na would be equal to P minus N. So value of P you would have already found, N value you would have already found. So from there you will calculate the value of Na. Is that clear to you? Okay then. So this topic is also completed. Next we need to study about EK diagram, but before that let's see some mathematics. Our next topic would be EK diagram, but before that I expect you to solve some question of mathematics. Can you draw the graph of y equals to x square? Yes sir, surely I can draw the graph of y equals to x square. As x increases, y also increases. So what kind of graph you will be getting? Sir, this kind of graph I will be getting. Y equals to x square, and since it is an even graph, so sir, this kind of graph I will get. Okay. Now the graph is y equals to x square. At x equals to 1, what is the value of y? Y is equals to 1. Now what about y equals to 2x square? At x equals to 1, what will be the value of y? That would be equals to 2. So what kind of graph you will get? This graph you will get, right? The graph will go like this or like this. The graph will be going like this or like this. It will be going like this, right? Why is that so? Because at x equals to 1, at x equals to 1, because at x equals to 1, at x equals to 1, this y equals to x graph, y equals to x square graph should give me value 1, but y equals to 2x graph, 2x square graph should give me value, higher value. So this value will be 2, but this value will be 1. Is that clear to you or not? Okay. 1, 2. So this graph is for y equals to 2x square. Now what I need to do, you need to find out double differentiation. So for the first case, what will be your double differentiation? For the first case, when y is equals to x square, when y is equals to x square. So here, what will be the value of? So first you differentiate, you will get 2x, double differentiation, you will get 2. And for this one, what you will get? So first differentiation you will get 4x and then you will get 4. So in this particular case, double differentiation is higher. Now if I ask you this curve and this curve, which graph is more curvy? This graph is more curvy or this graph is more curvy? This graph got the curve, no? So this is more curvy. So this is having more curvature, more curvature. Now in these two graphs, if I ask you y equals to 2x square or y equals to x square, which graph is more curvy? This graph is more curvy, right? Y equals to 2x square is more curvy. So y equals to 2x square is having more curvature. Y equals to 2x square is having more curvature. Curvature. Along with that, y equals to 2x square is also having higher value of double differentiation. Higher value of double differentiation as well. What does that mean? If you are getting higher value of double differentiation, that means you will say that your graph is having more curvature. High double differentiation means high curvature. Is that clear to you or not? From this particular question, only this conclusion is there. What is the conclusion? The conclusion is that the meaning of double differentiation is nothing but the curvature. That's it. Higher curvature means higher value. That's it. This is the meaning of this question. We will be using it somewhere. To understand our concept, we will be using it somewhere. That's why I took this question. I draw the graph of y equals to x square, y equals to 2x square. This is how the graph will go. I know that this graph is having more curvature. Y equals to 2x square is having more curvature. More curvature means along with that you can see that it is having higher value of d square y by dx square as well. So higher value of double differentiation means more curvature. That's it. Okay, I will be using it somewhere. Another question, you need to draw the graph of y equals to x square, y equals to minus x square. So what will be the graph of y equals to x square? Sir, the graph of y equals to x square we have already made. It will go somewhat like this. Now what will be the graph of y equals to minus x square? So the graph of minus x square will go somewhat like this. Okay. So this is the graph of y equals to x square. So this is the graph of y equals to minus x square. What this is? This is your concave upward. Concave upward. Can I call it concave downward? This graph is concave downward. What will be the value of double differentiation here? That would be 2. And what will be the value of double differentiation here? That would be minus 2. So if your graph is concave upward, then your double differentiation will be positive. And if your graph is concave downward, then your double differentiation will be negative. Understood? All fine? Okay. Sir, why you are teaching all this thing? It will be used somewhere. That's why. Otherwise, like when I teach the concept, in between I teach the mathematics, then it will be, you will feel like that, sir, why in between mathematics? But before teaching the concept only, I am teaching you the mathematics. Now the concept will feel like a cakewalk for you. So did you understand? This was the more important point. This was the most important point, I would say. If you understand this point, then surely the gate examination question you will be able to solve. That's for sure. That means higher differentiation means more curvature. Okay. Higher double differentiation. Higher double differentiation means more curvature. Now before starting our EK diagram, let's revise our chemistry that we studied in our class 11th 12th. So what de Broglie said? De Broglie said that if a particle is moving, it could be electron, it could be proton, it could be any particle, although proton doesn't move, but any moving particle will feel like a wave. Any moving particle will behave like a wave. What is the wave? This is like a wave. This is a wave. This is a wave. Now if there is some wave, so with respect to the wave, there are some parameters which we can define, and those parameters we study in EMFT. So there is one parameter that is known as wavelength. So the distance between the two peaks, this is one peak, this is other peak. So the distance between these two peaks is known as wavelength. So what is the wavelength? Distance between two peaks or crest of the wave. Crest means the bottom. Okay, so you just remember that the distance between two peaks is known as wavelength. And lambda is equals to h by p. This was the formula that was given by de Broglie. Lambda is equals to h by p, where p is the momentum and h is the Planck constant. So momentum, what is momentum? If mass m is moving with the velocity of v, then its momentum is given by p equals to mv. H is the Planck constant, whose value is 6.63 into 10 to the power minus 34 value joule into second. I was just thinking of the unit because E equals to h mu. So joule mu will be 1 by second. Yeah, joule into second. So you know what is the meaning of momentum? If m mass is moving with the velocity of v, then its momentum will be m into v. H is the Planck constant. Lambda is equals to h by p. What is wavelength? The distance between two peaks. There is another term that can be defined as just wait a second, guys. Yeah, so sorry for the interruption. Actually, I am having the cough, like serious it is. So I hope it is not creating much problem for you. Okay, when I am coughing, so I don't think that much of the sound is coming. I hope it is okay for you. Okay, So you guys can let me know in the comment section, like if this is troubling you. So what I would do is that I will not record at the time when I am not feeling well. Like currently, forget about it. Okay, let's go to our topic, which is wave vector. So there was a wavelength. With respect to wavelength as well, there is another term that can be defined as wave vector. When we study EMFT, we define it as phase constant, right? Beta equals to 2 pi by lambda. Beta is equals to omega by beta. Sorry, Vp is equals to omega by beta. So beta is equals to omega by Vp. So all these things we define in EMFT. In EMFT, you will understand the deeper meaning of wavelength. Okay. In EMFT, you will understand the deeper meaning of wave vector as well, or phase constant as well. But as of now, you just need to remember the formula. K is equals to 2 pi by lambda. Okay. So if K is high, if K is high, what does that mean? Lambda is low. If lambda is low, what does that mean? That means this distance is low. That means to reach from this particular point to this particular point, you will be taking lesser time because distance is low, no? Right? If K is high, that means lambda is less. Lambda is less. That means the distance between this point and this point is lesser. That means this wave is moving fastly. So what they have written, it is a way to describe the wave in terms of how fast it will oscillate in the space. So if K is higher, that means lambda is lower. If lambda is lower, that means oscillations are faster. So you don't need to think that, sir, what will wave vector represent? Wave vector is just representing that how fast the oscillations are. What is wavelength? Wavelength is the distance between two maximas, or you can say two peak values. And this relation that was given by de Broglie, that was lambda equals to h by p, and another relation you need to remember, K is equals to 2 pi by lambda. Okay, in EMFT you will study about all these things. You will study about the wave nature, everything in very detail. As of now, you just need to remember these two things. So de Broglie said that lambda is equals to h by p. So can I write down p is equals to h by lambda? Okay, p is equals to h by lambda. So let's do something. What I am doing is that p is equals to h by 2 pi. 2 pi by lambda. What I have done? Multiply and divided by 2 pi. So this h by 2 pi, h was a constant, 6.63 into 10 to the power minus 34 divided by 2 pi. So it would be another constant that I can write down as h bar. And what is 2 pi by lambda? 2 pi by lambda is k. So h bar is nothing but a constant only, which is equals to h by 2 pi. So don't worry about that. What is the final expression that you are having? P is equals to h bar into k. So from here you understood that momentum and wave vector are analogous to each other, right? So I will say that I am drawing the EK diagram, that means energy versus wave vector diagram, energy versus wave vector. But this diagram is known as energy versus momentum diagram. K is not momentum. K is not momentum. Who is the momentum? Momentum is P. But whenever I say EK diagram, in theory I will say energy versus momentum diagram. Is that clear to you? Are you able to understand this point? So in your mind, when I say K, momentum should come. Wave vector, forget about wave vector, anything. Everything is gone now. Only thing, this is the final conclusion now. P is equals to h bar k, where h bar is a constant. So whenever I say K, at that time wave vector should not come in your mind. At that time momentum should come in your mind. Is that okay for you? Right? So let's just say at one electron is moving with the velocity of v. Every particle have two kind of energy: kinetic energy and potential energy. Potential energy is coming because of its position, and kinetic energy will come because of the velocity. Like for me, let's just say I am sitting at a height of h, so and moving with the velocity of v. So my kinetic energy will be half mv square, and my potential energy will be mgh. Classical mechanics, right? But what we are assuming is that this is a free electron. For two charge, let's just say one charge is q1, another charge is q2. If I ask you what is the potential energy of this charge q2, what that would be? So that would be k q1 q2 divided by r. This distance I am assuming as r. So potential energy of charge q2 will be k q1 q2 divided by r. But what I am assuming only a free electron. That means I am not taking effect of any other charge. The electron is free. That means its potential energy will be 0. I am not taking action into its potential energy. Are you able to understand this point or not? Right? So here I am writing down the energy of free electron as half mv square only. Now some will have a doubt that, sir, why you haven't taken potential energy? Because I have assumed free electron. That means it is not there, it is not influenced by any other positive charge or negative charge. There is no influence on this particular electron. So it is a free electron. So energy will be half mv square. Now what I can do is that I will multiply by m here and then divide by m. So m square v square divided by m, right? So that would be half p square by m. So p equals to mv. What is p? P is equals to mv. So half p square by m. What is p? P is equals to h bar k. So what will be p? H bar k square divided by 2m. So what relation you are getting? E is equals to h bar k square divided by 2m. So this is the relation between E and K. What was our target? Our target was to find out the relation between E and K. So I started with E equals to half mv square. Then I know that from mv I can get the from mv what I can get? From mv I can get my momentum, right? So what I did, I multiply and divided by m. So this became p square by 2m. Since it became p square by 2m, then I know that p is equals to h bar k. So I can replace h square k square divided by 2m. So E is equals to h square k square divided by h bar square k square divided by 2m. Now what is the relation between Ek? If I want you to draw the Ek diagram, will you be able to draw the diagram? Y equals to some constant x square. E is equals to some constant k square. So Ek diagram will be a parabola. So if I ask you to draw the Ek diagram, then this is how the diagram will look like. Ek diagram will be a parabola. So this Ek diagram you are making for electrons. Now you know one thing, that for electrons energy increases in the upward direction. Electron energy will increase in the upward direction. So whole energy increases in the downward direction. So we have understood the Ek diagram for free electron. Electron means free electron only. So if I ask you to draw the Ek diagram for holes, how will you draw it? This is how I will draw it. Ek diagram for holes. In the negative direction, this is the E increasing K. So this is the upward direction. Now in the downward direction it will increase. So parabola only, but in the downward direction. Okay. So Ek diagram for free electron, Ek diagram for holes. So you would see that Ek diagram for holes will always be concave downward. Ek diagram for electrons will always be concave upward. Is that clear to you? Let me explain again. Lambda is equals to h by p, k equals to 2 pi by lambda, p is equals to h pi by lambda, h by 2 pi by lambda, h bar k. So p is analogous to k. Whenever you say wave vector, that means you are talking about the momentum. Okay. Now I want to find the relation between Ek. So half mv square, multiply and divide by m. So p square divided by 2m, p is equals to h bar k. So h bar square k square divided by 2m. So E is equals to h bar square k square divided by 2m. Right? The relation between Ek is simply parabolic. So E versus K diagram I have drawn for electron and holes. For electron, energy increases in the upward direction. So for holes, if I want to draw the diagram, I will make the parabola concave downward. This is concave upward, this will be concave downward. Is that clear to you? Everything is crystal clear, all good, all fine, right? Now what we need to find? We need to find the relation between effective mass and Ek diagram. This Ek diagram that I have made, how can I get effective mass out of it? So what I will do the double differentiation. If I do one differentiation, what I am getting? I am getting h square, 2k will come, 2 and 2 will get cancelled out. So h square by m. If I do another differentiation, what I will get? H square divided by m. So what you see here? What do you see here is that the value of m is h square divided by double differentiation. What does this double differentiation represent? What does this double differentiation represent? Curvature. So what do you see here is that m is inversely proportional to double differentiation of EK diagram, or you can say that M is inversely proportional to curvature. So if your curvature is more, that means your effective mass will be lesser, and if your curvature is lesser, then your effective mass will be higher. So if I give you two diagrams and there I ask you which of the particle will have higher mass, will you be able to tell me? We will solve these kind of problems, don't worry. But as of now you have understood that higher curvature means lower effective mass, and lower curvature means higher effective mass. So you will be able to understand that. We will solve some questions, but before that let's find out the same kind of relation between velocity and EK diagram as well. So what we need to do, we need to find out the same kind of relation between velocity and EK diagram. So somehow I need to get velocity. How can I get the velocity? Velocity I can get from the momentum, right? So if I do one differentiation, d by dk, what I am getting? h square k divided by m, right? You agree to this point? Now I know that P is equals to h bar k and P is equals to mv as well. So V would be equals to, basically I need to get the velocity. This is my target. So in place of, oh sorry. Yeah, so what I can see here is that d by dk, one h bar I am taking aside. So h bar k by m is equals to velocity. So what you are getting? Velocity is equals to 1 by h bar d by dk. So what do you see here? Velocity is proportional to the d by dk and proportional to the slope. So on, if I give you one EK diagram and I mark a few points and then I ask you at which point the velocity will be highest. So will you be able to tell me the velocity at which point the velocity of the electron will be highest? You will just see the slope. At the point where the slope is highest, at that particular point the velocity will be highest. So now we are going to solve all the questions of Niemann. Whatever the question are given in the Niemann, if they want to ask any question on EK diagram, then either it will be coming from this or this. That's it. From 3 questions only you will be able to understand every single thing about the EK diagram. So these are given in the Niemann and you will be able to understand. Let's revise whatever that we have studied. What we have studied, we started with lambda equals to h by v, p equals to h by lambda, then we find out the relation E is equals to h bar square k square divided by 2m. Whenever I say momentum, at that time you need to think of k only. Then we draw the EK diagram for electrons and holes. Then we saw the relation. If I double differentiate it, then I can get the value of m. I got to know that m is inversely proportional to d square by dk. That means more curvature would result in lesser mass, okay, and lesser curvature would result in more mass. And the same kind of relation I could have find out for velocity as well. So for the velocity I just did one differentiation. So I got to know that velocity is proportional to d by dk. So it is proportional to slope. Now see this question. Two possible conduction band diagrams are shown in E versus K diagram given in the figure. State which diagram will result in heavier electron effective mass. So here the word effective mass is written. Effective mass is written. But here I did not use effective mass. Here I did not put the star. Why so? Because this was a free electron, no? This was a free electron. But if the electron is moving in the conduction band, that means it will have to pass through crystal. Let's just say in the conduction band, if there is a free electron, so how it will move? It will move passing through the crystal, no? Like here it can be some impurity. This can be scattered, this can be vibrating as well. So here electron is not moving freely. It is going through this potential as well. It can have some negative potential as well. There could be phonon scattering as well. So here electron is not moving freely. So at that analysis, if I talk about the conduction band electron, and I write down the EK relation. So how will I write down the EK relation? I will write down the EK relation for conduction band electron in this manner. H square k square divided by 2 me star. Is that clear to you or not? I will use effective mass here. Why I am using effective mass? You understood? Because this is not the free electron. It is free electron but not completely free, not moving very freely, right? Although we will draw the EK diagram for conduction band and valence band as well. That is our next topic only. So let's solve this question. These kind of questions only will come in your examination if it is coming from EK diagrams. So two possible conduction band are shown. For this particular question, this is the diagram. This is the diagram for this particular question, that is, and here this is the diagram for this particular question. Two questions are there. EK diagram are shown. State which band will result in the heavier electron effective mass. So who is having more curvature? More curvature. So what I am saying is that d square by dk square for A will be more than the d square by dk square for B. That means effective mass of A will be lesser than the effective mass of B. Did you understand this or not? Okay, very simple. More curvature. How did you tell more curvature? Because this is more curvy. More curvature means lesser effective mass. So effective mass of A will be lesser than effective mass of B. One analogy I will tell you. Based on that analogy, you will be able to write down the answer very quickly. You don't need to think of EK diagram or anything. This is just a way to answer. What is the way? If I put a ball here and if I put a ball here, which ball will come faster? This ball will come faster, no? Because it is having more curvature. So if I put a ball here, this ball will come faster and this ball will come slower. So if some ball is coming faster, what does that mean? Its effective mass is low. That means the ball on curvature A is coming faster and ball on curvature B is coming slower. And if something is coming faster, that means its effective mass is low. So effective mass of A will be lesser than the effective mass of B. There you go. Just an analogy, just a way to answer in a quicker manner. If someone asks you in the interview, you will tell in this manner. That sir, this is having more curvature, then you can derive the things as well. Sir, I will do the double differentiation. Effective mass is inversely proportional to the curvature, inversely proportional to the curvature. So if it is having more curvature, then effective mass will be lower. If you want to answer in the competitive examination, you will just see that this ball will be coming faster. Since it is coming faster, that means it is having lower effective mass. There you go. What about this one, which is having more curvature? So effective mass of A here as well will be lesser than the effective mass of B, because here this is having more curvature, right? Very, very simple question. Okay, fine. Let's see the next question. At which of the position the velocity of the particle is higher? I am talking about the magnitude. Okay, I am talking about the magnitude. At which of the position the magnitude of the velocity, velocity of the particle is higher, and what is the direction of the velocity? That also you need to tell. So what I know is that velocity is h bar 1 by h bar, or what? This is the relation 1 by h bar d by dk. So 1 by h bar d by dk. So just I can say that more slope means more velocity, right? So let's see at which point you will get the more slope. This point, this is the highest point, you will get the most slope here, and then this would be the second most. I am talking about the magnitude. Someone will say that sir, this is the negative slope. Magnitude of the slope, this is near to infinity, right? And this point is C and this point is A. So you can see that the slope at the point D is higher than the slope at point B, higher than the slope at point C, higher than the slope at point E. This is the order of the slope, right? C is at the higher. If you move on this curve, just let me know in one thing. If I am moving on this curve, my slope, if I go from here to here, my slope is increasing only, right? Here the slope is 0, then it will increase, at some point it will become infinity. So if I am walking on this particular curve, my slope will increase. And if I am walking from here to here, then also my slope will increase, but in the negative direction. Here the slope is 0 and here the slope will become minus infinity. Here the slope is negative only, negative, at some point it will become minus infinity. So on this curve as well, the slope is increasing only. Are you able to understand this point? If I go here, then it is increasing, but in the negative direction it is increasing. although it is increasing only, no, magnitude is increasing only, right? Now I need to see the position of point C and A. I will see the position of point C. This is the position of point C and this is the position of point A. So although by looking at the diagram I am not able to tell that, sir, this slope is higher, basically this value is higher or this value is higher. I am not able to tell looking at the diagram, but I know that C point is a bit above. Point C is a bit above than A. The position of point C is a bit above than the position of point A. So I know that if I work on this graph, then my slope will increase. Similarly here as well. That means if my point is at higher level, then my slope will be higher. So point C is at the higher level. Point D is at the highest level. Then point B, then point C, and then point A. So looking at the position of the points, I can tell that their slope will be higher because I know the nature of the graph. Are you able to understand this point? Someone will say that, sir, just by drawing these diagrams you cannot tell which slope is higher. You just put the you just made the slope at a particular point. Just looking at the slope at a particular point, I cannot tell which slope is higher. But you can think more. How you can think that if I move on the graph, that's why I said that for this particular graph dy x square is always positive. That means when you are working on this graph, the slope is always increasing. The slope always increases. So yes, slope is always increasing, and in this direction as well the slope is always increasing, but the sign is opposite. And what about the velocity sign? What about the direction of velocity? So here direction of velocity for position D, it would be negative because slope is negative, no? The slope at point D and at point A. So from here I can say that velocity at point D is greater than the velocity at point B, is greater than the velocity of point C, is greater than the velocity of point A. And I am talking about the magnitudes. I am talking about the magnitudes. What I can see is that here MD and MC is having the negative slope and MA and MB is having the positive slope. Now they need to tell where the electron is moving. If electron is working in the positive x direction, then you say that at point D and C the velocity is in the negative x direction, and at point A and B it is in the positive x direction. Okay, is that clear to you? So basically whatever the direction of position A and B is there, whatever the direction of velocity of position A and B is there, the direction of D and C would just be opposite. That's it. This is the only conclusion you can make. You don't know what is the velocity of electron, you don't know anything about the wave equation as well. Wave function also you don't know. So the only comment you can make that if A and B are having positive velocities, then C and D will have negative velocity. That means at point A and B, if you are looking towards plus x, then at point C and D you will be looking towards minus x. So if I am saying that VA and VB is positive, then VC and VD will be negative. If I am saying that VC and VD are positive, then VA and VB will be negative, because wave equation I am not having, right? Although wave vector will have the same direction as the wave propagation. So if this is happening in the positive x, that means I would say that at point A and B the velocity will be in positive x, and at C and D the velocity will be in negative x. Don't go too much into depth. These kind of questions have never come in the examination, and very rare chance that it will come. But if it is coming, you should have this idea. That's it. If you have this idea, then surely you will be able to solve that particular question. More slope, more velocity. If they talk about the direction, what you will see? You will see the value of slope. So slope at point A and point B are positive. Slope at point C and slope at point D are negative. So if they are positive, that means they are working in plus x direction. If they are negative, that means minus x direction. So in that manner you can tell. Okay, this you will say minus x direction, and this you will say plus x direction. Because just as I noticed that the direction of wave vector is in the same direction as the wave propagation. Now how did you tell that? This thing also you understand in EMFT, e to the power minus j k dot r. Basically the thing is, EDC is the subject that should be studied from the quantum mechanics part. In quantum mechanics, you will introduce the wave function, then you will write down the equation of wave function, you will solve that, you will solve the differential equation. From there you will get this relation. Then from here you explain the concept of electron and holes, and then you move to the conduction band and valence band. But actually we started from the conduction band and valence band. Directly I said that energy splitting will be there, this kind of a waveform we will get. This will be the valence band, this will be the conduction band. And now I am explaining this EK diagram, because you cannot study that much in depth, right? In the examination, that much in depth is not coming. Till this date, they did not ask anything from EK diagram. Are you getting this point? Okay. So if they ask these kind of things only, they will ask. They will also make sure that it's not coming from the particle nature, particle and wave nature. Electron should be studied. First, you will study about the particle nature, then about the wave nature, then you will go to the quantum mechanics, and then you will come to the EDC. But you see the syllabus, in the syllabus, whatever the things that they have mentioned, they will ask from that particular point only. EK diagram is taught everywhere, since it is related to conduction band and valence band. That's why I taught it. That's it, nothing else. Okay. So this question you will be able to answer. Fine. You just need to, and this question is given in the Niemann book as well. Semiconductor Physics by Donald A. Niemann. So in that book as well, this kind of question is given. So from there only I took this question and I am explaining it here, because whatever that is given in the Donald A. Niemann, that is high probable for your examination. Okay. All fine. So this K is in the positive direction. So you would say that A and B are having positive slopes, so plus x direction, and C and D are having negative slopes, so minus x direction. Fine. Let's draw the EK diagram for our semiconductor. So in our semiconductor, you will have a conduction band and you will have the valence band. Whenever I talk about the conduction band, I always talk about free electrons, and whenever I talk about valence band, I always talk about the holes. So if I am making the EK diagram, how will I make the EK diagram? This is how I will make the EK diagram. Energy versus momentum. Looking upward. Why is that so? Because whenever I say conduction band, I talk about electrons. And now if I make the EK diagram, this EK diagram I have made for conduction band. Okay. And now if I make the EK diagram for valence band, then I will make it downward. I will make it downward. I will make it downward. Sir, why is that so? Because whenever you talk about the valence band, you talk about the holes. So electron energy will increase in the upward direction, hole energy will increase in the downward direction. Is that okay for you? All good? All fine? Now you see that conduction band, this is the energy only, no? This is the energy axis. Basically, this kind of graph it is there. This is the energy axis. But I have just made E and K. I did not make the full axis. Are you able to understand this point? Okay. So you can see that the minima of the conduction band and the maxima of the valence band is occurring at the same momentum. You would say, sir, this is wave vector. Wave vector and momentum are same thing, I told you, right? Because P is equals to H bar K. So whenever I say K, you should think about momentum only. So what I would say is that conduction band minima and valence band maxima is occurring at the same momentum, at the same value of K. So let's just say if there is some electron, if there is some bound electron here, if there is some bound electron here, and this bound electron wants to go to conduction band, So without changing the momentum, it can go into the conduction band. Say yes or no. Without changing the momentum, it can go into the conduction band. Without changing the momentum, it can go into the conduction band. And if it wants to fall back, I told you always there is generation and recombination process. Here electron hole pair are generated, and it may happen that it want to fall back as well. So if the electron is wanting to fall back, that means it will recombine with this hole. So when it is generating or when it is recombining, at both of the phenomena, it is not changing its momentum. So if the electron is going from valence band to conduction band or coming back from conduction band to valence band, in both of the conditions, momentum is not getting changed. And if this is the condition, then it is known as direct band gap semiconductor. So we were actually studying about direct band gap semiconductor. Okay. So when an electron is going from valence band to conduction band or coming from back from conduction band to valence band, it doesn't have to change the momentum. That means conduction band minima and valence band maxima is occurring at the same momentum. So that kind of semiconductor is known as direct band gap semiconductor, direct band gap. Okay, so this has been written here. Only just read about direct band gap semiconductor. What it is written? Conduction band minima and valence band maxima is at the same K value. Electron transition needs only photon. So this point I will explain. These points I will explain later on. But you just read the point that conduction band minima and valence band maxima is at the same K. But now if your conduction band minima and valence band maxima is occurring at the different K, then what will happen is that then it is known as indirect band gap semiconductor. So this is your conduction band, this is your valence band. So your valence band maxima and conduction band minima is occurring at the different momentum. So what will happen is that, let's just say some electron wants to go from valence band to conduction band. So it cannot go like this. What it will do? What it will do is that first it will gain some energy, then it will reach here. Then what it will do? It will change its momentum. It will change its momentum. Then it will reach here. It will change its momentum. It will reach here, and then it will go to the conduction band. So from here the hole is made. So one electron wanted to go from the valence band to conduction band. So what really happened is that it gained enough energy, then it went to some particular energy level, then it changes its momentum. Let's just say here the momentum was K1, here the momentum is K2. So it made a change of K2 minus K1 momentum, and then it went to the conduction band. Now how the momentum can change? Let's just say I am having a mass of m and I am working with the velocity of v. So I am working with the constant velocity of v, right? If I collide with something, then only my momentum can change, no? Like if this is a flat road, I am working with a velocity of v, my momentum will never change. But if I collide with a small stone, then my velocity may change, and if my velocity is changing, then my momentum can change. So for the momentum change, collision is necessary, and whenever there is a collision, heat is generated. What I am saying, whenever there is a collision, heat is generated. What does that mean? That means if there is a change in momentum, that means heat will be generated. The same process, if the electron wants to recombine as well, then what it will do? It will go back. It will be coming at this particular energy level. Then what it will do is that it will again change its momentum, and then it will fall back here to the hole. So for both generation and recombination, in both of the process, the momentum is getting changed, and momentum getting changed means there is a collision, and collision means heat is generated. So in indirect band gap semiconductor, heat is generated. So whenever an electron makes a transition from conduction band to valence band, heat and light both are generated. But in the indirect band gap semiconductor, since there is a change in momentum, so more heat is generated and less light is generated. Are you able to understand this point or not? In indirect band gap semiconductor, electron is not going directly. It has to change the momentum. Since it is changing the momentum, that means there is collision. Collision means there is heat. So in indirect band gap semiconductor, heat is generated. But in direct band gap semiconductor, light is generated. In both of the process, light and heat both are generated. In direct band gap semiconductor as well, in indirect band gap semiconductor as well, light and heat both are generated. But in direct band gap semiconductor, light is more, because here momentum is not changing. If momentum is not changing, what does that mean? Heat is not generating, right? So heat will generate, but in a very, very few amount. Similarly here, heat will generate in a very large amount, so light will not take much of effect. So most of the energy will be lost in the heat, and here most of the energy will be lost in the light. And light means photon. Light means photon, and heat means phonon. So when it makes the transition from conduction band to valence band, it will generate the light. So to excite this as well, I will give the light only. Basically, I will throw some light to my semiconductor. Then what will happen is that electron from the valence band will go to the conduction band, and when the electron is coming from the conduction band to valence band, at that time it will generate light only, because there is no change in the momentum. So this is the line that has been written, that electron transition needs only one photon, and energy released mainly as light only, and that is known as photon emission. And one photon can excite only one electron. Although this point is not important, I am just telling that one photon will excite only one electron. Okay, and energy is mainly released at light only, so that's why we will use direct band gap semiconductor as LEDs, laser, and in all these kind of things. And examples are gallium arsenide and indium phosphide. Okay, so these are the examples. And what about indirect band gap semiconductor? So in the examination, how the question can come? Question will be coming from this theory. That's it. That in direct band gap semiconductor, direct band gap, you will see direct band gap. Okay, there is no change in the momentum. No change in the momentum. That means there is no heat. No heat means light. Light means photon. So in direct band gap semiconductor, photons will be generated. Photon emission will take place. Okay, photon means light. Light means it will be used in LEDs and laser. What all are the examples? Gallium arsenide and indium phosphide. These are the two examples. In indirect band gap semiconductor, conduction band minima and valence band maxima will occur at the different K. That means momentum change would be there. If momentum change is there, that means heat will be generated. Okay, so electron transition needs both photon and phonon for momentum conservation, and energy will be released mainly as heat, but light will also be released. If an electron is making a transition from higher state to lower state, then surely it will release some light. But here, more part will be of heat. Okay, so poor light emitters, so it will be used in electronics. Electronics means mostly we will make diodes, transistors. So for making diodes and transistors, we use indirect band gap semiconductor. Those are silicon, germanium. So what is the key difference? One liner key difference is direct band gap semiconductor means photons only, that means only light, and indirect band gap semiconductor means photon and phonon both will be generated, but mostly phonon will be generated. Is that okay for you? You will be able to remember direct. Okay, direct transition, photon. Indirect, change in momentum. Momentum is collision. Collision means heat. So heat is generated. That's it. This is how you need to remember. Now it feels like that, sir, compound semiconductors are direct band gap semiconductor and indirect band gap semiconductors are elemental semiconductors. But this statement is wrong. What is the correct statement? Correct statement is all elemental semiconductors are indirect band gap semiconductors, but all compound semiconductors are not necessarily direct band gap semiconductor. Okay, so very important line. Look, silicon, germanium, diamond, these are elemental semiconductor. Only one element is there, so all of these are indirect band gap. All of these are indirect band gap. None of them is direct band gap. Germanium can be used as a direct band gap semiconductor. Currently research is going on this. Okay, so it can be used as a direct band gap semiconductor in some particular condition, but the bottom line is elemental semiconductors are indirect band gap semiconductors and compound semiconductors are direct band gap semiconductors. This line is not true, because you can see that these compound semiconductors, gallium arsenide, indium phosphide, gallium nitride, and cadmium, whatever it is, that is direct band gap semiconductor. Cadmium telluride. And indirect band gap semiconductors are gallium phosphide, aluminum arsenide, and silicon carbide. So these are indirect band gap semiconductors. Okay, so only the points you need to remember. If first thing is that very rare chance that any question would be coming. If it is coming, then you will be able to answer. Now there is one semiconductor that is known as aluminum gallium arsenide. This semiconductor is known as aluminum gallium arsenide. So based on the composition of aluminum and gallium, it could be direct or indirect. So if x is equals to 0, the semiconductor is aluminum x gallium 1 minus x arsenide. If x is equals to 0, then what will be the semiconductor? Gallium arsenide. So gallium arsenide is direct band gap semiconductor. If x is equals to 1, then what will be the semiconductor? Aluminum arsenide. So that will be the indirect band gap semiconductor, right? But the typical value of x is 0.45. That means if x is less than 0.45, that means gallium is more. If X is 0.4, then gallium is more, aluminum is lesser. So if gallium is more, aluminum is lesser, that means it is more towards gallium arsenide. And if it is more towards gallium arsenide, that means it will be direct band gap. And if it is more towards aluminum arsenide, then it will be indirect band gap. A very famous example in EAC, sometimes question have been asked, that's why I wrote it here. But in GATE examination, again, very rare chance that any question will be asked. So there is one semiconductor, aluminum gallium arsenide, based on based on the number of atoms, or I should not say number of atoms, based on the fraction of atoms. If gallium fraction is more, then it will be towards the direct band gap, and if aluminum fraction is more, then it will be towards the indirect band gap. So this slide is clear to you. Okay, there is nothing to explain in this slide. This slide is also clear to you because I have made the EK diagram for conduction band and valence band for direct band gap semiconductor and for indirect band gap semiconductor. In indirect, the electron is going indirectly. It will change the momentum and then it will recombine, or for generation as well, it will change the momentum and then it will recombine. So direct band gap semiconductor we have studied, indirect band gap semiconductor we have studied. So this lecture will end here. Okay, so this last part is not very important, just whatever that has been written, just remember that particular part and you will be good to go. And in this EK diagram, these questions are important. This particular question is very important and this question is also very important, and whatever the relation that we derived here, these are also important. Okay, so if some question is coming from this particular topic, then it will be coming from this analysis only, whatever the analysis that we have done. All good, all fine. So we have seen semiconductor physics, 3 lectures we have done. In the next lecture, we are going to study about Fermi direct distribution. So we will comment on the probability of finding electron on a particular energy state. So that we are going to see in the next lecture. Okay then. So I hope you enjoyed the video. Thank you very much. Happy learning. Let's meet in the next lecture.